Hello and welcome to the course on data science. I'm super excited to have you here and we're going to have a fantastic journey together. We're going to dive into 4 separate realms of data science and each one will feel like a unique adventure. And in this quick tutorial, I just wanted to introduce myself quickly and give you an outline of the course. So my name is Kirill Romenko and I have been in this field for about 5 years. I have both worked for companies as a data scientist and for consulting as a data scientist. I worked at Deloitte Australia and I had exposure to many different industries and developed lots of skills and experiences which I want to share with you in this course. And moving on to the course outline, I'm just going to jump behind my computer and I'll walk you through the different sections of the course so that you know how to navigate it better.
Alright, back behind the computer, and here I've got the course as we see it. So I'm going to zoom in a little bit so we can see everything a bit better. And at the top here we've got the Get Excited section, that's where we are right now. Then we have the What is Data Science section, which is a bit of an extended introduction into data science, and it tells you about the different areas or domains of data science, why data science is going to just grow in demand and is going to be a very popular profession in the future, and why you want to be on this wave early. And also there's an important tutorial here which is called Course Pathways. Now this tutorial is important because it will allow you to create your own learning experience based off the sections in this course. And let me explain in a bit more detail what I mean here. So here we've got section 3, part 1, visualization. There is 4 parts to the course and they are quite substantial. So they have lots and lots of lectures. And you might want to go through them in the order that they laid out, or you might want to combine them into your own learning experience based on what you are after in terms of learning data science. So here we've got Tableau. We're using Tableau because it will allow us to do visual data mining, a very interesting topic which we cover off. Then we get an introduction here, this introduction to Tableau. Then I explain how to use Tableau for data mining. Then I will show you how to do advanced data mining in Tableau. And we'll actually talk about statistical significance of your data mining based on chi-square tests. Then part 2 is modeling. So we won't go through all the sections right now, but because there's just a lot of them. But basically, we refresh our stats in this section, and then we learn how to build models step by step. So we go through simple linear regression, multiple linear regression, logistic regression, building a robust geodemographic segmentation model. Then we'll learn how to assess the model. Then we'll learn how to draw insights from your model. We will learn about model maintenance. And then we will move on to data preparation. So this is part 3. And here this is also a very big part. Here we're going to learn what business intelligence tools are, and we'll set up all the software for this part of the course. Then we will talk about data wrangling before the load. We'll talk about how to use SSIS for uploading your data. Then we will talk about how to handle errors. And this is going to add some realism to what we're doing. So there'll be very realistic errors that you will find in real life scenarios. Here we will learn how to program in SQL for data science. So some basics of SQL programming, which we'll need in further sections. Then we will learn how to perform data wrangling after we've loaded data into a database. Then we will learn how to handle errors during the last phase of our extract, transform, load process. And there will be also another very realistic data set here. So you'll learn everything about cleaning data. And finally, part 4, communication. So this is the part where we talk about how to work with people. In this section, we talk about how to work with people and extract information from them to use in your data science projects. And in this section, we learn how to present data science projects. And I actually give you some case studies of my own presentations. And finally, at the end, we've got some homework solutions because there will be homework throughout the course. So that's how this course works. Make sure that you check out that tutorial that I mentioned on creating your own pathway, because it will also help you understand how you can structure these sections to gain the maximum benefit in your specific situation. And I look forward to seeing you inside the course. And until next time, happy analyzing.
Welcome to the first section of the course. This is an overview section, and here we talk about things like areas of data science, why it is the profession of the future, and what is the philosophy behind everything we do. These are some important topics that will help you understand this course better and understand better what we're studying and why we're studying it. However, from my point of view, the most important topic in this section is the course pathways topic. And that is because this course is quite large and you're definitely encouraged to take it at your own pace, and that is what this tutorial is designed to help you do. I outlined 7 separate course pathways which you can take to tailor your learning experience to your needs. So make sure to check out that tutorial, and I look forward to seeing you inside the section.
Profession of the future. In today's tutorial, we will find out why data science is the place to be going forward in the next couple of years or even decades, why this is the profession that you want to be in. So there's lots of data in the world, and ultimately data is the resource that data scientists work with. If there's more data, there's more work. If there's less data, there's less work. So let's find out what's been going on with data and what will be going on with data in the coming years. So let's jump straight into it. Since the dawn of time, up until 2005, humans had created, are you ready for this? 130 exabytes of data. Wow. Kirill, this tells me absolutely nothing, right? What is an exabyte? Why is this so impressive? Well, let's start from the ground up. Let's start with 1 byte. Here we've got the letter A. It takes up exactly 1 byte of space. Now, if we zoom out 1,000 times, then we have a page of letters. Now, a page of letters can have anywhere between 2,000, 5,000 letters. So we'll say that half a page of text is about right for 1 kilobyte. Now let's zoom out another 1,000 times and we'll get a book. So a book with about 500 pages, that will take up about a megabyte. Now let's zoom out another 1,000 times and what we'll get is a gigabyte. And a gigabyte is sufficient to fit the whole human genome. So a human genome, once it's coded, it can fit into a gigabyte. In fact, even 750 megabytes should be enough to fit that, but we'll say a gigabyte. So you can fit an entire person onto a gigabyte if you think of it that way. But here you'll say, well, Kirill, actually, the genome of a person is not sufficient to tell you everything about that person. A person has, life experiences. A person, different people live their lives differently, and there's lots more to a person than just the genome. Well, then let's zoom out another 1,000 times, and we'll get to a terabyte. Well, if you take an HD camera and you follow a person for every single day of their life, for every single hour, minute, and second, and you film everything that they're doing for 70 or 80 years, you can fit all of that material onto 1 terabyte. How about that? That is pretty impressive already. So 1 terabyte can fit all of your life experiences filmed throughout your life for every single second that you live. Now let's zoom out another 1,000 times and we'll get to a petabyte. And for a petabyte, I've got one of my favorite examples. Here's the Amazon rainforest. The Amazon rainforest takes up about 1.4 billion acres. That's 1.4 billion acres of trees. There's about 500 trees per acre, making it about 700 billion trees. Now, if you take all of these trees and you chop them down and you turn them into paper and you fill all of that paper with letters completely on both sides of the sheet, then that will amount to somewhere between 1 to 2 petabytes of data. That is pretty impressive already for a petabyte, how much a petabyte of data is actually. Well, now if you zoom out another 1,000 times, you will get an exabyte. An exabyte is 1,000 petabytes. Going back to our example, since the dawn of time until 2005, humans had created 130 exabytes of data. That is a lot of data, and this includes everything. It includes written, it includes spoken, it includes folklore, it includes songs, it includes any kind of data ever produced by humans, even all the words that they ever said. Now, by 2010, this number had grown to 1,200 exabytes of data. So it nearly increased tenfold just over 5 years. Then, in 2015, this value is estimated at 7,900 exabytes of data. And finally, by 2020, it's expected to be 40,900 exabytes of data. So you can see that data in the world is growing very, very quickly. In fact, it's growing exponentially. We are creating much more data by the day. And if you visualize it, it looks something like this. So this is the growth of data between 2010 and 2020. It's a 50-fold growth of data, and the source for this report is IDC's Digital Universe, sponsored by EMC. Now, where is the opportunity for data scientists here? Why is it such a lucrative profession to be in? Well, if you plot computers on this chart, how computers are able to cope with data, then I would expect there'd be somewhere over here. So that's how machines are able to store and process and do something with this data. As you can see, there's so much more data in the world that machines can actually use and make sense of and add value with. Well, now if you plot the data scientists of the world, they're actually over there, way below the machines. From here, you can see that there's a massive gap between the amount of data and how much data scientists can process, and even between the amount of data that machines can process and derive value from a data scientist. And these gaps are actually just going to grow and grow and grow with time. And that is why there'll be a huge growing demand for data scientists in the future. And we can already see that now. We can already see how data scientists are becoming very popular. Salaries are going up and through the roof, especially for very qualified data scientists who know what they're doing and can add value, can do something with all of this data in the world. And in fact, data science has already become a degree. You can take different courses on data science and programs in universities like Berkeley and so on. And in fact, you're actually taking one of these courses right now, so you definitely already know that. And this is why data science is the place to be. Data is going to grow in the world, demand is going to grow, and there will always be a need for people who know what to do with that data. In fact, with time, data science will become like a norm. It will become a norm, just like everybody now has to know how to use an iPad. Everybody in 10 years' time will be expected to know some level of data science that they will be expected to apply in their role. There you have it. That is why data science is a great place to be, and it's not going anywhere. And you definitely did the right thing by enrolling in this course, and you will learn tons to help you be one of the top data scientists that's going to take advantage of those gaps that need to be filled. And I look forward to seeing you on the next tutorial. Until then, happy analyzing. Data science domains. In this tutorial, we will talk about the great variety of disciplines that data science encompasses. And you're probably already familiar with this Venn diagram, which portrays data science as the intersect of three worlds: computer science, maths, and domain knowledge. By the way, here by domain knowledge, we mean the intrinsic knowledge you develop about the business or industry you work in. Also, you might have already heard the definition that a data scientist is a person who is better at statistics than any software engineer and better at software engineering than any statistician. Though amusing, these definitions are very outdated. Their days have passed long ago. A modern data scientist is expected to be proficient in many more disciplines and has to possess way more skills than just programming and stats. Personally, I really like this picture. How about we use it as a starting point in our quest to find out what data science actually is? Starting from the top. Statistics. Because data science involves working with data and hard facts all the time, you have to be able to separate random noise from actual trends. Also, you need to know how to build models that classify populations and provide reliable forecasts of future events. Visualization. Humans don't speak in ones and zeros. A data scientist has to be able to see data, and what's even more important, to show it to others. This is why visualization is not only an art form, but also a crucial skill you have to have in your arsenal. Data mining. Along with visualization, data mining is the creative part of your work. Interrogating data, looking for trends, looking for anomalies, finding things that have never ever been seen before. This is where you put your Sherlock Holmes hat on. Database and data process. This involves everything from cleaning of data to storage and manipulation. It's like knowing how to hold a book and to turn pages. If you cannot perform these basic tasks, then you'll never get to read the story. Now these three, pattern recognition, machine learning, and neuroplasticity, are separate here, but personally I would put them all together. They all cater to one goal: teaching computers how to learn without being explicitly programmed. This is quite an advanced realm for a data scientist, and this is where you go once you've gotten quite proficient at all of the other areas that we've covered off. And moreover, not every data scientist has to go down this pathway, because this is a very specific set of skills that's applicable to certain business problems and challenges. Now, we've discussed everything on this picture, but I think that even that is not enough. There are a few things that I would add. Number one, communication. A data scientist has to interact with people on a daily basis. Not all insights are in the data. Some things you can only learn from people who are working with that data. And I will show you some vivid examples of this further down in the course. Therefore, a data scientist who cannot talk to a human being for longer than 5 minutes is not setting himself up for success, regardless of how smart he is. You have to be an outgoing person to be successful in this profession. Presentation. Another form of talking with people, only this time it's the other way around. You are trying to put information into their heads. I believe that this is one of the most important skills of a data scientist, if not the most important one. Because apart from having all the other expertise we already talked about, a modern data scientist is the gatekeeper between insights and people. You can derive thousands and millions of valuable business insights, but if you cannot effectively communicate them to the key decision makers, then those insights are worth nothing. Domain knowledge. Personally, I admire data science so much because it is an extremely transferable set of skills. One day you are searching for fraudulent transactions in a large mining corporation, the next day you are building a remuneration model for the employees of a medical facility. Quite likely, the data scientist is the only employee who can adapt to a new organization and even industry so quickly. And funnily enough, this example shows that you can be a successful data scientist even without domain knowledge. However, domain knowledge does add to your capacity to deliver insights. You just have to do your research and develop the bulk of this domain knowledge very quickly, and the rest of it will come as you're working in this industry or in this company. Real life practice. The saying practice makes perfect says it all. This concept is extremely applicable to data science. Programming. Another important part of data science. The better you can talk to a machine, the more efficient and more successful you will be. If you haven't yet, start learning programming today. It should become a hobby. It should be something that's just a natural part of your life. And finally, creativity. You have to be creative. If you cannot generate your ideas, you might find yourself stuck as a data analyst forever. To become a great data scientist, you have to cultivate creativity inside yourself. Allow your curiosity to guide you and help you find insights that nobody thought you would ever find. Those are the main disciplines and qualities that I would add to this list. And to finish off, let's see what we will cover off in this course. Statistics, visualization, data mining, database and data preparation, communication, presentation, creativity, programming, and real life practice. You'll definitely have a lot of that last one. And as you will see, some of these we will cover off in more depth, some in less. But in any case, here you will develop a great foundation for your data science career. And in the next tutorial, we will expand on this a little more, and I will show you the exact pathways you can take in this course. It's an important tutorial because it will help you shape your learning journey the way you want it. So make sure you don't miss out on it, and I look forward to seeing you there. Alright, course pathways. Exciting tutorial ahead. As you will see, this course consists of 4 major parts: visualization for data mining, modeling, data prep, and communication and presentation. And you can combine these modules into your own learning program. The thing is that this course has over 200 lectures and over 20 hours of content. And of course, it's very beneficial to go through everything. However, you might want to go through it in different order, or something might be an urgent requirement for you right now and you want to address that. So let's have a look at some of the template pathways that you can create using these building blocks. We're going to put the pathways on the right over here. And the first and most obvious pathway is the independent one, where you can take any of these modules by itself. And the course is structured in such a way that these modules are completely independent, so you don't have to worry about missing out on some lectures that might be required in the module that you're taking. You can simply start the module and you will safely get to the end without having to worry about a thing. So if you have a pressing need to get into one of these topics right away, feel free to do that. You will be able to get to the knowledge you need very quickly. Number 2, the full Monty. You just basically go through the full course as it's laid out, and you'll go from visualization for data mining to modeling to data prep to communication and presentation. Now, the course is structured in exactly this way because this is the most fun and engaging way to discover these topics. Option number 3 is the sequential option, where you take these modules in the sequence that they would come in a data science project. So you basically start with data prep, then you move on to visualization for data mining, then to modeling, then to communication and presentation. Now, I had the idea of putting data prep at the very start of the course, but I realized that this is the most tedious task and it does take the longest in any given data science project. So it would be a major turn-off to put it at the start of the course because it's not the most fun part of data science. So therefore, we first go through visualization and then through modeling, and then we go to data prep when we already know why we're sacrificing so much time, what the end result of our data prep will be. However, having said that, if you feel that you would like to start with data prep, please feel free and go ahead and do that. Just be warned that data prep will take quite a long time. It's the biggest module of this course. Number 4, the Explorer. Here you start with visualization for data mining, and then you proceed directly to communication and presentation. The prerequisite here is that you have to be sure that your data is clean and it's ready to be analyzed. And also through this pathway, you won't be creating any models or forecasts. So basically, you'll be skipping the part where you create a long-term solution for the problem that you've identified. Nevertheless, these insights will be very agile and you'll be able to communicate them properly to the key decision makers and take it from there. Pathway number 5 is called the modeler. So this pathway is for people who are tasked in their daily jobs to create models and deploy them. So once you already have knowledge of what goes into the model, for instance, you might be working in a bank and you already know how your credit scoring model works. So all you need to do is prepare the data, load it into a database, and then build the model for that credit scoring system. So you don't need to do any investigations, you don't need to communicate it later on, you just need to build it and deploy it, and then maintain it, assess it, and see how it goes in a year or so, then deploy the next one and so on. And that is quite a frequent type of role, and this might be very useful to some people. Number 6, the senior. So here I mean senior data scientist. And basically these are the lucky people that have somebody else doing their data prep for them. And of course you have to trust these people and rely on them. But if you're sure that your data prep has been done and your data is clean, then you can totally skip the data prep part and just do the fun bits, which is the visualization for data mining, modeling, and communication and presentation. And finally, number 7, reporting services. So I've done quite a lot of work with reporting services or business intelligence units of organizations, and I've seen what the work they do, and it really fits in well with what we discuss in these 2 parts. So if you, in your role, are the data custodian in the organization, or you work closely with the data custodian, you find yourself creating reports and preparing the data to be stored in warehouses and working lots with SQL and Microsoft Visual Studio and SSIS and things like that, then you might be interested in this pathway, because here we talk exactly about that, how to store your data, how to clean it, how to prepare it, and also then you can move on straight to the communication. So basically this pathway doesn't imply any kind of analysis or data mining or modeling. It's just getting the data, putting it into the right place, and then presenting it to the right people. So those are pathways for this course. Once again, this is not an exhaustive list. You can come up with your own totally unique pathway that will suit your needs. But otherwise, I hope you enjoy the course, and I look forward to seeing you within these modules. And until next time, happy analyzing.
Hello and welcome to this visualization part of the course. I really wanted to use this tutorial to set our expectations for the upcoming sections. As you will see, visualization is a very powerful tool in the arsenal of a data scientist because it ultimately allows you to see your data. And from my experience, visualization can be used for 2 purposes. Number 1 is data mining, and number 2 is reporting. And in this part of the course, we're going to be focusing on data mining in terms of visualization. And we'll be using a tool called Tableau, and these tutorials will be very, very practical. And if by the end of this part of the course you feel like you like Tableau a lot, which I suspect will happen, then you're welcome to check out my other course, which is called Tableau for Data Science, where we talk about visualization for reporting. And you will notice that this part of the course has been broken down into logical sections. First, you'll get an intro to Tableau. Then we will talk about the basics of data mining and visualization, and I will show you how to use an A/B test, how to create an improvised A/B test in Tableau. And finally, in the third section, I will show you my way of running chi-squared tests in Tableau. And don't worry if all of this sounds a bit too statistical for you. I can promise you that it'll be very visual and we'll have lots of fun. And to finish off this tutorial, allow me to show you a very quick sneak peek into Tableau.
Tableau is a very simple yet powerful tool for everything to do with data. The company's mission is to help people see and understand data. And as you can see here, Tableau is a completely drag and drop software. And using Tableau, you can create visuals sometimes 10 times faster than you would have created them in other programs. And overall, Tableau is a new and innovative approach to business intelligence.
In this section, we will learn how to navigate Tableau, and I will introduce you to this powerful tool. You will also see how intuitive it is and how much easier it is to perform analytics in Tableau than in Excel. Also, I'd like to mention that if you've already completed my separate course on Tableau, then you might want to skip this section and jump straight into the next one. Otherwise, I hope you're excited to get started, and this is going to be a light and fun section, and I look forward to seeing you on the first tutorial.
Hello and welcome back to the course. In today's tutorial, I will show you how to install Tableau. So let's jump straight into it. The first thing that we're going to need is a browser. And once you have a browser up, let's go to www.tableau.com. Now this is the main page of the Tableau software, and here you have a couple of options of which package you can install. Now for this course, there are two versions of Tableau that will suffice, that will work great for us. One is Tableau Desktop and the other one is Tableau Public. Now, Tableau Desktop is a paid version, and if you already have Tableau Desktop, then that's great. Go ahead and use your existing license of Tableau Desktop. If you don't have Tableau Desktop, then I will show you just now how to install a trial version of Tableau Desktop. The other option is Tableau Public, and why would you opt in to use Tableau Public instead of a trial version of Tableau Desktop? Well, the reason is, well, first of all, Tableau Public is free, completely free. And the other thing is that Tableau Desktop, that trial, is only 14 days long. So at some point you'll run out of it, and maybe you'll want to continue learning, maybe you'll want to continue experimenting. So in that case, you've always got Tableau Public to go to, and you can always use it. And as you'll see further down in this tutorial, it's completely identical in terms of functionality, and you can totally go through this whole course with Tableau Public. So first off, I'm going to show you how to install Tableau Desktop, the trial version. Here you've got a Tableau or a Try Now button. So if we click the Try Now button, then here you've got a couple of options. Once again, Tableau Desktop, Server, Online. We want to select Tableau Desktop, so let's click Get Started over here. And as soon as you click that, automatically a download will commence, and this download contains the correct version of Tableau Desktop for your machine. So I'm using Windows 64-bit, and that's the one that's being downloaded right now. If for some reason the correct version wasn't picked up, then you can always select the correct version here. So you can select 32-bit Windows, or you can select a Mac version. Yes, that's correct. There is a Mac version of this wonderful software. So go ahead and download that if you're using a Mac. All right, so once that's downloaded, here you've got a couple of steps that you will need to go through to start your trial of Tableau. I'm not going to do that because I've already done that, and I will show you what it looks like inside just now in a second. So that is how to install Tableau Desktop, the trial version. Now, if you want to install Tableau Public, then the website is a bit different. The website is public.tableau.com. And here you will need to enter your email address and click this button, download the app. Once you've done that, you will get an email with Tableau Public, a link to the installation, or the installation will actually commence as soon as you click that button, and then you'll be able to install Tableau Public. So here I'll just scroll down to show you what Tableau Public is about. If you scroll down to the bottom, you can see that Tableau Public has 135,000 authors, 15,000 visualizations per month, 25 million views per month. Tableau Public is mostly used like by journalists and public-facing organizations that don't have like trade secrets and things like that. And that is because anything you create on Tableau Public has to be hosted on a public server and has to be accessible to anybody on the internet. For us, it's not a problem because we're learning. We're going to be creating visualizations as part of this course. Totally not a problem. We're totally fine with that. So if you want to use Tableau Public, go ahead and use Tableau Public. All right, so let's have a look. I'm going to cancel this download because I already have this file. Let's have a look at Tableau inside and Tableau Public inside. So here I've got both of them installed, and I'm going to bring up Tableau first. So this is Tableau, where it's got like lots of these plus signs. Here you can see a whole library of visualizations that some of them are from this current course, some of them are from my other courses on Tableau or advanced Tableau. So here you got some animations and so on. But basically, this is the first thing that you see. This is the library of your recent visualizations that you have created. Now, I'm not going to go into detail on Tableau desktop right now. First, I'm going to bring up Tableau Public. So I'm going to double click Tableau Public over here. And here you can see Tableau Public has come up. So as you can see, it's exactly the same interface, exactly the same program, and I have created the same visualizations using Tableau Public. The only difference here is that I can connect to less types of files as opposed to Tableau desktop, but that's not a problem because we don't need that many types of files to connect to in this course because we are learning, and it's more about the concepts that we're learning rather than the data connections that we can establish. And so let's just bring up one random one of these visualizations. So maybe that one and maybe that one. So here you can see that inside they are also very, not just similar, they're actually identical. You can see that they're structured the same way and they work the same way. The only other difference that I can think of is you can't create an extract in Tableau Public because your data is hosted on a public server anyway. And probably the other thing is that it's you can't just export images from Tableau Public. You need to take screenshots or export them from your published visualization. That's pretty much it. So other than that, the functionality is exactly the same, and you can go ahead and install either of these versions. And once you've installed that, in the next tutorial, we will start drilling into our data, and eventually we'll start creating some great visualization and doing some cool data mining with Tableau. Okay, that's all for today, and I look forward to seeing you on the next tutorial. Until then, happy analyzing. All right, let's get this section started. So to get the data sets, you need to go to superdatascience.com/training. And then here, if you scroll down, you'll see part 1 visualization. And we need the first data set, which is office supplies. So go ahead and download that. And once you've downloaded it, put it in your folder. So I've created here a folder on my desktop, which is visualization section. And I've got my 3 sections over here, and I'm just putting it in the first folder. And once you have the file, let's open it up. So it's a CSV file, and basically it means it's like a text file, but separated with commas. And you can totally open it with Notepad. So I'm going to use Notepad++ to open it up. And here what you can see is 1, 2, 3, 4, 5, 6, 7 columns. And there's quite a few rows. So 43 rows in total. Now, if you don't feel like opening this file with Notepad++, because it is kind of out of alignment, the columns are not exactly under each other, you're welcome to open it with Excel. So let me bring that up here and just drag it into Excel like that. And what do we have here? So this is a file which represents a store that sells stationery, as you can see from here. And it operates in a couple of regions, so East, Central, and West, 3 regions in total. It's got quite a few representatives. It's got like an item description. So these are sales. Well, how many sales did these people make? And as you can see, these are bulk sales. And there's the unit price over here per each unit sold. And the challenge for this data set is that the management wants to know who made the most sales in dollars for this period that's reflected in this data set. Looks like a financial year, so a financial year that starts in July and ends in June. And the person who made the most sales in dollar terms in each region gets a bonus. So there's a total of 3 bonuses to hand out, and they will only go to the person who made the most sales in each region. And management wants you to find that out. And there we go. So we're going to use this example to practice Tableau. And off we go to the races. We'll get started in the next tutorial. Hello, this is Kirill from superdatascience.com, and today we'll be connecting our data source to Tableau. So I'll bring up Tableau, and this is the data source that we're talking about, office supplies. So we downloaded it in the previous lecture. As soon as you open Tableau, here on the left, you have a column called Connect. So let's click on Text File. And now we will select our file here, officesupplies.csv, and we'll open it up. And right away, we're redirected to the connection manager for this data source. And let's have a look around here. So on the left here, you've got a directory where the file is located. And at the bottom here, you've got only one file currently. That's because we only have one file in that directory. Later on through the course, you'll notice that when we have more files of the same type, there will be more, they will all be listed here and you'll be able to select from them. So here you've got a window where all the files you have selected are located. And so what does that mean? Well, that basically means that you can select many files. So I can show you an example now. I can drag another one of these into here, and right away something happens. Tableau is trying to find a way to connect these two files and basically join them, but we won't do that now. So we'll just click the red cross here and cancel that. We will talk about joining data further down in the course, but just bear that in mind that your data that you're working with in Tableau doesn't all have to come from one file. It can come from many files, or it can come from many tabs in a file, or it can come from different types of files. But once again, we will talk about that later on. At the bottom here, you've got a preview of your files. So certain rows and columns of the files, just so that you can have a look and see what you're dealing with. And in our case, we do have the order date, which correctly here has been identified as a date. So you can see this icon, that's a date icon. Then these are have been identified as text, and these have been identified as numbers. And here are some more controls which we will talk about in further sections of this course. And up top here, also an important part of the connection manager, the live or extract connection. Once again, we will have a separate lecture on that, and we will understand what the difference is and when you would prefer to use an extract. For now, let's just leave it at live. So everything looks good over here. Now we can proceed on to the dashboard. So we would just have to go here, and we'll talk about all of this in the next section. I just wanted to show you here that we have a data column, and here we've got our data source. So this little icon is an icon that is used to illustrate a database. If we right click on it and click view data, you will see our data just as we saw in the previous window. The columns can be rearranged here. That happens. That's totally normal. But this is like a preview of the data just as we had before. So that's pretty much it. That's as easy as it gets to connect to a data source. And before we finish up this lecture, I just wanted to show you one more thing. So if I want to connect to more data sources, I can always go here. This is a new feature in Tableau 9 that you can click, just go back to the data source connections over here, or you can just go data, new data source, and connect from here. So if you want to connect to another data source, you just click this icon over here. But what we are looking at now is the types of data sources that Tableau can work with. So as we already discussed, there's Excel, there's a text file, which includes CSV files. There's Access databases. There's now statistical files. So this is a new feature of Tableau 9. You are able to connect to statistical files. And as you can see here, these are SAS files, SPSS files, and even R files for those of you who are interested in statistical modeling with R. Let's have a look what else we have. We've got Tableau server files. We've got Microsoft SQL Server. So we will have an example of this in the course. There's MySQL databases for online use. There's Oracle, and there's lots of other different types of servers here. So if you are doing, for instance, Hadoop and big data analytics. Then you've got Pivotal, Green Plum databases, PostgreSQL, and you even have SAP HANA here. So as you can see, Tableau guys are constantly introducing new connections to Tableau and trying to keep up to date with the technical trends. So that's just, even if you don't use any of this, just a good thing to have, kind of in mind, to know that Tableau is not this tool that will become obsolete one day. It's always changing and it's always adapting to the market and what's happening. All right, so that's it for today's lecture. We did connect very quickly. We just had a lot of discussions about other things. Going forward in the course, connections to data will be much faster. So there you go, and I look forward to seeing you next time. Until then, happy analyzing. From superdatascience.com. In today's tutorial, we will learn how to navigate Tableau, and we'll get to play around with the tool. So here you can see where we left off last time. We had just connected to our office supplies.csv data source. So let's move on to the Tableau workspace. Here you can see at the bottom a tab called Sheet 1. Let's click on that. And right away, we're presented with the Tableau working area. And it may seem a bit overwhelming at first, but that's exactly why in the previous section we had this quick agile run through where we very rapidly created a map, and it was quite intuitive, wasn't it? So that's exactly what we'll talk about today, how easy it is to navigate this workspace in front of us. So the two main areas here are the data connection on the left, or the data tab on the left, and the working area on the right. So this is where you will be creating things, masterpieces. So let's talk about the data tab on the left first. The data is always broken down into two sections, dimensions and measures. And there's a very distinct difference between them, and it's important to understand it. So dimensions and measures are roles, two different roles that any data element can take. And normally what Tableau does is into measures it puts any kind of numerical values, and into dimensions it puts all the categorical and kind of qualitative data. So that's the default setting for Tableau, and you're easily able to drag them around. So if you're not happy with something being a measure, you can put into dimensions like that, for instance, as easy as that. But we won't do that right now. So I just click Ctrl-Z there to undo an action. That's the standard Windows key to cancel something. So the other way to think about dimensions and measures is dimensions are independent variables and measures are dependent variables. So for instance, we have units. So how many units of a certain item were sold. And here we have region. So we can find out how many units in each region were sold. So region will be the independent variable and units will be the dependent variable because it will be grouped by region. And based on that definition, which is the correct definition, things might you might require to move things around from dimensions into measures and measures to dimensions. But we won't focus on that right now because Tableau usually guesses it quite correctly. Okay, so what do we have here as well? At the top, we've got the normal ribbon for Windows. So file, basically you can save your file, open a new file. Data, you can connect to new data sources here. Worksheets, so this is considered a worksheet. What we're going to be creating now is going to be a worksheet. And we will get to work with these elements a bit more in the future. Dashboards, we are not talking about dashboards right now. It'll come further down in this course. A dashboard is a combination of worksheets. A story can be a combination of worksheets and dashboards, and we will get to work with stories as well. That's a relatively new feature for Tableau. Analysis, it just basically specifies how you want to do your analysis on the current sheet that you're working with. We will be working with this tab a little bit in the future. Map, we'll work with this when we get to maps. Basically format, there are other ways to access formatting and we'll be doing that in the course. Server, we won't be looking at server right now. And window, help, these are just auxiliary functions. So then what we're going to look at now is basically we won't talk about this right away because we will get to know this ribbon as we progress through the course. But right now I'd like to focus on the main working area where we will be creating a worksheet. So here, the main elements are columns and rows. So most of your worksheets will be created by deciding what goes into columns, what goes into rows, and then what goes into these other elements, like what decides the color, what decides the size of your shapes, what decides what text is attached to your shapes, the level of detail. We will talk about aggregation more further in the course, and any tooltips that you want to pop by. So the easiest way to explore is probably to explore by doing. So let's drag a few things onto this worksheet. I would assume let's start perhaps with region. So we just drag it into the middle here. And so we've put one dimension in, and let's put another dimension, let's say units. And right away you can see that by dragging those two in, Tableau has decided to put region automatically into rows, and your units into, it's summed them up, so it's aggregated them by region, and it's put them into a label. And so here you can see that now you can tell right away how many units were sold in each region. So now we can just drag and drop here. So if we're not happy with having units here, we can put them into columns. And right away we have a bar chart. And now we can expand this a bit, and then reduce this a bit. Now we can see by region, we can also see how many units have been sold, and you can also see that there's a tooltip popping up every time you hover over one of the bars. Now there's a very handy tool in Tableau which is called Show Me here. So I encourage you to play around with it. I don't normally use it in my work because I already know what I want most of the time, but it gives you kind of suggestions and quick shortcuts to different things. So let's look at a pie chart, for instance. Here now we can see a pie chart instead of our bar charts. And now if we want to increase the size, it's a bit small usually, these pie charts. So first of all, we'll drag it like that. And if we're still not happy with the size, this is button over here, size. So just click that and you'll see how it grows. Well, that's a bit too much. So what does this show us? It shows us what region by color has what proportion of the total sales in units. Once again, we're just playing around now. There's no intention of for what we're doing. We're just exploring Tableau. So here you can see central, east, and west. And yeah, it's a pretty cool pie chart. But let's see what else we have. So we can do a bubble chart. Right away, Tableau puts everything in the right positions for us. As you can see, there's nothing in columns and nothing in rows. Everything's been put in here. Tableau has selected circles for us from this drop down and it's created this bubble chart. So what else? Then we can look at a tree chart, tree map. That's what it's called, tree map. So here, so it's like a bubble chart, but it's a bit different because it's got boxes instead of circles. And here, once again, the relative size of the box, the area of the box is directly correlated to the number of units sold in that region. You can just keep clicking around and you'll see different versions of the dashboard that or the worksheet that Tableau is suggesting for you. And maybe you might be happy with one of them, but we won't rely on that, and we will create our own version in the next tutorial. So before we finish up, I just wanted to show you that in this Show Me box, some of the things are grayed out, and that's because you need certain elements of data to create these. For instance, to create an area chart, you need at least one date. So 0 or more dimensions, 1 or more measures, and at least one date. Because we don't have a date in our worksheet right now, Tableau can't create an area chart for us. So if you want to add a date, you just drag a date in here, and now it's highlighted, and now we can create a area chart. But once again, we'll get to area charts, line charts, and all of these other things further down in the course. Today, we're just exploring Tableau. So I look forward to seeing you in the next tutorial, and until then, happy analyzing. Hello, this is Kirill, and today we will get to start solving the problem that we have at hand. Who gets a bonus? So we left off here last time. We were just playing around with Tableau. I hope you had a chance to explore further the different buttons and tools that Tableau has to offer, because the more you play around with it, the better you get at it, and it happens very quickly because Tableau is very, very intuitive. And that's just, we're talking just about the navigation. So you know basically where to look for what. Right now, I'll show you another cool feature is clear the dashboard. So we don't want any of this. And so there's a button over here, the red one, clear sheet. And so we're just going to click that and voila, everything's gone. By the way, if you're using the Mac or a MacBook, some of these layouts might be a bit different. So just kind of follow along and you will be able to find where they are, but just bear in mind that they might not be in the same exact place as I'm showing. Okay, so let's start answering the question. We already know that we can create bar charts. Let's create a bar chart for the representatives and see what they've sold. So we want representatives to be kind of in the columns. So there they are, our salespeople. And let's see how many units each one of these representatives has sold. There we go. So we can see that Richard has sold the most units, which is great. And how about we now break it down by region? So we know that we have 3 bonuses, one for every single one for the best representative in each region. And like this, we can't really tell who's the best in each of the regions. We can just tell who's the best overall. So what we're going to do is we're going to take region and we're going to drag it into columns, but we're going to put it before representative. So as you can see, I'm doing here, and I'm just going to let go. And what does that do? Well, it gives us a kind of another level on top of our representatives. So first, the chart is broken down by regions. So that you can see that here. So I'm just going to make this a bit smaller so I can zoom in. So here you can see that the chart is broken down central, east, and west. And then inside every region is broken down into by representative. And so that way we can easily tell who's the best in sales in each of the regions. So here it's Alex, here it's Richard, here's James. And so now I'll show you another cool feature. You can order these bars by their size. So if you see this little button here, so when you come roll over the axis, this little button here. So if you click that, automatically they're sorted by size. So you can see how it drops off. And you'd think that this answers our question, but in reality, no, it doesn't, because units is actually the number of items that has been sold. But as we know, our representatives are actually measured based on the dollar value of their sales. And so we need to find out the dollar value. But as you can see here, there's no actual dollar value, total dollar value of sales. We know that, and it's really easy to find it or to see that, because all of our numbers are kept in measures. So we don't even have to look here. We can see here that we only have units and we only have unit price. And we have some of these other fields, which we will talk about further down in the course. But like the ones from our data are units and unit price. There's no total dollar value. And that means that we have to create that total dollar value. How do we do that? Well, it's quite easy. You just have to multiply the number of units the representative had sold by the total unit price for those units. So if I click our data here, I go to view data, you can see here that when, for instance, Nick sold binders, he sold 29 binders at the price of $1.99 each. So the total revenue from that sale would be 29 times $1.99, making it somewhere around $58 for that sale. So we need to calculate that multiplied value, and apparently it's not present in our database or in our data set. So let's go ahead and do this in Tableau. And this is where we talk about creating calculated fields. So all you have to do is right click on measures, create calculated field, and we'll call it total sales. And here we will take unit price or units, and we will multiply units by unit price. We'll click OK. So now we have a total sales value. And as you can see, there's a little equal sign before the hashtag. That means it's a calculated field. So what we're going to do now is we're going to take total sales and we will drag it onto our chart to replace the units. So I'll just drag it exactly on top. And as you can see, Tableau picks it up and aggregates it just as it did with units. The other way to do it is you can take this one off, remove it, and then take total sales and put it on where you need it to be. And so now we have sum total sales. And now if we order by this value, you will see that we have a different picture. Now Richard is no longer the best seller overall. Susan beat him in the East region. Matthew is the best in the Central region. And James is still the best in the West region. So now we know who has deserved the bonus. It's Matthew, Susan, and James. And that was an example of how to create a calculated field in Tableau. Hope you enjoyed that, and I look forward to seeing you next time when we will be talking about colors. Until then, happy analyzing. Hello, this is Kirill, and a warm welcome back to the course on Tableau. Happy to see you here. Last time we left off after creating our first calculated field, which is total sales, and you can see it over here on the left. I just wanted to mention that creating calculated fields is a very important aspect of working with Tableau, because you will often find that the data that you have does not have the right level or does not have the right variables for you to work with. It does have the information there, but it's not in the right format. It's not aggregated properly or correctly for your needs, or it doesn't have the right level of detail or other things. So you will be inevitably working a lot with calculated fields, and this was a very simple example of a calculated field where we just multiplied two values. But Tableau has very vast functionality in this space and allows you to create just insanely helpful calculated fields, and we will be working with them going forward. So that's why I kind of put it at the beginning of the course, so you get used to it going as we go along. All right, so today we're talking about colors. Colors are important because as you'll probably hear me say quite often, data science is not just about crunching numbers. It's a form of art. It's a form of communication. It's a very creative activity or profession. So get used to working with colors. You will need this skill. Okay, so let's get straight into it. How can we color this chart? Imagine that this picture has to go into a presentation for the executives of the company who will be distributing these bonuses, or maybe even this picture will be hung up somewhere on a wall so that everybody can see. So you don't want it to be plain like this. You want it to be colorful and bright. So we need to use this color button over here, and there are many different ways that we can do it. First of all, what we can do right away is just change the color. We can change it to red, we can change it to green, we can change it to basically any color. And that's kind of the basic thing that you can do here. What you can choose more colors, and then you can choose even more colors. It's all under control here. What else you can do is you can change the transparency, but there's nothing behind it, so there's not much point. You can add a border, make that border thicker, I think, or change the color of the border if you want, but we won't be doing that right now as well. What we want kind of the colors to differ from bar to bar. So the first thing that you can do is you can take your representative, and let's say from here, and drag him onto the color button. And what that'll do is it will give each representative a unique color, and it'll give you a color legend over here. And so as you can see, the color legend matches your column names. So Matthew is blue here, Susan's light blue here as well. I wanted to show you a quick tip here as well. So by the way, going forward, I'll be showing you quick tips along the way, which I will be using just because they're kind of a habit, and I think you should get into the habit of using them too. So just keep track of when I give out these quick tips, because they will be very helpful. So let's take out the representative, and instead of taking the representative from here and dragging him onto the color, what we can do is take representative from here, hold him. As you know, if I just drag him onto the column now, then it'll screw up the visualization, because now he's no longer, or this column or this dimension is no longer in the columns. So I'm just going to press Ctrl Z now. what you need to do is you hold them, or hold this dimension, you drag them and you press Control, and as you can see, this little plus sign appears under your mouse, and then when you let go, you basically copied that dimension onto this new role, and it's still in the columns. So that's an easy way, especially when you have like 100, or 100 is maybe too much, like 30 or 40 dimensions here. It might be hard looking for it. When you know exactly what you want, it's already on your chart. You just drag it like that with Control. Okay, so we've got the representative here, and now if we're not happy with the colors, we can just click Colors, Edit Colors, and choose a different color palette. So Tableau has a lot of different color palettes that are already built in. Right now it's using Tableau 20, so you can say, how about we go for purple gray 12. You click Assign Palette, and now it's assigned a purple gray palette. That looks pretty cool, doesn't it? Now we can also, another good one is colorblind. So just to be cautious of people who might be colorblind, just click Assign Palette there. It will tell you that your colors are being duplicated because you have less colors than people, but you know, that might be okay for you as long as you want, because you do have the names underneath, so it might not be a problem. Anyway, I don't think this is the best way to color this chart. Let's have a look at another one. So I'm going to actually leave representative in color for now. And what we'll do is we'll take sum of total sales, we'll press Control, and we'll drag that into color. As you can see, representative has been replaced, and now sum of total sales is dictating a color. And now it's not a discrete color, it's a continuous color. And so the more sales you've had, the darker your color. The less sales you've had, the lighter your color. Also quite useful, but in our case it's not the best because we already see the size of the bar and it tells us how much sales each person has had. So maybe a different approach. My favorite one in this particular case will be if I take region and I drag region onto color. By the way, I'll just Control Z that. You'll see that I can also drag region, Control it, and then replace this current dimension that's in color. Or not even dimension, this is a measure. So replace that, and now you can see that your bars have been colored by region. And I think, personally, to me, this appeals the most because I can right away visually see that these are three distinct regions or three distinct elements, and that kind of also backs the idea behind why there's three bonuses and that these people don't have to be compared to these people, and these people don't have to be compared to the rest of them. And so personally, I would leave it at that, and that's how you work with colors in Tableau. We will definitely be talking more about colors along the way in this course. This is just the basics, and have a play around with that. See what personally appeals to you the most, and it's a very individual preference. So find your style, and I look forward to talking to you next time when we'll be discussing labels and formatting, making our chart look really appealing. And until next time, happy analyzing. Hello, this is Kirill, and welcome back to the course on Tableau. In the previous tutorial, we had a play around with colors, and we had a look at 3 different approaches that we could take to coloring our bar chart. And we also discussed that coloring has a lot to do with personal preference, because I might find something appealing, but you might not find the same approach appealing, and vice versa. And therefore, there is that element of creativity. And I do hope that you had a chance to play around with colors a bit more to kind of understand what you're leaning towards, what color palettes you prefer, what styles and approaches to coloring you enjoy more. But in any case, don't worry, because as we progress through this course, you will naturally start developing a unique approach to coloring, to formatting and adding labels, and creating your own unique visualizations and developing this unique style of visualization. And today, let's move ahead and talk about labels and formatting. So we've got this chart in front of us, and as we discussed, there's a very high likelihood that this chart might be featured in a report or be posted somewhere on a wall. So we want to make it look very schmick and just very, very appealing to the eye. But that is not the only thing we're pursuing today. There is one more thing that we are after, and it might be, it is definitely as important as making the chart look awesome, and that is ease of understanding. Let me demonstrate with an example what I mean. So here on this chart, we definitely have all the information that we need. We've got the names of the people, we've got the regions that they're working in, we even have the total values of sales that they have performed, and so the bars have this axis, and you can, by looking at the bars, tell how much approximately each person has made in sales. So let's see what happens if, for instance, I ask somebody to tell me how much sales has Bill made. The person has to find Bill, so we'll look around and we find Bill here. Then the person has to move their eyes up to the top of the chart, and then the person has to, don't worry about this pop-up on the right here, it's just in Tableau, so when you do produce this report, you won't have this pop-up window. So once again, the person has to find where Bill is, move their eyes to the top of the bar, and then move their eyes to the left to understand where the total sales sit. And here they sit at about maybe 1,000. They're between 1,500 and 2,000, so maybe they sit at around 1,750 or 1,800. Let's do another one. Let's see how many sales James made. So once again, we find James, we move our eyes to the top, then we move our eyes to the left here, and we can see that James is somewhere between 1,001 and 1,500, but because he's further away from the axis, there's a bit more room for error. So maybe he's with this eye movement, maybe he's sitting at 1,600 or 1,700. We can't really tell. And so that means that the person who's reading this chart has to put in some effort to get the information out of it. And that's not the way it should be. Tableau is a tool that allows you to very easily create visualizations, but also it has the capacity to make those visualizations to be very, very easy to understand. And that is an art form in its own. That is a part of what data scientists do. We look for ways to communicate information in very simple forms so that people don't have to put in effort to understand it and extract information visually from what we're presenting them. So let's try fix that. What can we do? Let's try adding a label. So here you can see this button over here, label, and what that does, it adds textual information to the chart. And what we're going to add is we're actually going to take the sum of total sales, we're going to hold it, press Control, and drag it onto label. And as you can see here, now the actual sum of total sales has appeared on the bar chart. Oh, actually, James was between 1,000 and 1,500, so that's, yeah, definitely not 1,600. There you go. Now we can actually see the exact number of sales that each of these people has made. And that already makes analysis or reading this chart much, much easier. Now, while we're on the topic of labels, we can add more information to labels. So let's say we want to add representative. Just drag him into label. Now we have the name there as well. We can also drag region. But that's a bit excessive because we already have the representative name here and we've got the region name here. And moreover, the region is the same for all these blue bars, the same for the orange and green. So that is definitely excessive, and we're just going to remove those now. So we'll take region out and representative out. And now we're left with the total value of sales. Now, you can edit the label further if you go into label and then you click this dot button here. You can add your own text if you like. So you can say sales, colon, okay. And so here now you can see that your text has appeared in the label. Also, you can see that this label is not displaying any text because it is too big. It would overlap this label. And you can fix that by right-clicking and saying mark label, always show. And that way, it's always going to be displayed. So now we're going to go back to label, go to the dot. We're going to take out this sales text, and we're going to click OK. So what we want to do now is we want to fix up the formatting of our chart. And that is probably the last step to getting our chart to the ready for production level. So let's start with the labels. If you want to change the size of the labels, you just go into label over here and you select size, and you select the size that suits you. So let's go with 12, and maybe you want to make them bold. That looks pretty good. Also, if you go into ... you can do the same here. So 12 and label size. Also, you can change the color. You can do a lot of things, but we'll keep it at black for now. So that's good. That part's done. Another thing that we want to do is we want to change the type of label, and I'll explain what I mean now in a second. So we'll just right click on the labels here, and so this is where you normally go to format things. Labels have their own formatting over here, but all other things in Tableau have formatting through this right click format button, which is pretty much the same as going here and selecting font or other things like alignment and so on. So here in when you right click and you go to format, once again here you can change, let me close that again. So right click format. So this is the axis. You've got to be careful here. You got to go to the pane because the label is in the pane, not on the axis. And here you can change the type of label. So just to prove that this is label, if I change this direction, you'll see that the label is changing its direction. Once again, you can do the same thing from here. You can change the alignment like that. What you can't do from this, from here, is the type of label and the type of numerical label that we're using. And in this case, we're using numbers. So let's go ahead and change that to currency. Let's say we want dollars. So we'll go currency custom. As you can see, it's automatically moved because it's not fitting, but it will take out 2 decimal points. And now you can see that this is much more appealing. It's got the dollar sign in it. And now also, let's say we want in units of thousands. So let's say K, and we'll add 1 decimal point back. So that's even better. So now we can see approximately how much sales each person's made. It's very, very easy to digest. There's no numbers that, that are unnecessary. One thing you should be aware of is you can't really change the font size through this menu here. You see, I'm trying to change the font size, but it's not changing, and that's something just like a feature of Tableau that hasn't been looked at. That's because the label font size actually overrides the font size that you select here. So be careful of that. Okay, so we've formatted the label. Now what else we're going to do is we're going to format the axis. So we're going to right click on the axis, once again format. We're going to go to axis here, and we're going to change this to 12. So kind of it's best to keep the size consistent throughout. Then we'll go to this axis. We'll also click format, and we'll change this to 12. You can see that Matthew is not fitting in, so maybe make this a little bit bigger. Now Matthew fits in as well. Format this axis, change this to 12. This is actually unnecessary because we know that central means region, and we know that these people are representative. So we'll just right click and we will hide field labels. And total sales, one more thing. So here we will right click, edit axis. We'll split total sales by the 2 words because that looks better. And also one more thing, if we edit axis, if we format the axis and we go to axis here, what we want to do is we want to make sure that these are also dollars. So currency, get rid of that, make it K, and there we go. So now it's consistent. You've got K's here. Also, it would be better to probably put 1 decimal place back because there is 1 decimal place throughout the chart. And that's how we format charts. In the next tutorial, we will look at how we can export this chart into other documents. And I look forward to seeing you next time. Until then, happy analyzing. Hello, this is Kirill, and welcome back to the course on Tableau. And in today's tutorial, we will learn how to export our worksheets as images for other files. Okay, so I'm just going to quickly close this format window here. All right, so we've got this beautiful report that's ready to go, how do we put it into a document like a PowerPoint or a Word document and so on. So one way is to take a snapshot, and I knew a friend of mine, he didn't know how to export and he kept taking snapshots. So you just take like a print screen of this report and then you stick it into your file. Well, that's not the proper way to do it. There's definitely a way to export files directly from Tableau, and today we're going to learn how. So right away, this is a worksheet as we discussed. So if you go into worksheet and you go to export, you go to image, you can copy the image. So I'm just going to close that because there's another way of doing it a bit faster. You don't have to move your mouse all the way up there. This is one of those tips and tricks. So if you right click and you go copy, you go image, you get the same menu. So there's two ways to export. So all we need right now is the view, the title, and the color legend. So we don't need the caption because we don't actually have a caption. We haven't created one for this chart. We'll talk about captions further in the course. They're pretty easy. So we'll take caption out, and we'll talk about this menu in a second as well. So we'll just click copy. Now let's bring up the document. So let's say I want to export this image into a Word document. So here I've got a Word document prepared. It's the annual bonus report, and I want to put the image in here. So what you need to do is obviously Control V or just right click and paste. And there you go. So there's your image here. So this underline is because I had the underline over there. So that's the image. It blends in really well. But what do we see about this image that is right away not good, wrong? Well, we see this name over here. So what went wrong? Where did it come from? Let's go back to Tableau and find out. If I click on Tableau, you can see that there's no name here. But sheet 1 sounds familiar, doesn't it? That's the name of the tab here. So that, remember when we exported the image? So if we go to right click and then when we go to copy image, here it says title. And title is actually the name of the tab. So you either have to unclick title or just change the name of the tab. And so let's do that. So I'll go into the name of the sheet. I'm going to call it annual bonus analysis. And now I want to see it here as well. So I'll go to worksheet and I'll click show title. So here now I can see the annual bonus analysis name, and that also gives me the power to change and format it. So if I click here and I click format title, as you remember, our formatting pane pops up on the left, and I can actually this doesn't allow you to change the size of the text, so we're going to have to work on this a bit. You need to double click on the title to be able to format the size of the text. In this case, it's 12, it's bold, so it's all right. It's the same as the rest that we have here. So just if you do need to change the format, that's how you do it. So I'll just click that. And now we can right click, copy, image, view title, color legend, copy. Now let's go back to our document, delete that, and paste in our report. Once again, this underline, should get rid of it. Okay. So here now you can see annual bonus report analysis at the top. And that's good. So that's pretty much ready to go. You add some text for the executives and it's ready to be presented. The only thing is, if you want a bit more space, so if you want this chart to be a bit bigger, then you want region at the bottom, and that way your chart can expand to the right. And that's what we'll try to do now. So we'll right click, copy, image, and color legend. So, but here we'll put the color legend at the bottom. We'll choose that one. Go back here and paste. And as you can see, the color legend is at the bottom and the chart has a bit more space. So that's the other way you can do that. So that's pretty much done. I just wanted to show you another tip and trick that I have for PowerPoint. So in PowerPoint, there's two things that you can do. Once you've copied it, so the worksheet is currently sitting in our Control C, or we can paste it anywhere we want. So I can paste it, but as you can see here, and I'll zoom in a little bit so that you can see a bit better. You can see that the text is actually a bit blurry in the whole of the image, and my PowerPoint's a bit old. It's still 2003, so whether I press Control V like that or whether I right click and paste, it's going to be the same. But if you're using PowerPoint 2007 or higher, then if you press Control V, it will be blurry like this. But if you right click and you paste, you will find that it'll be very crisp, just like it is here in our Word document. So that's another tip and hack for you for using PowerPoint. I'm quite sure that you're probably going to be using a later version of PowerPoint. So do right click and paste rather than Control V into PowerPoint when you're exporting your Tableau worksheets. And so that sums it up for us for today. I just wanted to tell you that we still haven't saved our workbook, so make sure you do. So you go to File, Save As, and obviously, for this workbook, it's Section 1. Just make sure you keep it saved because Tableau doesn't actually auto-save your work, and you want to keep it for yourself for the future. And that is it for this section. I hope you enjoyed it. Very easy introduction to Tableau. That was an easy data set, but it did help us get our head around a lot of things. And we talked about navigating Tableau, creating first calculated field, adding colors, labels, doing formatting. So all of that together, that's our base. We're going to take that forward in the course. But before you do proceed with the next lecture, do not forget to do the quiz. It's right under this one. It will help you make sure that you've covered everything that we talked about in this section. I look forward to seeing you in the next section, and until next time, happy analyzing. Section recap. I hope you're enjoying your acquaintance with Tableau. It's really a very powerful and incredibly unique tool. We are definitely benefiting from having it in data science. It has made the work of data scientists so much easier, so much more enjoyable. And today we'll have a look at what we learned in this section when you were getting to know Tableau for the first time. In this section, we learned, number one, how to connect Tableau to a CSV file. As you saw, it's a very simple, very straightforward process. You just point Tableau in the direction of your file and it connects automatically, and from there you just take it to the visualization phase straight away. You don't have to waste your time on any data loads or anything like that. Everything's done for you. Number two, how to navigate Tableau. Very easy as well. As we saw, there's quite a few menus, but they're highly intuitive, and you get to learn them along the way. And I'm sure after these couple of tutorials, you're already much more comfortable with Tableau than you were at the start. And that's the way the tool is built. It's very, very simple, and that's why we like it so much. Number three, the difference between measures and dimensions. Very important core difference. One of them basically represents variables, independent variables, and the other one represents dependent variables. And Tableau is able to pick up your measures and dimensions from your data set automatically by looking at things like, is it a numeric variable, is it a string, and so on. But you're able to also adjust that and convert measures to dimensions and vice versa by simply dragging them into the correct pane. Number four, how to create a calculated field. You'll notice that a lot of courses out there talk about this way down the track, but I brought it in the very start, in the very first section about Tableau, because I feel that this is an important topic. It's not that complicated, and as you saw, it is pretty simple to create a calculated field. You just type in a formula, give it a name, but at the same time, it greatly expands your flexibility and your control over your visualizations. So good that we covered that off early, and that is something that will definitely benefit you along the way in your future work with Tableau. Number five, at least 3 ways to add colors in Tableau. So we talked about adding colors based, in this specific example, based on the representative's name, based on the amount that was actually sold, so the sales, and also based on the region. And once again, Tableau is like art, or visualization is like art, so it's everybody's own personal preference. You might have a different style to me. So play around, find what your favorite colors are, find what your favorite style is. There is no right or wrong answer here. Everything works as long as it makes sense, as long as you can convey the message you want to convey to your audience. Number 6, how to add labels and formatting to your charts. Also very important because it makes your visualizations look pretty and makes them legible. And finally, how to export your worksheet. So I showed you the correct method of exporting your worksheet through the right click and paste rather than just pressing Ctrl V. That will make sure that your visualizations are crisp and clear in your PowerPoint. So I hope you enjoyed this section, and I can't wait to see you in the next one. Until then, happy analyzing.
In this section, we will learn how to search for various anomalies and dependencies in our data. And I will show you my own unique way of running an improvised A/B test in Tableau. Now, I do appreciate that all of us might be coming from different backgrounds and different work environments. So if you find that the things that you're learning in this section are very applicable to your role, to the work you do, then that's great. I'm really happy we've hit the nail on the head. However, if you find that the things you're learning are not as applicable, then don't stress out, because you will still learn a lot of great methods, you'll get some good ideas, but most importantly, through the exercises that we do, you will really learn Tableau. So let's jump straight into it.
All right, so to get the dataset, you need to go to superdatascience.com/training. And then if you scroll down, in part 1 visualization, we need this section 2, how to use Tableau for data mining, this data set. So once you've downloaded it, it's a couple of megabytes, I think. Then if you go to visualization section, or this is the folder that I created on my desktop, it's got 3 sections for this part of the course, and then churn investigation. There's churn modeling. Oh, it's just below a megabyte. So we're going to open this up in Excel. Let me just drag this here. And the interesting thing about this data set is it's actually the same one that we're going to be using for modeling down the track in the next part of the course. And therefore you get kind of a sneak peek of what to expect. It's always a good thing, and that's how you would normally do it in a data science project. You would investigate your data set, you would mine it for data, and then after you have some insights, you would only then go ahead and create the model. So kind of we're doing it in the right chronology there. Anyway, so what is this data set? It's quite a large data set. It's got 10,000 rows. It's got quite a few columns. This is a list of customers of a bank. Of course, this is all fictionary, so not a real list of customers of a bank. And they've got customer ID here. They've got their surnames, the credit score of the person, where the person's banking. So let me explain the situation. There's this bank in Europe. It has operates in 3 countries: France, Spain, and Germany. And it's got a lot of customers, but recently they've been seeing a problem. A lot of customers have been leaving the bank, not normal churn rates. So churn is when people leave a company, and something they're not used to seeing, and they decided to hire you as a data scientist to investigate this situation and tell them what exactly is going on, and give them some insights into the problem so they can come up with ways to fix it. So what this data set represents is it's not all of their customers. This is a massive bank. So this is just a small sample of their customers. And what they did is they took this snapshot of their customers. They took 10,000 customers, randomly selected 10,000 customers. And then they said, okay, let's find out everything we can about them. Their customer ID, surname, credit score, geography, where they bank, gender, age, how long they've been with the bank, that's tenure, balance, number of products they have with the bank. So do they have a credit card, a loan, maybe a savings account? Do they have a credit card or not? Are they an active member? So have they logged into the online banking in the past month? Or the definition of this can be different. It can be, have they logged into their online banking in the past month? Or it can be, have they made a transaction in the past 2 months? Or something like that. So it can be anything, but they gave you this variable as a flag, so you can go ahead and use it now. And then like you would either know the definition as they give you the variable, or you can find out later if you find that this is an important variable. Estimated salary, so how much does the bank think they're earning, because they can't tell, they don't know that information. They estimated the salary. And then they didn't have this column originally, so what they did is they found out all this information, and this is how these things are normally done, right? So when you have a problem, you want to run a test. So they found these 10,000 customers, randomly selected them, found all this information about them, and then said, okay, so we're going to watch these customers for 6 months. And within 6 months, we want to find out who of these customers will leave and who of these customers will stay. And that's how this column appeared. So 6 months later, they went back to this list and they checked, okay, who left the bank? And if the person left the bank, they put a 1. If the person is still with the bank, they put a 0. So basically what this means is that you have some information on customers which was measured before, 6 months before the event or the second measurement took place. And then when the second measurement took place, you kind of know now, okay, 6 months on the track, which customers are more likely to leave, or which customers actually left. And from this information, all of this information together in here, you need to derive some insights for the bank and tell them, okay, maybe, like things that you can observe, some trends or some behavioral tendencies. So this is what we're going to be analyzing, like behavioral segmentation. It's going to be fun. We're going to look at, for instance, are females more likely to leave the bank than males? And this kind of makes sense, right? It's a basic A/B test. You want to see, all right, how many female customers left, how many male customers left of all of these totals, and then obviously you have to normalize it by the number of total female and male customers, because this is probably going to be disproportionate anyway. And then you want to find out, so based on this column, who is more likely, females or males, or is it equal? And then you report that to the bank and you tell them, okay, actually, imagine if you see that only female customers are leaving. How valuable is that to a bank? They'll be like, oh, we're definitely doing something wrong, and we need to cater for this segment of our market and make sure that our offering is the right thing, exactly what they're looking for. Or maybe there's a competitor, a bank, in one of the regions, there's another bank that is taking away all of the customers from this bank. So there's lots of things that you might be able to find, and you will find in the upcoming tutorials. It's going to be fun, and this is how you investigate. You will learn how to investigate data sets like this. So look for dependencies when you have like a binary outcome. And it doesn't have to be customer data. So for a lot of customer-centric organization, this is going to be valuable. So I've done this personally. I've done this so many times. It is such a value add to any customer-centric organization. So whenever an organization deals with customers, this is a lot of value add. This is we're slowly venturing into the territory of segmentation. And then the other thing is, even if your organization is not dealing directly with customers, or you don't have data sets like this, or as a data scientist, you're working on different projects, you will still find a lot of valuable insights here. How to run A/B tests in Tableau, how to work with chi-square tests, what they mean basically. And even just working with Tableau will be very valuable along, learning how to work with Tableau will be valuable along the way. So without further ado, let's get straight into it. We're going to get started in the next tutorial, and I look forward to seeing you there. Now that we have downloaded our data, let's get Tableau fired up and we can start this analysis. So we're going to connect to a file, and this time it's going to be an Excel file. And here we will select the file that we downloaded, click open. And as you can see here, there was only one tab, so Tableau chose it by default. If you have several tabs in your Excel file, they'll be all listed over here. And here you can scroll through, just check everything is okay, everything looks fine. We've got all our 10,000 records here, and that's pretty much it. So we've connected the file to Tableau. Now what we can do is do something interesting here while we're here. As you can see, we've got geography. So how about we visualize a map of our customers and see where they're from? So if we drag geography onto this area, we expect a map, but nothing happens. We only get a column with the different geographies. So why is that? Why is this action different to the one we undertook previously in our first tutorial about Tableau? Well, the reason is because geography here isn't recognized as an actual geography by Tableau. It's being recognized as a text field, and you can tell by the ABC label over here on the left. So we can very easily fix that. If you go to geography and you click this drop down, and here you select geographic role, and because we know from what we see in our visualization right now, we see that it's a country. So how about we select country region over here? Now we're going to just get rid of geography and do that action again. As you can see, it's changed to a globe. So it's no longer ABC, it's a globe, meaning that it's been recognized as a geography. And also there's latitude and longitude columns that have been generated for us. So if we drag geography into the middle, this time we see a map. So I'll make some space. I'll make this map a bit smaller so we can zoom in a little bit. All right. Now what we want to do is we want to get rid of these dots and change them into an actual color. So color the countries that our customers are from. And in order to do that, we have to select a measure. And I would like to know how many customers I have in each country. And because I know that in my data set, every single row is a new customer, what I can do is I can use number of records. That way, Tableau will visualize the number of rows that are associated with each country. So I'm going to take number of records and drag it onto color. And right away, you can see that our colors have appeared. Now we can tell that most customers came from France and about the same amounts came from Germany and Spain, but we don't know exactly. So what we need to do is add a label. To add a label, we're going to go to number of records again, and we're going to drag it onto label. So now I'll zoom in a little bit. Oh, actually, it's a bit too much, so I'll keep it like that. I want to increase the size of the text. I'll just click on label, drop down here, and maybe make it a 14. Maybe that's a bit too much. Make it a 12 and make it bold. So that is how many customers we have in each country. And if you want to zoom in specifically, you can select a region here and you can do like a zoom area like that. And you select what you want to zoom into. Okay, so here we can see that most of our customers are from France, approximately half, actually more than half, because we only have 10,000 records. And Germany and Spain have the same number of customers. So that's just a basic thing to check about our data. And in the next tutorial, we will start actually performing the data mining tasks. And I look forward to seeing you next time. Until then, happy analyzing. In this tutorial, I will show you how to run simple A/B tests in Tableau. And as you will see, they will be extremely visual, just like everything else in Tableau. To start off, we're going to save the name of this worksheet, and I'm going to call it map so that we can remember what exactly it contains. And now I'm going to go to File, and I'm going to save the whole workbook. So I'm going to click Save As, and I'm going to call my workbook Data Mining, and I'll save it into the same folder as the dataset. By the way, if you're using Tableau Public, the free version of Tableau, then you will have to save your workbook to the Tableau Public servers. But that's not a problem because we're not working with sensitive data here. This is all mockup data. So now what we're going to do is create a new tab or worksheet. And in this worksheet, we're going to run our very first A/B test in Tableau. So the first thing we need is the dependent variable that we're examining, which is exited. Did the person leave or not? And as we can see, it's in measures at the moment. So Tableau has recognized this column as a measure, meaning that it's looking at it as a number rather than as a category. For us, exited is actually a category. Did the person leave or not? So it's basically a flag. And that's why we need to move it into dimensions. I'm just going to drag it into dimensions as we saw in the previous section of the course. And now we have the exited flag here, and we can start constructing our A/B test. And I will show you a step-by-step method to perform this visualization of an A/B test. So let's get started. The classic and most commonly used example of an A/B test is an A/B test for gender. So how about we run one of those for our data set? And basically what we'll be testing is if we hold everything else equal and we take a male customer and a female customer, which one of them is more likely to exit? So let's take gender and we will drag gender onto columns. Now we got two columns, male and female. Now what we want to do is take exited and drag it onto color. This gives us two colors, blue for 0, meaning people who did not exit, and orange for 1, meaning people who did exit. And now we're going to take number of records because we want to see how many people actually left, and we will drag a number of records into our rows. So I'm going to move this up a little bit so that we have some space. So what you can see here is there's more males than females, and of the females, quite a large portion left, of the males, a small portion left. However, this is not sufficient for us to understand what exactly is happening, and we have to fix this up a little bit to visualize the A/B test. First of all, let's add the total number of records as a label. We already know how to do that, and we'll take number of records and drag it into label. And let's increase the font of this label so we can actually see it, right? Make it bold. There we go. So that's how many records we have in each of these boxes. Now, what we want to do is we want to replace the actual number of records with a percentage. So we want to see, rather than the absolute value of female customers that left and these ones left in the orange bar and the ones that stayed, we want to see the percentage. So what percentage of female customers left and what percentage of male customers left? Because that way we'll be able to compare them to each other. Right now we can't compare them because there's a different number of total customers in each of these groups. In order to convert these absolute values into percentages, we need to go to the drop-down menu of this sum number of records. Now, here we need to select Add Table Calculation. Once we've selected Table Calculation, we need percentage of total. And here an important step is to change from table across to table down. And what that will do is it will give us a percentage of total in each column. So we click OK, and as you can see, the number has changed. What we will do now is we will format the label. So we'll right click, we'll go to Format, and we'll change this to percentage just to 0 decimal places. And finally, to make this consistent, what we're going to do is we're going to take a sum number of records, the table calculation, and you can see that there is a table calculation by this little triangle that has appeared on the right, and we'll hold down Control and we'll drag it to replace the existing sum number of records in the rows area. What that does is now it's consistent, and even the axis over here represents the percentage. Before it was just the absolute value, but now the height of the bar and the label inside the bar are actually aligned. And so let's analyze this for a second. From here, we can see right away that irrespective of the number of female and male customers, the percentage of male customers that left the bank is only 16%. And that is less than the percentage of female customers that left the bank. So the conclusion that we can make from here is that female customers are more likely to leave the bank than male customers, all other things held equal. And bear in mind that this is not the full statistical A/B test because we did not check for statistical significance. However, this is a very quick and convenient and visual approach which can give you very fast results. And then if you find something of interest, you can go and investigate it further and do the proper statistical A/B test, check for significance and things like that. But personally, I really like this approach. I like this method because it helps me focus on things that actually matter and not waste my time on variables that don't actually affect my end result. So we'll be doing lots more of these in this section. Hope this framework is useful and you will see how powerful it is as we go through the tutorials that are ahead of us. I look forward to seeing you next time, and until then, happy analyzing. In the previous tutorial, we stopped after we made this visual A/B test, and we have the results here. So I really hope that it was quite clear what exactly we did. We have now percentages of the total males that left the company, so those are the orange, and the percentages of total females that left the company, 25%, also in orange. And so now just comparing them visually, you can say that females are more likely to leave the company than males, all other things held equal. However, do bear in mind that once again, this is not a full fledged statistical A/B test. We didn't check for statistical significance, but it does give you some insights into the data. So today what we're going to do is we're going to learn how to work with aliases. But before we proceed, let's quickly fix up the format of this tab. So we're just going to right click somewhere not on the data, and we'll click format, and we'll change this to 12, so it's 12 overall. Now the beauty of using Tableau for data mining rather than visualization is that you don't have to always make things look great, because you're not going to be presenting every single chart that you're creating. For instance, I'm not going to change this header over here. Like if I was going to put in a report, I would change it. But in this case, it's just for our sake, so I'm not going to rename the y-axis over here. So now what I want to do is I want to rename the sheet. So here we'll call it gender. And now working with aliases. So here you can see that we've got exited 0 and 1, meaning 0 is people who didn't exit, and 1 is orange, people who did exit. Now, even for our sake, let alone when we put this into our, if we decide to put this specific chart into a report, this is a bit, it's not that obvious. So why is it a 1, why is it 0? People don't think in binary terms, people think in words. So how about we change these and give them some aliases? So one way is to create a calculated field. Another way is to actually change your dimension or your column. You're not changing in the data set, we want to change it in Tableau, because we know that for every single chart we create, we want this to actually say words rather than numbers. We're never going to use the numbers, we're never going to add them up or do anything with them. So we're going to right click this exited column, and we'll go to aliases over here. And so now in aliases, you can specify what alias to use for certain values. So let's say if our value is 0, then we want to say stayed, right? That person stayed. And the value is 1, we want to say that that person exited. Okay. And so right away you can see that the values changed over here in the color legend. And they're going to be like that throughout every worksheet that we create, so it's going to be much more convenient for us. And now, because we have these aliases, we can even drag the this column onto our label as well. So here you can see it's much better now. People don't have to look at the color legend to understand which people stayed, which people exited. So you can do it either way. If you feel that this is sufficient for you, then go ahead with that. If you want to present and perhaps you want to make it more clear what exactly is going on, then I would put the exited in here. Of course, you have to make sure that it fits, and we'll see that. We'll talk about that later when we're creating more of these. So that's how you work with aliases. Hope that was useful, and hope you do find ways to use aliases in your work. They can really make life easier and make your presentations more legible. And I look forward to seeing you next time. Until then, happy analyzing. In the previous tutorial, we learned how to work with aliases. And today I'll show you how to add a reference line to your chart. But before we continue, I wanted to show you another cool trick in a Tableau. So here you can see that your labels are ordered in a specific manner. First comes the label for the percentage, and then the label for the actual class or the classification. So if you want to change them, all you have to do is drag one on top of the other, or change the order here in the marks pane. So I'm going to take exited and put it above some number of exited, which is our table calculation. So now you can see that first we see the classification and then we see the percentage. Personally, I think this looks better for this type of analysis. And we'll leave it like that. Now I'll show you how to add a reference line. So why would you need to add a reference line? Well, in order to compare your results that you see here with some benchmark. And what will our benchmark be? Well, how about we check how many people exited the company from this sample on average. So generally speaking, without looking at any kind of classification, male, female, country, credit score, anything, we just want to see what is the percentage of people that actually left this company from this sample. And we can create another chart, so we can do this, a similar procedure, but omit a classification. However, because Tableau is so convenient and it's so easy in terms of drag and drop, all we have to do here is just take gender and remove it from the columns. And let's just make some more space. And right away, you can see that we've got our new chart. So there's no classification here. And out of the whole sample, there's 80% that stayed and 20% that left. So now we know that the exit rate is 20%. And we can always get back to it this simple way. Just remove your classification and your chart will collapse into just the overall picture for this whole sample. So I'm going to press Ctrl Z twice now to return gender. But now that we know that 20% of people left, how about we add a reference line so that we can then look at it and compare our exit rates that we see for different classes to the overall exit rate. So we're going to right click the axis, and here we'll check or select add reference line. And here you've got a couple of options. So you can add a line, you can add a band, you can add a distribution, you can add a box plot. They're pretty self-explanatory. We're going to work with a line, and we want to add the line for the entire table. So not per pane or per cell. And here it might be a bit confusing because you've got first you have to choose the value, and it's a bit like non-intuitive what you got to do here. Well, actually you got to change this one first here. So you can either do the sum of a certain value, and this value has to be present in your worksheet. So that's why we only see this table calculation, because that's the only measure that we have present in our worksheet. Once you have more, you'll be able to select different ones. But in this case, we don't want sum, we don't want minimum, maximum, average, median. What we want is a constant, and that's why it's a bit confusing, because constant has nothing to do with this specific value. All of the other ones, yes, they work with this specific value that you choose. But as soon as you select constant, the value disappears and you can enter a constant, and that's what we need. So we're going to change this to 0.2. So that's our average. Here you can change the label. So what will it show? It can show nothing. You can show the value and show the computation. So that's when you have like a computation here. You can add a custom label. So in this case, we don't want any label because we already have an axis which tells us 20%. Line. So what type of line do you want? Do you want a dotted line? Do you want a even smaller dotted line? You can change the color. I'm just going to leave it at a standard line. So for 20%. And that's pretty much it. So once we click OK, we've got our 20% line, and we can see that females exit or female customers are more likely to exit than customers on average overall, and male customers are less likely. And that makes sense because we only have two categories here. So obviously if one is greater than the other, then one's going to be above average, one's going to be below average. And that is how you add a reference line to your chart. And in the next tutorial, we're going to start replicating this chart for other classifications, and it's going to be lots of fun. So I look forward to seeing you then. Until next time, happy analyzing. In the previous tutorial, we added a reference line to a chart, and today we're going to start replicating this chart and analyzing other categories. So it's very easy to replicate this A/B test. All you have to do is right-click your tab over here and click duplicate sheet. And I'll rename it right away because we'll be analyzing country. And this framework that I have shown you here, it actually is very simple to alter for different classifications. And the beauty of it is that over here, we only have gender one time in a whole tab. As you can see, it's not in the marks, it's not in the rows, it's only in the columns. So whenever you want to change the category, all you have to do is drag your new category on top of gender and replace it. So in this case, we're talking about geography. Let's drag geography, replace gender, and let's make some room. And bam, it's all done. We've got our reference line, we've got our labels, we've got our percentages. Everything has been done for you. So you see how quickly it is? And this is why I am a big fan of data mining through Tableau. You can talk to your data and it just happens like lightning fast. And so here right away you can see what's going on. Okay, so Germany, people in Germany are exiting the bank at a rapid rate. 32% of customers in Germany left over the period of the observation. And France and Spain are below average. Once again, it makes sense that these two are below average because they're equal and approximately equal, and this other one is above average, so they have to be below. So right away from here, we've got some insights. We can, run to the executives or to your manager and say, hey, something's going on in Germany. Maybe there's a competitor there. Maybe the products are not suitable for the market. Maybe there's some sort of new legislation. Something is going on, and you can already start digging into this deeper. That's how we do this is not actually an A-B test anymore, because there's 3 categories. So this would be an A-B-C test, or you can just call it like a classification test or categorization test or something like that. But you kind of get the picture that we can see that there is an anomaly. Something's going on in Germany. And that is exactly what we're looking for. Through this process, we're interrogating the data to look for anomalies. And once we find them, we can investigate them further and take them to the next level. So now what we want to do is do another one. It's so quick and easy. Why don't we do a couple more? So let's right-click country and duplicate sheet, and let's look at another variable. So I'm not going to rename it for now. Let's select a variable. Here we've got some measures, so actual numeric variables. And here we also have some categorical variables that happen to be in our measures, like has credit card. That is a 1 and 0 flag, right? So we need to change it into dimension. We don't need it as a number. So let's drag has credit card into dimensions. And let's now drag has credit card on top of geography. Once you've done that, what do we see here? That in fact, there isn't much of a difference between has credit card, yes or no. And once again, here you can see the aliases are not fixed up. So let's do that. Let's go to has credit card and create some aliases. So here we can say has credit card. So 0 would be a no, and this would be a yes, and okay. So here we can see that 20 of the people that have a credit card, 20% left the company, and the people who don't have a credit card, 21% left the company. And why I say that there's no big difference? Well, because the difference is only 1%. And more importantly, remember that this is not a full-fledged statistical A-B test. And if you do run the statistical A-B test, then little differences like that, when there's only a 1% difference, they require a very large sample size to be statistically significant. And in our case, it's only 1,000 people. So you could check and take this further. But my point here is that this is not your best investment of time. You would much rather look at country or gender, because there the differences are massive, and there you can actually have a impact and maybe make some business rules or business decisions around what you're going to do to fix the problem. In this case, there's not much to fix. There's only a 1% difference. So now we're going to rename this tab to has credit card. And let's do one more. So let's look at our variables. We've got is active member here. So people who have been active in the past couple of months, a bank can determine that in different ways. So it can be whether a person has logged in the past 3 months onto the online banking, whether they've made a transaction in the past month or so, and the period can be different. So there's a number of ways this can be determined, but since we have this column, let's work with it. I'm going to take this column and I'm going to convert it to a dimension. I'll show you another way you can do it. Here, instead of dragging it, you can just right click and say convert to dimension. Now we have this has credit is active member here. Let's duplicate our sheet just like we did before. Right away we can rename it, because we know what we're investigating is active member. And once again, our beautiful framework allows us to just take his active member and replace it here in columns. And what do we see here? So once again, let's do the aliases right away so that we can analyze properly. Is active member 0 usually means no, 1 means yes. Click OK. So what do we see? People who are not active members, of them, 27% left the company in the period of observation, and 14% or only 14% of active members left the company. So this is above average, this is below average. And what does that tell us? Well, it kind of backs our intuition right here that people who are active, who are actively using your bank, they are less likely to leave. they're invested into your bank. They maybe like your products. They keep logging in. They keep checking their balance. Why would they want to leave? Of course, some of them will leave because competitors, and maybe they have better offers somewhere else. Find better offers somewhere else. Maybe they're consolidating their accounts. But people who are not active are at a higher risk of leaving. And that makes sense. If somebody hasn't logged into your bank, online banking for 3 months, he's a major suspect to leave your bank. Maybe he's already banking with somebody else. Or if somebody who usually does a transaction, sometimes a transaction per month or a couple of transactions per month, has stopped doing that, then once again, there's a higher chance that this person is going to leave. So there we go. We've created so far 4 A/B tests, and it took us just a couple of minutes. So we've got gender. We can see that female customers are at a higher risk of leaving. Germany is at a higher risk of leaving. People who have credit cards, that doesn't really affect. It's not a important variable in this situation. And is active member, people who are not active are more likely to leave. So what I wanted to suggest for us moving forward is we've got one more categorical variable here, and that one is number of products. So how many products does the person have with the bank? Does he only have a savings account? Does he have a savings and a credit card? Does he have a loan? And so on. So I wanted to suggest that you practice with that variable and do it as homework before our next tutorial. So just create another A/B test, but this time for number of products, and see if you can find any anomalies, see if if what you see actually backs your intuition, and create an alias and just have a look and investigate that variable, and then we'll get back to it in the next tutorial, and I will show you how I created this same A/B test. Although it's very simple, very straightforward, just like the ones we did here. I'm sure you'll go fine, and I look forward to seeing you in the next tutorial. Until then, happy analyzing. Welcome back. How did you go with the exercise with number of products? It wasn't difficult, was it? Here is the result that I got. And here you can see right away a couple of things. First of all, there are a few anomalies. So you would expect that as the number of products increases, the customer is more likely to stay with the bank. So in banking, the term I think is called stickiness, or the share of the wallet of the customer. So as the bank has a greater share of the wallet, it is harder for the customer to leave. And that is what we are observing in the first two. So people who have 2 products with the bank are less likely to exit than people who have 1 product. In fact, as you can see, we can't see the labels here because the font is too big. So why don't we just take out the text label for now for our analysis, and that way we'll see all of the labels. So here you can see that only 8% of customers with 2 products left, and 28% of customers with 1 product left. So the massive drop, it is much harder for these customers to leave. But then we see an anomaly here. So we see how as you get more products, so 3 and 4 products, customers are leaving at a rapid rate, at a very, very high rate, 83% and 100% at 4 products, which does not align with our intuition whatsoever. So those are massive anomalies, or very distinct anomalies, and we need to understand what we can do about them. So the first thing that comes to mind, and the first thing that you should always remember when you have anomalies that great, there might be something wrong with the data, or not wrong with data. It just might be a insignificant result. That's what I'm looking for here. It might be an insignificant result, and therefore it might not be worth reporting. What if there are only 5 people that have 4 products, or if because this is a large sample, it's 10,000 people together. What if there's like only 100 people that had 4 products, and they all just happen to leave? So it's kind of like a random effect rather than something that you can rely on. And that is why we have to be cautious that these tests that we're doing, they're not statistically full-fledged statistical tests. They're more ad hoc visual tests. So in these cases, we would need to check the actual number of people. So now I'm going to show you how to do that. And in order to check the number of people that left, we'll talk more about this kind of approach, or a more thorough approach on this in the next section of the course. But for now, I'll just show you a quick way to do it. So I'm going to take the number of records over here, and I'm going to drag a number of records into label just as a text. So rather than doing a table calculation, I'm just dragging it as it is. And so here you can see, now we will just take out the table calculation for now, because once again we can't see what's in there. So here what you'll see is that these two categories, they have quite a lot of people in these categories, but these categories, they have fewer people in the categories. So there's only 266 people in with 3 products. There's only 60 people with 4 products. So that can possibly explain why we're seeing this anomaly. It just happens that the sample that we randomly selected, among them, all the people that had 4 products, they were at very high risk of leaving, and they actually did leave over the observed period of time. So sometimes when things like this happen, you have to investigate further and you have to conduct proper statistical tests to make sure that these results are valid. So in this case, you can say that going from 1 product to 2 products, it's harder for people to leave. For 3 and 4 products, you would need to investigate this further. So that's what I wanted to show you with this chart. We will return it back to its previous state now. And maybe you want to add a comment for yourself here so that in the future you remember that there's some investigation to do. So you go annotate, and then you just select area, for instance, and here you want to say something like low observations in last 2 categories. So just a label for yourself. So we're not going to go into the details of these investigations. Our goal is to understand how to work with Tableau, but nevertheless, you want to have some information for the future. So there you go. I just added a label. So whenever I go back to this chart, I'll be able to see that there's a low number of observations in these categories, and I need to do something about it. So that's all for this chart. What I wanted to show you today is how to validate your approach and, in fact, validate your data. So let's go ahead and create another test. I'm going to duplicate this one over here. So duplicate sheet, and this one we'll call validation. And we can get rid of this comment. So the idea here is to find a variable that you know for sure does not affect your end result. So something that is definitely not a important variable in the choice of customers to stay with the bank or exit the bank. And a good variable here would be a number. So like a digit, 1-digit number. So if say the customer, my favorite is if the customers, if you have mobile phones in the data, you can just take, say, the last digit of the mobile phone. Or in this case, we have customer ID. So let's take the last digit of the customer ID. As you can imagine, it has nothing to do with whether or not the customer will leave the bank. It's not a predictor. It doesn't matter what last digit. In fact, it doesn't matter what customer ID you have at all in terms of your decision for staying or leaving the bank. And so once we run the test for the last digit of the customer ID, we can then check that, yes, everything is fine. It has to be all of the last digits have to have the same probability of leaving. So let's go ahead and check that. We're going to right-click customer ID, and we're going to create a calculated field. Haven't done one of these in a while, have we? So we're going to say last digit of customer ID, and here we're just going to say right, as in the last character. 1, and as from here you can see that table calculation is not correct. That's because customer ID is still deemed as a number. We need to change it to a string, so we'll just say str, and we'll close the brackets there. So that looks good. And now we have a new variable here, last digit of customer ID. As you can see, it's a calculated variable, and we can take this and replace number of products. Let's go ahead and do that. And so right away, you can see a beautiful, very uniform picture here that approximately on average, every customer ID that you have, or the last digit of the customer ID, it has the same, people with that digit have the same probability of leaving as average, about 20%. So plus or minus, some fluctuations exist always in your data, but in this case, it's plus or minus a little tiny bit, which is insignificant. So on average, it's 20%. So that's how you check your data. Another way you could do it is you could look at the last or first letter of the customer's surname, but that is a bit more tricky because letters are generally less uniformly distributed. They're not as randomly, so you'll find that letters like Q are rarer, letters like T are more frequent, and that can affect your results. So try to find something that is uniformly distributed across your population or your sample, and at the same time, it does not affect the end outcome at all whatsoever. And that will allow you to validate two things. First of all, our approach. Now we can see that our approach is valid, because if it wasn't, or if we did see some skewness here, then maybe we would question our approach. And also we can see that the data is, there are no errors or issues with the data, because let's say if we saw that one or a couple of these is too high, then that would mean that perhaps maybe there's some problems with the data. Why is there this observation, this anomaly that shouldn't be there? And that's the end of this tutorial. You can come up with other similar ways to validate your data, and I encourage you to use them just to make sure that along the way, while you're doing your analysis, everything is running smoothly. I look forward to seeing you next time, and until then, happy analyzing. Section recap. Another section behind your belt. Congratulations. Let's see what we learned in this one. In this section, we learned, number one, how to connect Tableau to an Excel file. Not that much different to a CSV file. The only probably difference that you might want to point out is that if you have many tabs in your Excel file, then you will see all the tabs in Tableau, and you have to select the correct tab that you want to be working with. And so if you want to connect to multiple tabs, then you have to create a new connection every time. Number two, how to visualize ad hoc A/B tests. So I showed you my personal invention, I would call it, kind of framework that I use for running ad hoc A/B tests. A very quick way to run your A/B tests. It's not a proper full-fledged statistical way of running A/B tests, so we don't check for significance and so on. However, there's 2 points to that. First of all, in the next section, we will change all of that, and you will see that it is very easy to get that statistical backing behind your findings, and I'll show you exactly how to do that. We'll be talking about something called the chi-squared test, which might sound scary, but it's actually very, very simple. And that will give our visual A/B test that we've been learning in this section full power, full statistical power, and full statistical weight. And the second point is that these visual A/B tests are so simple. You don't have to waste your time running all the stats or crunching all the numbers just to find out that there's no significant difference or something that doesn't matter to you. Like this in Tableau, you just throw in your variables, and within a couple of minutes, you've run maybe 5 visual A/B tests, and you know where to keep looking. So this is what data mining is about. It's not about stats. We're not statisticians. We're data scientists. We're mining the data. We're getting insights fast, and we get what we want and as quickly as possible. And then we take it from there. Number 3, how to create aliases. Very powerful technique in Tableau, which makes your work easier because you know which variables you're dealing with. You don't have to deal with numbers. We're not computers after all. And you can convert a 1 into a yes, a 0 into a no, or you can rename basically values inside your columns. Very powerful technique to have, not just for working with Tableau, but also for visualization. It helps your audience understand better. When in your color legend, for instance, you don't have 1s and 0s, you have yeses and nos, or exited and stayed with the bank, and things like that. How to add a reference line to your chart. Also a good technique. So we added a fixed reference line because we already knew what our average rate of leaving the bank was, which was 20%. So having that visually present allowed us to analyze quickly and understand what is below average, what is above average. So adds value to your analysis and helps you analyze faster. We also learned how to use ad hoc A/B tests to find anomalies. So probably 2 things I wanted to mention here. You saw that by running these A/B tests, we were able to quickly find variables that matter to us, variables that don't matter to us, find any anomalies. Anomalies are more like things that we don't expect to happen, but they do happen, like the situation that we saw with a number of products. Like that was kind of an anomaly, and that is definitely something we would take forward and investigate further what's going on there. And that is definitely not normal to see that with the rise of number of products. The churn rate also increases after some stage, and you'll be surprised at how many weird things you'll be able to uncover in the data through these kind of tests. And it is by looking into those insights that you are able to not only fulfill the requirements of your project, but actually go above and beyond and add immense value to your business, sometimes much greater than what you were going to add through your project itself. And so also the second point on number 5 is that you saw how easy it was. Once you've set up your template, you've set up the formatting, you put the reference line in, you just have to duplicate it, replicate it, and change the name of your column. So replace the column. It's very easy to run these ad hoc tests. Once you've set up the first one, very easy to replicate. And number 6, how to validate your data approach. A very handy trick there. Use a column or a variable you know has no influence on the result. For example, the last digit of their mobile number or their client account number, and check that there is a uniform distribution. That will help you avoid any errors you might have in your approach, or check any errors in the data. And that's the end of this section. I look forward to seeing you next time. Until then, happy analyzing.
Hope you enjoyed the previous section and now you truly see the power of visualization when it comes to data mining. I mean, we were deriving insights at lightning speed by just using Tableau. However, up till now, we've only been dealing with categorical variables like gender and country. And today we're going to take it a step further. We're going to learn how to deal with numeric variables such as age and balance. And moreover, I will show you how you can use the chi-square test to back your findings. But don't get upset if this sounds too statistical. I've separated the hard stats into their own tutorials, and you can choose to skip them if you don't want to get involved in the details. And so let's dive straight back into the world of data mining.
Today we're going to continue working with our data mining workbook, which contains the bank churn dataset. However, we will start looking at a bit of a different, we'll start looking at our data from a bit of a different angle. Let's create a new work tab, and this one we'll call, well, we won't call it anything yet. What we want to visualize here is we want to understand how our customers are distributed by age. So are our customers predominantly older or younger? What age groups are they in? And so on. And as you can see, we already have an age variable here. So the first thing that comes to mind is, let's take age and drag it into columns. And now let's take number of records and drag it into rows. And now we have one big dot over here at the top. Why do we have one big dot? Because, well, what happened is Tableau took the sum of age of all of your customers, and it got just over 380,000 years. And then it took the sum of number of records, so the total number of records, 10,000. Before we continue, I'm just going to fix up the format here so we can see better. So you can see here 380,000 or 390,000 and 10,000 customers. So how do we avoid doing that? Well, in my course on Tableau, I talk about aggregation and granularity. We won't go into details about that yet. I'll just show you how to avoid this happening. So if you go to sum age and you just change this from a measure to a dimension, then what will happen is it's not aggregating age anymore. It's using it as a dimension. And as you can see, you've got this nice shape of a curve. So basically, it is telling you how many customers at every given age there are, and it's plotting it with a line. So that's good. But the problem here is that this is a nice data set. So I'm going to right click and I'll show you the data set. If you right click your data set up here and click view data, and you go in here, you will see the details of your data. So there we go, there's age. So here you can see that this is a nice data set in the sense that age has been already rounded for you. In a way, it's not good because you don't have the details, exactly how old the person is. Is he 29 or is he 29 and a half? Or is he 29 and 11 months and a couple of days old? So you don't have that decimal point. You can't tell how exactly old he is, and therefore you've lost some information. But on the other hand, you can't do anything about it. If this is how the data set was provided to you, well, then you got to work with it, and you might as well just enjoy it, because that means it's a nice data set and you have one listing to worry about. You don't have that decimal point to worry about. So what does that say to us? Well, that says to us that yes, in this case, because they're rounded, Tableau will be able to group your customers. For instance, there's a person who's 36, and there's a person who's 36, and there's a person who's 36, and there's a couple more people who are 36, and then you go to this chart, and then you find 36. Let me just close this. And you find 36, and you find that there's 456 people that have 36 in that column. What you will find is with other data sets, when it's not rounded for you, then you'll have people who are 36 and a half, you'll have people who are 36.2, 36.3, and that will cause this chart to go to create very strange patterns, because you might have a lot of people who are 36 and a half, but you might have very few people who are 36.6. So it'll be very spiky, and you don't want that in your data. You can already see a spike over here. This is not normal, right? So 29 and then 31. So 348 people, 404 people, and this one went down. Just so happened, maybe these people are about to turn 30, or these people just turned 31, and therefore you have this spike. And you'll see a lot more of them if your data is, I would say, more proper, in the sense it's more precise. So we have to find a way around it, and we have to find a way to visualize our distribution of age regardless of the way our data is presented to us. And this is where we can use bins. This is where bins come in, and this is where we start thinking about converting our numeric variables to categorical variables, into dimensions. So let's start by having a look at that. I'm going to right-click age, and what I want to do is I want to group people into bands. So I want to group people into, for instance, 5-year bands. Anybody between 20 and 25 will go into one group, 25 to 30 will go into the next group, and so on. Well, it's very easy to do it in Tableau. All you have to go do is right-click your variable, and then here select create, and then select bins. And here you want an age bin, so we don't want size to be 10, we want size to be 5. So every 5 years, there'll be a new bin. We'll click OK. And here you can see age stayed as a measure, but now we have a dimension which is also age, but it's called age bin. And now what we'll do is we'll take age bin and we'll drag it in to replace age. Well, actually, I need to take age out and then put age in bin there, because one's a dimension, the other's a measure. And what you can see right away is a nice distribution, just like the ones we are used to seeing in economics and mathematics. Because what happened here, we've grouped our records by category, or by these bins. And the bins are acting as categories. So just like, let's say, gender, or the country that people live in, similar way. So it's not recognized, Tableau is no longer recognizing these as numbers. These are categories. So people in this category are between 20 and 25. People in this category are between 25 and 30. By the way, it includes the starting number. So starting from 25 up to the last number before 30. In our case, it's 29. So 25 to 29, 30 to 34, 35 to 39, and so on. And right away, you can see how many people there are in each of these categories. So what else would we want to do here? Maybe let's give it a color so it looks a bit more pleasant. Let's take some number of records, hold down Control and drag it onto color. Personally, I use green for money, so let's use a different color. How about we go with kind of a brownish color, something like that. Apply. And maybe we want to add a label as well, so we don't have to visually check every single time where this is sitting. So we'll go and use some number of records as a label as well. And now you can see that exactly how many people you have in each of these categories. So, and this approach allows you to assess your data a bit more. So now you understand from this sample, which is quite a significant sample, 10,000 people in this sample. So it's very representative of the overall population of this bank. And what you can see is that most people are aged 35 to 40. quite a few people are between 30 to 40. So basically, this is telling you what is the demographic of the bank like. I would say, more younger people, so in their 30s, that are most customers are presented by age groups between 30 and 45. So you have the most of your customers are in those age groups. And in fact, if you want to see the percentages, you can easily convert this. So you can just go here and add table calculation like we did previously. You can even add a quick table calculation in this case. So you just need percent of total. And there you go. So you have the exact percentages. This gives you 43 plus 16 gives you 59, right? 59 plus there's like a bit of a percentage. So that gives you 60%. 60% of your customers are in these age bands, and the rest there's like a long tail. So this is a right skewed distribution. So that is a thing to remember as well. So maybe another tip, that when the skewed means where the tail is going. If the tail is going to the right, then it's a right skewed. This is not a left skewed. A lot of people get it wrong. A left skewed would be if the tail was going to the left. So that's a statistical term to keep in mind. It's a right skewed distribution. You got a long tail to the right. You even have customers at 90 years old. And so what are we going to do now? That's pretty much what we want to do with this chart. I'll just show you one quick thing. You can change the bins very easily. You can just go to age and then you go to edit. And here, let's say we want a 10-year band. See, right away it's changed. And now you can see that you got most customers between 30 and 40, and then 40 to 50, you have 26%. So I'm going to Control Z that. And that's all we wanted to do here. The last thing you might want to do is change this axis because it's not consistent with your percentage. You might want to change it to percentage, but that's details we're just investigating. So we won't be doing that right now. And that's all for today. I look forward to seeing you next time. And until then, happy analyzing. In the previous tutorial, we visualized our distribution of customers by age bands. And we talked about bins. We created a new categorical variable for age when it's binned. And we created this amazing chart. Now let's go ahead and save this worksheet as age distribution. And also let's just save our workbook in general because we haven't done that in a while. And now what we're going to do is create a new chart. And let's have a look here. Now in our dimensions, you'll notice that we have a new dimension, which is age bin. Oh, wow. What a surprise. Where did that come from? Well, yeah, we created that in the previous tutorial. So what we want to do now is, how about we take advantage of this and go ahead and create a kind of like an A/B test that we were doing previously, or a classification test, but now with this new variable. So we already have our tests here. So let's take one of them. Let's say this one, and we'll duplicate the sheet. We'll move the sheet to the end, and we will call this age. Just call it age because that will tell us that it's not a distribution because it doesn't have the word distribution. And now we'll just take age bin and we'll drag it to replace is active member. And let's make some space. What I would like to do here is get rid of the text label because it's taking up too much space. Maybe let's shrink this now because there's less labels. So there you go. As you can see, we've got a beautiful distribution, or actually test. This is not a distribution. These are percentages. It's a beautiful test has been already created for us. And how quick was that? I just want to focus on that for a second. How quick did we create this test? It's amazing. What can we see from here? Well, we still have our average line, as you remember from the previous section. That's how many people leave the company, or from this sample, how many people left over the observed period of time. So if I take out age and remove it, you'll see that right away. That's our 80%, 80-20 split of people who stayed and left. So I'm going to press Ctrl Z to return age. So that's our average, that how people leave. So here you can see right away that people in the lower age bands are less likely to leave, and people in the higher age bands are also very much less likely to leave. People that do leave quite a lot, or the age bands that are at most risk, are these age bands over here between 45 and 60. So 40 and 65, they're about average, even though 40 is a bit higher. But between 45 and 65 years old, people are at a very high risk of leaving. So those are the customers that are for some reason leaving this bank. And that is something that you need to, like something that can be put into reports. You can investigate that further, understand why these customers are leaving, why customers between 35 and 40 are less affected, or because customers between 25 and 40 are less affected, and so on, why these customers not affected. So that would have been, that's already great insights. But at the same time, remember that thing we talked about, that you have to make sure that you're avoiding anomalies, like, or kind of anomalies that are not, that are there due to insignificance of your test, or they are there because there's a lack of records. So here you can see right away there's a couple of those that might be suspicious. For instance, 100% here, 100%, 100%. It does look, because these are the tails of your distribution, so not this distribution, your age distribution, the one that we looked at previously, because they are the tails of the distribution, there might be not too many records here. And so how do you check that everything is going smoothly? Well, we'll find that out in the next tutorial. I will show you how to combine the two charts, how to combine your age distribution chart and your test chart, so that you can very quickly visually assess what is a significant result and what is a non-significant result. And I look forward to seeing you on the next tutorial. And until then, happy analyzing. In the previous two tutorials, we created two independent charts. One is kind of like a test, like an A/B test or a classification test, which tells us which age bands are more at higher risk of leaving the company based on the sample and the observed period of time, based on the test that was conducted, basically. And the other chart, which is over here, tells us the distribution of age overall. So today we're going to learn how to combine these two charts into one, and so that we can draw insights from them at the same time. And we're going to be combining them on this age chart. So we're going to be adding the distribution to this age classification chart. And let's go ahead and do that. In order to add a second chart, all you have to do is decide on what exactly you want to add to this chart. So we want to keep the bins, right? We want the columns to be the same because they're the same across both charts. So here and here they're exactly the same. And so all we want to add is a new type of rows. In this case, we have the percentage of total, which is our table calculation here. And now we want to add another type of row, which is going to be just the number of records. So now I'm going to take number of records and drag it onto the rows pane over here. As you can see, a new chart has appeared. And in order to make more space, just drag, find this delimiter between the charts and drag it upwards a little bit so that we have sufficient room. That looks like it's good. Okay, before we do anything else, I would like to point out a few things that have changed in our workbook or on this worksheet overall. So first thing, we now have rows in, we have a new measure in rows. Of course, we have this new chart, but also if you look at this marks area, now it looks very different. Now we have all, a tab which is all, so for all the charts. Then we have a tab for our first chart, and we also have a tab for our second chart, right? So that is very interesting. It gives you control. If you want to control everything, you can control it here. So for instance, I could, what could I do here? I could change the colors, right? And they would change everywhere. So I could say stayed would be green, exited would be red. Okay, that changed everything. Or I can go into one of them, and let's say the new chart, and I can remove exited if I don't want it. And as you can see, it doesn't affect the top chart. I can remove the label if I don't want it. That doesn't affect the top chart again. And then I can go and change the color here, which I'm going to do. I'm going to change it to, just like we had previously, to a type of brownish color. And then I can add something here. So as you remember, we had a percentage, oh sorry, the color was dependent on the number of records. So let's take number of records and hold control and drag it into the color. Once again, I'm going to have to change the brown. There we go. That's our brown. Okay. Now what I wanted to do is, I don't like this red actually, so let's go back to now this chart, this top chart over here. So you can see how what it's like to work with several charts. You can have many more than that. And here you can quickly go into colors and state. What did we have for state? I think it was blue, exited was orange, apply. That's what our chart looked like. And that's looking good, much better. But now we want to add a label to this chart over here. So let's add a label, which is some number of records. So we'll take this some number of records, hold down control, drag it onto label. There it is. That's our number of records. And what else did we want to do? Well, from here, what I would suggest doing is like this, they look kind of a bit separate. To be honest, I like when this chart is on top of the other one. So let's try and experiment with that one. Let's try and do that. In order to switch their order, you just have to switch the order over here in rows. So I'm going to take the new chart and drag it before the old chart over here. As you can see, they've switched their order, and also the panes or the tabs in the marks pane have switched their order as well. Now, this is the top chart, this is the bottom chart. You can always tell by this triangle. The triangle signifies a table calculation, which we have over here. So there we go. That's our two charts. And what can we see from here? Well, we can see that, as we knew before, our customers are mostly represented by these two age groups, so between 30 and 40 or 45 years old. And also in these three age groups, the probability of leaving is the lowest in the 30 to 35, then it's a bit higher 35 to 40, but still below average. And then at 40 to 45, it goes above average. Then the probability of leaving increases for these age groups, but the number of customers in these age groups reduces. And then what we were talking about, these anomalies over here, as we suspected, there is a very low number of customers overall in these bands, in these age bands, and therefore these anomalies may not be statistically significant, probably aren't. And just like this one over here, so customers between 15 and 20 years old. And that gives us some quick insights or additional insights into the chart. This is how you can very quickly and efficiently analyze two charts. But the main focus, I guess, of this tutorial was to get comfortable with working with two charts on one worksheet like this, because which one do you put at the top, which one do you put at the bottom, what colors do you set, but most importantly, of course, how to work with these separately. So remember that you can control the charts together or separately. And here you can see that the colors are grayed out, the labels are grayed out. That's because that tells us that each of these charts has their own color palette and their own labels that have been applied to them, and then you can go into these separately. So have a play around with that, have a look at what you can do, change around, because after all, even if you break something, you can just quickly recreate the chart, no problem at all. Just try to get as comfortable as you can with this new feature of Tableau that we've just discussed. And in the next tutorial, we'll discuss something very interesting. I will show you how to, well, I'll give you some ideas about how to assess the statistical significance that we keep talking about. And it'll be quite an interesting tutorial, a bit more statistical, but also quite important. It'll give us that additional leverage in terms of what the analysis that we can extract from these charts. And I look forward to seeing you next time. Until then, happy analyzing. Hello and welcome back. I hope you had a chance to play around with Tableau in terms of the new functionality that we discussed, where you can have several charts on one worksheet. And that in turn brings quite a few tabs over here in the marks pane, so you can control the charts separately. And today, as promised, we're going to talk a bit about stats, and in particular the chi-squared test. But don't worry, it's not going to be heavy stats. We'll just cover off some like basic intuitive things. The heavy stats, or not even so heavy stats, the main discussion about chi-squared, I've taken it out and put it into two separate tutorials that are at the end of this section. So feel free to check it out if you do want to get into the nuts and bolts of chi-squared and understand it a bit better. However, today we're just going to look at the practical application of chi-squared. So what is the whole reason we're doing this? Why do we want to look at the statistical significance and learn about it a bit more? Well, the reason is all of these results that we are seeing here, they're great. Like we can see that it looks like it's pretty obvious that, for instance, age has a significant impact on the choice of people to stay with the bank or not. You can see that these age groups are more likely to leave. These age groups are less likely to leave. Let's look at another one. Say we can see that here's gender. We can see that gender has a significant impact. So being a male customer or female customer impacts, or there's an association between gender and the choice to stay or with the bank or leave the bank. However, as you recall, I've mentioned a couple times that this is not the hard statistical test. So it is just a visual interpretation or a visual improvisation of the test. Well, how do we get confident with this visual improvisation? How can we be sure that what we're reporting is actually the result and that we can use this as insights to drive business decisions and we can communicate this to managers and executives? Because we all agree that if we have an insight but we're not totally sure about it, then it's kind of not the best idea to report it probably, or you wouldn't feel as comfortable. So that's why we need the chi-square test. And basically what the chi-square test will tell us is this result a statistically significant result? So as simple as that. The chi-square test will tell us we do observe this difference in the sample, so in our 10,000 records. Well, is this a random difference? So has it happened by chance that there's a difference between female and male? Or is this a consistent difference? Can we surely confidently say that in the whole population of the bank, which can be 1 million customers, which can be 10 million customers, can we confidently say that we will observe a similar discrepancy, a similar difference in the whole population of the bank? That's all the chi-square test does. It can tell us whether it's just by chance or there is an actual difference that can be and will be observed in the population. So how do we run this chi-square test? Once again, there's more details in the last two tutorials of this section, and if you do wish to dive into that, please go ahead and check those out, because there I talk about how to run it in Excel and all the details about chi-squared. But here I will just show you some online tools that are very quick and can help you do these things very ad hoc. So I'm going to bring up a browser now, and there are two websites that we're going to be looking at. The first one is www.evanmiller.org/ab-testing/chi-squared.html. So you can find lots of these websites. Just if you Google for chi-squared test online, you'll find quite a lot, but I kind of fancy this one, so we'll talk about this one to start with. What you have to do here is basically input your values. So now the rule number one here, an important rule, is that with chi-squared you cannot use percentages. You have to use the actual values. So if you put percentages in here, you will get a wrong result. So getting back to the actuals is very easy. I'm just going to go back to our Tableau worksheet. Here I'm going to duplicate the tab, duplicate the sheet, and I'll call it gender actuals, or you can call it absolutes. And here we just need to replace the table calculation. So I'll just take number of records, drag it into here, and then drag it into here as well. So there are our absolute values, and now we can input them into our tool. The only thing is that we'll also need the absolute total. So for each of these columns, a quick way of doing that is we go to edit, or right click the axis, go add reference line, and then we'll just sum, and then we want the sum, right, and we want it per cell. So we want just the sum to appear at the top so that we have it for our reference purposes, and we want it per every cell. And here we don't want the computation, we want the value. That's just a quick way of bringing up the sum without changing your chart. And now I'm going to bring back the online tool. So all I have to input here is I'm going to get rid of these values. So sample one, it's this one, and we're going to look at you can choose any one of these as success, stayed, or exited. Doesn't really matter. I'm going to choose exited as success in floating quotation marks. And so I'm going to type in here 1139. The total number of trials, or not, the total number of observations in this category is 4,543, 4,543. And here it's 898. And the total number of observations 5457. Okay, so what can we see here? There's a verdict. Sample 1 is more successful, meaning that this female customers have a higher exit rate, and it is statistically significant. Here you can see this p-value is less than 0.001. We don't talk about p-values right now, and what you will find is that basically if the p-value is less than 0.05, so less than 5%, then it's a statistically significant result. So in our case, you can see that it is more likely, it is going to be the same in the overall population of the bank. You can confidently say that female customers are more likely to exit. That's how you use a chi-squared test using this tool, or any other tool basically. Just follow the instructions that it gives you here. Let's look at another one. So we've validated this one, and sometimes when, say, you validate something, I like to change the color of the tab, right-click the tab and maybe change it to green, so that in the future you know that this is a validated result. You've checked the chi-squared test and you're 100% sure that you can report this observation. Well, basically this observation and these numbers were used to check the chi-squared test. Now let's look at a different one. Let's look at has credit card. Same thing here, right? So we want to duplicate, or even faster, if you just duplicate this sheet, right? And then you take the color off because we haven't validated yet, and you rename it has credit card actuals, and then here you just need to change gender, replace it with has credit card, and there you go. So once again, Tableau, drag and drop, super awesome. Get rid of the label here so that you can see the total values, and let's go back to our tool. Okay, so here we've got different values. Let's put them in, right? Sample 1, successes 613, trials 2,945, successes 1424, trials 7055. All right, so verdict, no significant difference. P is very high, greater than 5%, no significant difference. And as you can see from here, it's hard to tell, but we already knew that. We already said that there's no significant difference just by looking at this chart over here. And that speaks of how great this template is. You can't tell with statistical significance, but just by looking at this, you can say probably there's no difference. 21%, 20% doesn't really, doesn't really sound like a significant difference. So, and this tool has validated that for us, so we can now confidently report this finding. So I'm going to change the color of this tab to green over here, and there we go. So that's how you use a chi-squared test in the case when you have two categories. So basically what we're doing here is an A/B test. If you noticed, we're just doing an A/B test. We're just validating it through a chi-squared test. What we're going to do in the next tutorials, I'll show you quickly how to approach the situation when you have more than two categories. So when you might have three categories like we have in country, or you might have many categories like we have in age. And for now, as a suggestion, you could practice with a different variable. For instance, we've done gender, we've done has credit card. How about is active member? So you could practice this exercise with is active member and see if you can confirm that there is a statistical significance between these two. And I look forward to seeing you next time. Until then, happy analyzing. All right, how did you go with that challenge? Here's what I got, here's my result. And as you can see, the p-value is very small, so there is a statistically significant difference. And today we're going to finish up with the chi-squared, and after today's tutorial we'll definitely get back to the fun stuff, the visualizations. However, we do need to discuss one more thing in terms of statistical significance, and that is what to do when you have more than 2 categories in your variable. And let's get straight into it. We've got a variable here which is country, right? So how about we create we start a statistical test for country. So I'm going to copy this tab over here, just as we did previously. I'll rename it to country actuals. And now I'm going to take country, where is it, geography, replace gender, and let's make some room, get rid of the label, and there we go. So we've got the actuals here. So I'm going to show you 2 ways. First, I'm going to show you the proper way, and then I'm going to show you my tricky quick way that I like to use sometimes. So to start off with the proper way, you need to run a chi-square test for a larger table. You can't just run it for 2 categories. You need to run it for all 3 categories. And for that, there's a different website, which is valsarstats.net/new/cs.html. And what we can do here is input the values into here. We don't even need the actual totals for each category. We just need the numbers in the blue and orange squares. By the way, there's a quick way to look at this data as a table. So if you just go to show me and you click table and then you transpose it and then you make some more space, then you pretty much have the table ready. So that way you can't make a mistake when you're copying your values. So let's zoom in a little bit, and there we go. 4204, 810, 1695, 814, and 2064, 413. So calculate, and this chi-square test has been run for 3 categories now, and as you can see, there's the p-value. It's very small, and once again, that means that there is a statistical significance, meaning that when you go to the overall population, rather than look at sample, when you go to the overall population, you will also see an effect similar to this. You'll see that people who reside in Germany are more likely to leave the bank than people who reside in Spain or France. So that's how you should do it properly. But as you can imagine, as you get more categories, it gets harder to input that table. And moreover, this specific tool only has a limitation of 5 by 5, right? And you don't want to sit there and just input data all the time, especially when you can already see that there is a difference. You can see it here, right? So why should you waste your valuable time and input this data just to validate something you already know? You do need to validate it, but is there a quicker way? So I offer you my approach that I kind of like a lot, and let's have a look at it in a visual manner that will make a lot of sense. So here's our countries. So France, Germany, and Spain, right? What we're trying to do is compare these rates of leaving, or these chances of people leaving the bank for different geographies, and I want to say, is this a statistically significant result? So will this result be the same for the overall population? Right now we're comparing all of them. So we're saying, is in general the country you reside in an important variable? So my suggestion here is, why do we need to compare all of them? Why do we need to compare all 3? How about we just separate one of them, like we forget about this part, forget about the or the people from the sample size that live in Spain, and just compare France to Germany, right? If we find a significant difference there just between these 2 categories, then that will mean that overall there is a significant impact. So basically we're saying that if people in Germany are leaving have a higher chance of leaving than people in France, then by adding people from Spain, it won't change. They're still going to have a higher chance of leaving than people in France. Maybe there will be a different relationship to people from Spain, but we don't really care about that right now. What we're saying is that there's a statistically significant difference for this specific variable, and we can extrapolate it onto the whole population. And in a way, the way you can confirm that this logic is true is, think of it as, this is your test, right? You had people from France, people from Germany, and people from Spain participate in your test. Now imagine you had designed your test differently. Imagine you had designed your test in a way that you only looked at people from France and people from Germany. You didn't look at people from Spain at all. And you looked at exactly the same people. So do you think the result would have changed? Well, obviously not, because these people are not related in any way. And that's how your test is constructed, that there is no interdependency. So the decisions of these people to leave or stay with the bank is not affected by the decisions of these people. And so therefore, you can totally separate your categories. So you can, if you have many categories within one variable, like here, country, you can take any subset of those categories and compare them between each other using a chi-square test. And that is totally, totally fine. So let's go back to our worksheet. So here you can see that between Spain and France, there's probably not a significant difference, right? So why would you ever run a chi-square test between this and this, right? To prove something. Instead, let's run a chi-square test between France and Germany and prove that there's a statistically significant difference between them. And that'll be sufficient for us to say that geography as a variable is an important variable. It does play an important role in the decision of people to stay or leave the bank. And that's my handy trick. So that's our country. We've already done the test for country actuals, right? So obviously, if we run this test now for France and Germany, we will also get a statistically significant result. And I'll leave that up to you if you'd like to check that. That's totally fine. The other thing I wanted to show you here is that if we now go to age, you'll see that there's a lot more categories here, and it would be a very painful exercise to run a chi-square test for all of them. However, you can use this as practice and pick out the categories where you think there is a statistically significant difference. I'll give you a hint, maybe 50 and 35, or 45 and 35, something like that. Any two that where you can see it looks like there's a difference, and just run a chi-square test for those two. And that way you will have sufficient evidence to say that age is an important variable. And so that's how we validate the insights that we derive from this visual improvisation of our statistical tests. As you can see, it's not that hard, and in combination, those two methods complement each other. You can quickly get insights using Tableau, and then where you do suspect a statistically significant difference, you can quickly validate it using a chi-square test. And that's all for today's tutorial. In the next one, we'll get back to creating some more cool visuals, and I look forward to seeing you next time. Until then, happy analyzing. All right, so I think we've had enough stats for now, and let's get back to building these charts. The first one we're going to do is we're going to look at balance. We've already done one for age. Now let's do a similar one for balance to really solidify in this technique. So we're going to take balance and we're going to create a bin, and there's our bin menu. We're going to say that the size of the bin should be about 10,000, and we'll click OK. There we go. So all we need to do is duplicate this chart, duplicate sheet, we'll call it balance. And here all we need to do is take balance bin and replace age bin. And as simple as that, right? So one thing we notice here right away is that there's a lot of $0 balances, or well, balances in the $0 category. They might be anywhere between 0 to 10,000, but if you right click and click view data, you will notice that you go to underlying here. You will notice that balance bin, that's the bin. And then if you look at balance, you will notice that they're actually mostly zero. So even if we order them, there is one, wait a second. There's one balance, $3,768, and the rest are zeros, completely zeros. So what does that tell us? Well, that tells us that's normal. Like sometimes people in a bank, they have zero balances, and that's, they just, because they have other accounts, or maybe they moved their money out but did close this account and things like that. So in this case, what we're going to do is we can just exclude this from our analysis. Of course, you have to put in a note that you're excluding something from your analysis, but it just does make sense because we want to look at the actual values. So people with balances, how are they behaving? What's going on there? Are they leaving? Are they staying? And so on. So just right click this column that you want to exclude and select exclude. And that's it, it's gone. So here you can see a filter. We won't be talking about filters per se in this course. It's a whole separate topic, and I covered that off in the separate course on Tableau. But basically what this filter does is, if you just click here and click show quick filter, you'll see the show quick filter pop up on the right. It's excluding a certain category, which is the $0 to $10,000 bin, and that's allowing us to just analyze everything else without it. So what we can do now is perform our analysis as per usual. Here you can see a very interesting picture. It's a bit different to what we saw previously, so I'll just show you age over here. This was age, right? And you could see like there's obviously people who are not like are different, so they're not conforming with the average. In here they're higher, there's a higher chance of these people leaving, lower chance of these people leaving. In balance, it's a bit different. They're kind of more uniform here, so you can see across the board it's around 20%. Some are higher, so these early ones and the later ones are higher, but once again here you can see that you have less records, so there's a higher chance that this will be a just, you know, a random error, or just like some sampling error. And same thing over here, you can see that this is just due to the way the sample was selected. You can't really rely on these things. For instance, for a 2 and a 1, you can't even run a chi-square test. You have to have at least 5 units or 5 observations in each cell to run a chi-square test. So you can still run one for here, but overall here you can see that there isn't that much of a difference. Maybe a bit over here more likely to leave, a bit over here more likely to leave. So that's very interesting. What we can do now is I would like to change the color of the top chart over here, because it's balanced and I'm kind of used to using balance as green. There we go. And so that's pretty much it for balance. What you can do from here is the way this situation is different is that you don't observe something that is like screaming out at you. You can continue investigating these discrepancies if you like, and if that is important to your company to understand, like, okay, so that's 29%, that's 25%, why is that higher? So if you feel that that is an important discrepancy, then you can apply the techniques that we've talked about to this specific case and take it further. However, if you feel that this is more or less conforming with average and you'd rather focus on other things, you can simply leave it at that. You can just say that from our analysis, it doesn't seem that there is a very high change across different categories in terms of probability of people leaving. And you just go from there and you focus on other things. Of course, it'd be great to cover everything, but that's why we call it data mining. You want to find the gems. You want to find the real golden nuggets rather than spending your time on things that won't give you much value. So if you target people with special offers who are in this age group between 45 and 60, you can really impact the amount of people that's leaving your company. But do bear in mind, you have to also take into account the actual number of records. So this distribution helps. So you can see that you might want to target these people more than these people because there's more of them. Whereas in balance, yes, these do have a higher percentage of leaving, but how much return on investment are you going to get if you try to fix this instead of fixing the problem that you can perceive with the different age demographics? So that's balance. The other one I wanted to look at today was estimated salary. Let's have a look at that because it's kind of related to balance. So we'll just duplicate this as we normally do because it's fast. And here we'll just say estimated salary. And let's take estimated salary and drag it. Oh, the bins. We haven't created a bin, so let's create a bin. Create bin. So same thing, 10,000. And here, just take the filter off, so there's no more exclusion. So we just want to keep the filter on that sheet, not on this sheet. And estimated salary, just drag it instead of the balance bin. And here you can see a different picture one more time. So I'm just going to change the color here quickly. Color, up to you, honestly. What color you think is the best? Please select that color. I'm going to select gray. So here what you can see is a very interesting picture, very uniform distribution here, very uniform distribution over here. So first things first, you look at this chart and you say, all right, obviously there is no impact whatsoever that from salary upon the probability of the person leaving, or upon the decision of the person to leave the bank. So salary is not an important variable. And we would leave it at that if we only had this chart. But this chart, this chart is telling us something very interesting. It's actually telling us that, whoa, look, there is an equal a number of people in every single bin for estimated salary. So we're saying that in our bank, there's the same number of people that earn between $180,000 and $190,000 as the number of people that earn between $30,000 and $40,000, and as the number of people who earn between $80,000 and $90,000. So this really kind of contradicts the whole balance situation where we have this nice normal distribution, and like as it probably should be, this is lots of people here probably, like you can say that they earn somewhere in the mid-range. These are people earning in the lower range. These are people earning in the higher range. And you would think that balance would somehow be related to estimated salary, or at least, well, you got a hint here that estimated salary is actually has the word estimated in it, meaning probably that the bank doesn't know what they're earning and they're estimating what these people are earning. And you'd think that you'd use the balance to estimate what a person's earning, right? Somehow in the calculation would figure there. But it doesn't look like it, because there would be a trace of a normal distribution, but there isn't here. So one thing you can report from here is that this is going above and beyond your task. So here, you've already said that no significant impact. But then looking at this, you can say, hey, by the way, it looks like the estimated salary calculation is completely wrong or out of whack, because it's not adding any value. It's just putting people uniformly across all bands. And although that's not related to your work, that's how data mining works. You will find that you will uncover very interesting insights about completely unrelated things to your analysis while you're doing analysis. And this is one of them. So you can go back to the department that runs this estimated salary and say, hey, your calculation is outdated, or there's an error, or something is wrong with it. Let's have a look at it. I can show you that this is not normal. This is not how it's supposed to be. And maybe just by doing things like that, you will add way more value than just by delivering your project. And that's happened to me heaps of times, that I was doing one thing and then I noticed something in the data that led me to uncover something else, and then something else, and then bam, I actually delivered so much more value than I just delivered on the project. Because the project you're doing, people already know what value they'll probably get from it. Here, you can uncover completely random things, and that's just fantastic. I personally find that is the fun part in data mining. You have a problem that you need to solve. Along the way, you find additional insights, and lots of them. So there we go. That's what we found about estimated salary, that probably the calculation is wrong, but the way the calculation is structured right now, we can see that this variable does not have a significant impact upon our variable, or our probability to likelihood of person to leave, or decision of the person to leave. So that's us for today. And as a homework exercise, I would like to suggest that you look at the remaining two variables that we have. So there will be credit score and tenure, and see what you can find there. Maybe you'll find some anomalies, and maybe you will drive some insights. I look forward to seeing you next time. Until then, happy analyzing. Welcome back to the course, and today we're talking about the chi-squared test. This is a statistical test that will allow us to back everything we've been doing so far in Tableau. So all those A/B tests and classification or categorization tests that we've been doing, they've been very intuitive, and we've always said that sample size matters, but we're not checking it per se, and it's not a proper statistical test, but it's very visual at the same time and fast. So it's kind of a trade-off. It's been a trade-off so far, but today we will actually talk about the chi-squared test in detail, and that will allow us to be more confident about the things we're doing in Tableau, those intuitive things, and especially when we're explaining them to somebody, we'll be confident that we are saying the right thing and that this is in fact the outcome and these are the insights. So let's get straight into it. This is the plan for today. First of all, we're going to identify the problem. We're going to look at an example from our previous Tableau manipulations. Then we will talk about what is a chi-squared test and how it can help us solve that problem. Then we'll look at another example, example 2. Then we will actually run chi-squared tests in Excel. So I will show you how to build a chi-squared test in Excel. And moreover, you will get my template. You'll be able to download it so you can follow along and create the same thing, or you can just download my template and follow along that way. And also we will verify the chi-squared results using an online tool. So I'll show you a couple of online tools where you can verify the results, which are very, it's a quick way to get the outcome of your chi-squared test. And finally, we will talk about the chi-squared rules. And also I haven't put it in here, but I will give you a challenge to take away home for you to practice a chi-squared test. Okay, let's get straight into it. This might be quite a long tutorial, so although it is quite an important one if you want to be 100% certain that you're talking about the right thing. All right, so we had a look at gender in our course so far, and there was a split between female and male, and we saw that 25% of females exited the bank in the period of observation from that sample of 10,000 people, and only 16% of males left the bank, right? So the question here is, and this is where we identify the challenge or the problem. The question is that a statistically significant result? Can we say for certain that females are more likely, or female customers are more likely to leave the bank than male customers? Or did this happen just by accident? Did this observation randomly happen, and that difference between 25 and 16, even though we can see it in our sample size, in reality in the population it's not going to be as visible, and in the whole population of the bank there's no difference. Whether it's a female customer or a male customer, they have the same likelihood of leaving. So that's when we need to run a chi-squared test. The chi-squared test will tell us if this is a random coincidence or this is in fact a statistically significant result that can be applied or extrapolated onto the whole population of the bank. So in order to run a chi-squared test, this is an important part that you have to remember, that you cannot use percentages. You have to change percentages to the absolute figures. So we're going to go back to our absolutes, and this is what it looked like in absolutes. As you can see, there's less female customers than male customers, and the exited value numbers are presented there. So now let's put this information into a table. This is what it will look like. This is the observed table. This is what we saw, the number of male and female customers that stayed and exited. So you've got the categories as rows, and you've got the outcomes as columns. That is the conventional way of representing a chi-squared test, a table for a chi-squared test. Now in a chi-squared test, there's a second table that you need to create, and that table is called the expected table. I'm going to use my mouse here because it's pretty important. So you've got a total of male customers. You take these two, you add them up, it gives you a total number of male customers, right? And that'll be about just over 5,000 customers. Now, if you take these two, the total number of exited, and you add them up, it'll give you about 2,000. And we know that there's a total in this whole table. The total is 10,000. So 2,000 divided by 10,000 gives you 20%. 20% of people exit, right? So now this expected table, what it represents is if there is no dependency. So if leaving the company, the decision to leave the company is independent of gender, then what we would expect is that 20% of males leave and 20% of females leave. Makes sense, right? So if you know that 20% of people overall leave the company from this sample size, then it should be the same for males and females. It should be 20% here and should be 20% here. And that's exactly how you create this table. So you calculate 20% of the total males, you add up the males, you get the 20%, and then whatever is left, those are the ones that stayed. And whatever went, for females, same thing. You add up, then you get 20% of that, and whatever is left, those customers decided to stay. And that's what we expect to see. This is what we saw in reality. Now, if you look at these two tables, they are quite different. So the expected value here is over 1,000, here is below 900, here is the opposite, it's just above 900, here is over 1,100. And so what the chi-squared test will do for you, it will tell you, is the difference between this table and this table a random difference or is it a statistically significant difference? So by default, we say that the difference is not statistically significant. It's just a random coincidence. So pretty much we're saying that this table is just like this table, plus minus some little random error which we can discard. What the chi-square test allows you to do is it allows you to rebut or disqualify that hypothesis and say that actually this is a statistically significant result. So that means the chi-squared is a test designed to test the probability of independence. So we're testing whether our variable that we're looking at, so exited, is yes or no. Is it independent of gender? That's what we're testing. We're testing the probability of independence. And that's important to remember. Now, let's look at a second example before we continue on to Excel. Here we've got has credit card. This is another test that we ran in Tableau. And here you can see that it doesn't look like there's any difference, right? It doesn't look like it makes a difference whether or not you have a credit card or not. You pretty much, like 20% of those who had a credit card exited and 21% of those who didn't have a credit card exited. Okay, so from Tableau, we can kind of see that intuitively. Now, if you move to the chi-square test, we have to get rid of the percentages. We have to go back to absolute values, which is important. We have to create the observed table, which looks like that. So we just put in these numbers in there. We have to create the expected table, which we know how to create now. So we take the total number of people who have credit cards and multiply it by 20%. That will give us this value. And then whatever's left is the people that stayed. So the people that we would expect to stay. And the same thing for people who don't have credit cards. This is 20% of the total that we have here. And that's everybody else. So what I wanted to highlight here, from here, we're going to move to Excel. But before we do, I wanted to highlight to you that in Excel, we're going to get some result. And like it's probably going to be not statistically significant. So meaning that there is no difference whether you have a credit card or not. But from here, what you can see is that in this chart, right, and in these tables overall that we're preparing for the chi-square test, it's all very complicated to see this. It doesn't scream at you, doesn't tell you like, hey, this is not a statistically significant result. But when you look at the Tableau result over here, you can see that it is pretty obvious that there is no statistical significance. Like without going into too much detail, you can say that I'm not 100% certain of the result, but I can see that most likely there isn't any statistical significance here, and it's just a random kind of coincidence that these are a bit higher than these. And that is the beauty of this approach, this framework that I'm showing you in Tableau, that you can do that so quickly. You don't have to run the full test every single time just to visualize these things. Anyway, so let's move on to Excel. I'm going to end this show. And I'm going to bring up Excel and I'll show you how to create the test. So here I'm going to zoom in a little bit and then I'm going to say chi-squared test and let's create our table. So the first table is the observed table. Whoops. Observed table, right? So I'm going to just copy the data. This is going to be for our, one second. So this is going to be this data that I'm going to copy for gender. There we go. And now what I'm going to do is I'm going to add up the records, right? So maybe let's take observed and put it there. I'm going to add up the records. I'm going to say Alt++ gives you the sum, Alt++, 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 right? And then just do another Alt++. So now we know there's 10,000 records in here in total. There's 5,400 males, females, and that's the people who stayed, that's the people who exited, right? So we've created the observed table. Now let's create the expected table, right? So it's going to be similar. We need male, female, stayed, exited, but this is going to be a calculation. So it's very simple to create in Excel. You go equals, and you look at the people who stayed, right? And you divide by the people overall, and then you multiply. So that's your percentage of people who stayed. then you multiply that by the number of males that you have in total equals. So here, what we want to do, we want to do the same for the rest of them. But in order to speed things up, we're just going to lock some of these cells by clicking F4. We don't want this one to move ever. Then with this one, we don't want it to move. We don't want the number to change, so we'll lock the number. And with this one, we don't want the column to change. We always want it to be in column D. So we'll lock the letter. Click OK. And now if I copy it here, as you can see, it's already done everything for me. It's looking at the percentage of people who exited. So this column divided by this column, or this cell divided by this cell, multiplied by the total number of males. So there you go, 111,000. In our expected table, we had a bit of a different value, but that's because of rounding errors. Because we took 20% by default. Here it's a bit different to 20% in reality. So let's copy this one here. Just check. You see that it's doing the same thing. Percentage of stayed times total females. And here, same thing. So we're taking exited divided by 10,000 and multiplying by total females. There we go. So one more time, Alt++, 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 Alt++. So here you can notice that this value is the same as this value. It doesn't change because total number of males doesn't change. It doesn't matter how you count, right? And total number of females doesn't change. But what does change is the proportion of stayed to exited in each one of them. So here you can see that it's different to that. Here you can see that it's different to that. But once again, these don't change. So the total number of exited didn't change. The total number of stayed didn't change. That's a good quality check for you. And here you have 10,000 people. Here you have 10,000 people too. So last thing that we need to do is check the p-value. So p-value will basically tell you if what the chi-squared test, what result it's giving back to you. So we're going to say equals chi test. And here we want the actual range. As you can see, actual range is that, comma, expected range, which is that. Click enter. And as you can see, p-value is very small. It even had to use a mathematical or scientific term. So that is a 10 to the power of minus 26, a very small p-value. What you need to check is significance level, right? So we're going to say our significance level is 0.05. What that means, without going into too much detail, what that means is that this is basically 5%, which is saying that what is the probability that what is our cutoff probability that we want to check that this is a random result. So basically we want to say, let me show you on an example. So if p-value is less than 0.05, then we will say not random. Otherwise, we will say independent, right? Independent. Okay, so what this is telling us is that, So what this is telling us is that because the p-value is less than your significance level, that this is not a random result, that what you're seeing is some sort of correlation, that the result, stayed or exited, is actually dependent on your variable, which is gender in this case. If, on the other hand, the p-value was greater than 0.05, then you would be able to say that the result is random, meaning that your variable here is not dependent on age. So I'm going to save this. I'm going to, wait 1 second. I'm going to just bring up my visualization section. I'll just save it here in advanced data mining. And this will be chi-squared. All right, so now what I would like to do is take the values for the stayed and exited in terms of the has credit card. So we'll copy these values into our test and see how that goes. So I'll just copy them here, and then I'll just copy, I'm just going to copy the values without the formats, and then I'll get rid of these two. All right. So here what you can see is a different result, right? Here you can see, well, we have to change this. This is going to be yes. No, don't forget to change that. So here we can see that this is our observed, and this is what we were expecting. And the p-value here is 0.47, so it's huge. It's a massive p-value, 47%, 47.5%. Once again, we're not going to details of p-value. We're just using it as a flag or a trigger for us, I guess. So then this is what the chi-squared test spits out. And since it's greater than the significance level, which is 0.05, here you can see that the result is independent, meaning that our variable state exited has nothing to do with whether or not they have a credit card or not. And once again, so I'm going to bring up the presentation now. Once again, here from Tableau, we could see this right away. We could tell 21%, 20%, not a big difference. Like you can't really tell from here or from any of this, but from here you can totally tell. And once again, you can run the chi-squared test just to make sure that you're on the right track. All right. So now what I wanted to show you is an online tool, how to run the chi-squared test. There's our online tool. So let me just move this to credit card. And you just, this is the website. I like this tool, evanmiller.org/ab-testing/chi-squared.html. So you put in your successes here, say in this case 613. Out of our total trials, okay, that's a good question. What are our total trials? So our total trials here is, so 613, there we go. And total trials is 2945. And here you've got sample 2, you've got 1,424, and your total trials is 5,631. No, I'm sorry, this is actually 7055. There we go. So what does the test tell us? No significant difference, right? So we put in our values just like here. Basically what it did, it just ran a chi-squared test for us. No significant difference. P-value, what is the p-value? 0.48. What did we get? 0.48. Exactly the same p-value. And we can do the same for gender now if we like. So if we just go back, there we go. So male, female, let's do the same thing. 898. Here is going to be 5457. Here it's 1139. 4543. So sample 2 is more successful. Don't look at that, which one is more successful. In our case, it's the opposite because we're looking at exited as the success. But what you can see here is that the p-value is tiny. We get a tiny p-value and the result is the same. It's not random. So here you can see that it's not random as well. So that's how you run the chi-squared test. We're running out of time. I'm going to end this tutorial now, and in the next tutorial, I will show you, I'll sum up on the chi-squared and I'll give you an exercise to take home. And I look forward to seeing you next time. Until then, happy analyzing. Hello and welcome back. Last time was a great and quite long tutorial on the chi-squared test. This time we'll make it short and sweet. We only have a few things left to cover off. And I'll just start off where we finished last time. So here we had the template that we created, or basically the Excel spreadsheet where we ran our chi-squared tests. By the way, you can get the template as promised. It's in the course materials, just like you would download a data set. You can go and download the same way. You can download this template and use it in case you need it you need to check some things or run a chi-squared test in the future. And here we also ran the chi-squared test on this website. Over here you can see the link, and we were able to confirm that our results are valid. So this is just a quick way of running a chi-squared test without having to create everything in Excel. And what we're going to do now is we're going to finish off with the rules of a chi-squared test. Let me just find them. I will bring them up just now. And there they are. So the rules of a chi-squared test. These are important things that you need to abide by to make sure your chi-squared tests are running correctly, and the results that they're giving, you can actually talk about them and use them to back your analysis. So we're using the chi-squared test to back what we're seeing in Tableau, but you need the rules to make sure the chi-squared test is working properly. Number one, the probability of independence. This is what the chi-squared test is about. This is the essence, the quintessence of the chi-squared test. it basically tells you or helps you understand whether there is some sort of correlation between your outcome and a certain category or certain variable. So whether it's gender, whether it's age, whether it's whatever other variable, chi-squared will by default assume that there is no relation. So it's the outcome is independent of that variable, and then running a chi-squared test will tell you. So if the p-value is less than 0.05, that means that that is a incorrect assumption and that there is actually some sort of correlation. Number two, chi-squared test does not test for the actual relationship between variables. It can tell you if it exists or not, but it can't tell you what that relationship is. So you cannot use the chi-squared test to say that gender has a more significant impact on your outcome than, for example, age, or for example the balance on their account, or some other variables. You can't compare, you can't contrast or compare. You can only say yes or no. That's all the chi-squared test can do. So just make sure that you're using the chi-squared test for the correct purpose. You cannot use percentages. You need absolute values. As we discussed, you have to convert your table into the absolute values. Make sure you don't put percentages in. That's a common mistake people make. They put in percentages and then they run the chi-squared test. It'll give you a wrong result. Categories must be mutually exclusive. So you cannot have a category where you can be in one category and then you can also be maybe in the other category. They have to be separate. Like in our example, a person either exited or not. You cannot do both. So that's a very important assumption of the chi-squared test. Number 5, never exclude one of the outcomes. Doesn't really apply in our case, but it's good to know about. Sometimes your data might have several outcomes. Like we have only 2, yes or no. Did the person exit or did the person stay? But maybe you might have a different data set that might have 3 or more outcomes. I'll give you an example. Let's say you're looking at political preferences of people. And so your independent, also your variables that you know about the sample are like gender, age, affluence, how much money they have, what car they drive, things like that. And then your outcomes can be Democrats, can be Republicans, and can also be Greenpeace. So 3 different political preferences, right? And you can't be 2 of them at the same time. They're mutually exclusive because you can only vote for one. And at the same time, there's 3 of them. So what this rule is saying is that you cannot, if you have 3 outcomes, you should never exclude 3 or more outcomes. You should never exclude one of them. So you can't just run the chi-squared test for Democrat and Republicans if the way your sample is constructed that you had all 3 in there, because excluding one of the outcomes can affect the results of the chi-squared test. Having said that, bear in mind that you can exclude categories of one variable. Like in our example, we had 3 countries, right? We had France, Germany, and Spain. And what that means is that we can run the chi-squared test with all 3 countries and just decide whether country as a variable impacts whether or not the person leaves. But what else you can do is you can completely forget about people who are from Germany, right? And you can just take them out for a minute from your analysis and just think about people who are from France and from Spain. And you can compare those 2 against each other. So you can run a chi-squared test just for the 2 of those countries. You just got to understand what the outcome will be. And in that case, the outcome will be whether or not there'll be a significant difference for exiting the bank, depending on whether you're from France or from Spain. So just those 2 countries. So you can do that. You can exclude different categories of one single variable. And finally, rule number 6, a minimum 5 observations in each cell. So that's an important rule of chi-squared test. If you have less than 5 observations in a cell, you can't run the test. You have to look for other tests that might be suitable to your situation. So we're done with the rules, and I'm going to give you a challenge to take away that you can work on in terms of running a chi-squared test. So here is our geography, right? So this is what we just talked about. It's in percentages, so let's convert it into absolute values. There's our geography in absolute values. And now let's create the observed table. That's the observed table. As you can see now, there's 3 categories on the in rows: France, Germany, and Spain. And there's still 2 columns: stayed and exited. And here's our expected table. Similar, right? So when you're going to be doing this, of course, you have to calculate the exited properly. In this case, I used 20%, but in reality, it's a bit different to 20%. So just use the same approach that we used previously. And that's it. So all you have to do is run a chi-squared test. I'll give you a few hints here. First of all, if you look back here, you kind of see right away that probably it looks like there might be some sort of correlation when you run it for all three geographies. So what that chi-squared test will tell you is that what it'll probably tell you is that there is a dependency between the people exiting and which country they're from. And so that's hint number one. So you kind of already know what the outcome should be. Hint number two is when you're creating your table, you just have to add another row here and just make sure that your calculations are correct when you're forming your expected table. Just make them similar to what you see here. It should be pretty straightforward. And that way you'll be able to practice creating a chi-squared test table and then just run the same thing here. So for the p-value, you have your actuals and your expected table. And finally, here's another hint. In case you get stuck, go to this website, vasarstats.net/newcs.html. So what this website can do for you is it will allow you to run the chi-squared test right here. So you just enter the data here, and you don't even have to enter the totals. So you just take the data as is. You just have to take these these cells, or the cells that we looked at in PowerPoint, and you just put them in here, you calculate, and it'll give you the p-value right away. It'll actually give you a lot more information which you can explore, but it'll give you the p-value so you can check that p-value against the one that you created in your Excel template. And so that sums it up for us for today. I hope these two tutorials were very insightful into chi-squared, and that now you're going to be very confident that what you're doing in Tableau, those tests, those very intuitive tests, that they are actually backed by hard statistics, and that you will always be able to stand your ground when you're talking to your manager, to your executive, or presenting to an audience. And I look forward to seeing you in the next tutorial. Until then, happy analyzing. Section recap. So this section was a bit more involved, a bit more technical, I would say, but nevertheless, it put the line under the A/B tests, and now we are sure and confident that what we are doing has statistical significance and backing behind it. So what did we learn in this section? In this section, we learned, number one, how to create and use bins. Bins are very powerful. They allow you to convert numeric variables into categorical variables. So instead of dealing with ages, which don't even have to be integers, which could be numbers with decimal points, now you're going to be dealing with categories. So is the person between 10 and 20, 20 and 30, or 30 and 40, or you could create larger categories like anybody under 25, then 25 to 50, 50 and above. It's all up to you. It's all in your hands what kind of bins you want to create. But basically, bins allow you to move from one type of variables to a different type of variables completely. Number two, how to visualize distributions. So here we saw how to use bins to visualize distributions. For instance, age and balance and any numeric variable. If you try to visualize your numeric variable in its raw form, you might come across the problem that you don't have enough counts in each value, because after all, it is a continuous variable. So that's where bins come in handy. They allow you to pack your observations into these separate segments, and therefore you can properly create a distribution, whether it's a normal distribution, a uniform distribution, or any other kind of distribution. The way to go about it is to create bins. Number three is how to create an A/B test for numeric variables. And this builds on from creating bins and converting numeric variables into categoricals. After you have done that, it's pretty simple and straightforward to build the A/B test. You just follow the framework that we discussed in the previous section of the course. Number four is how to combine two charts in Tableau. So this was a new technique that we learned in Tableau, combining two charts, one under the other, and at the same time working with the new marks pane and seeing the different tabs that appear there, and knowing that you can control each chart separately or you can control them together. So that's a bit of an intermediate technique, I would say, in Tableau, and definitely one that will benefit you whatever type of work you do in Tableau. It's always good to have two visuals on one chart because it allows you to save time. You don't have to switch the tabs all the time, and also gives more power to your visuals, allows you to drive more powerful insights. Number 5, what the chi-square test is and how to use it. So in this course we had, or in this section of the course, we had an introduction to chi-squared, and I showed you exactly how I use the chi-squared to back my findings in Tableau. Up until now, our A/B tests were always kind of very visual, very powerful, very quick, but we weren't sure, can we rely on the results? But now we know how to check whether we can or cannot rely on the results. You use the chi-square test, and in particular, you can go ahead and use online tools that allow you to run it very quickly to check whether or not the difference that you're observing is statistically significant. And what that means is what you're observing in the sample, does it extrapolate onto your whole population or not? You can check that very quickly, and you will from then be confident in whatever you present to your manager, to your executives, to your board of directors, or to any audience you're talking to. It will give you that extra confidence in your findings. And 6, chi-squared for over 2 categories. So chi-squared for just for a variable that only has 2 categories is pretty simple. It's very similar to an A/B test. But a chi-squared test for over 2 categories is still possible. There are online tools that will allow you to do that. But I also showed you my tip or hack on performing this test. You just select the 2 categories that you think there is a difference, and you just run a 2-category chi-square test. Because if there is a difference between 2 categories in a set of categories, then overall the difference will be statistically significant. And even logically, that is sufficient information for you to report. If on the other hand, if you have like 100 categories or 10 categories and only one of them is falling out of place, maybe you want to exclude that category overall and then report there is no difference. So that's kind of a different approach. But nevertheless, you have this method in your arsenal now, and you know how to go about a variable with lots of different categories, and you won't be put off by the fact that there's a lot of categories in your variable, and you don't have to run that huge chi-squared test. You can just check subsets of your categories. And finally, the bonus tutorials on chi-squared, they were more statistical, they were more in-depth about chi-squared. So if you skip them, not a worry. The information that you learned in the rest of the tutorials is completely sufficient. If you did do those tutorials, it just gives you some extra information about the chi-squared and how exactly it works and how it's set up, and just gives you a few extra exercises that hopefully you were able to complete. So that's the end of this section. I really hope you enjoyed it and picked up a lot of valuable tips and hacks from here, and I look forward to seeing you next time. Until then, happy analyzing.
Welcome to the modeling part of the course. You're about to embark upon a journey which is interesting and challenging, which will take you from not knowing anything about stats to being able to build a full-fledged statistical model end to end. And we're talking about building the model, assessing the model, testing the model, deriving insights from the model, and even maintaining the model post-delivery. This section has over 50 lectures and will feel like a separate course in itself. And that is why I wanted to take some time to make sure that our expectations are set before you commit to this journey. So let's go over some key goals that we want to cover off in this part of the course. Key point number 1. There is a huge tendency these days to associate data science with R programming or Python programming. This course is not like that. My goal is not to teach you R programming or Python programming. My goal is to teach you how to be a data scientist, how to think like a data scientist, how to create models, and what tool you use, whether it's SPSS, SAS, R, Python. You can use any tool later on after you have learned the fundamentals of creating a model. And so with that in mind, we won't be going through R programming. I won't be teaching you how to program in R. R has a very steep learning curve, and it could take a whole separate course to teach you how to program in R. And I don't want to get bogged down in all of the coding. I would rather focus on the actual modeling part of the things and explain the intrinsics of modeling to you, because I personally believe that that is way more valuable. And with that in mind, we're going to be using a visual software package which is called Gradle. It's free, and I will show you how to download it and install it, and that will allow us to get rid of that whole part where you have to think about coding and understand it and like learn a lot of stuff about R in order to get to the end result. We can just actually focus on the modeling. Key point number 2. As mentioned before, our end goal is to be able to build a full-fledged statistical model. However, I don't want to just give you a set of mechanical steps that you need to follow to get to the end result. I want to help you understand what exactly is going on when you're running these models. And that's why I will be focusing quite a bit on intuition of things. We'll talk about the intuition of a logistic regression, we'll talk about the intuition of multicollinearity, and quite a few other aspects of modeling. So by the end of this part of the course, you should not only be able to create the models, but you should be able to intrinsically understand what is going on in the background when you're running these models. And finally, in order to get to our end goal step by step, I have broken down this part of the course into logical sections. First, we will have a stats refresher. Then we will talk about the simple linear regression. Then we will move on to the multiple linear regression. After that, we will talk about the logistic regression, and then we will build our geodemographic segmentation model. And after we've built it, we will learn how to test and assess our model. Then we will learn how to derive insights from our model. Then we will talk about how we can maintain our model post-delivery and fight any kind of deterioration that might be going on. And finally, at the very end of this part of the course, I will give you some extra tips, tricks, and hacks that you can take away to really improve your modeling. So that's what we're going to be talking about in this part of the course. I really hope you enjoy this journey and go through it all the way with me, and I look forward to seeing you in the first section. Welcome to the stats refresher section of the course. In these tutorials, we will be covering off the basic stats that will be required in this whole modeling part of the course. This section is not compulsory, so if you feel like you already know all of these things, then feel free to skip this section. You can always come back later if something is unclear. And in these tutorials, we will cover off things like types of variables, types of regressions, the R-squared, adjusted R-squared, and a few other things. So let's jump straight into it.
Hello, this is Kirill, and today we're talking about types of variables. So, variables, they can be of two distinct types. Number one is categorical. And categorical variables, as the name suggests, they describe quality or a characteristic of a data unit. So basically they're answering the question, to what category does this record belong, and what are its properties? So there are two subtypes of categorical variables. Number one is nominal. And nominal variables are observations that cannot be organized into a logical sequence. So basically things like gender, male or female. Let's have a look at a few examples actually. So male or female, you can't order them. You can't say one is greater than the other, or the other one is comes first, the other one comes second. You can't put them in order. Same thing with red, green, black, with colors. You can't order them. So they do categorize your data, but you cannot do anything about it. You can't put them into a chronological or any kind of order, and that's why they're called nominal. So basically a good way to remember this is like names. So nominal and the word names, they sound similar, and therefore, as with names, you can't order them. Nominal variables, you can't order them either. The other subtype of categorical variables are ordinal variables. So these are variables which are categorical, but you can order them. Let's have a look at a few examples. So for instance, small, medium, large. These categories, say in terms of clothes in a store, you can break down your clothes into groups based on what size the label states, small, medium, or large. And moreover, you can order them. So you can put these groups of clothes in a logical order, meaning that clothes in this batch are bigger than clothes in this batch, and then they're bigger than the clothes in the smallest batch. And simple thing with grades, A, B, C. So, A is the highest grade, B is the next grade, C is the lower grade, and so on. So even though they're ordered, even though they're they don't have numbers here. They have a logical inherent order within them. And so those are the two different types of categorical variables. Now, if we move on to the other type of variables, we will go to numeric. So numeric variables are basically numbers, and there are two types of numeric variables. And these variables actually, overall numeric variables, they answer the question how much or how many. So for instance, there are discrete numeric variables, and discrete numeric variables, they are basically whole numbers. So how many units of something or they are, or how much of something occurred, but it can't be a fraction of a number. Let's have a look at a few examples here as well. So for instance, 1, 2, 3, 5, 10, 100 businesses. You can't have 1.5 businesses, right? You can't have 2.25 businesses. So basically there can be an infinite number of observations. That doesn't matter, but as long as there's nothing in between. So there's two businesses, there's three businesses, but there's nothing in between. You can't have a value in between. Same with people. You can have 568 people, you can have 567 people, but there's nothing in between. So you can't find another variable between two set discrete variables that are that come in sequence. And finally, the last type of numeric variables or overall variables that we're going to look at is continuous variables. So continuous variables are a subtype of numeric variables. They also answer the question how many or how much, but unlike discrete variables, they can be a fraction. For instance, age or height. So you can be 173 meters tall, you can be 173.5 meters tall. So basically any two continuous variables that you take, or continuous values that you take on your scale, say 173 and 173.5, there will always be another continuous variable between them, so 173.25. And even if you take 173.25 and 173.5, there'll still be another one in between them, 173.257, and so on. So there's always another variable between any two, or there's always another value between any two continuous values. So they can be, of course, restricted at the minimum and maximum, so you can't be lower, or for instance, with age, you can't be younger than 0 years old, and you can't be older than 150, unless medicine goes through the roof in the next couple of years. So there can be restrictions, but within those boundaries, there's an unlimited number of values that the variable can take. So those are 4 types of variables: nominal, ordinal, discrete, continuous. Have a look around you. Try to think of other examples. It's a very good exercise to remember these 4 different types. In this whole section, we'll be dealing with regressions quite a bit. So in today's tutorial, we're going to talk about the different types of regressions we will be covering off. This is how Wikipedia defines a regression. In statistics, regression analysis is a statistical process for estimating the relationships among variables. The focus is on the relationship between a dependent variable and one or more independent variables. So let's look into this a bit more. They're going to look at 2 types of regressions in this part of the course, the linear regression and the logistic regression. And they both have 2 subtypes, the simple linear regression and the multiple linear regression, and the simple logistic regression and the multiple logistic regression. In terms of logistic regression, the distinction between simple and multiple, it's of course there, but people rarely use a simple logistic regression. So whenever you hear logistic regression, it implies multiple. And moreover, we're going to talk about logistic regression when the time comes, because we're not ready for that yet. So in this tutorial, we're just gonna talk about a simple linear regression, and we'll also cover off multiple linear regression in the next few tutorials as well, a little bit. So simple linear regression and multiple linear regression, what are they? Well, a simple linear regression is basically this formula where y equals b0 plus b1 times x. And you might recognize this formula from back in high school. It's just a formula of a trend line, or a sloped line on a xy axis. And let's go through these variables and coefficients one by one. So This is the dependent variable. The dependent variable is something you're trying to explain. For instance, how does a person's salary change with the years of experience that he has? So in that case, y would be the dependent variable. Or what grade does a student get depending on how much time he's put into studying? In that case, y would be the dependent variable. So something that you're trying to understand how it depends on something else. X is your independent variable. In this case, in the simple linear regression, we only have one independent variable, so we don't even have to call it x1. We could just call it x. And this is the variable that you're assuming that it is causing the dependent variable to change, or as we will learn further, sometimes that independent variable might not be a direct causative factor, but it's still, there might be an implied association between the two. And in that case, you're trying to figure out this association. Then B1 is the coefficient for the independent variable, and it kind of says how the effect, or how a change in x1, a unit change in x1, and we'll be talking about this a lot, unit changes. A unit change in x1, how that affects a unit change in y. So it's kind of, think of it as the translator or the multiplier or something like that connects the two, the connector between y and x1. So you can't just say, you can't always say x1 is directly proportional. There is, well, you can't just say y, the change in x is always equal to the change in y. There might be this coefficient of proportion, to which proportion that change is inflated or deflated. And B0 is a constant, so it's a constant term, and we'll talk about the constant just in a few seconds, or in a minute after we cover off the multiple linear regression. So multiple linear regression, same thing but many variables. So B0, one constant, and then many combinations or many pairs of B and X, and it can go up to quite a lot. Depends on how many regressors you have. Here, once again, you got a dependent variable, y, so something you're explaining, but this time the difference is that you think there might be a few causations to it. So in the case of salary, for instance, it could be how much years of experience you've done, how many other courses you've done, how much, how much time you spend at work, or things like that, or how valuable, how much money you make for the company. In terms of a student and his grade, so if your dependent variable is what grade does the student get, then in the independent variables could be how much the student has studied for the exam, maybe how much he has slept before the exam, how many lectures he has attended throughout the course, and things like that. The constant is still there, and also you got the coefficients. So now let's look at the simple linear regression, because it's the easiest one to discuss. It's very pretty straightforward. You can visualize it quite well. So here we've got the y and x axis. Let's look at that specific example where we have experience and salary. So experience is going to be our horizontal axis, salary is our vertical axis. And we want to understand how people's salary depends on their experience. Well, what we do in regression is we don't just come up with a theory, we look at the evidence, we look at the live hard facts. So here are some observations we've had. So in a certain company, this is how salaries are distributed among people who have different levels of experience. And what a regression does is, so that's the formula for regression. In our case, it will change to salary equals B0 plus B1 times experience. And what that essentially means is just putting a line through your chart that best fits this data. And we'll talk about best fitting in the next tutorial when we're talking about ordinary least squares. But for now, this is the chart, this is the line that best fits this data, and even looks like it, right? So it's quite hard to draw a line that fits this data better. And the assumption here is it's impossible. This is the best line that approximates this data. What does that mean? Well, we'll talk about that in the next tutorial once again. For now, let's focus on the coefficients and the coefficient and the constant. So what does the constant mean here? Well, the constant actually means the point where the line crosses the vertical axis. And let's say it's $30,000. What does that mean? Well, it means that when experience is 0, so when, as you see on the horizontal axis, when experience is at 0, then in the formula on the right, you can see that the second part, B1 times experience, becomes 0. So salary equals B0. That means that salary will equal to $30,000 when a person has no experience. So as soon as somebody's fresh from university and joins this company, most likely they will have a salary about $30,000. There will be some confidence intervals there, but we won't go into that right now. Just we can say that according to this model, that person will be probably getting paid $30,000. Now, what is B1? B1 is the slope of the line, and so the steeper the line, the more you get, more money you get per extra year of experience. Let's look at this in this particular example. Let's say somebody went from, I don't know, maybe 4 to 5 years experience, right? So then to understand how his salary will increase, you have to project this onto the line and then project that onto the salary axis. And you can see that here, for 1 year experience, the person will get an extra $10,000 on top of his salary. So if the coefficient B1 is less, then the slope will be less, and that means the salary increase will be less per every year of experience. If the slope is greater, then that means the experience will yield a more increase in salary. And that's pretty much it. That's how a simple linear regression works. So the core goal here is that we're not just drawing a line theoretically that we came up with somehow. We're actually using observations that we have to find the best fitting line. And what a best fitting line is, we'll talk about that in the next tutorial. Ordinary least squares. In the previous tutorial, we talked about the linear regression being a trend line that best fits your data. Today, we'll find out how to find that best fitting line, or in fact, how the simple linear regression finds that line for you. So here's our simple linear regression, the same chart, salary versus experience. We've got these red dots, which represent the actual observations that we have in our data. And we've got the trend line, which represents the best fitting line, or the simple linear regression model. So now let's draw some vertical lines from the actual observations to the model. And let's look at one of these specific examples to understand what we're talking about here. So here you can see that the red cross is where that person is sitting at in terms of salary. So let's say this person with 10 years of experience is earning $100,000. Well, the model line, so the black line at the bottom, it actually tells us where that person should be sitting according to the model in terms of salary. And according to the model, it should be a bit lower. It should be somewhere where that green cross is, which is about maybe, let's say, $80,000. So now the red cross is called YI, so Y with the subscript I, and that is the actual observation. The green cross is called YI hat, and that is the modeled observation, or the modeled value. So basically, with that level of experience, where would he be? Where does the model predict that he would be earning? And so the green line, therefore, is the difference between what he's actually earning and what he should be earning. So, or not should be, what he's modeled to be earning. So therefore, the green line, it will be the same regardless of what dependent variable you have, whether it's salary, whether it's grade at school, whatever. So it's the difference between the observed and the modeled for that level of independent variable. Now, to get this best fitting line, what is done is you take the sum, you take each one of those green lines or those distances, you square them, and then you take the sum of those squares. Once you have the sum of the squares, you gotta find the minimum. So basically, what a simple linear regression does is it draws lots and lots and lots of these lines, these trend lines. Well, this is like a simplistic way of imagining it. The linear regression draws all these, all possible trend lines through your data and counts the sum of those squares every single time, and it records it somewhere in a temporary, file or something like that. And then it finds the minimum one. So it looks for the minimum sum of squares. It finds a line which has the smallest sum of squares possible. And that line will be the best fitting line. And that is called the ordinary least squares method. So that's how the simple linear regression works. And I look forward to seeing you on the next tutorial. R squared. This is a very interesting parameter. A lot of people use it, and sometimes they use it without knowing the underlying principles of R squared. So let's quickly get a understanding of what R squared is, because we will be using it too. So last time we stopped over here, we talked about the simple linear regression being constructed through the ordinary least squares method, where we are minimizing the sum of squares of those differences yi minus yi hat. And basically, we are looking at what the model is predicting and what is actually happening at a certain level of experience or at a certain level for the independent variable. And we're looking at that difference. We're squaring it. We're summing it for all of the observations we have. We're counting that sum. And then the line that has the smallest sum will be the best fitting line, or will be the simple linear regression model. So let's get rid of that call out for a second, and let's remember this value. So we'll need it just now, and in fact, this value has a name. It's called the sum of squares of residuals. So we'll just label it SSRes. And now let's do something else with our chart. We'll get rid of those lines. So this is our raw chart with the observations. And instead of drawing the regression line, let's draw the average line. So this is your average salary across all of your observations. Now let's do the same exercise and project our observations onto this line. And now if we calculate the distances, the red distances, and we square them, then it'll look like this. It'll be yi minus y average squared, and then we'll take the sum of all of these distances. Now this value also has a name, and it's called the total sum of squares. And what r squared is, r squared equals to 1 minus sum of squares of residuals divided by total sum of squares. And so what this is saying is that there will always be a sum of, or total sum of squares, right? So the average, not all, your records are not always going to be all equal to the average, otherwise it's a very boring data set. So sum of, the total sum of squares will always be some sort of value. And what you're trying to do with your regression is you're trying to fit a line to minimize, as we discussed previously, to minimize the sum of squares of residuals, to make it as small as possible, right? So in a way, the way to think of it intuitively is the average line, which we have on the chart right now, is also a type of a trend line. It's just horizontal, right? It's not sloped, it's just a horizontal trend line, but it kind of also is. So you can think of it as a model that is fit to a dot. It's not the best model, but it's just y average. So what you're trying to do by fitting a sloped line and minimizing the sum of squares of residuals is you're trying to fit the best line. And what r squared is telling us is it's telling us how good is your line compared to the average line, which anybody can think of, right? So it's not hard to take the average. You take a calculator, you get the average. But in order to fit the best fitting line, you have to actually run a linear regression. And if you look at the formula, so you're trying to minimize SS residual, right? So sum of squares of residual. So on the right over there, that part of the formula, as you minimize SS residual, it goes smaller. It always becomes smaller. And that way, SS residual divided by SS total becomes smaller, and 1 minus SS residual divided by SS total becomes greater. So ideally, if your SS residual is 0, so basically your trend line that you're modeling goes through all your records, then in that case, r squared is equal to 1. And that's the ideal scenario. But that normally never happens. So the closer r squared is to 1, the better. The further away it is from 1, so the lower it is, the worse. A good question is, can r squared ever be negative? The answer is yes, of course r squared can be negative, and that is if your, for instance, SS residual actually fits your data worse than your average line. It's hard to do, but you gotta try, because if you just draw a random line, I guess, then facing the wrong way, so here it would be going downwards, then probably yes, you would get a negative r squared. So that means that the model is completely broken. It's better to use the average and even to use the model. But normally, so r squared is normally between 0 and 1, never gets greater than 1, and the closer it is to 1, the better. All right, so this is the fun part, adjusted r squared. So here we've got a simple linear regression. We've talked about how the r squared is derived. So what the formula for r squared is, it's equals to 1 minus sum of squares of residuals divided by total sum of squares, where sum of squares of residuals is the sum of squares of the distances from the observations to your fitted line. So we don't see it here. That's your simple linear regression line that we fit onto our data, and the total sum of squares, we can see it here. So that's the total, the sum of the squares of those red lines we can see here. So the difference between your observations and the average. So basically r squared is telling us how well is your model fitted to the data, and in fact how much better is it fitted than the average line that you can just draw through your data very easily. So let's get rid of all of that and put our r squared formula on the left for a second. Now, we talked about r squared for a simple linear regression. Well, the same concepts apply for a multiple linear regression. So for instance, with two variables, r squared would be calculated in the same way. We're just not going to go through all these derivations right now because it's just easier to visualize the way we've done it, and exactly the same concepts apply to a multiple linear regression. And still, so what that means is that the ordinary least squares method is used, and the best fitting multiple linear regression is the one that has the least sum of squares of residual. So you're trying to minimize the sum of squares of residual. And why am I bringing that up? Well, we'll need that in a second. So we want to use r squared, as we discussed, as a goodness of a fit parameter. So the bigger it is, the better. The closer it is to 1, the better your model. And that's awesome. We can totally try doing that, but there is one problem. And the problem is, or starts to occur, when you add more variables to your model. So here you can see we've got two variables in our multiple linear regression. What will happen if we add a third variable to our model? Think of it as an example. Let's look at that example with salary. So your salary equals to a constant 30,000 plus 10,000 times the years of experience, plus, for instance, B2 could be a constant coefficient times the number of qualifications you have, and I don't know, B3 could be how much money you brought the company in the previous year. So if you're a salesman, for instance, so a coefficient times the amount of dollars that you brought the company in the previous year, something like that. So you can keep adding on variables that you think are actually impacting the outcome, so are impacting the dependent variable, and you want to fit a model and see, you know, if it's better or not. So in this case, we're adding a third variable. We already have a model with two variables and it works okay. And now we want to add a third variable and see if maybe using the third variable, we can fit our model even better. So we can create an even better model with three variables. So how can we judge that? After we've added our variable and we've run the model, we can look at the r squared. Did the r squared get better or worse? So in fact, did the r squared increase, or did it decrease or stay the same? So the problem here is that r squared, because of these two things, r squared will never decrease. And let's go through that in a bit more detail. I'm going to use my mouse here because this is quite an important part. So r squared over here is equal to 1 minus sum of squared of residual divided by sum of squared of total. So once you add a new variable to your model, right, it's going to somehow affect what the model looks like. And the fact that we're trying to minimize the sum of squares of residual, what that means is that either this new variable will help minimize the sum of square of residual, somehow the regression process will find a way to give it a coefficient that will help minimize the sum of square of residuals, and then and in that case, r squared will happen to r squared. It'll be 1 minus something that is less than it used to be, right? Divided by the same value, because by adding a new variable, we're not affecting the observations, we're not affecting the averages of the observations, right? This does not change. So by adding a new variable, the regression process through this condition will definitely try to minimize this value, make it even smaller than it is currently. And that way, this whole part will decrease, and this whole part will increase. So your R-squared will increase. If it so happens that the new variable that's added, whatever coefficient you give it, a new coefficient you give it, if you cannot decrease SS residual, right? What will happen? Well, this coefficient will just become 0. It rarely happens. I don't think I've ever seen a coefficient like be exactly 0, and I'll tell you just now why. But in the worst case scenario, the regression process will say, nah, this variable is completely just making the model definitely worse, so I'll just put a 0 instead of this coefficient and forget about it. And that way SS residual won't change and R-squared won't change. So you only have two options. Either R-squared will increase or it won't change at all. So R-squared will never decrease if you add variables. And why I say that B3 is never equal to exactly 0, because there can always be, or there will always be, at least a slight random correlation between the independent variable and the dependent variable. It doesn't matter what you put in here. So even in the example when we're looking at salary, so salary equals years of experience plus how many qualifications a person has, and then we can add in what is the last digit of the person's mobile number, right? Of course, that is not going to, it doesn't have any correlation with the independent variable whatsoever. Well, there's no causative factor, there's no association between the two. The last digit of your mobile number has no effect on your salary. But if we add it in, and there will randomly be a slight correlation, it'll just be a random correlation, and the regression process will pick it up and will give it a coefficient, and R-squared will probably decrease by that tiny little, or increase by that tiny little bit. And so that is why there's a problem with R-squared. You can add variables and you will not know if those variables are helping your model or if they're not helping, because your R-squared is biased. It's basically always increasing regardless of the actual improvement or non-improvement in fit. So we got to come up with a different parameter to measure goodness of fit, and that is where adjusted R-squared comes in. And this is the formula for adjusted R-squared. Here, P is the number of regressors, so the number of independent variables, n is the sample size, so it's over here. Now they say that adjusted R-squared has a penalization factor. It penalizes you for adding independent variables that don't help your model. And let's talk about that. That's the important bit about adjusted R-squared. So P is the number of independent variables. Let's look at P. P here is in the bottom, in the denominator. That means that when P increases, when you increase the number of independent variables, this whole part decreases. And when this whole part decreases, the denominator decreases, the ratio increases. And as the ratio increases, this whole bit increases as well. And as this whole bit increases, 1 minus this whole bit decreases. So as you can see, as you're adding more regressors, the adjusted R-squared is decreasing. It's going further away from 1. And that is the important part. Also, you can see here what happens when R-squared increases. When just normal R-squared increases, so this part decreases, right? 1 minus R-squared decreases. And that means that this whole part increases. So you've got a battle here. On one hand, R-squared, by adding a new variable, you're increasing R-squared. So you're increasing adjusted R-squared. But on the other hand, by adding a new variable, you're increasing P. So you're decreasing adjusted R-squared. And in that sense, it's a fair battle here. If your variable is not good, is not helping the model, then adjusted R-squared, this will be an insignificant increase, and this penalization factor will actually drive R-squared down, adjusted R-squared down. If on the other hand, your new variable that you added is helping the model a lot, then the increase in R-squared will be substantial, and it will overwhelm this penalization factor. So even though you'll still get penalized for adding a variable, the increase, the benefit to the model will be so great that even the adjusted R-squared will go up. And so that's how the adjusted R-squared basically works. It's a very good metric. It helps you understand whether you're adding good variables to your model or not. And we'll be using adjusted R-squared throughout this course to make sure our models are robust when we're building them.
Welcome to the section on linear regression. I hope you enjoyed the stats refresher, and today we're starting to slowly ease into modeling. And this first section is really designed to get you comfortable with the software package that we'll be using, which is Gradle. And along the way, you will learn how to upload data into Gradle, how to run some simple descriptive statistics, then how to run a simple linear regression, how to read the output, and how to plot a chart. And altogether, all of those things will actually just give us this little first step into modeling, and then we'll build on from there. And I hope you enjoy this section. I look forward to seeing you in the first tutorial.
What is Gradle? Gradle stands for GNU Regression, Econometrics, and Time Series Library. This is a free software package for econometrics analysis, and this is what Gradle looks like on the inside. Those of you who have worked with SAS and SPSS before will notice that it's got a similar interface. And that is correct. All of these software packages for modeling resemble each other's interfaces, and conceptually, they are very similar too. Once you learn one of them, it's much easier to grasp the rest. In Gradle, we will be able to do the same modeling just like in R and Python, but we won't have to code. And that's the big deal here. Some of you may already know R very well, but some may not know it at all. As I mentioned in the intro to this section, my goal is to show you how to build a robust model and give you a framework of steps that you can apply in any tool you choose. That's where Gradle will help us avoid getting bogged down in our coding. Now let's go ahead and install Gradle. To start off, you're going to need a browser. And in Google, type in simply Gradle. And then here, one of the top links will be the SourceForge link. Go ahead and proceed to that. Here, you need to find a link which takes you to the installation packages. So at the bottom here, it says Gradle for Microsoft Windows can be found here, and Gradle for Mac OS can be found here. So I'm going to click the Windows link. Inside this page, you can see that there are several different versions. You need the latest release, and there's one for the 32-bit operating system. There's one for the 64-bit operating system. So select the correct one for your system. And also, you know how sometimes at work you can't install programs because you don't have admin rights? I remember at my previous job that was the case, and it was very annoying that I couldn't install software like this. So in this case, you can actually download a zip archive. It's a portable version, so that means once you download it, you just unzip it and you can use it out of that folder right away without having to install the program. And that will allow you to use it even if you don't have admin rights. So if you need that, go ahead and install that. And for the Mac OS, it's very similar, very straightforward. Here you just have to select the type of operating system you're running, or type of processor actually your computer is running, and then the instructions are straightforward from there. And once you've installed Gradle, make a shortcut on your desktop and you're ready to proceed to the next tutorial. In this tutorial, we're going to download the dataset we're going to be using in this section. In order to get the dataset, let's go to superdatascience.com/training. And here, if you scroll down here, part 2, modeling, we need to go to section 2, simple linear regression, and just get this dataset, which is salary data. It's a CSV file. And then I've created a folder here, modeling section. And here I've got the 4 sections prepared. And if you go into simple linear regression, I've put the file here already. Now it's a CSV file, so it's basically a text file separated by commas, and we can open it up with Notepad++ or any Notepad type of editor. And here you've got your data. And if you don't like looking at it in this way, because it's not really, the columns are not exactly under each other, so you can open up with Excel. I'm just going to drag it into here. All right, so what we see here is 2 columns. Very simple data set. Years of experience and salary. And basically it's telling us for a given company, there's 30 observations, and they took 30 random people and said, all right, so how many years experience do you have? This is not just with the company, this is overall years of experience in the workforce. And what is the salary of that person? And then what they did is they wanted, or they've asked you, they've hired you as a data scientist to find out if there is any sort of correlation, or what is the correlation between salary and years of experience. So this is one of those cases when management obviously knows that there is a correlation, that it's they set the salaries, right? But maybe it's like it's a new company, maybe they only have 100 employees or something, and they've been kind of setting them randomly so far. They know that, you know, experience matters, and they've been taking it into account when when setting the salary for a certain employee. But there's always this range within which it fluctuates, and they've got like ballpark estimates that they are adhering to, but they don't have a certain strict rule. And what you're going to be doing in this section, well, first of all, you're going to investigate what is the correlation. Well, obviously, it's probably going to be the more years of experience you have, the higher is your salary, and we kind of can see that trend already. But we will actually be creating a model, a simple linear regression model, which will tell us what is the best fitting line for this relationship. And if you want to look at it from a business value add perspective, what is the business value add of this project? Apart from us, of course, learning about simple linear regression, the business value add here is that if the company doesn't know they don't have a certain set of rules how to set salaries, you can then go back to them with this model and say, okay, actually, this is how so far you've been setting salaries, and if you want to continue, then this is the model you should be applying, you know, plus or minus a certain deviation. But you'll be able to tell them for future employees, say here you can see there's only somebody with 10.5 years experience. So what do they do when somebody with 15 or 20 years of experience comes into the company? They can either randomly like guess a number, or they can use your model to set them a salary that everybody else, you know, won't feel uncomfortable with. So something like that. So there is a business value add even in a small project like this. And let's get started to learn and practice simple linear regression. I look forward to seeing you in the next tutorial. All right, so let's launch Gradle and import our data. To launch Gradle, double click the icon, and here now go to File, Open Data, User File, and here we're going to need to locate where we are storing our data set. So mine's on my desktop in my modeling section, simple linear regression, and here just at the bottom in the drop down, select all files. You can select CSV, but I usually select all files, and there it is. That's our file. So let's double click that and open it up. And right away, we've got a message here saying that the imported data have been interpreted as undated cross-sectional. Do you want to give the data a time series or panel interpretation? So here, just click no. We don't want a time series or panel interpretation. Here you got some stats on what data was imported. So that's normal. And here you have basically your variables and the constant. So what we can do here, let's start getting used to Gradle. And you'll get more and more familiar with the interface as we get along. It's very simple. After a few of these tutorials, you'll be swimming here very, very easily. Okay, so what we're going to do is we're going to go to View, and here we want to look at the summary statistics of our data. So if you go View Summary Statistics, here you can select the variables that you want to view. So let's start with one, for instance, say years experience. We want to see what population we're looking at here, or what sample we're looking at here. And here you can see the mean. So on average is 5.3 years experience. The median, the minimum 1.1, maximum 10.5, standard deviation, stuff like that. Then you got the percentiles of your year's experience and no missing observations. So that's quite useful. The other thing we can do is we can do the same but with both variables. So summary statistics, and we can just put both variables in here. So you can see this is like a drag and drop interface, or more just probably a very handy visual interface, not really drag and drop, but you can take things out, so you can like put things in, out, very intuitive, I guess. So here you click OK now, and there you go. So now you have your statistics for both variables. So you've got your means, your medians, minimums, maximums, percentiles, standard deviation. The rest of them we won't be that interested in. So that's basically the most basic thing you can do probably in Gradle. You can also like right click your variable here and say display values, and it'll show you the exact values that were imported if you want to look at them. What else? You can, for instance, edit values if you want. That will allow you to actually manipulate your values, which I don't recommend doing. But if you need to adjust something, you can do it right in here. You don't have to go back to the CSV file. Then what else? You can edit attributes. So you can change the name of the variable, you can add some description and so on. And by the way, like we'll see later on, if you make changes to your data that can't really be stored in a CSV file, like descriptions and other things like that, then you can always, when you save your data, you have an option to save it as a Gradle data file. And that way Gradle will actually store all these modifications that you're making, and they won't be lost. So Gradle does have its own type of files that it creates. So that's basically the most simplest thing you can do in Gradle. If you like, play around, click around here, what else you can find. There's lots of stuff. Even if you break the data, you just modify it or something, doesn't really matter. This first section, we're just getting to know Gradle, and we'll just do a simple linear regression in the next tutorial. So nothing bad can happen even if you play around with it. Just as long as you're comfortable with this interface, and we'll get straight into it in the next tutorial, and I look forward to seeing you then. All right, so our data is imported, and now we're going to run our very first linear regression model. Hope you're excited about this. Let's get straight into it. So in Gradle, we need to click this menu up at the top, model, and then we'll just select the ordinary least squares, which is our simple linear regression. So here we're going to take salary and we're going to put it into the dependent variable, because that's the variable that we want to predict. And years of experience, we want to put it into the regressors. So that's going to be the independent variable, and we want to see what is the relationship between salary and experience. And also here you see that there's a variable here by default, which Gradle puts in there for you. It's constant. It's always going to be there by default, and we're going to leave it in there as well. Okay, so we're going to click OK now, and voila, this is the magic screen. So if you have not seen this before, then you should start getting used to it, because depending on how you structure your data science career, you will either see this a lot and all the time, or you might see it occasionally, infrequently, but you will still eventually have to deal with this report, and this is actually the result of running your model. And this report will be exactly the same wherever you run your regression, whether it's in SAS, SPSS, R, Python, anywhere. The report will look like this. So let's learn how to read this report, and let's learn how to extract the valuable data that we need. So at the top, you've got the observations that were used, the type of regression, so ordinary least squares in this case. Then you've got the dependent variable name, it was salary. Next, there's two parts, this part and then this part. This part is a breakdown of information, of statistics per independent variable. Right now we only have two independent variables, so the constant, which isn't actually a variable, it's just the constant, and then we've got this independent variable, years of experience. And then here you've got information which relates to the model overall. So let's start with the first block. What are we seeing here? Well, here you see the coefficients. Those are the coefficients that we discussed in our formula. And constant being $25,792.2 means that the line of the linear regression crosses the vertical axis at 25,792.2, which means that if you have 0 years of experience, so if this variable is 0, then according to this model, your salary should be $25,792.20. And then the coefficient for years of experience is $9,449.96. What does that mean? Well, that means that for every 1 year increase in experience, the salary goes up by $9,449.96 in the modeled world. So it doesn't necessarily happen like that in real life, but from what we've modeled, and we'll see that in a second when we look at the graph, this is the way things work in the model world. With somebody with 0 years of experience starts with this salary, and then for every year of experience, the salary increases by so much. And if it's a fraction of a year of experience, so if it's half a year, then it'll be an increase of half of that. And that's all in line with the linear regression formula. Then you've got the standard error here, you've got the t ratio, and you've got the p-values for each of your constant or variables. In this section, or in this part of the course, we'll be focused. Of course, these are all important, and it depends on what you're doing with your data science project. You might need to work with these, but in this particular part of a course, we're going to be talking about the p-values mostly. Why? Well, that's because the p-values allow us to understand the statistical significance of individual variables, and we will be focusing on this quite a lot in the further sections of this part of the course, because it will allow us to filter out variables that are not actually predicting anything. So I'll give you an example here. Right now the p-value is very, very small, so it's 1.14. Looks quite a lot, but then you got to multiply this over here is a scientific term for 10 to the power of minus 20. So that's, you got to multiply 1.14 times 10 to the power of minus 20, which makes it a very, very small value, tiny value. And well, that is a good thing. The smaller the p-value, the better. That means that this variable actually predicts something. So if you had a p-value which is great, which is quite high, for instance, even higher than 0.05, so in percentage terms, higher than 5%, that is already considered a high p-value. And what it's saying is that when you change the independent variable, it won't actually be associated with any change in the dependent variable. So you can only, you got to pick, and we'll talk about this further in this part of the course, in the modeling part of the course, but you got to pick a threshold for your p-value. So for instance, if you stick to 5%, which is probably the most used p-value or the conventional p-value threshold, then if your p-value is above 0.05, so if here you see is above 0.05 and there's no multiplying by 10 to a very negative number, then that means that your p-value is above 5%, and that means that the relationship between these two variables, salary and years of experience, isn't statistically significant. And so basically your model, in layman terms, it's not actually working. So this variable is not predicting anything. So that's how you read this part of the report. Let's move on to the second part. So here you've got some stats about the model overall. And the ones that we'll be focusing on in this course that are most important to us are the R squared over here and the adjusted R squared. And we've already spoken about these two parameters back in the previous section when we were talking about refreshing our stats knowledge. So we will see how we're going to be using them further in the course, especially when we're building our customer segmentation model further on. All right, so now what we're going to do is look at the graphs. The first way you can bring up the chart of the linear regression model is you go to graphs and you go to fitted, actual, plot, and then just go actual versus fitted. And here you've got your observations, which are in red, and the model, the fitted model, in blue. Before we continue, I'm going to bring up the other chart, or show you the other way you can bring up the chart. So if you cancel that and you go to analysis and then you go to forecasts, and then without forecasting anything, you just click OK. Then here, what you'll see is two things came up. So the chart, which we'll look at in a second, and also the forecast. So basically what happened here is Gretel took your existing records. So here you got your 30 records, and it didn't print any information on the independent variables. So years of experience is not here, as you can see, but it does have salary. So the actual salary that was in your file. And then it's got the predicted salary. So the salary that the model is predicting for that record. And you can just visually compare them here, see the standard errors, 95% confidence intervals, if you like. And also what this would have done if you, in terms of prediction, why is it called prediction? Well, if you did have some records where there was an empty value for salary, say 31, 32, 33, then it would actually populate them for you. It would it would still generate a prediction, and that way you could, for instance, extrapolate what you have this line onto new salaries. So you could see what the salary would be for people with more years of experience than you have in your data set. So we're going to close that, and we're going to look at the graph now. So this graph is a bit more involved because it has the 95% confidence intervals here in green. So in short, in a quick summary, what happened here is originally we only had the red dots or crosses, meaning that that's how salary is dependent on years of experience. So basically, if you take 9 years of experience, then you can, using this blue line, you can predict where the salary for 9 years of experience will be. And what the confidence interval is telling us is that there's a 95% chance that that salary will actually be somewhere between these two green lines on this vertical 9-year line. So basically, it doesn't have to be on the blue line, and as you can see, a lot of the actual values are not on the blue line. Some are, but mostly they're not. But we know that according to our data, with a 95% chance, it's going to be between these two green lines. And also, what we can see here is that the blue line, if it were to cross the vertical axis, it would cross somewhere at that constant value that we looked at, which is 29,000 and something. So here we have it. It's actually 25,792. That's where the blue line would have crossed the vertical axis. And as you can see, well, of course, like there's not enough space here, but that's because this axis should be a bit more to the left. There, 0 would be somewhere here, so there would be enough room for it to cross. And years of experience, that's the slope. That's basically the angle at which this blue line is going. If years of experience were also basically the coefficient for years of experience, so if this value was more than $9,449, then the slope of the blue line would have been higher. If it were lower, the slope would have been lower, so it wouldn't be as steep. So this is basically saying that whenever you move from, say, from 3 years to 4 years, from here to here, your salary increases by approximately $9,500 from here to here. So that's how this whole simple linear regression works. Hope it all makes sense. Play around with the data, maybe run a few more of these just to get comfortable with it. And remember that we'll be working with this screen quite a lot coming forward. And I look forward to seeing you next time. Until then, happy analyzing.
Welcome to this section of the course on multiple linear regression. I hope you enjoyed the tutorials on simple linear regression, and now that you're comfortable with Gretel, we can move on with our next step in our modeling journey. And in this section, we will learn quite a lot of things. We will start off by talking about dummy variables, and you will find out what you need to do when you have categorical variables as some of your regressors. Then we'll talk about the dummy variable trap, so that we can get that important topic right out of the way right away, so you never fall victim of the dummy variable trap. And then we will learn all the ways that you can build, or the main dominant ways that you can build a regression model. So we'll talk about the forward selection, backward elimination, and bidirectional elimination methods. Then we will actually learn how to apply one of those methods in practice, and we will build a model ourselves. And finally, we will finish the tutorial, this section off by reading the output, learning how to use the adjusted R-squared to make our models even more robust, and of course, understanding how to interpret coefficients of a multiple linear regression. So quite a saturated section ahead. Hope you enjoy the tutorials, and I can't wait to see you on the first one.
Before we dive into this section, I wanted to give you a quick heads up that there's a caveat around everything that we're doing with linear regressions. Linear regressions have assumptions, and the assumptions are listed below: linearity, homoscedasticity, multivariate normality, independence of errors, and lack of multicollinearity. And before building a linear regression model, you need to check that these assumptions are true. And then you can only proceed and be sure that you're building a good linear regression model. Well, in this section, we won't be focusing on that. We won't be checking these assumptions at all. And the reason for that is that we have a different goal in mind. Linear regression is not our end game. Linear regression is just a stepping stone for us to get used to regressions and get comfortable with them, and then proceed onto the main part of our modeling section, which is geodemographic segmentation. We want to build a geodemographic segmentation model, and for that we will actually need a logistic regression. And logistic regressions have different assumptions around them. And therefore, we won't be focusing on the assumptions of linear regressions in this section of the course. But if you ever do need to build a linear regression, then make sure that you don't just blindly follow the steps that I present to you in this section of the course, but you do need to go back to the assumptions of the linear regression and research them and make sure that they're correct when you're building your linear regression. However, having said that, I want to point out that from my personal experience, logistic regression is hands down by far the most frequently used type of regression in data science. So what you will learn in this part of the course will definitely give you the maximum benefit for your data science career. All right, so multiple linear regression data set. Let's get straight into it. This one's going to be fun. We've got multiple linear regression here, same URL, part 2 modeling, section 3 multiple linear regression, 50 startups. This is going to be a venture capitalist fund challenge. All right, so once you've downloaded the file, let's put it into our folder, multiple linear regression. There it is. I'm going to bring up Excel, and we'll open up an Excel right away. All right, let's zoom in a bit. So what do we have here? We've only got 5 columns, but the real interesting thing about this data set, this is like a very realistic, lifelike business challenge. So you've got 50 companies here, 50 companies in total. And what they have is they have some extracts from their profit and loss statements, from their income reports. So how much did the company in this given financial year that you're analyzing it for, how much in that year did it spend on research and development? How much did it spend on administration, like paying employees, paying executives and so on? And how much did it spend on marketing? So those are the three major operational spends, I guess. And which state it works in. Does it work in New York, or does it operate in New York or California? And finally, what is the profit? What was the profit of that company for that financial year? And the challenge here is, this is a data set. It's totally anonymized, so we don't know the companies. And also, there's only 50 companies. So there's a venture capitalist fund that has hired you as a data scientist to analyze these 50 companies, or analyze this data set and create a model that will tell the venture capitalist fund which types of companies it is most interested in investing. And their main criteria is the profit. So profit is their dependent variable, the most important variable for them, and these are all independent variables. So you have to create a model which will tell you about profit based on R&D spend, administration, marketing spend, and state. And bear in mind that the venture capitalist fund is not looking to invest in these 50 companies per se. It's not just giving you a data set and then, like, obviously then they would invest in this one because it's got the highest profit. But what they're looking for is, this is a sample, and they want to understand, for instance, where companies perform better in New York or California, all other things held equal, or which companies perform better. If you hold these columns equal, right, will a company that spends more on marketing perform better, or a company that spends less on marketing? Also, they want to understand, the main thing probably they want to understand is how when they assess companies, do they look for companies that spend more on R&D spend, or on research and development, or companies that spend more on marketing? So which of these two spends yields better results of profit, brings more results of profit? And based on your model that you'll create, they'll set up a set of guidelines for their own venture capitalist fund, and they'll be like, okay, so we are most interested in companies, this is just an example, that work in New York, that operate in New York, and that have a very low administration spend and a very high R&D spend, so the R&D spend has to be much higher than administration and marketing spend, something like that. So basically you're helping them create a model based off this sample that will allow them to assess where and into which companies they want to invest to achieve their goal of maximizing profit. So there you go. It's already not an obvious data set. It's got many variables, got many records. You can't just tell off the top of your head. You probably can see that they're ordered by profit here, right? But there is kind of a mix all over the place. So let's get into this. It's going to be a fun and exciting section, and I look forward to seeing you on the first tutorial. Today we're talking about dummy variables. As you can see here, I've copied the top 5 rows of our data set and I've moved the profit column to the left. So basically the information that we have in our data is the profit of each company or of each startup, then the R&D spend, the admin spend, the marketing spend. So those 3 are expenses that the company incurred, and then the state in which it operates, either in New York or California. And as you recall, the challenge that we're faced with is that the venture capitalist fund wants to see if there's any correlations between profit and the amounts that have been spent on different expenses, R&D, admin, and marketing, and also in which state the company operates. So is there a correlation between profit and all of these variables, and how would you go about creating a model to understand how knowing R&D spend, admin, and marketing and state to predict profit? And so therefore, profit is our dependent variable, and the rest, the blue ones, are all independent variables. And what we need to do is build a linear regression. So let's go ahead and get started. As we would with a multiple linear regression, we would start by saying y, which is profit, is equal to what? What is it equal to? Well, first of all, there's a constant. In this case, it's b0, and I've put it under the profit column just because I needed to fit it somewhere. And then we would start adding on these variables into our equation. So then we've got the b1 coefficient times the x1 variable, which is R&D spend in this case. And x1 is actually the amount, the dollar amount that you see in the R&D column. Then you've got the admin variable, which is x2. It's got a coefficient of b2, once again admin. So in this case, x2 is going to be the dollar amount you see in the admin column. Then you've got the marketing spend, x3, which will be the dollar amount you see in the marketing column. And then you've got the state variable. And here, when we get here, we're questioning what should we place in our equation for the state column, because we don't actually have a number. We don't have a dollar value or any other type of number to add into our equation. We can't just add a word into our equation. And the thing here is that state is actually a categorical variable. So we talked about types of variables before, and we understood that there's categorical variables and there's numeric variables. Well, in this case, state is a categorical variable, and therefore we can't add it to our equation. We need to do something about this situation. And the approach that you need to take when you face categorical variables in regression models is you need to create dummy variables. Let's see how we can do that. First, you need to go through your column and find all the different categories you have. So in this case, we have 2 categories. In all of our data, there's only 2 categories, New York and California. And they are essentially categories. So basically, they're categorizing our data into 2 classes. One is companies in New York, another one is companies in California. In a very similar way, we could have had a different column. Instead of state, it could have been company size, for instance. It could have been small, medium, and large. And that would have classified our companies into 3 different classes, and so on. So you can have any type of categories. In this case, it's the state in which they operate. So for every single category that you found, you need to create a new column. For New York, we're going to create a column called New York, and for California, we're going to create a column California. So we're kind of expanding our data set and adding some additional columns into it. And how do we populate the columns? So this is the fun part. To populate these columns, let's start with the New York column. You need to find all of your rows where state actually says New York. And you need to, for those rows, you need to put a 1 in the New York column. And then in California, for all the rows that say California, basically for all the rows that don't say New York, whatever else they say, you just put a 0. And then for California, for the column California, you do the same thing. Wherever a row says California in the state column, you place a 1 in the California column. And for any other values in the state column, you place a 0 in the California column. And so you end up with a data set like this. And these 2 new columns are called dummy variables. And building your regression model from here is very simple. All you have to do is use the New York column, and you're going to be using it instead of state, so you're not going to be using state anymore. And basically you add a variable, which is b4 times d1. And d1 in this case is your dummy variable for New York. And you don't use the California column either. So as you can see here, all of the information in our data is preserved if we just stick to the one New York column. Because you can tell right away, if D1 is a 1, then it's a company that operates in New York. If D1 is a 0, it's a company that operates in California. So we didn't lose any information by including only the New York column. And we'll actually talk more about why you should never include all of your dummy variable columns in your regression model. We'll talk more about that in the next tutorial when we're talking about the dummy variable trap. But for now, I would like to discuss two things. So first of all, the New York column, or all of the dummy variables, they work as switches. In this case, let's look at the New York column, which we're including in our regression. It works like a light switch. So if it's a 1, then you know that this company is in New York. If it's a 0, so off in this case, in the case of the picture, then you know that the company doesn't work in New York. And so then you go, obviously it works in California because you only have two options. So the dummy variables work like light switches, and that's why they're 1s and 0s, and they don't need any other values in them. And the second thing is that when you look at this approach, it might seem biased. So we are including a variable for New York, and there's a coefficient for New York. So we basically have this benefit of having a coefficient in our equation for New York, which is B4. But for California, there's no coefficient because when D1 is 0, that whole last part of the equation becomes 0, and there's no benefit of a coefficient in our equation for California. And it might seem biased at first, but in reality, that's not the case, because the way regression models work is that they will take by default that state or that variable, that dummy variable that you have not included. It will become the default situation for this regression model. So basically what that means is that the coefficient for California is going to be included in the constant in B0. And by default, when D1 is equal to 0, this whole equation will turn into an equation. You can think of it as it will turn into an equation for California. But then when D1 becomes 1, you're adding B4, which is, once again, like this is a very basic explanation, but you're adding a coefficient which is the difference between New York and California. So basically you're altering from California to New York by flipping this light switch. If it's on off, then kind of default state, and the whole equation is working for California. If it's on, then by adding that B4, you're altering the equation from the default state of California to New York. So that's a intuitive way to think of dummy variables. So there's nothing wrong with the fact that we're only including one. And once again, in the next tutorial, we'll talk more about why it is a bad idea to ever include both dummy variables. I look forward to seeing you next time. Until then, happy analyzing. Dummy variable trap. Last time we learned how to create dummy variables to replace our categorical predictor state in the model. We also discussed that you can never include both dummy variables at the same time. In our example, we omitted the California dummy. Now, why is that? What will happen if we include the second dummy variable in the model as well? Let's see. The intuition here is that you're basically duplicating a variable. This is because D2 always equals to 1 minus D1. The phenomenon where one or several independent variables in a linear regression predict another is called multicollinearity. As a result of this effect, the model cannot distinguish between the effects of D1 from the effects of D2, and therefore it won't work properly. And this is called the dummy variable trap. If you do the math behind the scenario, you will see that the real problem is that you cannot have these three elements in your model at the same time, the constant and both the dummy variables. I will leave it up to you to figure this one out on your own, and let me know if you have any trouble. I'll definitely help you out. So to sum up, whenever you're building a model, always omit one dummy variable. And this applies irrespective of the number of dummy variables there are in that specific dummy set. If you have 9, then you should only include 8. If you have 100, then you should only include 99 of them. Also note that if you have two sets of dummy variables, then you need to apply the same rule to each set. For instance, we could have had a column which specifies the industry in which the companies operate. To build the model in that case, we would have had to perform exactly the same steps and create another set of dummy variables specifically for that column. And then we would include all but one of those dummy variables in our actual model. I hope this explanation was useful and you will never fall victim of the dummy variable trap in your modeling. Next time we're going to cover the different ways you can build a model. We will learn all about backward elimination, forward selection, stepwise regression, and much more. It's going to be an exciting tutorial and I look forward to seeing you then. Welcome back to your Ultimate Data Science course, and I'm super excited about today. I've got an incredible tutorial prepared for you. We're going to cover off a very important topic, and that is how to build models. Step by step. I couldn't hold myself. I had to add that extra line step by step to the name of the tutorial because that is exactly what we're going to be looking at. I'm going to give you a framework for several different methods, and it's all going to be step by step. So let's jump straight into it. Do you remember the good old days when we had one dependent variable and one independent variable? Everything was easy and we just had a simple linear regression that we had to build and everything worked great. But now, in our data, we have all these columns. Those easy days are gone. Now all of these columns are potential predictors for our dependent variable, and there's just so many of them. And we need to decide which ones we want to keep and which ones we want to throw out. And you'll ask, why do we need to throw out columns? Why do we need to get rid of data? Why can't we just use everything in our model? Well, I can think of two reasons off the top of my head. Number one is garbage in, garbage out. If you throw in a lot of stuff into your model, then your model will not be a good model. It won't be reliable, it won't be doing what it's supposed to be doing. It's going to be a, so to speak, garbage model. And number two, at the end of the day, you're going to have to explain these variables and understand not just the math behind them, but actually what it means that certain variables predict the behavior of your dependent variable. And you will have to explain that to your executives, to your boss, to people you're presenting to. So if you have 1,000 variables, it's not going to be practical to try and explain that. So you want to keep only the very important ones, the ones that actually predict something. So how do we construct a model? This is the process of building the model, selecting the right variables. So how do we construct a model? Well, there are 5 methods that we're going to discuss of building models. Number 1 is all-in. Number 2 is backward elimination. Number 3 is forward selection. Number 4 is bidirectional elimination. And number 5 is score comparison. We're going to talk about each one of them just now. Before we do, I wanted to say that sometimes you'll hear stepwise regression. So stepwise regression actually refers to number 2, 3, and 4. Because those are like really the true step-by-step methods. But sometimes you will hear people say stepwise regression in reference to just number 4. So they will replace bidirectional elimination with stepwise regression, and that's fine. That's normal. That's just because that's the more, as you'll see from what we discussed, bidirectional elimination is kind of the more general approach. And when people say stepwise regression, they kind of by default imply that it's bidirectional elimination, and you have to infer it from there. Okay, so let's move on to our methods. Method number 1, all-in. It's not a technical term, I just call it all-in. Basically what it means is just throw in all your variables, something we just discussed that we shouldn't do. When would you do that? One is if you have prior knowledge. If you know that these exact variables are your true predictors, you don't have to build anything. You already know that this is the case. You might know it from domain knowledge, or you might know it because you've done this model before, or somebody just gave you these variables and said, please build a model. Well, then you don't really have a choice. You just build the model. The other one is you have to. Perhaps, like, I can't really think of good examples here, but maybe there's some framework in your company that says that you have to use these variables, right? So it's kind of similar to prior knowledge, but it's not your decision. You might want to do it differently, but there is a framework, like maybe a bank, and to predict credit, like or the likelihood of somebody defaulting on something, they have to use these specific variables. Once again, I'm not sure in which industries that would be the case, but perhaps that could be the case. And number 3, you would use this method if you're preparing for a backward elimination type of construction of regression, which is our next type. So let's move on to backward elimination. Okay, so here comes the step-by-step stuff. You might want to get your pens out and write these things down, because we're going to have a truly step-by-step method now. All right, backward elimination. First thing, step 1. You have to select a significance level to stay in the model. So by default, we're going to go with 5%, so 0.05, and we're going to use it in the next step. So at the beginning, you decide on this significance level. Step 2, you fit the full model with all possible predictors. So you kind of do that all-in approach, which we just talked about, and you put all of your variables into your model. And now we're going to start getting rid of them. Step 3, you consider the predictor with the highest p-value. So remember those p-values that we talked about in, for instance, in Gradle or in any software, you can see them. So after you fitted the model, you'll see the one with the highest p-value. So if p is greater than your significance level, then you go to step 4. And step 4 is you have to remove that predictor. So you remove basically the variable that has the highest p-value. And from step 4, you fit the model without this variable. So there's a star here because I just wanted to remind myself to tell you that if you just remove the variable, obviously you can't just say that, okay, now I've got the new model. You have to actually refit the model. You have to recreate the model, rebuild it with the fewer number of variables. So if you had maybe, I don't know, 100 variables and you removed them, one of them, you have 99 now, well, you have to rebuild it. So the coefficients are going to be different, the constant is going to be different, and you need to perform that step, because once you remove a variable, it affects all the other variables in your whole regression. And so after step 5, you go back to step 3. Once again, you look for the variable with the highest p-value in your new model, you take it out, you remove, so basically step 4, you remove it, you fit the model again with one less variable, and so on. You keep doing that until you come to a point where though even the variable with the highest p-value, that p-value is still less than your significance level. So if that condition p is greater than SL is not correct, then you don't go to step 4 anymore, you go to fin. In this case, fin is the finish. Your model is ready. So as soon as all of the variables that you have left in your model are, their p-values are less than the significance level, your model's prepared. So that's how the backward elimination method works. Let's move on to the next one. Next method is the forward selection. It sounds like the opposite, and the picture in the top right corner does illustrate the opposite, but it's much more complex than just simply reversing the procedure. You will see that it's a much larger procedure. We start with step 1. Select a significance level to enter the model. And in this case, once again, we're going to select 5%. Then we go to step 2. We fit all possible simple regression models. So we take the dependent variable and we create a regression model with every single independent variable that we have. And then we select, out of all of those models, we select the one which has the lowest p-value for the independent variable. So you can already see that that is in itself a lot of work. Then what we do is we move to step 3. We keep this variable that we've just chosen, and we fit all other possible models with one extra predictor added to the one you already have. So what does that mean? That means we've selected a simple linear regression with one variable. Now we need to construct all possible linear regressions with 2 variables, where one of those 2 variables is the one we've already selected. So basically we add on all of the other variables one by one. So we choose, okay, let's add on this variable, and then let's add on the next one, but separately. So we construct all possible 2 variable linear regressions, and just definitely keeping the variable that we've already selected. So what do we do after that? Out of all of these possible two variable regressions, we consider the one where the new variable that we added had the lowest p-value. So if that p-value is less than our significance level, meaning that that variable is a good one, it's a significant variable, then we move back to step 3. What does that mean? It means that now we have a regression with 2 variables, and now we will add a third variable, and we'll try all possible variables that we have left as our third variable. And then out of all of those models with 3 variables, we will go to step 4 and we'll select again the one with the lowest p-value for that third variable that we added. And we'll keep doing that. So basically we'll keep growing the regression model, but not just randomly. We'll be actually selecting out of the all of the possible combinations every single time and growing it with one variable at a time. And then we will only stop when the variable that we've added, it has a p-value that is greater than our significance level. So when this condition p is less than SL is not true, then we don't go to step 3, we finish the regression. Why? Well, because that variable that we just added is no longer, is not significant anymore. And we also know that we selected the one with the lowest p-value. So there's no other variable that we can add that its p-value will be greater, or will be less than SL. Any regression that we choose from then onwards, it will, the new variable will always be insignificant. And so here we finish the regression. And the trick here is that you keep not the current model, but the previous one. And that makes sense because you've just added a variable which is insignificant. So what's the point of that variable? Just move a step back. So that's how forward selection works. I know it's a bit confusing, but just try to wrap your head around it. Maybe read through these instructions one more time. It does make a lot of sense when you kind of picture what exactly is going on. And next, we're moving on to the bidirectional elimination. So this one, as you can assume or perhaps guess, it combines the two. Step 1, select a significance level to enter and a significance level to stay. So we're going to select in both cases 5%, but it's up to you what you select. Step 2, perform the next step of the forward selection, meaning that the one that we just discussed, so where new variables, when they enter, in order to enter, they have to be less than the significance level to enter. So basically add on a new variable based on the forward selection method. Step 3, perform all of the steps of the backward elimination process. So now, if you have 2 variables, start getting rid of them and see if you can get rid of any of them. And then move back to step 2. So then grow it by another variable. And every time you grow it by a variable, say let's say you were at 5 variables and you went to 6. As soon as you went to 6, you have to perform all of the steps of backward elimination. So you don't just eliminate one variable if you can. You eliminate 1, 2, 3, however many you can. And then from there, you go back to step 2. And so this is a very iterative process. You keep doing that until at some point you cannot add new variables, no variables can enter, or no old variables can exit. And as soon as you get there, then you proceed to the finish because your model is ready. You can't add anything, you can't take anything out. That means you've created the model. So this is one of the more tedious methods. Of course, you would have to get a computer to do this for you because otherwise you'd go insane putting variables in and taking them out. But that's how bidirectional elimination works. Once again, some people call it stepwise regression. And finally, all possible models. So this is the most probably thorough approach, but also the most resource consuming approach, because you select a criterion of goodness of fit. For instance, the Kaiki criterion can be the R squared, lots of different criterions. Then you construct all possible regression models. So if you had n variables, then there'll be a 2 to the power of n minus 1 total combinations of these variables, and that's exactly how many models there can possibly be. And then step 3, you select the one of these models with the best criterion that you're looking at. There you go, your model is ready. So sounds easy, but let's have a look at an example. Even if you have 10 columns in your data, you'll have 1023 models. That's insane. That's an insane amount of models. And we're not talking about columns that you've already filtered out. So columns that you know, that's like in our example, you might have 5 or 6 columns. No, we're talking about when you get a data set that you just is pretty much raw, and it has like maybe 100 columns. Like I've worked with data sets with around that, maybe 50 to 100, maybe more columns. And instead of going through them, this what this method is suggesting, instead of going through them and picking out the ones that you think should be in your model, you just throw everything in. Well, it's not a good approach, because basically it's growing exponentially. The number of models is growing exponentially, and it's very resource consuming to get a result from this approach. And finally, so where have we come to? We've come to our conclusion. We have 5 methods of building models. All in: backward elimination, forward selection, bidirectional elimination, and score comparison. So the one we're going to be looking at in these tutorials, in order to get our head around how to build models step by step and get some practice, is the backward elimination process, because it is the fastest one out of all of them. And you will still get to see exactly how the step-by-step method works. And plus, we'll throw in a few extra tricks along the way to make sure our models are very robust. Can't wait to get started. Lots of theory. Let's get to the practice. I look forward to seeing you next time. All right, exciting tutorial ahead. Today, we're going to build our very first multiple linear regression, and we're going to be using the backward elimination method. I hope you're pumped about this. Let's get straight into it. Open up Gradle and let's connect to our data. File, open data. Mine is on my desktop. Modeling section, multiple linear regression. So it's a CSV file. There it is. That's fine. We don't need to do that. And the first thing you can see here is that Gradle has identified that we have a categorical variable. It says variable 4, which is called state, is a string. So it is warning us that we're going to have to deal with this. And there's 2 categories, New York and California. So very, very convenient. Now we know that there's 2 categories. So let's go ahead and deal with these dummy variables right away. As we discussed previously, because we have a categorical variable, we can't just include it in our multiple linear regression formula equation, because that way it's not a number. So we need to replace it with some dummy variables, as we discussed before, and that's exactly what we're going to do here. It's very simple to do in Gradle. All you have to do is select your variable, go to add, and down here it actually has an option, dummies for discrete variable. Click that, and here make sure you're encoding the right variable. And here you have 3 options: encode all values, or you can skip the lowest value or the highest value. And Gradle is smart like that. It knows that you won't be able to use all of your dummy variables in your models anyway. You're going to have to omit one of your dummy variables. And we discussed that also in this course just previously when we were talking about the dummy variable trap. Because you can't, if you include all of them, then your model won't work. So it's right away, it's offering you to skip one of them. But as we agreed, we're going to encode all, and then we'll select the one we want to use ourselves, because that gives us a bit more flexibility. So we'll just click OK here. And if you expand state now, you will see that there's 2 dummy variables, dstate_1 and dstate_2. And one is for New York and one's for California. We don't want to remember the names and which one is for what, so we'll just quickly modify the names. Right-click your variable, click Edit Attributes, and here take New York and put it in the name of the variable. So we'll just call the variable New York. You can't have spaces, so get rid of the space. Click this check mark here, and then proceed to the next variable by clicking the down arrow. Take California, and same thing. Okay, so now we have 2 dummy variables, New York and California, and they're ready. Great, we're ready to proceed with our modeling part. So I've put a picture over here of our previous slide. By the way, I didn't mention this, but I am intending on attaching the slides as a downloadable file to the previous lecture. So go ahead and download that in the course materials, and you can keep this file for yourself and refer to it whenever you need to. So this is our building a model backward elimination method. Our first step is to select the significance level for variables to stay in the model. In our example, we're going to use 0.05. So I'm going to say it out loud. I am selecting the significance level to be 5% or 0.05. Good. Step 1 done. Next, fit the full model with all possible predictors. Let's go ahead and do that. So, model, ordinary least squares, and here we're going to take profit and we're going to move it into our dependent variable. And because we're going to be doing this process quite a few times, it's going to be an iterative approach. We're going to click this box here, set as default. So every time we come back to this menu, profit is already the dependent variable. And now let's go ahead and move our independent variables into the regressors box. We'll start off one by one here. R&D spend, so spend on research and development. Yes, that's one of them. Administration expenses, yes. Marketing spend, yes. State, no, because we've agreed that we will replace state with dummy variables. Profit is our dependent variable, and now we have two dummy variables. We can only include one in order to avoid the dummy variable trap, and we're going to include the New York. Well, I'm going to include the New York one. You can feel free to include whichever one you like. So there we go. Our regressors are ready, and all we have to do is click OK. Voila! Congratulations! This is your first multiple linear regression model. And as you can see here, you have the 4 variables present plus the constant. You are modeling a dependent variable profit. And let's have a look at this. And now we know how to read these. Let's extract some information from here. So these are our coefficients, and we'll talk about interpreting coefficients in the next tutorial. So we'll leave that for now. We're not going to focus on the standard error or t-ratio. What we're interested in is in the p-value, right? So we've got the p-values for all of our 4 variables. And here you can see some stars, meaning that it's a good p-value. It's a significant variable because it is so small. It is 7 times 10 to the power of minus 22, a tiny value. These values are quite large, actually. So 0.65, 0.12, 0.62. So that's why they don't have stars. You get, I think the way it works is you get 3 stars if you're less than 0.01, 2 stars if you're less than 0.05, and 1 star if you're less than 0.01, so 10%. So that's how this rating system goes. Anyway, let's go back to our backward elimination step-by-step method. So we've run the full model with all possible predictors. How about we do the next step now? Step 3, consider the predictor with the highest p-value, right? So let's go ahead and look at him. Predictor with the highest p-value is this guy, administration. He's got the highest p-value. Good, we've picked him out. Next, if the p-value is greater than the significance level, go to step 4. Let's check that. P-value is greater than 0.05, definitely greater. So we're going to step 4. In step 4, remove this predictor and fit the model without this variable, and then move back to step 3. Okay, that's interesting. Let's go ahead and do that. So basically what that's telling us is run a new model but without this variable. We're going to do exactly that. We won't touch this window, we'll leave it open, and we'll go back to Gretel. And here we're going to go model, ordinary least squares, and now we're going to take administration out of our model. So we'll just remove it like that, and we'll click OK. So now if we go back here and put it side by side, you will see what happened. Now we have 1 variable less. So here administration is present. Here administration is no longer present. And also you can see that some things have changed. So for instance, the constant has changed, the coefficients have changed, the p-values have changed. Basically everything has changed. And even a star has appeared for marketing spend. So before it was so large, so it was 0.12, it was greater than 10%. Now it's less than 10%, so it's got a star. So it became more significant without the administration variable present, and that happens. That's normal. That's there's lots of factors that influence that, and excluding or including variables will always affect your existing variables, and that's one of the reasons why you can't just exclude administration and assume that everything else stays the same. That's exactly why we have to rerun the model. And so we're ready to proceed to the next step. But before we do, I wanted to show you one quick thing, a good exercise to do. And this is not part of our step-by-step method, And this is also not the awesome tip or hint that we're going to look at to make the model robust. This is just something for us to understand what happened here. A way to understand is always a good way to understand is always to visualize things. So let's go ahead and visualize this variable, or visualize the profit against this variable if we hold the other variables constant. It's very simple to do. Just go to graphs, fitted actual plot, and here select against administration. And what that'll do is it'll plot profit against the administration variable, assuming that all other variables are held constant. And so the blue values are fitted, the red values are actual. So ignore the blue values for now. What we're looking at is that, is there any kind of relationship, any kind of obvious relationship that we can see between profit and administration? So is there like we used to see, like a line that we can draw that goes through the variables or the values, and it's quite close? To me personally, it looks like there is no relationship, and like it's all scattered all over the place. And what that means is that even if you change administration spend, so how much money you're investing into your administration or how much that expense is, if you increase it or decrease it, you can't really affect profit. So by changing this independent variable, the dependent variable is not affected. And that is exactly why we chose to exclude administration from our model, because it is not a predictor of profit. You take two companies that are identical, but they spend different amounts on administration, you can't really tell which one will have a higher profit, or you can't even, according to our model, make a prediction. So we're going to close this window now. That should kind of explain a little bit better, more intuitively, what this means that we're excluding a variable from our modeling. Now we're going to move on to this part. We're going to proceed with the next step of our backward elimination process. So I'm going to bring up the rules again, and here we can see that we've just fit the model without the new variable, and now we're going to do this part again. So consider the predictor with the highest p-value, check if p-value is greater than your significance level, and if it is, go to step 4. Let's go ahead and check that. So we'll find the variable with the highest p-value, which is this one, New York. So our dummy variable has the highest p-value, 0.57, very high p-value, definitely greater than our significance level, which is 0.05, and therefore we need to exclude this variable from our model as well. Let's go ahead and do that. Model, ordinary least squares, take New York and take it out. Click OK. And let's move this window over here. All right, so what have we got so far? We've got two variables. Once again, coefficients changed, the constant changed, p-values changed. As you can see, this p-value got even smaller. It's now 0.06. It can really go both ways. You never know until you actually run the model. But now we've got a new picture. We've got two variables, and we're ready for the next step. Once again, you can quickly check the graph if you like. Go to fitted actual plot, and here we want to check against New York. So look at the reds again. Basically, because it is a categorical variable, or this is a dummy variable now. So 0, 1, remember we're talking about the on-off switch. So are you in New York? Yes. Are you not in New York? Where else can you be but California? So you're in California. So, but basically what this is saying is being or not being in New York doesn't really make a difference. The way, if there was a difference, you'd see like a lot of red here and a lot of red here, meaning that if you're in New York, your profit is much higher than if you're not in New York. But here it's kind of evenly distributed across across the whole line here and across the whole line here. So no wonder we were suggested to exclude that variable from our regression. It doesn't really predict anything. It's not that much of a predictor. So that's why we took it out. All right. So now we're doing the next step again. We don't need to go back to rules because by now we should remember them. Look for the highest p-value. It's this one. And check if it's greater or less than our significance level. So 0.06 is quite close to 0.05, but it's still greater than 0.05. So what does that mean? We need to exclude this variable. Let's go ahead and do that. This is our Gretel software, and now we're going to go order least squares. Once again, which one is it? Marketing spend. So we're going to take it out and we'll click OK. And now we'll move it over here. Okay. Let's have a look at what we have now. So now we have only one variable left. It's very significant, lots of stars. It's definitely less than 0.05. So what does our method tell us? Let's go back to our method. Here, our method would say that we've only got, we get to this part. This is not true, as you remember. That means we don't go to step 4, we go to fin. Your model is ready. Good. So theoretically, according to this approach, this is our model done. It only actually has one variable. We went from 4 variables down to 1. And it's very, very significant. So what I wanted to show you here is, let's do the same thing we did with the previous ones, and let's look at the chart and let's see what actually went on here. Is marketing spend really that not much of a predictor? Let's go to graphs, fitted versus actual, and we'll go against marketing spend. And what you can see here is, even though they're kind of scattered, right? The observations, we're looking at the red ones, and there are some outliers, but in reality, personally, I think I could draw a line for this. I could go like that. Yeah, it does look like there is a good level of correlation here. And that is what we saw here, that marketing spend, it's there's 1 star, basically, that it's not a huge p-value like we had with administration or with New York. It's quite a small p-value, but still it's not sufficient enough for our significance level. And this is the problem with these stepwise regression building methods, that they're very arbitrary. Once we said our significance level is 0.05, we stick to that and we just follow this cold-blooded rule that if it's greater than 0.05, we have to exclude it from our model, and there's nothing you can do about it. So that's the rule, and that's how it works. But in reality, when you look at something like this, you think maybe there is a chance that just maybe I should have kept it in. Maybe my model would have worked better with it. And how do you tell? And this is where I'll show you the handy trick that will help you make your models more robust. And we'll talk about it in the next tutorial. Great to see you back here. And today we're going to look at the handy trick that will help your models become more robust. Before we continue though, I wanted to quickly recap on what we did last time. And what we did is we used the backward elimination method to construct a multiple linear regression using our data. And through that method, we constructed 4 separate models. You can see them on in the background here. So model 1, 2, 3, and then 4. And when we got to model 4, we were only left with 1 independent variable spent on research and development, because all of the other ones were eliminated. And basically we completed the backward elimination process. However, we were left with kind of a feeling that maybe we shouldn't have excluded the last variable. And why is that? Well, first of all, we saw that this p-value is not that much bigger than the significance level that we selected. We selected a significance level of 0.05. The p-value here is 0.06, so just a bit greater than the threshold. And also when we looked at the chart, so the plot of the profit by marketing spend, we could see that even visually there is kind of a correlation here. So if you just look at the red dots and ignore the blue ones, you can see that there is kind of like a linear looking correlation here in that direction. So that kind of leaves us with a feeling maybe we shouldn't have excluded that variable. The problem here is that these methods, these stepwise regression methods, they are very arbitrary. So once you select your significance level threshold, you got to stick to it, right? We selected 0.05, this one's 0.06, so that's greater, and we just got to cut it off and not look back anymore and just proceed with the method. So how can we improve our method of building models to assess situations like that and give, like an extra opinion, or have another criteria to tell us whether or not we should have actually kept this variable? And there is a way, and we're going to talk about it right now. So let's look at this top part over here. The top part is responsible for the variables. So you have the coefficients and you've got the p-values and so on. So we've talked about it quite extensively. But now let's look at the bottom part, the second part of our report. And here, as we discussed before, we've got the stats that are for the model as a whole. So how well it's been fitted, how well it's working, and so on. So the stats that we'll be looking at today are R squared and adjusted R squared. And they will help us come up with a cool approach, or great approach, to improve our backward elimination method. So we already talked about both the R squared and adjusted R squared in the stats refresher section of this course. However, if you chose to skip that section because you're not interested in the formulas and so on, then I'll quickly recap for you now. So R squared over here is basically a characteristic or a parameter of your model which tells you about the goodness of fit, so how well your model has been fitted. And R squared can never be greater than 1, and you want it to be as close to 1 as possible. The closer to 1 it is, the better your model is deemed to be fitted. However, we also discussed this part in the stats refresher. R squared is biased, and it's biased in a way that the way it's constructed and the way these models are run, so the ordinary least squared method, it doesn't allow R squared to ever decrease. So the more variables you add to your model, the greater R squared will be. So basically what this means is that as long as you keep adding variables, R squared will always grow. And we can observe that here. So if we start from the end where we have only one variable, you can see that R squared is 0.94. Then R squared became, well, if we go this way, it's 0.95. 0.9504, then it's 0.9507, then it's 0.9510. So as you can see, the more variables we have, the greater R squared gets. And that's always going to be the case just because of the way R squared is derived. And moreover, you can even include completely random variables. So if I throw into this model, I throw another variable, which is basically the temperature outside, like air temperature outside right now, then and I throw that in as an independent variable. Of course, it's not a predictor. It can't predict profit of a company that works in New York or California, but R squared is still going to grow and is going to imply that our model is now even better fitted. So that way R squared is biased. And that's where adjusted R squared comes into play. Adjusted R squared is very similar to R squared. It's got a very similar formula, but it actually has a penalization factor. So basically, just like R squared would grow if you add more variables, adjusted R squared would also grow, but there's a penalization factor which makes it smaller, which reduces adjusted R squared as you add more variables. So there's kind of these two effects battling each other. On one hand, it's growing because of the way it's constructed. On the other hand, the penalization factor is penalizing you or penalizing the adjusted R squared and reducing it every time you add a variable. So basically, if the variable that you added doesn't make R squared grow that much, like for instance here you can see 0.9504 to 0.9507, so it only grew by a fraction, very, very small amount. Well, if that happens, then the penalization factor is going to overwhelm this growth, and therefore the adjusted R squared is actually going to decrease in that scenario. And that way we can use, and we will use, the adjusted R squared to watch the goodness of fit of our models and how it changes. So let's go ahead and do that. Let's observe the adjusted R squared in our method. What was the adjusted R squared here? It was 0.9466. Then once we excluded administration expenses, adjusted R squared went from 0.9466 to 0.9475. So as you can see here, adjusted R squared went up. We reduced, basically what that means is that the model is now better. It's fitted better. It works. These variables in this combination fit the profit variable, fit this model to explain the profit variable better than these variables in this combination to explain the profit variable, which is good. It's a good step. Okay, so that means we improved our model. Here, adjusted R squared is 0.9475. Let's see what had happened to it when we move to the next step. In the next step, adjusted R squared is 0.9483. So it went up again, meaning that once again we improved our model. So altogether, these variables are doing a better job explaining profit, then these variables together are doing a job explaining profit. That's great. We improved our model again. And now let's see what happens when we take out the last variable, marketing spend. So we went from adjusted R squared 0.9483 to adjusted R squared 0.9454. And what does that tell us? Adjusted R squared went down. It went down by 0.003 approximately. So that means that this model, this new model, is actually worse than this model. So this model was better fitted to predict or explain the variance in profit than this model is doing so. So there you go. So even though we excluded a variable according to our backward elimination method, this variable shouldn't have been excluded because it was improved. It was with this variable, this model is actually working better. And that is your takeaway handy trick how to observe your models and how to create them. You don't only just follow the backward elimination or whatever method that you're using and arbitrarily follow the rules. Just instead follow the rules, but also watch the adjusted R squared and see if it's actually improving. So if it's growing, then you're doing the right thing. As soon as you see the adjusted R squared drop, then you have to stop and question, did I just do the right thing or not? And what is the trade-off of excluding a certain variable or the opposite of including the certain variable? So adjusted R squared is kind of your indicator how you're going along the way. And that's it for today. I just wanted to say that adjusted R squared is not the only model parameter. As you can see, there's quite a lot of them here. And I've already mentioned the Kaike criterion. A Kaike criterion is this one over here, and it also works in a similar way, but it's got a different calculation. We won't go into detail, but if you want to, you can look these things up a bit more and understand which one suits which of these criterions or parameters works better in your case. For instance, a Kaike criterion, you got to find is better when it's lower. So here you can see it's big, then becomes smaller, and then goes up again. So the Kaike criterion also confirms that this model is doing a better job. So if you like, have a look at the other criterions, Schwarz criterion, for instance, and see how you can maybe apply them as well. But that's it for today. Hope you find this useful and hope you'll find ways to apply this in your actual work. I look forward to seeing you next time, and until then, happy analyzing. And finally, interpreting coefficients. In front of us here, we've got the 4 models that we built in our backward elimination method. And as we agreed, model number 3 is the best one. It's the best fitted model. And if we were to deliver a model on our project, it would be this one. So let's go ahead and start interpreting coefficients by looking at this model. Here we've got 2 variables, R&D spend and marketing spend. So it's basically how much companies are spending on their research and development and on their marketing. And we've also got the constant, and we're predicting profit. So these coefficients here, these are B1 and B2, what they're telling us is that, so how to interpret them. First of all, you look at the sign. If the sign is positive, that means your variable is correlated with your independent variable is correlated with your dependent variable, meaning that if you change the value of your independent variable, then you can see that the dependent variable will be changing in the same direction. So basically, if you'll be increasing spend on R&D, then your profit will be increasing. If you're increasing spend on marketing, then your profit is also increasing, which makes sense, right? So if you're spending more on research and development, making your product better, then probably your profit should increase eventually as well. Same thing with marketing. The more you spend on marketing, the more you sell, and therefore the profit should also go up. And that's the sign. If the sign is negative, if the sign were negative, we'll look at an example a bit later, then it's the opposite effect. So basically you increase your independent variable and your dependent variable decreases. And now let's look at the magnitude. So here you can see right away that the magnitude is higher for R&D spend, and the magnitude is lower for marketing spend. Magnitude is always tricky with regressions. Be careful with magnitude. Sign is kind of, pretty obvious. It's one way or the other. Magnitude can really trip you up. And I can give you an example here. So you might think that, okay, right away, magnitude is greatest. So this coefficient for R&D spend is bigger than the marketing spend coefficient. So definitely R&D spend has a bigger impact. Well, what if I tell you that I could easily, without changing anything in the regression, I could easily make this coefficient bigger by a lot, by 1,000 times bigger than R&D spend? Well, it's easy to do. All I have to do is say marketing spend, instead of looking at it in dollars, how about I look at it in a fraction of a cent? So every marketing spend, or let's look at it in cents. So marketing spend, instead of counting it in dollars, let's count it in cents. Right away, because our variable has gone down 100 times, our coefficient will proportionally increase. So it'll go up 100 times. And if I change my data and replace everywhere marketing spend with cents, and everything else I will leave the same, then I rerun this model, I guarantee you that the coefficient here will actually become 2.99079. So it'll just increase 100 times. Everything else will stay the same. And that way, right away, you'll see, oh, wow, the marketing spend coefficient is greater. So then marketing spend has a bigger impact on your dependent variable profit. And that's a mistake that a lot of beginners make. You should not fall into this trap. Magnitude is a tricky thing. And the way to think about it is always say magnitude in terms of units of the independent variable. So the correct way to analyze this is, even without knowing what they're measured in, maybe this one's measured in thousands of dollars and this one's measured in dollars. I don't know, for instance, although I do know, of course, I've seen the data. But if, say, I don't know, you can still make a conclusion. All you have to say is R&D spend has a greater impact on profit per unit of R&D spend than marketing spend has per unit of marketing spend. And that's all. So basically, even if they're measured in different things, by saying per unit of the underlying variable, you are protecting yourself from that error that they are measured in different things. And moreover, imagine if they're measured, one's measured in dollars, the other one's measured in kilometers or something like that. You can't compare dollars and kilometers, right? But you can always say per unit. And this leads us to the actual interpretation of these variables or these coefficients. What does it mean? So this means 0.79 means that for every unit, if you keep all other variables constant, so you only have one other variable. So if you keep everything else constant, but you are able to adjust R&D spend for in this model, or for a hypothetical company, for every dollar or for every unit of R&D spend that you increase, your profit will increase, according to this model, your profit will increase by 79 cents. That's exactly what this coefficient is saying. And so for every unit that you decrease in your R&D spend, your profit will decrease by 0.79 of a unit of profit. And because R&D spend is measured in dollars and profit is also measured in dollar, that means so for every unit increase in for every dollar increase in R&D spend, your profit will increase by 79 cents. So let me just repeat that again. That you are looking at units increase in R&D spend, they translate through this coefficient into units increase in profit. So if your profit was measured in apples, then a $1 increase, a 1 unit increase, this is always going to be true. 1 unit increase in R&D spend will drive a 0.79 unit increase in profit, and of course of the profit units. So let's turn that into dollars and apples. A $1 increase in R&D spend will drive a 0.79 or 80% of an apple increase in profits. So here you're talking about units of R&D spend. In profit, you're talking about units of profit. And this coefficient, it links them together. So as long as you say per unit, you're fine. Once you already know what these variables are measured in, then you can start comparing them if they're on the same scale. And in this case, they are on the same scale because everything's measured in dollars here. And you can say that a dollar increase in R&D spend drives 79 cents 79 cents increase in profit. A dollar increase in marketing spend drives only 3 cents increase in profit. So basically, if you're the venture capitalist, which companies you're going to invest in? Well, from this model, you're going to decide that you should invest into companies that are spending more on their R&D. There may be lots of reasons behind this, and this is not just a random fact. This could be true in reality because profit is revenue minus expenses. Maybe marketing does drive a lot of revenue to your company, but at the same time, maybe for these specific companies that we're looking at, their expense, the cost of marketing, so the prices that they pay for marketing is so high that the increase in profit, the net increase in profit is actually marginal. So the marketing is eating up a lot of the revenue that it's creating, whereas R&D is is creating a lot of revenue, and a lot of it is actually staying in profit, something like that. But we're not worried about that right now. That's more financials. What we're doing is we're delivering a model. All right, so that's how you interpret coefficients with the same sign and on the same scale. Once again, if they're on different scales, just say per unit. And now let's move on to one of our previous models. Let's look at this one over here, for example. And we'll kind of ignore for now that they are insignificant. So we'll say, okay, we're not looking at that right now. We just want to practice with the coefficients. Let's say, for instance, that they're all significant. What would have this said to us? Well, R&D spend, here you can see we already know that these are all dollars. This one is a dummy variable, so we'll get to that in a second. So R&D spend, what happens here? You know that per dollar you increase in R&D spend, your profit will increase by 80 cents. Great. Then marketing spend, per dollar that you increase in marketing, your profit will increase by 2.6 cents. Great. Then with administration, what happens here? Well, you can see that it's negative. And assuming, once again, that this is a significant variable, independent variable in this model, then what this is saying is that for every dollar increase in administration expense that you incur, your profit is decreasing by 2 cents. So the more you spend on administration, the lower your profit will be. And that's an important thing to understand. Once again, this is not a significant variable, so it's not the case in this example. So it doesn't really matter what it's saying here. It could say 1,000,000. It's not significant, so we're throwing it out of the model anyway. But if it were significant, then that's a thing to think about. So if you're running a company and you know that the more you spend on administration, the lower your profit, then maybe you should stop spending on administration, or maybe you should reshuffle your funds or something like that. So it's very insightful actually to know these things. And in terms of New York, what is this saying? Well, this comes back to the point that which we were talking about, that our models are not actually biased towards one category or the other. As you can see, we don't have California here. So what this is saying is that by default, if New York is 0, then the equation is deemed as if it's for California. And then if you're in New York, if your company is in New York, what happens is this is a 1, and that means that this profit goes down by 1,332 units. If you keep everything else constant and you compare a situation in California and New York, then, so basically two companies, everything's the same except for one is in California, one's in New York, then the one in New York will have profit which is less by 1,332 units, 0.09 of profit. Because profit is measured in dollars, that means the profit will be lower by $1,332 just because that same company is in New York. But once again, this isn't a statistically significant variable, so it doesn't matter what it says here. It doesn't matter what the sign is. It's not part of our model because that's our final model. So this is just an example. But once again, it would be insightful. So if that was a statistically significant variable, then maybe the venture capitalist is interested in that, and that can drive their decision in which region they want to invest, whether it's California or New York. So that's how you interpret coefficients. With a linear regression, it's very simple. Just remember about that per unit trick or tip, I guess, because if you forget about that, you can make the wrong conclusions. Otherwise, it's all pretty simple. The last thing that I wanted to mention here is that you can see that every time we run a model, the coefficients change. So what that is telling us is that coefficients actually only talk about the additional effect of every single variable, given that the other variables are already in place. So for instance, in this example, your coefficient of marketing, which is 0.029, means that given that R&D spend is already in your model and it's fixed, then marketing spend adds additional, contributes this additional effect of 0.029979, meaning that if you were to run a different model and take out R&D spend, then the coefficient would be completely different. And that's what we see here, that when we take out marketing, the coefficient for R&D spend is taken out. So that's another thing you should remember about, that coefficients merely portray the additional effect that every single variable brings into the model. Hope you enjoyed this tutorial, and I look forward to seeing you next time. Until then, happy analyzing. Alright, section recap. In this section we learned, number 1, how to create dummies for categorical independent variables. We went through the whole process of how you look at the categories, you create new columns, you populate them with ones and zeros, and then you use the categories instead of the actual categorical variable in your modeling. Number 2 was how to avoid the dummy variable trap. Remember that you can't, for any set of dummy variables, for one given categorical variable, you can't use all of these dummy variables. You have to always omit one. Otherwise, your model won't work and you'll fall into the dummy variable trap. We don't want that to happen. So just remember that always use n-1 dummy variables for any given set of dummy variables. Number 3, we learned the backward, the forward, the bidirectional, and the all possible methods of creating models. The all possible method here is the one where you create all of the models and then you just compare them and you find the best one. So we actually went through step-by-step blueprints for every single one of these methods, and hopefully you can take them away, and whenever you need to reference them, you will know exactly where to find them, or you will already know how to perform these methods. Number 4, we actually built a model step by step, and you can see that I'm very proud of that. I put 2 exclamation marks. Step by step, we actually manually built a model using the backward elimination method, and we learned a lot along the way. We had variables that dropped out, variables that changed their significance, variables that we didn't want to drop out. We looked at charts. It was personally, I really enjoyed it, and I enjoyed explaining it to you. I hope you learned a lot from that part of the course. Next, we learned how to use the adjusted R-squared in modeling. So we actually learned how to not only bluntly follow our significance level threshold, but also apply a criteria, in this case the R-squared metric, to understand if we're on the right track through our modeling, and that helps create more robust models and not just blindly exclude or include variables just because the rules say so. And finally, point number 6, we learned how to interpret coefficients of a multiple linear regression model. Once again, there was a tip there that use per units of variable, per units of independent variable, per units of dependent variable, and that will keep you out of trouble, because that way you don't have to make sure that the variables are on the same scale. If you start talking about dollars, kilometers, or actual absolute values, then you have to make sure that you're on the same scale. And one last point there is that this interpretation method works for multiple linear regression. Later on in the course, we'll be talking about logistic regression. Interpretation there is different. So just keep that in mind. Hope you enjoyed this section, and I really look forward to seeing you in the next section of the course. Until then, happy analyzing.
Welcome to this section on logistic regression. Slowly but surely, we're venturing into the more advanced topics of modeling. Now that we're comfortable with multiple linear regression, we can take the next step and talk about logistic regression. And in this section, you will find out what exactly you need to do when your business problem has a yes-no outcome. For instance, will a person purchase your product? Yes or no? Should a person get a credit loan? Yes or no? And therefore, you're modeling a binary outcome rather than a numeric outcome, like a continuous outcome, like we were modeling previously when we were talking about profit, for instance. Here you're modeling a binary outcome. You still have a lot of independent variables, but you want to see how they affect this yes-no answer. And in that case, you need to use a logistic regression. we'll be talking about the logistic regression from an intuitive level. It'll be a challenging tutorial because it is a complex tool, but understanding it from an intuitive level will give you so much more insight into what exactly is going on in the background when your software package is running a logistic regression. We will actually run our very first logistic regression, which is going to be very exciting in this section of the course. We will talk about false positives and false negatives. We'll talk about the confusion matrix. And finally, we will find out the do's and don'ts about the coefficients of a logistic regression, because the rules there are a bit different to multiple linear regression. Can't wait to get started with this section. I look forward to seeing you on the first tutorial.
Let's go get the dataset for our logistic regression. Once again, same URL, part 2 modeling, and then section 4 logistic regression email offer. And once you've downloaded the file, put it in your folder. Here I've got logistic regression, email offer. So we can open this one in CSV or in a text editor. What you can see here is 3 columns, very simple data set, 100 rows. And this is a sample of people that your company recently contacted. So the company that hired you as a data scientist to analyze this project, what they do is they send out email offers to customers with like a proposal to buy certain products. It might be a clothing store, it might be a grocery store or something like that. So what they do is basically they send out a offer in email to a lot of customers to purchase certain product. And here you've got a sample of those customers that they contacted recently. You've got their age and their gender, and also you have a variable whether or not they took action. And so took action can be measured differently. For instance, for a company, it might be whether or not they clicked the link, whether or not they opened a certain page, whether or not they actually purchased the product, whether or not then they printed out this coupon and that they got and came into store and used that coupon. So it can be measured in different ways, but the main point here is that the action either happened or not, and that's a binary outcome. And we'll be talking a lot about binary outcomes in this section. And here you can see that this person, for instance, totally anonymized database, data set, and here you can see that this person, she did not take any action, this person didn't, this person did. And so your goal is to report back to the company and say which of their segment of their customers is more likely to respond to this offer. So first of all, they'll be looking at things like, is this offer more interesting to females or males? And also, is this offer more interesting to people that are older or people that are younger? And all of that you can derive from here, and we'll be using a logistic regression to do that. So as you can see, that's quite a powerful technique to know already. And even if you're not dealing with customers in your company, you'll still be able to use this and apply this to look for any kind of correlations between independent variables like these two, age and gender, and dependent variables. I'll give you another example. Let's say you're working at a factory, or you're a data scientist hired to do some analysis for a factory, and there your dependent variable could be if the product was faulty or not. Let's say they're making electric toothbrushes, and the dependent variable could be whether or not the toothbrush was faulty or not, and the independent variables could be certain parameters of the manufacturing. For instance, what kind of material was used for the plastic. So there would be 2 different types of materials. And instead of age, for instance, you could have what temperature was the toothbrush manufactured at. So at what temperature was the plastic molded into the correct form. Things like that. And then you could analyze, is there a dependency between the product being faulty and what kind of plastic was used and at what temperature it was manufactured. So once again, you can use this type of test wherever you like, in whatever industry, as long as you have a dependent variable which is binary. And once again, we'll talk more about that in this section, and let's get straight into it. Hello and welcome back. And today we're going to investigate our dataset that we're going to be using for this section of the course. So let's go ahead and open up Gradle. Go to File, Open Data, User File. Mine's on my desktop like always. Modeling section. As you can see, we're slowly getting through the section or through this part of the course. So logistic regression, CSV file. There it is. Email offer. That's fine. That's fine. And then in this window here, you can see that Gradle picked up that we have a categorical variable, which is gender. It's got two categories, and one is going to be female, two is going to be male, but we know how to correct that or how to deal with that. So we'll get to that later. Now what we want to do is select all of our variables and go to data, display values. So we just have a brief look at the values. So what can we see here? First of all, we've got the age variable, right? That's good. Then we've got the gender variable. So those are our independent variables. And then you've got the dependent variable, took action. So whether or not the person opened up the email, clicked the link, took up the offer, bought the product. So whatever our action was in our specific case when we were sending out this email offer. And we also see that we have 100 records. The interesting thing that we see right away is that our independent variable, our dependent variable, took action, is binary. So it's either 0 or 1, a yes or no. It makes sense. That's what we're measuring. Did they take action or not? Not how much money they spent, not how much time it took them to take action or anything like that. We're just measuring, did they take action or not? Very simple, straightforward. Yes or no. So I'm going to bring up the types of variables slide that we had in the stats refresher part section of the course. And here I wanted to show you, so we are kind of venturing to new territory. So we've said that we have variables and we have categorical and numeric variables, and let's just focus on those two now. We've already experienced scenarios when our independent variables are numeric, like age or years of experience or how much money a company is spending on R&D or marketing or administration. So we've seen those scenarios. We've also seen scenarios when our independent variables are categorical. For instance, gender, or if the company is located in New York or San Francisco. So when we had to create dummy variables and include those in our model. So for independent variables, we've done both this and this. For dependent variables, though, we've only done so far numeric variables. So both in the simple linear regression and the multiple linear regression, we always had numeric dependent variables. So that y value, the variable that we're predicting, it has always been numeric. It has been how much profit the company is going to make, how much, what the salary is of the person. So it's always been a number, or it's never been a category. Well, when I say that we're venturing into new territory now is because now our dependent variable is actually categorical. So this whole yes-no situation, that's a category. You're categorizing your respondents or the people that took or were part of this experiment are falling into two categories: those who did take the offer and those who didn't. And that is why things are going to be different. And we'll see exactly how right now. So I'm going to close this, and we're going to close this as well. So let's go ahead and construct a chart that we've seen many times. We often see charts where our dependent variable is on the y-axis, vertical, and one of our independent variables is on the horizontal axis, the x-axis. So let's go ahead and construct the chart. We'll do that for took action, of course, that's our dependent variable. We'll put on the y-axis, and we will, on the horizontal axis, we'll look at age. Let's go ahead and do that. You need to go to View, Graph, Specified Variables, XY Scatter, and here we want to put age onto the x-axis. So the x-axis is at the top here, be careful, and took action on the y-axis. And click OK. And what do we see here? First of all, what are we used to seeing? We're used to seeing lots of scattered dots all over the place. For instance, like in the example of of people's experience and their salary, or of how much you're spending on marketing and what your profit is. So we're used to seeing these scattered data points all over the place. And then one line like this that goes through them and approximates a simple linear regression, or represents a simple linear regression that goes through them. Here, on the other hand, we see something completely different. Because our dependent variable is categorical, it is either on 0, which means people didn't take up the offer, or it's on 1, which means people did take up the offer. At the same time, the funny thing is that Gretel tried to actually put a simple linear regression through this data set, and this is the best line it could fit. And although the simple linear regression makes no sense here at all, it's not the right tool to model this data or this phenomenon that we're observing. We do at the same time see that it looks like there is some sort of trend or sort of something going on in the data. It's not all random. You can see that people in the younger age groups from 25 to 45, they're more skewed to the left, so they're less likely to take up the offer. And people between 35 and 50 are more likely to take up the offer, so they're more skewed to the right, or more shifted to the right. These dots are shifted to the right, these dots are shifted to the left. So definitely something is going on, but at the same time we see that the linear regression modeling, simple linear regression is not the right tool to predict this data set and predict this phenomenon, or explain this phenomenon. So that's what we're going to be doing in this section. We're going to introduce a brand new tool called logistic regression, and we will see how it can help us solve these scenarios. And why do we need to do that? Well, because you will come across such situations quite a lot. It's a very common type of analysis when you're trying to predict whether something is going to happen or not going to happen. The classic example is in medicine, when you have, say, a drug, and you want to test whether it's helping patients or not. You can use an A/B test for that, definitely, but sometimes A/B tests are not sufficient because you have many independent variables. So you can't just control for everything and just check one independent variable. No, sometimes you might have the age of the people that you're testing, the country they live in, the mood they're in, all sorts of different factors. And when you have a combination of factors, then you need a logistic regression to test that. You will also come across these types of problems in a business environment a lot, especially if you're dealing with customers or in a customer-centric organization, because you need to do a lot of classification. And we'll talk about this, about classification versus regression in the next tutorial quite a bit. But what that means is that you need to categorize your customers, or you need to create segments. You need to understand how they respond to different offers, how they, not only offers, how they behave based, do they browse via mobile? Do they browse via internet, or when do they come into your store, or what type of products they prefer? Lots and lots of different things. And so every time you can think of a yes/no question, and at the same time there's quite a few independent variables that can affect that yes/no question, then you need a logistic regression. And if you pause for a second after this tutorial and think about it, how in your work, when situations like that arise, when you have to deal with them, or when your company, they arise, and you can possibly, research them and understand them, investigate them, and improve how the company is performing just based on some modeling in that space, I'm sure you'll be able to come up with at least one or two examples of how these situations occur in your business environment. And that's it for today. Next time is going to be an interesting tutorial. We're going to talk about logistic and regression intuition, and I look forward to you then. Until next time, happy analyzing. All right, let's do this. Logistic regression intuition. And you can probably already tell by my voice that I'm pretty excited. There's some very interesting slides coming up, and this is quite an important topic. But at the same time, it is quite challenging. So a quick heads up, there will be some math, and I've done a few run-throughs of this presentation already, and I will try my best to convey everything in the simplest way possible. So let's get into it. We already know about the linear regression. We know that there's a simple linear regression, and it has this very short formula with one independent variable. And we also have looked into the multiple linear regression, which has many independent variables. So we already know how to deal with this type of challenge. So when we have a scatter plot like that, where On the horizontal axis, we've got the independent variable. On the vertical axis, we've got the dependent variable. And this is an example we looked at: salary versus experience. How do we create a model here? So we use a simple linear regression. It puts a line through our data, and that line is modeling our observations. So we can basically forecast things and compare our actual observations to our model and so on. But so we know how to deal with challenges like that, or problems like that. But what we saw in the previous tutorial was a bit different. Well, actually, it was very different. It was completely new. We saw this. So we saw age on the horizontal axis, so an independent variable as we expect. But on the vertical axis, we saw a categorical variable, which only had two values, either 0, meaning no, or 1, meaning yes. So did the person take up an action, perform an action? Did they take up an offer? Did they buy a product? Did they open up an email, respond to our email, and so on? So was the action taken or not? And very black and white, very different. But at the same time, like, even though we don't know what to do, we don't know what's going on here, it's not what we're expecting. But at the same time, intuitively, we can see that there is some sort of correlation. We can see that the observations on the bottom, they're a bit more to the left. Observations on the top are a bit more to the right, implying kind of that probably older people are more likely to take action based on this offer, and younger people are more likely to ignore it. So can we somehow model this? How about we try our the existing method in our toolkit, which is the linear regression. Let's run a linear regression, and that's what it looks like. And this is exactly what Gretel did for us in the previous tutorial. As you can tell, it doesn't look like the best approach, doesn't look like the best method to solve this problem. So let's look into this in a bit more detail. We're going to draw the other horizontal line over here. Instead of trying to predict exactly what's going to happen for any given person, let's imagine a person, and let's say we want to predict for that person, knowing their age, we want to predict whether they will take up the offer or not. But instead of predicting exactly whether they're going to take it up or not, how about instead we will predict the probability. We will state a probability or a likelihood of that person taking up that offer. And if you think of it in that way, right away things start becoming clearer. Right away you can see that, okay, so this chart is actually from 0 to 1. And I also know that probabilities are from 0 to 1. Oh, that's interesting. So basically I could fit in probabilities between 0 and 1. The fact that the red dots, the red observations are already either 0 or 1 and nowhere in between, well, that's simply because we already know the result. We already know that they're either there or there. But for something that we're predicting, it kind of makes sense to say, well, I don't know for sure, I don't know 100% he'll take it up or not, but I know maybe with an 80% chance he'll take it up or not, right? And when you think of it that way, the linear regression line, or at least that part that's in the middle between 0 and 1, it makes sense, right? Well, it makes some sense, because that is basically, it's telling you that anybody between those ages of, for instance, where it's crossing the horizontal line for the first time, it might be, or where it's crossing the horizontal axis, it might be like 25, or let's say 35. And where it's crossing the horizontal axis for 1, it might be, let's say 55. So those people between 35 and 55, they, anything in between, any person that falls in between that age, there is a probability of them taking up this offer, and that probability is increasing as we move to the right. As we take more and more older people, that probability is increasing. So the part of the linear regression in the middle kind of makes sense, and we can do something with it. But the parts that don't make sense at all are the ones at the top or at the bottom, because a probability can never be less than 0, it can never be above 1. So what is the linear regression trying to give us a hint about here? Well, what it's probably saying, what we could interpret it as, is that people above that age, that nominal age, we said 55, above that age, they are very, very likely to take the offer, actually more than 100%. So basically, they're definitely taking it up. Anybody below 35 on the other side, on the left, they're definitely not taking it. So essentially what we're saying is, if we ever take that approach, then we would have to replace this linear regression line with a line that looks like that. So let's just cut those bits off and replace them with horizontal parts. And that would be a very basic, but it still would be an attempt at creating a model for this situation. So we would still be able to use this to make some sort of predictions and assumptions that talk about the correlation between the action and the age of a person. So that's a very basic understanding, and that's kind of the start of our understanding of intuition behind logistic regression. So let's see what the actual scientific approach is. So here we've got the line that we looked at, and it is described by this equation. Now this part is going to be, this is the most fun part, so bear with me. If you apply to this equation a sigmoid function, which looks like that, so you put the y into the sigmoid function in purple, and then you solve for y from the purple box and you put y back into the blue box, then you will get the green box. So basically your linear regression will start to look like this. And this is the formula for logistic regression. And what that will do to a chart, which is most importantly this visual part, it will convert it from the chart that we see at the top to this new chart, which is actually the logistic regression function. So if at this stage you're asking yourself what just happened, then you're not alone. The first time I saw this, or I learned this, this was the expression on my face. If you're totally comfortable with all of that, that's super great. That means you'll fly through this section. But if you're confused right now, not a problem. I was the same when I was in your shoes. So let's take this step by step. Let's look at it step by step, exactly what happened. So there's our graph. There's our independent variable. There's our outcome, yes or no. So that's the y, the dependent variable. And there are our observations in our data set. Based on these observations, and plus using this formula, which we're going to take as given, this is the logistic regression formula. Using this formula and these observations, we come up with this line. And what is important to understand here, it's not a magical line. This line for the logistic regression is the same as a slope or a trend line for a linear regression. So basically what this line is doing is it is using the formula, it's following the formula, and it's the best fitting line that can fit these data sets. So basically we're doing exactly the same thing as with a linear regression, but it just looks different. That's all. So there are heaps of these lines that you can draw that look like that, but only one of them is the best fitting line. So the point of the logistic regression is to find that best fitting line. And this is it. So we found the best fitting line that follows that equation and fits these variables that or these observations that we had in our data set. After that, we can forget about the equation, we forget about the variables. We've got our line. So this is our logistic regression function. We found it. Same thing as with the linear regression. We've created the model. We've built the model. You can see it. This is the model in front of you right there. Now, what can we do with this logistic regression? Well, we can use it to predict probabilities. And we've already touched on probabilities, that they lie between 0 and 1, and that instead of predicting for sure that something will or will not happen, how about we predict probability? So let's look at, oh, by the way, probability here is called p hat. So that's a little sign about the p gives it the name p hat. And anything you see in the with a hat in this section just basically means that it's something we're predicting. So and that's a way to remember it, that picture, p hat. So we're predicting this probability. Okay, so let's take 4 random values for the independent variable. For x, we're going to say 20, 30, 40, 50. Let's see what happens to these variables. So let's put them on the x line. Those are the dots. And I specifically put dots, not x's or crosses, because it doesn't mean that they're on the horizontal. The bottom line doesn't mean that their probability is 0 or that their dependent variable is 0. No, they're just there because they're on the x-axis. We just plotted them there. It has nothing to do with the vertical axis. Now, what you need to do to find the probabilities is you need to project these values onto your curve. Once you project them, you get these blue dots or blue observations, which plotted basically. So these are the fitted values. As you remember, in Gretel, you have in red you have the actual, and in blue you have the fitted values. So these are your fitted values. And now, if you project them, if you want the probabilities, you need to project them to the left, like that. And let's have a look at these probabilities. So the person who's 20 years old, the probability of taking up this offer is very low, perhaps 0.7%, so less than 1% to take up this offer. The person who's 30 years old, the probability is higher. It's about 23% to take up this offer. The person who's 40 years old, their probability to take up this offer is 85% according to this model. And the person who's 50 years old, their probability is 99.4%. So that's the first thing that you can get out of a logistic regression. That's what we're going to be using we're going to be using it very actively when we're talking about building geodemographic segmentations, because you use this probability as a score, and I will talk about this more. So you can actually rank people, who is the most likeliest to take up your offer and who's the least likeliest to take your offer up. So it's actually even better than just having a 1 or a 0. You have a probability, so you can order people by this probability. Anyway, you might want to say, well, I don't want the probability. I want a prediction as because this is a regression. I want a prediction for the y value. So okay, we can do that. Can we get? Let's get rid of those probabilities. Now, can we get the actual? Well, obviously we can't get the actual, because the actual is something that we can only observe in our data set or in real life. We can only get a prediction for the actual. So y hat, as the hat suggests, is the predicted value for the dependent variable. How do you get y hat? Well, the approach is very arbitrary. You have to select a line. Let's wait for that. Okay, so you have to select a line. In this case, we're going to select 50%. You can select it anywhere, but 50% is usually selected because it's in the middle, and therefore you have symmetry. And anything below this line, so anything that falls on the curve below this line, will be projected downwards onto the 0 line, which makes sense. So it's basically saying if your predicted probability of taking up this offer is less than 50%, let's say it's 40% or 20%, then we're just going to say that you're probably not going to take up this offer. And so that's what's happening. The person with 0.7%, the person with whatever it was, 27%, 23%, their probabilities are not 0, but they're below 50. So if you do require a y hat, so a predicted value, a yes/no value, then makes sense that if something's below 50%, you're probably going to say that they're not going to take up the offer. Now, anything so there you go. Both of them, y hats are 0. Now, anything above the horizontal line that we've selected, the 50% line, it is agreed that all of those values that fall onto the curve above that line are projected upwards. They're projected onto the yes line, the 1 line. So the person that had a probability of 85% is projected upwards, and the person that had the probability of 99.7% is projected upwards. Also makes sense, right? So if somebody's got you're predicting that somebody's probability of taking up an offer is 85%, then if you have to say yes or no, then you're probably going to say yes. You're going to say yes, this person will take up the offer if you have to choose one of the two. So those are our predicted y hat values. In this case, they're both 1 for those two variables. And those are the two things you can get out of the logistic regression. So you get the probabilities, which are important. Also, you can get the y hat, so the predicted values for the dependent variables. Once again, it's important to think of it as it's doing exactly the same thing as a linear regression. It's fitting this line, even though it's not a straight line, and the values are not scattered. Everything looks bizarre in its uniformity, or in the way in its structure. Its structure makes it look very bizarre, but still, it's pretty much the same way. We've agreed on a line, or a formula for a curve, and we're trying to fit the best curve to our data. Once we've done that, we've got a model, we've got the coefficients, which we'll talk about later, and we can start drawing conclusions or insights from this model. And some of the insights are we can get a probability of somebody taking action or of the event occurring, and or basically of the answer being yes. So it's not a yes no, it's a probability, so 85% or 20% or whatever. So that's when we project it to the left onto the y-axis. And also we can get a predicted value for the dependent variable based on where we select this arbitrary line, 50%. You can select it anywhere you like. You can select it higher, lower, depends on your knowledge about the problem at hand. And as you understand, depending on where you select it, that will significantly affect your variables. So I really hope this explanation was trivial enough and yet insightful enough for you to gain an intuitive understanding of logistic regression. And in the next tutorial, we will build our very first one in Gradle. I look forward to seeing you then, and until next time, happy analyzing. In the previous tutorial, we had quite a lot of theory about the logistic regression. And even though we were talking about intuition of the logistic regression, we had to look at a few formulas anyway. So today it's time to make up for that with some practice. And finally, today we're going to build our very first logistic regression. I hope you're excited. So here I've got Gradle opened up, and I've already loaded the data set, which is email offer, and I have even created 2 dummy variables for the gender categorical independent variable. So please go ahead and do that. And once you've done that, we will start creating the model. In order to create a logistic regression model, you need to go to Model, and then go to Limited Dependent Variable, and then go to Logit, and then go to Binary. And so here, you need to take your binary dependent variable and put it into the dependent variable option. And also let's set it as default, because we'll need to rerun this model in a bit. And we're just going to run the model with 1 variable. We're only going to use age, so we won't worry about gender at this stage. And before you click OK, make sure to change show slopes at mean to show p-values, because we are used to using p-values and we'll continue doing that. So click OK, and there you go. That's your model. It's been run. It's ready. As you can see, it's very similar. So here you've got your similar to the linear regression. Here you've got your variables. There are coefficients and p-values. Here you've got some stats about the model, as how it's running, how it's been fitted, and so on, and some additional information at the bottom, which we won't worry about right now, but we will get back to it after we're more comfortable with the confusion matrix. Now what I would like us to do is to look at the graph, the charts of the logistic regression, which we spoke in depth about in the previous tutorial. So just go to graphs and then go to fitted actual plot and select the one which is against age. And here you can see the logistic regression graph. It's exactly the one we talked about previously. So vaguely at the bottom, at the top, you can see the actual observations. They've been plotted in red, and in blue you can see the chart for the logistic regression, or the line for logistic regression. So let's take a random age here. So for instance, for age 39, which is over here, you've got some variables. You've got a variable over here, you've got a red line, and you've got a red line over there. So some people did take up of the offer, some people didn't. But according to our model, anybody who's at age 39, their probability of taking up the offer is about 30%. So it kind of makes sense, right? Even if the probability is 30%, some people, most people probably won't take up the offer with that probability, but some people still will. And that gives credit to our model. All right, so now we're going to close that, and we're going to move this model to the side, and we'll run a new model with the second variable included. So let's go ahead and do that. Model, limited dependent variables, logit, binary, and here just add in your new variable. In this case, you can add male or female, doesn't really matter. I'm going to add male, and then just click OK. And here we'll look at the chart, but we'll do that later. For now, let's look at something else. Let's go to analysis, go to forecasts, and without forecasting anything, let's just run the model and see what the results will be. So here what you get is a table which includes your actual took action or didn't take action variable or dependent variable, so you know what the result was, and you have the prediction for the same person. Here it only has the row number, so it doesn't have the gender or age, and that's not very convenient. So what we're going to do is we're going to save this new variable by clicking the plus up over here. And right away it gives it a name. So the name is quite funny in this case. It says took a hat, and that's just a because it abbreviated or shortened our um, variable, the name of the variable took action. So we're going to say took action underscore hat. And as you recall, this is exactly what we were talking about previously. Hat means prediction. So this is our y hat that we looked at in the previous tutorial. So if we click OK now, and we can close this, and we'll leave the model open, just move it to the side, you can see that a new variable has been added to the data, took action underscore hat. And now we can have a look at all of them together. So just highlight the variables. And as you can see, the dummies won't be highlighted that way. Well, if you keep this closed, you see the dummies are not highlighted, which is good. And we go to view, or no, let's go to data display values. So here now you can see more information. You can see the age, the gender of the person, and whether or not they took action and took action had. So let's have a look at a couple of examples here. And why are we doing this? Well, I'd like you to be a bit more prepared for the next tutorial when we're talking about false positives and false negatives. And if we look at this now, it'll make more sense what we're talking about in the next tutorial. So age, this person, the first row, was 38, female. They didn't take up action, and what our model actually predicted for them is a 1% chance of taking up action. So that's good. So basically means that our model is in line with them not taking up action. Next person is 32, female, didn't take up action, and our model predicted a very low value, which is good. Next person, 46, male, took action, yes, and our model predicted a 99.9% chance of taking action. Great. Next person, 34, male, didn't take action. Our model predicted a 2.7% chance. Good. So far, so good. Next person, 40, male, did not take action, but our model predicted an 85% chance of them taking action. So here you can see that our model made an error. If we applied that logic where we derive the y hat value, so this is the probability. If we derive the y hat value, so that 1 or 0, and we use the 50% line, for us this would mean that the person is predicted to take action, but in reality they didn't take action. There is a 0 here, meaning that they ignored the offer. So this is an example of when a logistic regression makes an error, and that's fine. This is normal. No model in the world will always predict 100% correctly. Once in a while errors will be made. It's about controlling these errors and making sure there isn't too many of them. And we'll talk about errors a bit more in the next tutorial. So that's what I wanted to show you over here. That's pretty much it for this tutorial. The last thing I wanted to show you was the chart for the model with two variables. So let's go ahead and look at it now. If I go to graphs and I go to fitted versus actual plot, and I plot against age, what you'll see here is a bit of a different picture. And you see here two of the sigmoid functions, or two of the logistic regression curves. And the question of the day is, why is there two curves? And I will let you think about that on your own. So it's a little challenge for you to figure out why there is two curves on this chart. And I look forward to seeing you next time. Until then, happy analyzing. In this tutorial, we will be talking about false positives and false negatives. As you remember, at the end of the previous presentation, we left off over here, where we were using the logistic regression function to observe where 4 random values of the independent variable will end up in terms of y hat, so in terms of the predicted value for the dependent variable. And we agreed that anything below the 50% line will be projected downwards onto the 0 horizontal line, and anything above the 50% line will be projected upwards onto the 100% horizontal line. And that allowed us to turn probabilities into actual predictions. So either yes or no. Now let's take a step back. Where did we get these 4 values from? So we took 4 random values of the independent variable, and we just had a look at what would happen to them, how we would use the logistic regression function to ascertain what probability they have and what y-hat values they have. So how about we take another step back and we forget about these 4 random values, and instead of taking 4 random values of the independent variable, how about we take 4 known values? In fact, let's take 4 values for the independent variable from our data set. So let's just pick out 4 values that we already know they exist in our data set, and we use them to create this logistic regression. And let's do the same thing with them. Let's see where they will end up if we apply the model to them. And as you can see here, the label of the vertical axis changed to y, because this is we already know that in red is the actual value of the dependent variable, because we know the result. Those the people on the bottom, so observations number 1 and number 3, they didn't take up the offer, the email offer, and the observations on the top, people number 2 and 4, they did take up the email offer. So let's see what happens to them if we apply our logistic regression model. So step number 1 would be to project these values onto the curve. Makes sense, right? So we just want to see where they'll end up on the curve. That's our blue dots over there. That's where they have been modeled by the curve. Now from here we can say what the probabilities are. You just have to project to the left, and you can see approximately that for observation number 1, it's about maybe 20%, 10, 15%, maybe let's say 15%. Observation number 2, it's about 40%. Observation number 3, I would say about 70%. Observation number 4, about 85%. But we're not interested in probabilities per se right now. What we want to get to is the actual y-hat. We want to see what the predicted value will be. So we want to see if the model will tell us, are these people going to take up the offer or not? And why do we want to do this is because we already know the result, right? We already know what the result will be or was, and we just want to see, we want to kind of assess the model. We want to see how well it's working and if it's going to make any mistakes. So let's go ahead and proceed with our logic for getting the y-hat. And what was our logic there? Well, the same thing that we discussed just a few minutes ago at the start of this tutorial. We're using this arbitrary horizontal line, 50%. So anything below this line is going to be projected onto the horizontal line, which is 0. So where we're saying that the offer is not going to be taken up. And anything above the 50% line will be projected onto the horizontal line, which is 1 or 100%, where we're saying that those people that end up on that line are definitely going to take up the offer. So let's go ahead and do that. There we go. In gray, we have our projections or our predicted values. So y-hat is in gray. And it's very interesting to see both y and y-hat on one chart. So that means what actually happened is in red, and what we predicted was going to happen is in gray. And right away, you can see that for observations number 1 and number 4, so for those people in observations number 1, number 4, we predicted correctly. So we said for person number 1, we predicted that he won't take up the offer, and he actually did not take up the offer because the red mark is also on the same horizontal line. Now for observation number 4, same thing. We predicted that that person will take up the offer, and they did take up the offer. That's good. But now let's have a look at observation number 2 and number 3. You can see that for observation number 2, the gray line's at the bottom, the gray mark is at the bottom, meaning that the model is predicting for this person based on their gender, based on their age. Well, in this case, just age, because we're doing a single variable logistic regression. So based on their age, this model is saying that this person is not going to take up the offer because the gray mark is at the bottom. However, we can see that the red mark is at the top, meaning that this person did take up the offer. And that means that the logistic regression made an error here. And same thing for person number 3. The gray mark is at the top, and that means that the model is predicting that the person will take up the offer, but the red mark is at the bottom, meaning that the person didn't actually take up the offer, and therefore the logistic regression made a mistake once again. And these mistakes, they actually have specific names. So the top mistake over there is a false positive, or a type 1 error. What does false positive mean? Well, it means that we predicted a positive outcome, but it was false. So we predicted an effect that did not occur. And the other mistake you see here has a different name. It's called a false negative. So we predicted that there won't be an effect, but the effect actually did occur. So our prediction was negative, meaning there won't be an effect, but it was a false negative. And it's called a type 2 type of error. And the way I personally remember them, it's important also to distinguish between the two. The way I personally remember them is I think of type 1 as less dangerous than type 2. So type 1 is less for me in my mind, although it's not necessarily the case, but that's the way I remember them, that type 1 is kind of like a warning. So that's why there's an orange exclamation mark, and it's a false positive. So basically you said something is going to happen, but it didn't happen. So you said maybe there'll be an earthquake, but there wasn't an earthquake. So, that's not the end of the world. But false negative is a bit worse in my, once again, understanding, because if you say something's not going to happen, but it actually does happen, then you can't even be prepared for it. And that's why type 2 is a false negative, and that's how I remember them personally. But once again, it could be absolutely, they can both be pretty serious errors, especially when you are dealing with like medical conclusions and stuff like that. So those are false positives and false negatives. We will be using them more when we talk about the confusion matrix in the next tutorial. And I look forward to seeing you next time. Until then, happy analyzing. Confusion matrix. Don't you just admire these terms sometimes that they come up with? Like, why would you call something the confusion matrix when it's designed to explain things? Anyway, let's get into the confusion matrix. So, last time we left off over here where we discussed false positives and false negatives, type 1 errors and type 2 errors. So, the false positive is when you predict that something will happen, but it actually doesn't happen, and that's a type 1 error. And a false negative is when you predict that something won't happen, but it does actually happen. And that's a type 2 error. So let's see what we can do with these. Let's start building a matrix, and we'll understand what it is exactly saying as we get along with it. So we've got the y hat at the top, so the predicted dependent variable, so whether or not we're saying that event will happen at the top. And on the left, we've got the y, just the y, the actual dependent variable. So there it's telling us whether or not that event actually did happen. Now under each one of them, let's put the two different options that are available. You can either have a 0 or a 1. So 0 for y hat, 1 for y hat, 0 for y, and 1 for y. And in that space between them, there's 4 more squares there. That's where our confusion matrix will be. So we'll start with the furthest square. Right away here, that is the intersection of when y hat is 1, so we're predicting something will happen, or the person will take up the offer, or the event will occur, and at the same time, it actually did happen. So let's say, for instance, we had 50 observations in there, or out of our observations, the ones that we said will happen and actually did happen, there's 50. Now let's look at the ones that didn't happen, and we also said that they won't happen. So basically we said they won't happen and they actually didn't happen. So let's say that in there we have 35. So 35 of the observations, let's say in total we have 100, and 50 of them actually did happen, and our prediction was that they will happen, and 35 of them, they didn't happen, but we also said that they won't happen based on our model. Now let's look at the other two squares. So can you guess from here which one is the false positives and which one's the false negatives? I'll give you a second to do that. You can pause the video if you want to try this on your own. So the false positives or the type 1 error are at the top on the right, because a type 1 error is when you're saying that something will happen but actually doesn't happen. And remember, the way I remember it is it's not as bad as saying that something won't happen and actually does happen. Although that might not necessarily be the case, but it's an easy way to remember it. So that's our type 1 error. It's up at the top over there on the right. Now on the left at the bottom, we've got the false negative or the type 2 error when we're saying that something won't happen, but it actually does happen. And let's say we had 10 and 5 in them respectively. So this is your confusion matrix. And what it's telling you is it's giving you a quick overview of how well your model is performing. If you look at the diagonal, the light diagonal, it won't be colored probably in the report that you'll be studying, but if you look at the top left and the bottom right, if you just remember in that way, those are the good things. So in total, that's how much you predicted correctly. And the other diagonal, so the top right and the bottom left, those are the bad things. Those are the observations that you weren't able to predict. Those are your errors. So the more you have in the first diagonal, the better. The more you have in the second diagonal, the worse your model is performing. And let's have a look at two ratios that you can calculate. So the first rate is the accuracy rate, and you take the correct predicted divided by total. In our case, we predicted correctly 85. The total is 100. So if we divide 85 by 100, we get an 85% accuracy rate. And you can tell it right away just by looking at the confusion matrix, especially if you know the total number of the observations right away, so you don't have to do the calculation, add up all the values in the matrix. That way you can just divide by 100. But even by looking at the confusion matrix, you can quickly understand what the accuracy rate is, and also the error rate. So you take the total that you were wrong about, and you divide by the entire total. So in this case, it's 15 divided by 100. It's 15% error rate. That's all for today. We'll be using the confusion matrix in our next tutorial. Hello and welcome back. In today's tutorial, we will look at the coefficients of a logistic regression, and we will understand what insights we can and what insights we cannot derive from our models. So let's go ahead and create our model. As you can see, I've already loaded the data. It's the email offer CSV file, and I have created dummy variables. Now I'm going to go to model, limited, logit, binary, and the dependent variables took action. I'll set it as default. Regressors, I'm going to use age and female, the dummy variable for female, and I will click show p-values. So once you've done that, click OK. And here is our model. So what we're focusing on today is this top part. And there are 4 main points that I wanted to get across today, and the last one will be a bit complex, but we'll get to that. So to start off with, the first thing that you can do, just like in a linear regression, you can look at the sign. So the sign here for female is negative, the sign for age is positive. That means that female detracts from the effect, age adds to the effect. What does that mean? That means that if you take hold everything else constant, but you increase age by 1 year, then the probability will increase. And same thing, if you take 2 people of the same age and one of them is male and the other one's female, then the probability for female will be lower. The probability predicted by this model will be lower. Now, that is the first thing that you can do. The second thing is something you cannot do, and you cannot use the coefficients to quantify any interpretations. Remember how in the linear regression, we were able to say, because one coefficient is greater than the other, then we can understand how much greater the effect of that variable is compared to the effect of the other one. So in order to understand this a bit better, I'm going to run a new model. I'll leave this to the side. I'm going to run a new model, but I'm going to replace female, the dummy variable for female, I'm going to replace it with male. And I'll run it now. So here you can see that both coefficients are positive. However, what we could have done in a linear regression, we could have said that because the coefficient for male is 5 times greater than the coefficient for age, that means that the effect of this variable, as you remember, we used to say per unit of that variable, is greater than the per unit effect of the age variable. However, in a logistic regression, you cannot use the coefficients to quantify any sort of effects. So let's go to the logistic regression formula to understand this. This is the formula for the simple logistic regression. This is a formula for the multiple logistic regression, and it's also called the logistic regression just because people don't normally use the simple logistic regression. In fact, I'll share a secret with you. Very, very often, the number of variables in a logistic regression can be very high. So 5, 6 is standard, 10, 20 is also very normal, can go up to huge numbers. Not saying that that is the best approach to use logistic regression, but you will come across these situations when there's lots and lots of variables in a logistic regression. So what else you can see from here is that the variable that we're predicting, p, is actually hidden. It's not just on the left of the equal sign. It's inside a ratio, which is called the odds ratio, and it's inside a logarithm. So this whole expression on the left is called the log odds. And people just don't think in log odds terms. So this variable or this new expression, log odds, it's not that easy to understand or visualize in your head. If you look at log odds as a separate variable, then this becomes a linear regression for log odds. And that way you could interpret the coefficients. But if you want to interpret the coefficients for the probability, then from here you simply cannot do that because the formula is so complex. So we will stop on that we cannot use the coefficients to quantify any effects. And that actually implies two things. The first thing is that you cannot use the coefficient to quantify the per unit effect of a variable or of an independent variable to your dependent variable. So like we used to say that a $5 increase or $1 increase in marketing spend results in a so many dollar increase in revenue. You can't do that. And the second thing, second sub part of this is that you cannot use the coefficients to compare the quantified effects of the two different variables. So you can't say if the coefficient for one variable is greater than the other, 5 times greater than the other, then the effect is going to be 5 times greater. Once again, it's because it's to do with quantification. You simply cannot do that because the formula is complex. So we'll end that part on that. That was point number 2. Point number 3 is what you can do. What you can do is you can look at the coefficients, and without quantifying the effects, you can still observe and you can determine which effect is greater. So just generally speaking, which effect is greater. Here you can see that the coefficient for male is greater than the coefficient for age. And that means that per unit of this variable, the effect is greater than per unit of this variable. And remember that everything is relative, and this is going to be important just now. It is relative to the scale that you are measuring these variables on. So we're measuring age in years. So if we start measuring age in months, then the values of age will go up 12 times. So that means the coefficient, the model will stay the same, but the coefficient will go down 12 times. And if we start measuring age in decades, then the values of the variable will go down by 10, but the coefficient will go up by 10. And so we can manipulate the coefficient, the absolute value of the coefficient, and therefore we always have to say per unit. So you can still do that. You can compare per unit and see which of the variables has a greater effect per unit. So remember, it's relative. Now, the last fourth thing is a more of an advanced technique, and for some of you it might not apply, so you just ignore it if you don't think that you'll be using it. But for those who are more interested in like the advanced type of stats, then there's this variable here, z-score. And z-score is basically a standardized coefficient. And how do you get z-score? Well, all that you need to do to get to the z-score is you take your coefficient and you divide it by your standard error of that variable. Same thing here, coefficient divided by the standard error. And here you get a z-score. So you can think of z-score in terms of a standardized coefficient. And what that means is that it is no longer dependent on the scale of that specific variable. So because the standard error is also measured in years, when you divide one by the other, you get this coefficient, which won't change if you change the scale on which you're measuring age. Or same thing with kilometers into meters, or inches and kilograms into pounds, and so on, or grams. So this z won't change if you change the scale of the underlying variable. However, it is much more complex to interpret because z is measured on its own scale, and that scale is in units of the standard deviation of the underlying variable. And once again, as humans, we don't think in those units. And moreover, because it's all relative, it can lead to seemingly different results. So here you can see that Z for age is 3.8. Z for male is 2.9. Although here we said that the effect of male is greater, based on the Z statistic, it looks like the effect of age is greater. But it might be confusing if we think of it in absolute terms, but it's all relative. So the effect here was greater for male in terms of relative to the units of each of these variables. Here, the effect of age is greater relative to the standard deviation of each variable. So although Z might be more convenient when you have like lots of variables, it might be more convenient because it's standardized and you don't have to remember the different units and always say them. It might be a bit harder to interpret. So once again, that's a bit more of an advanced topic, and you can still use your models without having to worry about Z, just focus on the coefficients. Those were the 4 things that you can and cannot do with your logistic regression. And here's a slide that you can take away after this tutorial. You can just simply download it and use it for your reference in the future. So it sums up those 4 things. Let's quickly recap. You can interpret signs. You cannot interpret magnitudes to quantify associations. You can still use magnitudes to contrast per unit associations. And you can use the Z statistic to contrast associations as well. However, the Z statistic is standardized, so it might be a bit harder to interpret.
Welcome to this section on geodemographic segmentation. We're finally here. It took us a while, it took us a couple of steps to get here, but we're finally going to create a proper, robust, very insightful geodemographic model like one you would find in a large organization. And the one we're going to be creating is a churn model for a bank. So we're going to be predicting the likelihood of customers leaving the bank or staying with the bank. And in order to build this model, we're going to use a logistic regression. If you recall, in the previous section of the course, we talked about a logistic regression with just 2 variables, and that was already interesting. Well, this time we're going to have many more variables, and it will be truly exciting. And along the way, we will learn quite a few new techniques like transformations of variables and creating derived variables, which will be handy in your future when you're creating proper, full-on models. And also we'll talk about multicollinearity and what it means for models and why you need to avoid correlation between independent variables. So it's going to be quite a saturated section, and I look forward to seeing you on the first tutorial.
This time we have 2 data sets. We've got churn modeling and churn modeling test data. So let's go ahead and download them. And once you've downloaded them, put them into your folder and let's open them up. I'm going to use Excel, and I'm going to drag churn modeling in here. And if you've done the section on, or the part of the course on visualization, this dataset will look extremely familiar because it's actually the same dataset. The only difference is that this time it's a CSV file, that time it was an XLSX file. And well, if you haven't, doesn't matter, we'll still go through it now. So I'll just make some space here so we can see everything. And okay, off we go. So this dataset has got a few columns. It's got row number, customer ID, surname. So what we're looking at is a dataset of a bank. Of course, it's all fictional. It's not a real bank, but it's very realistic. And here we've got a snapshot of, if you scroll down to the bottom, there's going to be 10,000 customers. So 10,000 rows in this dataset. And what the bank did is they measured some things about these customers. right? Why did they undergo this whole thing? And what's the challenge here? Well, the bank has been seeing unusual churn rates. So churn is when people leave the company, and they've seen customers leaving at unusually high rates, and they want to understand what the problem is, and they want to assess and address that problem. And that's why they've hired you to look into this data set for them and give them some insights. And how did this data set come to be? Well, 6 months ago, the bank said, all right, there's a big problem. We got to take a sample of our customers. By the way, this is a sample. 10,000 is a tiny number for this bank. This bank has millions of customers. It operates, this fictional bank operates in Europe, in 3 countries, France, Spain, and Germany. And they have lots and lots of customers. So what they did is they took this sample of 10,000 customers, and they've measured 6 months ago everything they knew about them: their customer ID, their surname, credit score, their geography, their gender, their age, their tenure, so how long they've been with the bank, the balance of the customers at that point in time, the number of products they had at that point in time. So a number of products is things like how many products do they have? Do they have a savings account? Do they have a credit card? Do they have a loan? Did the customer have a credit card or not? So there's a yes/no flag. Is the customer an active member? Another yes/no flag. Active member can be measured differently by different organizations. It could be whether or not the customer logged into their online banking in the past month, whether they did a transaction in the past 2 months, or some other measure like that. And estimated salary. So the bank doesn't know the salary of the customers, but based on the other things they know, they could estimate a salary for that customer, and they also gave you this information. So 6 months ago, they measured all of these things and said, all right, so for these 10,000 randomly selected customers, we're going to just watch them. So we're just going to wait 6 months, and 6 months down the track, we're going to check who of those customers left and who of those customers stayed. And that's what this column exited represents here. It tells you whether or not the person left the bank within those 6 months. So this person over here, sometime within the 6 months, he left the bank, and as of a couple of days ago, he's no longer with the bank. This person over here, on the other hand, is still with the bank. So there's a 0 here. This person left the bank, this person stayed, and so on. So if you see a 1, that means the person's no longer with the bank. A 0, the person's still with the bank. And your goal is to create a geodemographic segmentation model to tell the bank which of their customers are at highest risk of leaving. So we're going to talk more about geodemographic segmentation in the next tutorial. The other thing I wanted to look at now is the test data set that we have here. So what is the test data set? So if I copy it in here, you'll see that it's exactly the same type of data sets, same columns, but the only difference here is that it's different customers. So you can see row numbers are higher, the customer's IDs are different. These are different customers, and there's only 1,000 of them here. So why have we been given this data set? Well, basically we're going to use this data set as a validation for the model we build using the other data set. And the way this data set was constructed is exactly the same. 6 months, so same periods of time, same snapshot. So basically the bank just literally separated this data set from that one. So you have 2 separate data sets. And that will allow us to assess our model. But more on that later when we get to the correct section. What I wanted to mention today is that this skill that you're going to learn in this section and upcoming sections is very transferable. It doesn't have to be for a bank. It doesn't have to be for churn rates. Geodemographic segmentation models can be applied to millions of scenarios. So here, for instance, even in a bank, the same scenario could work. Should the person get a loan or not? Should the person be approved for credit or not? And once again, you'd have a binary outcome. So based on prior experience, you would know whether or not a person is reliable, and you'd build a model and say which people are more likely to be reliable and which people are more likely to default. And that could govern the bank's decision on whether or not to give loans. This could be in terms of fraudulent transactions, not even in a bank, in a different financial institutions. You could find out which transactions are more likely to be fraudulent, which are less likely. There's lots of scenarios where you could apply a geodemographic segmentation model, and it doesn't even have to be geodemographic. So we know that we're going to be using a logistic regression, and whenever you have a scenario when you have a binary outcome and you have lots of independent variables, you can throw all of that into logistic regression, and as you'll see in this part of the course, build a proper, robust logistic regression, and that will tell you which factors influence your outcome. So going back to our example of toothbrushes, you can have here whether or not it's a faulty toothbrush, and here you can have a myriad of independent variables, like, as we've discussed, what plastic was used, at what temperature the toothbrush was built. You could have what other components you added, whether or not you added other components to the plastic, what electrics you used in the toothbrush. You could have how long the toothbrush was being created for. You could basically have anything, even the humidity in the factory at the time of making toothbrush. So basically, it doesn't have to be a customer-centric organization. That's what I'm trying to explain here, that you can apply this knowledge that you're going to learn in any kind of scenario where you have a binary outcome and lots of independent variables. And on that note, let's jump straight into our modeling section. I look forward to seeing you in the next tutorial. Until then, happy analyzing. Geodemographic segmentation. What is it and what is it used for? Let's imagine a scenario. You're a data scientist working at a bank, and this bank has lots and lots of customers. And at some point, you decide to take a random sample of these customers and take a snapshot in that point in time. Meaning that you gather all the information you can on these customers. And we're talking about things like age, gender, how many products they have with your bank, whether or not they have a credit card, how long they've been with your bank, and things like that. So as much as information as you can. And you attach it to their records. In this case, for simplicity, we're going to track two things. The first thing is gender, as you can see here, and the second thing is their favorite color. Now, tracking the favorite color of a customer or bank might not add a lot of value. However, this is just a representation for something, for any other variable. It's just for simplicity's sake in this specific example. And then what you do is you track these customers for the next 6 months. And 6 months down the track, you look back and assess which of these customers left your bank and which of these customers stayed. So my question to you here is, do you think that this information would be helpful to you? That you now know that out of a sample, which is quite a large sample, let's say 10,000 customers, out of that sample, every single female whose favorite color is red left your bank. And 2/3 of the males whose favorite color is purple left your bank, and 1/3 of the females whose favorite color is green left your bank. So do you think that you could somehow apply this information in the foreseeable future to prevent other customers from leaving the bank, or as they call it, churning from your bank? And that is exactly what geodemographic segmentation is. What you would do going forward is you would take another sample of your customers, or even perhaps all of your customers, and the first thing you would do is you would find out their gender, which you already know, and their favorite color. Once you found out their favorite color, based on your prior experience, you can group them or segment them. And this is how you would segment them. The first group on the right here is the group at highest risk of churning. So these are females with their color red. Based on what you know, within 6 months, they're probably all going to be gone. Then the next group is the males whose favorite color is purple. Also, based on your experiment, probably 60% of them will be gone within 6 months. And then it's the females with their favorite color green, 30% of whom might be out of your bank in 6 months. Then you've got a group over here who are kind of in between. So their favorite colors match those that leave, but then their genders don't. So they might be at risk, they might not. You would give them a probability of leaving, so a certain chance, a likelihood that they will leave. And then you've got the orange and the blue, who are definitely your loyal customers and who are not going anywhere. And so this knowledge and information will allow you to further preempt any kind of churn that might occur, and perhaps talk to these customers or give them special offers or do something that will prevent them from leaving. So be proactive in your approach. And this is why it's called geodemographic segmentation, because you are taking into account factors like where these people live, in what country, what region, what postcode. Then you take into account their demographic status, so how affluent they are, what their income is, how much they bank with you, how many children they have, whether they're married or not, whether their spouses have accounts with you as well. So you don't know the future, but based on certain similarities of these customers that you're investigating right now to the customers that actually left, you can put the new customers or the existing customers into groups and assess the likelihood of leaving. And this is what we're going to be doing in this section. Well, in this section, in the next section, and the section after that. We're going to be creating a robust geodemographic segmentation model using logistic regression, because this is a 0 and a 1 situation, right? Yes, no. Did the person leave or did the person stay? And so finally, we're going to put everything together. We're going to use logistic regression to create this incredible geodemographic segmentation model that will allow us to draw conclusions and predictions on who is most likely to leave our bank and who is most likely to stay. And then we'll be able to draw insights and give recommendations. So that's how geodemographic segmentation works. And in the next tutorial, we're going to start building this model. Welcome back to your ultimate data science course. This is Kirill Eremenko as always, and today is go time. We are building our first geodemographic segmentation model. Hope you're excited about this because I'm super pumped. And let's get straight into it. So I'm going to open up Gradle, and now I'm going to open our data set. So mine's on my desktop as usual. Modeling section, geodemographic segmentation. It's a CSV file. So not the test data. We're looking for the churn modeling.csv. Open that up. Nope. Okay. So here we've got a list of categorical variables. We've got the surname, which we won't be using, so we don't care about that. Then we've got the geography, which has 3 categories, and we've got gender, which has 2 categories. So we need to take care of those right away. And that's what we're going to do now. We're going to create dummy variables for geography and gender. So let's go add dummies gender, add dummies geography. Okay, hope you're following along. So we're going to recode these now. Edit attributes, France. I'm gonna go to France. Next, Spain. And Germany. So we're just basically changing the names so that it's easier for us to navigate. Now they have proper names. And gender, same thing. Edit attributes, female. And male. Okay, good. So that took us about a minute. Now we want to run our model. As you can see, there's so many variables. It's going to be very exciting. All right, model, limited, logit, binary. Okay, so now let's take our exited variable. That's the variable that we're trying to model. We're trying to predict if a person is going to exit or not. So that's our dependent variable. And we'll set as default because we're going to be running a lot of these models. Now, as you remember, the bank had a snapshot of 10,000 people at a certain point in time, and then it watched which ones of them exited and which ones stayed. So that's why exit is our dependent variable. Now let's look at the other variables that we want in our regressors. So row number doesn't affect whether a person exits or not. Customer ID, same thing. Surname, same thing. So those are obviously not going to be in our model. Credit score, that could be a regressor. Credit score could affect or could be associated. So the effect is probably not the right word when you're talking about logistic regression, because there's no actual causation. What we're talking about here is association. Is credit score associated with people exiting? And that's important to understand, that it's not that credit score makes them leave. It's the people that leave. Do they have a certain type of credit score? Can we describe them by looking at their credit score and say, for instance, people with high credit scores are more likely to leave than people with low credit scores? So that's not effect, that's association. But sometimes you'll hear me say effect. Just think of association when you're talking about logistic regression in any case. So credit score. Geography and gender, we won't be using these two because we've created dummy variables which are at the bottom, and we'll get to them in a second. Age. Age could affect or age could be associated with people leaving or staying with the bank. Good. tenure. So how long has the person been with the bank? Is he a loyal customer, or is he somebody who just joined the bank recently? That probably could also determine whether a person is going to leave or not. Balance, so how much money does the person have with the bank? How affluent is he or she? Number of products, how many products does this person have with the bank? A very good one, it's stickiness. It's what share of the wallet does the bank have? Does the person have a mortgage loan with the bank? Does the person have a credit card? Does the person have a savings account? How many of these products? The more products, as you can imagine, the more products you have, the harder it is for you to leave the bank. So we'll put that in. Has a credit card or not? That's kind of a subset of number of products. So this is a yes/no variable, but it's already been coded for us by the IT department into a 1 and a 0. So we don't have to create dummy variables because it is already in essence a dummy variable. And does the person have a credit card with the bank or not? Is that associated with them leaving? Can that help us classify the people? So we'll put that in as well. Is an active member. So active member is an interesting one. Different companies define that but differently, and it's also a good metric to have for any company because it kind of tracks how frequently your customers engage with you and what they do on the website, what they do with all of the with your services and so on. So in this case, it could be that has the person logged into online banking in the past month, or it could be has the person made a transaction in the past 3 months. So it's a time frame and a certain action that you're looking for in that time frame, and that way you classify every person as an active or inactive member. And in this case, we won't go into detail what exactly this means. We're actually just given this variable, and that's the beauty of logistic regression. You can throw it in, you can see if it actually affects your logistic regression, and then you can, when you're reporting, then you can dive deeper into what exactly it means, and maybe we should adjust the definition. So we'll put it in. Estimated salary. Based on the person's balance and age, perhaps, maybe industry they work in, the bank is able to estimate the salary of the person, and it's provided us this information. So let's put that in. Has the person exited or not? That's our dependent variable. So we're not going to touch that. Now, in terms of gender, we have to select the baseline. So the variable that we don't include in here will be the baseline. And I suggest we select male as the baseline and just insert the female dummy variable into the regressors. That way, whenever female is 0, it's implied that it's male, the person's male. If the variable female is 1, that means that the person is female. And for countries, we'll select France as the baseline, and we'll put the other 2 into the regressors. So you are welcome and free to choose your baseline here with dummy variables. However, if you want to see exactly the same p-values and the same coefficients as you will see in this video, then I suggest that you select the same baseline. So put female, Spain, and Germany into your regressors and leave out male and France. Once again, whatever you choose won't affect the ultimate final result. So your scoring and how the model works and so on, these are just dummy variables. But for the sake of training, you could copy what I'm doing. So I'm going to put show p-values here because we don't want slopes at mean, we want p-values, and I'll click OK. Whoa, that was nerve-wracking, wasn't it? Our very first geodemographic, first iteration of our very first geodemographic segmentation model. So here we've got all our variables, our independent variables, their p-values, we've got some stats on the model, some confusion matrix. So this is all exciting. We've got a lot of variables here, and we won't go through the coefficients right now because we still have to build the model. Right now they don't mean much because some of these variables will be eliminated through our backward elimination process. And we will commence the backward elimination in the next tutorial. I will show you exactly step by step how to do everything and how to track your changes. There's going to be lots of steps. This is the real deal. We're building this thing. I look forward to seeing you next time. Glad to see you back here. Today we are commencing our step-by-step elimination. And as I mentioned, there will be a lot of steps, so prepare yourself for this. This is going to take a while, and we're going to be really diving into creating a proper, robust logistic regression. So let's get started. This is our first iteration that we did last time. Once again, we're not discussing the coefficients right now because a lot of these variables are going to be eliminated. The coefficients are going to change, p-values are going to change, everything's going to change. Then we've got over here stats around the model. So what we are looking at is adjusted R squared. We want to see that with our steps, is it going to improve or is it going to deteriorate? And that will help us keep track of whether we're doing the right thing every single time or not. We've got our accuracy rate here, 81%. We can also look at that and see if it improves or drops off as we remove variables. Here you've got your confusion matrix, so you can see a few type 1 errors and quite a lot of type 2 errors. So those are false negatives when we said they won't leave, but they actually left. And so as we go through this process, we're going to be trying to improve the parameters and statistics of this model, but most importantly, get rid of the variables that don't have a significant impact. And at the bottom, we have a message from Gretel actually telling us that excluding the constant, the top one over here, p-value was highest for variable 18, Spain. So there it is actually telling you which p-value is the highest. Here you can see 0.6181. And it is indeed the highest out of all of them. Why does Gretel tell you that? Well, that's because Gretel is smart. It already knows what you are probably going to do, and that is the backward elimination method. And it knows for the backward elimination method, you need the highest p-value. As you remember, we take the highest p-value, we exclude it from our model if it is greater than our threshold, and then we redo that step again, looking for the next highest p-value. So that's what we're going to be doing right now. Let's get straight into it. I'm going to move this model over here because we're going to have a lot of them, and I'm going to create a new one. So we're excluding Spain, right? Limited logit binary. Let's find Spain and get rid of it. Okay. So there's our second iteration. And here you can see Gretel is telling us variable 18 has the highest, has credit card. Let's have a look at that. Has credit card, 0.44. That is greater than our threshold, so let's exclude that as well. It's going to start taking up some space. Limited logit binary. And we want to get rid of has credit card. So meaning that living in Spain, that's right, let's go through them. First one was that if you live, the baseline is France, right? So then we have Spain and Germany. We have a dummy for Spain and we have a dummy for Germany. The fact that this one is significant and this one is not, what does that mean? Well, that means that people who live in Germany are substantially different in terms of their probability to leave the bank to people who live in France. Whereas people who live in Spain, because this variable is not significant, what that means is people in Spain are as likely to leave the bank as people who live in France. So all other things equal, if you take 3 people, one from Germany, one from France, one from Spain, then the person from Spain and France, they're going to be as likely to leave the bank. So they'll have the same likelihood to leave the bank. Whereas the person who lives in Germany, because this variable is greater than 0, that person will have a higher likelihood to leave the bank. So that means that perhaps maybe there's a competitor in Germany that is taking all of the people, or maybe the departments in Germany are not performing as well, or the customer service is not as good, or the product that was rolled out in all of these regions, it didn't succeed for some reason in Germany. So something is going on there. And that's what we did. We took out Spain because it's the same as the baseline as France, but we left Germany because, as you can see, it's very significant. Next step, what we're doing now is we're taking out credit card, right? So let's have a look here. Has credit card. As you can see, it's got a coefficient, but before you look at the coefficient, whether it's positive, negative, small, large, always look at the p-value. If the p-value is is not in your threshold and is, like in this case, very far from your threshold. Our threshold is 0.05. Here it's 0.44. So that means it's not a significant variable. That means that we can't say with confidence that this effect is predicting anything. So what we're doing now is we're taking this variable out, and in terms of logic, what that means is that people who have credit cards are not either less or more likely to stay with a bank. It doesn't matter if you take two people and hold everything else equal, then whether or not that person, one person has a credit card with the bank, the other one doesn't, then they'll have the same likelihood or probability of leaving the bank. So that's why we're taking out has credit card, and I think I've already taken it out, right? Yep. So let's click OK. That's our third one. Now let's see where we're up to. Next one is estimated salary. So we need to remove this variable because it's not significant. It's the highest p-value, and the p-value is above our threshold. Why are we removing estimated salary? Well, there could be a lot of reasons. For instance, it actually doesn't affect how likelihood of people leaving or not. Or another reason is that it could be calculated incorrectly, that the algorithm that calculates estimated salary might not be the best one. And therefore, we can see that this variable is not having any influence. So maybe we can investigate that further later on, or put that into our report that estimated salary didn't have an effect. However, if you did expect it to have an effect, then perhaps review the formula for estimated salary. So let's run another one. Binary, estimated salary, take it out. Okay. So, by the way, we should be looking at our R squared. So here you can see 0.1507, 0.1509. It went up, right? That's good. Then here you can see 0.1509, 0.1511. Good, it's going up. As you remember, when R squared increases, that's good. The models these variables fit the model better than these variables. And also you can see that the accuracy is actually going up as well. So here we got 81.1%. Here it was only 81%. That's also good. And now what do we have? We have adjusted R squared 0.151197. So it went up a little bit, and accuracy actually went up a little bit as well. So that means we haven't excluded a variable that we shouldn't have excluded. Good. So what are we excluding this time? As you see, Gradle hasn't given us any hint on what we should exclude. And what that means is that all variables have a p-value of 0.1 or less, so less than 10% or less. But for us, it's not sufficient because our threshold is 0.05. So let's have a look through these and see if there's a variable that we need to exclude. So first of all, we look for the one with the highest p-value. It's this one, tenure over here, and it's got 0.0873. So that's above our threshold. And however, it's not that far above. So here we got to be careful. This might be one of those variables that we should exclude according to our rule, but in reality does help the model. So that's where our adjusted R squared will help us out. Let's go ahead and see if we need to exclude it. We're going to go limited logit binary, and here we'll take tenure and take it out. Click OK. And now we'll just compare these side by side. So what happened? We took out tenure. Did the R squared go up or down? So 151197, 151106. So it actually went down. What happened to the accuracy? Accuracy was 81.2% and went down to 81.1%. It's not a lot, just 3 people. But so this is not your main criteria. Your predominant criteria should be the adjusted R squared or any other coefficient that you're following over here. So it says that it went down. It didn't go down that much. It went down a little bit. So it's kind of borderline. You can take it out if you like. If you feel that it doesn't have any sense to keep it in. I'm actually going to keep it in because I believe that tenure should be a factor. Because the longer you've been with a bank, right, you develop loyalty over time. So the longer you've been, you should be less likely to leave. And here, that's why we see it's a negative sign. So they're less likely to leave. But the fact that it's such an insignificant variable, what that is telling us is that the bank is not doing a really good job of developing loyalty in their customers. So there's something wrong over there, and that is definitely something that should go in the report, that we were expecting, and from maybe industry standards, benchmarks, that tenure is a good indicator that you're going to stay with the bank. But in this case, it wasn't. So that's basically what we will decide about tenure. We'll leave it in for now, but we'll definitely include a comment or a footnote about this observation. So now I'm going to bring this over here. And as you can see, there's nothing else to exclude because they're all above our thresholds. So I'm going to return tenure. There we go. So this is our model. And if you think that this is the final model, then it's actually not. It's way too early to celebrate. We still have some extra steps, and I will show you some really cool tips and tricks starting from next tutorial. Next time we will talk about transforming independent variables. Should the variables be included in their original form, or should we actually do something with them before including in the model? It's going to be a fun tutorial, and I look forward to seeing you then. Until next time, happy analyzing. We've come a long way in creating our customer geodemographic segmentation model, and in fact the backwards elimination process has already been completed, and we have this output, which is a model with some variables and some p-values that we're comfortable with. And by now you're probably asking, well, what is there else that we can do? Well, actually there are a couple of things, and one of them we will explore today, and that thing is transformation of independent variables. And what does that imply? Well, there is a assumption or suggestion that perhaps the independent variables, they might not be the best fit, or they might not be the best representation of the effects that they are describing in the raw format that they're presented to us. So perhaps we can do something with these variables in order for them to represent the effects even better and therefore make our model even better. And there's a couple of transformations that you can do. And I'm not just talking about changing the scale. That's not a transformation that we're interested in right now. We're talking about very significant transformations. And here are a couple of them that you will be working with if you get very, you start doing modeling quite a lot. You will be working with these following transformations. So number one, or one of them, is the square root of your independent variable. And you can apply this transformation, of course, when your independent variable is 0 or greater. Number two, or another one, is when you apply a power to your independent variable, like squaring it or taking the cube of your independent variable. And number three is taking the logarithm of your independent variable. And once again, here you can only take the logarithm when your independent variable is greater than 0. And these are the most common transformations that you will be applying to your data. And I can't give you a framework that will work in every scenario, because ultimately your transformation will depend on your data, your intrinsic knowledge of the business, what kind of variables you're working with, and many things like that. So a lot of it is actually trial and error. So while you're creating your model, you input a variable in one form, then you input it in another form, and then in another form. So you have some ideas as to which form the variable will work best in, and then you try them out and you see if that improves your model or not. However, what I can do is I can give you one specific example that I've used and a lot of data scientists use quite often, and that way we'll have something to look at and understand how transformation actually works. And moreover, you'll be able to take this away and apply it in your work in the future. So kind of as a starting point, something that you'll right away know why this transformation might need to take place. So let's get started. The one we'll be looking at is the logarithm. I'm going to close this presentation, and in fact, we're going to be taking a logarithm of balance. And I will explain why why this is necessary after we do it. So first we'll create the transformation, we'll apply it to a model, and then we'll talk about why I think this is a good idea to take a logarithm of a balance. So let's go ahead and do that. In order to create a transformation Gradle, right-click in your working space and select Define New Variable. Here, we're going to type in first the name of the new variable, so it's going to be log_balance, and then we'll put an equal sign and we'll say the formula. The formula is going to be log, so smaller case l, then 10, because we want a logarithm with a base of 10, and then we will say balance. But we can't just leave it like that because we know we have 0 balances in our data, so we're going to add a 1. And a lot of my colleagues here will critique me for adding a 1 to the balance because it's kind of an arbitrary thing to do. There are other approaches. Another approach would be to split your balance variable into 2, and whenever balance is equal to 0, then you'll have a flag, kind of a dummy variable that will signify that. And whenever balance is not 0, you'll take a log 10 of just balance. I find that it's a more complex approach. I think that for us it'll be sufficient to undertake this approach. And moreover, I believe that this approach is completely valid when you're building models. You're totally fine to use this approach in order not to overcomplicate things, and you will you should still get very good results just as you would with the other method. So we're going to click OK, and that will create our variable over here. And now what we want to do is we want to replace our balance variable with this new variable. And I say replace because ultimately we shouldn't keep both of them in, since that can lead to effects of multicollinearity, and that can break our model. Basically, we'll have correlated variables, independent variables in there, and that's not a good thing to have. So we're just going to take log balance and we'll put it in instead of balance. And now we'll just rerun this model. And now let's put them side by side and compare. So what you will notice here is that balance, it had a very small coefficient, about 2 times 10 to the power of minus 6. Now log balance has a good coefficient, it's about 0.06. So we could have easily corrected this problem by changing the scale of balance. But what we did, we actually transformed the variable, and let's see how that impacted our model. In terms of adjusted R squared, you can see that here it's 151197, here it's 151006. So it actually went down a bit, meaning this model is a bit of a worse fit. And at the same time, you can also see that the accuracy went up a little bit. But once again, accuracy is not the defining factor for us. We do see that the R squared has dropped a bit. And nevertheless, I prefer to keep the balance as log balance, and you won't always see that R squared drops. Sometimes this will be a great transformation and will actually increase R squared. But let's have a look at why I think that log balance is better to have as a variable than just balance. I'll bring up another slide to explain this. To start off with, let's look at the raw balance variable. And let's say it's measured in thousands of dollars. Then a 1 unit increase in balance means $1,000 on top of the existing balance. So let's look at 2 scenarios. Scenario 1, when you balance it, we want to understand what the effect of a 1 unit increase is for a $1,000 account. In that case, a $1,000 account goes to a $2,000 account. So it basically doubles. In scenario 2, we want to understand what the effect of a 1 unit increase is for somebody who has $10,000 in their account. In that case, the account goes from $10,000 to $11,000. So it's nowhere near doubling. It's only a 10% increase. And the greater your balance is, your starting balance is, the less significant will that 1 unit increase be. And that is the key point. So now let's look at the logarithm of balance. Logarithm of balance, if there's a 1 unit increase in this transformed variable, then what that means for the actual variable is that it increases 10 times. So in scenario 1, your starting balance was $1,000. Your new balance after a 1 unit increase is $10,000. In scenario 2, your starting balance was $10,000, and now your new balance after a 1 unit increase is $100,000. The second approach here, which is in green, has a much more consistent effect than the first approach, which is in red. Why? Well, because in the first approach in red, as your starting balance is the balance that you're looking at, or the person that you're trying to segment, as his balance gets greater and greater and greater, then the effect of a 1 unit increase becomes less and less and less noticeable. And therefore, we can't equally segment somebody who has a balance under $10,000 and somebody who has a balance of $1 million, because for them, this 1 unit increase will mean absolutely different things. Whereas the approach in green, it has the same effect on any time, on any person, regardless of their starting balance. It's always a 10 times increase. So a 1 unit increase has a consistent increase in the balance variable, which is 10 times. So whether your balance is $1,000, it goes to 10,000, or whether it's $10,000, it goes to $100,000. So regardless of who we're segmenting, we can say that the effect of a 1 unit increase in the new transformed variable is consistent throughout our population. And that is much more powerful because that allows you, it doesn't restrict your logistic regression. It doesn't just focus on one part of your segment. It can be applied across all of your population or all of the observations that you have equally. And that's why personally I believe that when it comes to balances, especially when it's balances of people on their accounts or their incomes and so on, it is a good idea to at least experiment and see what will happen if you transform your balance or that monetary variable into a logarithm of that monetary variable. So that's our basic transformation. Once again, that's just one example. Through your data science career, you will get to work with many more, but do keep this one in mind, and it will always be a good starting point for you when you're investigating transformations. Last time we looked at transforming variables, and we ended up with this log balance variable, which we are now using in our regression instead of the balance variable. So I'm just going to put this to the side, and what we're going to talk about today is creating derived variables. The concept is very similar to transforming variables, but the nature is a bit different. What we're doing when we're transforming variables is we had an effect, but we thought it was misrepresented by the variable. We wanted to contrast it and maybe represent it more significantly or less significantly by transforming that specific variable. Whereas when we're creating derived variables, we're creating representation for new effects that are currently not illustrated by our data. And let me explain through an example. So here we've got a column which is balance and a column which is age. And it is normal for balance to grow with age. It doesn't always happen, but generally, the older a person gets, the more balance they will have on their account because they accumulate wealth over time. However, there's also a different effect where different people accumulate wealth differently. And somebody who is in their late 50s might have a great balance, but somebody who is in their early 30s might have a very similar to that person balance, even though they're younger, just because they're more successful at work, they're more ambitious, they maybe save better, they have different financial strategies or goals. And because we're mixing everything up together and we only are looking at balance, those two people will get mixed up, and in a way they'll be regarded in a similar fashion. But what if we want to separate those effects? So we want to separate people who accumulate balance over time naturally from people who are actually determined to save up a balance or to grow their balance, and therefore they are able to do it at an early age. And also, we might want to separate people who are the opposite, who are old but have a low balance, and maybe they're at risk of defaulting, or maybe they are banking with somebody else. And so there's lots of different effects in that are just getting masked by the fact that we're treating everybody just based on the balance. So in this way, in this sense, there's a very popular method to create a variable which represents the speed at which people are accumulating wealth. And that is by taking balance and dividing it by age. So that's exactly what we're going to do now. We're going to right click and define new variable, and I will call it wealth accumulation. And we'll just take balance and divide it by age. That's as simple as that, because we know that age is not a zero ever. And there we go. That's our new wealth accumulation variable over here. So what we can do now is we just can include it in our regression. We'll go to model, logit, binary, and find our new variable, and let's just put it into our regression. And we'll click OK. And now let's compare it to what we already had. So what happened here? Well, first thing that we can see is that there's our variable, and it's actually got a negative sign, but it doesn't really matter what sign it has because it is not significant. And another thing you'll notice is that the r squared, what happened to it actually decreased a little bit, and our accuracy decreased a little bit. So adding this variable is not a good thing for this specific model. However, what we're not taking into consideration right now is the fact that there might be some collinearity effects, because wealth accumulation log includes balance, which is in log balance, and age. So basically what that means is that this variable might be somehow, or these three variables are correlated, and by including them in the model, maybe we are actually causing damage to the model, and therefore one of them has to be excluded. So effects like that of multicollinearity we will talk about in the next tutorial when we're checking for multicollinearity using the VIF method. But for now, what I wanted to say is that sometimes you might want to include a variable like that, balance over age, and you might have other ideas for creating new variables. You could take tenure and divide that by age, or understand, you know, the difference between some variables. You could even create a variable which is like a flag, like whether a person has a zero balance or doesn't have a zero balance. So you might want to try that. That might work well in this data set. Different types of variables. So anything that comes to mind. And also, like I said, with transformations, there's a lot of business knowledge involved here. It's actually, in derived variables, it might be a bit easier than transformations because you don't have to know whether you need to square a variable or take a logarithm or square root out of it, but you can somehow assess effects. Maybe, for instance, if you're doing some modeling for a manufacturing plant, you might know that it's not about how much oil you put into the machines, but it's how much oil per square meter of something that you put into the machines. And you might know that you need to actually, these metrics are used by the engineers, so why don't I put it into my regression and things like that. So your domain knowledge will help you identify these derived variables that you need to create. So I just gave you an example here. That's how you do it, and then you just include it in your model. And in the next tutorial, we will have a look and see how you can also check for multicollinearity effects to make sure you're not breaking a model. Okay, so today we're talking about multicollinearity effects. As you recall, last time we created a new variable, which is a wealth accumulation, which basically equals balance divided by age, and we included it in our model. And what we can see right away is that it doesn't have any significance. However, that sometimes can happen when you have multicollinearity in your independent variables. And what that means is that they're correlated, and therefore, as we know, it's not a good thing when your independent variables are correlated. It can cause for your model to break. So wealth accumulation, balance, and age, or in this case log balance, are all linked because wealth accumulation is basically balance divided by age. So how do we check if there is any multicollinearity present in our model? Well, there's a very simple step, a first step, which is to use the variance inflation factors. And to get to that in Gradle, you just have to go to your model, click test, and click on collinearity. And as you can see here, we've got a new screen that popped up. It's got variance inflation factors, and it's got some basics information for you here right away. Minimum possible values 1, values over 10 may indicate a collinearity problem. So here you can see that log balance and wealth accumulation actually have a 5.8 and 5.7. Now, that's not over 10, but that's already greater than the rest of the variables. So it's indicating that something might be going on. So what else we can do right now is we can rerun this model, but we'll take log balance out and see what happens to wealth accumulation. Let's go to model, limited, logit binary, and I'm going to simply take wealth accumulation out of the log balance out of the model and rerun it like that. So I'm running out of space here. I'll put it down here. So we're comparing this to this. Here you can see that wealth accumulation doesn't have any significance. Here you can see right away it became very significant, and it even changed its sign. So that is always interesting. Here you remember log balance was positive. The greater somebody's balance, the more likely they are to leave. Here, log balance was positive as well, and the coefficient increased. Wealth accumulation had a negative sign, but it was insignificant. We didn't care about the sign. But now it became significant and has a positive sign. That is a good indication that perhaps what was happening is that log balance and wealth accumulation, because they're correlated, the regression model was giving them opposite signs so that they would negate each other out. And don't forget that this is actually times 10 to the power of minus 5. So, well, doesn't really affect our conclusion. But anyway, so there is a chance that because they're correlated, they were getting different signs. And as soon as you excluded one of them, this one got an opposite sign. It switched its sign and also became significant. That's a good indication that there is some sort of correlation. If we go to tests again and go to collinearity, now you see that everything is below 2. So wealth accumulation dropped its collinearity. Okay, that's interesting. So what we can do now is, in order to explore the effects of collinearity even in more detail, what we'll do is we'll create another variable. So for now, I'm just going to put all of these here. You can see how it's growing. Very steadily it's growing. And we'll talk about this more later, about manually creating models, or in the summary for this section. But as you can see, we're doing a lot of work and a lot of thinking, and we're using business knowledge to make corrections to the model and things like that. So something a machine can't really do, not at this stage anyway. So that is important. I just want you to remember this picture mentally when we talk about models, the way we created the model in the summary for this section. Anyway, moving back to what we're doing now is creating a new variable. Let's create a variable which is a log of your wealth accumulation. Define new variable, log underscore WA for wealth accumulation equals, so it'll be the same, log 10 balance divided by age plus 1, because balance can be 0. Looks good. All right, there it is. So now what we want to do is, how about we include this variable along with log balance? Just like we had here, we had log balance and wealth accumulation. How about, just to amplify the effect, any possible effect of correlation, we'll include these two because they're more similar than wealth and log balance. These two are way more similar, and that way we'll be able to explore correlation a bit better. So let's go to logit binary, and we'll take out wealth accumulation, and instead we'll include log balance and log wealth accumulation, and we'll click OK. And now let's look at what we have here. So here you can see that both log balance and log wealth accumulation are significant. Very interesting observation, right? So they're both significant variables. They both have a impact or have association with the independent variable, a dependent variable which is exited. However, again, you can see that they have different opposite signs, right? So one is improving. So one is actually means that people are more likely to exit. One is saying less likely. Another thing that you might want to notice is that back here, log balance had a positive sign. Now it has, still has a positive sign. So log wealth accumulation, though, has a negative sign. So here, wealth accumulation had a positive sign. Here, log wealth accumulation has a negative sign. So let's go ahead and check for our, what are we checking for? Collinearity over here. So here you can see that the VIFs for log balance and log WA are through the roof. They're not just over 10, they're well over 10. They're 700 plus. So that is the model screaming at you, saying that you have included two variables that are basically the same thing, and this is very, very bad for the model. It's pretty much breaking it. So we want to definitely exclude one of them. When you see something like that, you need to exclude one of the variables. And in this case, we're going to exclude log WA because in our scenario, log balance is, I believe, better. But we can still explore. Like, so if we want to understand which one we want to exclude, how about we just take log balance out, leave log WA, and now I go to this model which had log balance. No, the one that that didn't have WA at all. So this model, right? And here we can just compare the two. This one had 151,006 and this one is 15087. So R square went down when we replaced log balance with log WA. And yeah, so what does accuracy do? Well, it increases a little bit, but in this case, so there's no point in replacing balance with a more complex variable. We just keep balance. So there we go. Put this one here. Dangerously running out of space. All right, where is my model? So log WA out, log balance in. That's checking for multicollinearity using the VIF. Last time we checked for collinearity effects using variance inflation factors, and today we will look at using the correlation matrix. By the way, I just wanted to say that we're not going into detail, into the formulas, into the whys and the hows of these methods, simply because I just can't fit everything into this course. I just want to show you the methods that exist and how you can apply them in practice, because I think that's the most important part. And whenever you do need to learn the nuts and bolts of what VIFs are or how the correlation matrix is constructed and so on, I believe there's lots and lots of ways you can learn that. But right now we're focusing on the practical application of these things. So we want to look at the correlation matrix. That's another way to investigate any kind of possible collinearity between your variables. To create a correlation matrix in Gradle, you need to go to Data, and we'll talk about it just now once we've created it. So view correlation matrix, and then select your variables. We want to check log WA, wealth accumulation, log balance, and what else? Age. Let's look at those. So I just put in 4. You can put in more, but I just put in 4 because this window, once you put in more, it goes to the next line and it doesn't look pretty. So what can we see here? A correlation matrix is basically a table which is half filled. Is half filled because this other part over here that's not there would have been a mirror image of that one. And in each cell you have a number which tells you about the correlation of the two variables, the one that's at the head of the column and the one that's at the head of the row. So if you cross these rows and columns, then say the correlation for log balance and log W is 0.9984. The correlation for wealth accumulation and age is minus 0.2463. And correlation can be between -1 and 1, and is basically a parameter that tells you about how in line these variables are. So when one variable changes, how similar does the other variable change as well. And the more correlated they are, the higher the number will be. So basically, correlation of 1 is ideal correlation, and that's why you can see here that age with age is ideally correlated. Any variable with itself is always going to be ideally correlated. And then 0 is no correlation at all whatsoever. So for example, here you can see age and log WA are very, they have very, very low correlation. And -1 is ideal anti-correlation or negative correlation, which means that they're still correlated, but they change in the opposite ways. And so basically, when you look at the correlation matrix, you should forget about the minus or plus, just look at the absolute value. Here you can see that right away, log balance and log WA have a very high correlation. They're pretty much behaving as the same variable. So that is very bad for our model. Then we have log balance and wealth accumulation. This is why previously we saw that there were some issues because they are also very well correlated. Age, this is an interesting one. Age is not very well correlated with log WA, even though it's part of that calculation, but it is quite a bit correlated with wealth accumulation. So as you can see, the logarithm changes the variable and makes it less correlated with that variable, which is part of the calculation. Basically, here, what you're looking for, a rule of thumb is anything above 0.9 is very high correlation, and you have to do something about it. Anything above 0.7, also very high correlation. So not very high, but I would say just high correlation. Also suggested to do something about it. 0.5 to 0.7 is moderate correlation, perhaps worth looking into. 0.3 to and higher, that's just like low correlation, and perhaps you could leave that in the model, but try to avoid those kind of things. And finally, anything below 0.3 is low correlation, and as you get closer to 0, there's pretty much no correlation left. So that's your rule of thumb, but it also ultimately depends on what variables you're looking into, what your ultimate goal is, and things like that. So that's how you read a correlation matrix. And you're probably wondering by now, why is it bad for a model when you have multicollinearity in your variables? It's kind of intuitive when you think about it, that you're pretty much double counting. Like here you can see, even though they're different variables, you're double counting a variable in the model. But why is it bad? Like on an intuitive level, I think it's worth covering this question. So I'll bring up the formula for logistic regression. So we're looking at this bottom one here. You can see that you've got lots of variables here. So let's say that x1 and x2, just like log balance and log WA, are very highly correlated. Then what happens is, when the regression is trying to build this model, it's tweaking x1 a little bit and trying to hold everything else constant to see how x1 affects the probability on this left side. And based on like lots and lots of those iterations, it will find the ultimate b1 coefficient for x1. Then it does the same thing for x2. It tries to hold everything else constant and tweaks this a little bit, a bit more, a bit less, and tries to find the ultimate coefficient for b2 that will explain how x2 is affecting what we're observing, the changes on the left, and so on. And then gets to xn, the same thing. It holds everything else constant as much as it can, as it possibly can, and tweaks this one a little bit to the left, a little bit to the right, looks at how the variable is changing for those observations, and then tries to find the b coefficient that best explains this this association between the two. What happens is, when you have two variables that are correlated, say x1 and x2 are correlated, well, the correlation simply cannot find the correct coefficients for these variables, because whenever it tries to assess x1, it's trying to investigate how x1 is associated with the dependent variable. So what it's doing is trying to hold everything else constant and just tweak x1 a little bit to the left, a little bit to the right, to see how this will change. Well, whenever it tries to do that, this one also changes. So as long as you change this one, and this one will change. Whatever it tries to do, it will always see that. So it cannot assess the individual effects of the variables on your dependent variable. Same thing when it gets to x2, it tries to hold everything else constant and tweak x2 a little bit to the left, a little bit to the right, and still it fails, because x1 will always change. Its change will always be aligned with the change of x2, and it just doesn't have those. It just doesn't have the opportunity to assess the individual effects, and that's what happens. That's what I mean when I say that multicollinearity breaks your models. It doesn't allow them to be constructed properly, and that's why you want to get rid of any multicollinearity effects in your independent variables. So that's a very intuitive way of looking at multicollinearity and why it's bad. I hope that's helpful. It's quite a complex thing, and I guess it's important to get your head around it. So I hope this my intuitive way of understanding it helps you understand it a little bit better as well. Last time we talked about the correlation matrix and also the intuition behind multicollinearity. And today we're going to finish off this whole section with a conclusion. But before we do that, I would like us to save the model, because we will be using it in the next section of the course. So I'm going to close this. We don't need the correlation matrix. Here, in our final version of the model, just make sure it's the one that includes log balance and doesn't have any wealth accumulation or log of wealth accumulation. So basically, if you use the same variables as me, then it should look like this. What you need to do is go to File, Save As, I'm going to save it as an RTF, so a Word document. Click OK, and then just select a folder. I'm going to save mine in my standard folder for this section. Save. Oh yeah, definitely a name. So what I'm going to call it? Let's call it, in my case, model 20, code name model 20. Okay, save. And now if I go to my folder, you'll see a new document here. So this is my model. It's got this thing needs to be fixed up. So basically save the final results, and that will allow us to, when we need to, recreate the model, because we'll know which variables went into this model. And so we're just gonna save that. Okay, so that's ready. And at this stage we can say, thank you, Gretel. It really helped us out. What I would like to do now is move on to our recap for the section. So just close Gretel. Yep. Oops. There we go. So there is our recap. Section recap. What did we learn in this section? In this section we learned, number one, what a geodemographic segmentation is. We talked about grouping your customers by similarities of their behavior and using prior knowledge to predict any future trends and basically predict future behavior, so you can anticipate it, so you can preempt it, maybe do something about it if required. So examples are like the example we looked in here is churn modeling to understand when your customers are going to leave and who's more likely to leave, who's less likely to leave. There's lots of different applications of demographic segmentation. Number two is we practice building a real segmentation model, which was great fun. We had real variables. So it was variables that you would find in a bank, such as balances, credit card, yes, no, what the tenure is of the customers, ages, and so on. So something that is very, very like the real world. It's a model like that, you would actually build it in the real world. And we went step by step through everything and understood how to exclude variables, how to see that our model is still robust. And we went the whole journey from start to finish, which was a great experience in my view. We also learned how to transform independent variables. So that's an important part. If you think that an independent variable is misrepresenting the effect just due to the nature of the effect, because it shouldn't be represented by this variable in its raw format, but it should be squared, or there should be a square root or logarithm or something. And we looked at an example of taking logarithm of balance plus 1. We learned how to create derived variables, so new independent variables, and you would need to do this in cases when you have certain business knowledge around how variables are combined to achieve the desired outcome. Very, very powerful technique as well. We understood the intuition behind multicollinearity and why it is basically bad for your models if they're correlated independent variables that you're inputting into the models. We also looked at how to check for multicollinearity using variance inflation factors, and also how to read the correlation matrix and basically check for multicollinearity effects that way as well. So those are two techniques that will allow you to get rid of or preempt any multicollinearity in your models and act upon it in a timely manner. So two things that I wanted to mention. First of all, of course, this is not your 100% coverage of everything that you will ever do when building a model. However, what we looked at today represents approximately 80% of any kind of techniques that you will be using to create a model. It's usually this standardized approach. A lot of it is trial and error, experimenting with derived and transformed variables, understanding which variables to include, exclude, and so on. Of course, there are little other things that you will learn along the way. You will pick them up as you create more of these. But what I gave you here, this blueprint, this is an 80% base of what you will need in modeling. And the second point is tools. Let's face it, Gretel is not going to be the ultimate tool that you're going to be using. However, any tool that you'll be using will have its own way of showing you the VIFs or the correlation matrix or running a binary logistic regression. So those things you get accustomed to quite easily. And once you know them, the fundamentals are the same. And what was important about this section is for you to grasp the fundamentals, to understand how exactly these things are done and why they are done in this way. And so once you've learned that, you can move on, and wherever you apply this knowledge, you're going to be successful. Thank you for staying with me through this section. It was fun, exciting. In the next one, we're going to assess our models. I will show you how to read the cumulative accuracy profile. We'll talk about the accuracy paradox, and I will give you a template, an actual Excel template for you to take home and play around with that will help you assess your models. I look forward to seeing you in the next section of the course, and until then, happy analyzing.
Welcome back. Now that we've built our model, in this section we're going to talk about how we can assess it. And we're going to talk about the cumulative accuracy profile. I will show you how to build this curve, and I will even give you an Excel template for the capped curve, which you can take away and which will save you lots and lots of time. Also in this section, we will learn how to apply our model to test data. We will understand the difference between training and test data, and we will learn how to avoid overfitting our model. So it's going to be an interesting section where we will learn the steps that you need to take after you've created the model. And let's jump straight into it.
Here I've got a confusion matrix, and this confusion matrix has 10,000 records in it, and it represents scenario number 1, which we'll be looking at. As you can see, this model has made 150 type 1 errors and 50 type 2 errors, but overall is predicted quite a lot correctly. Now let's calculate the accuracy rate in this scenario. The accuracy rate is the total correct divided by the overall total, and it's 9,800 divided by 10,000, which is 98%. Okay, great. But what we're going to do now is we're going to tell the model to stop making predictions whatsoever. We're just going to abandon the model completely, and we're going to say that from now on, our prediction is always 0. We're always going to predict that the event is not going to occur. So basically what will happen to the confusion matrix is these records will move from the right column to the left column. And our new confusion matrix will look like this: 9,850, 150, and then nothing in the predicted column where we predicted that something will occur. And of course that moves against all logic, right? Why would you abandon a model? But let's calculate the accuracy rate in this scenario. Scenario 2, accuracy rate has the same formula. In this case, accuracy rate is 9,850 divided by 10,000. So it's 98.5%. The accuracy rate went up by 0.5%. And as you can see, what we did is we just completely stopped using a model, but the accuracy rate went up. And that is why you should not base your judgment just on accuracy rate, because things like this can happen. And even though obviously you're not using a model anymore, which means that you're not applying any kind of logic into your decision-making process, your accuracy rate is going up. So it's misleading you into a wrong conclusion that you should stop using models. And this effect is called the accuracy paradox. And starting from the next tutorial, I will show you a much better way to assess your models using the cumulative accuracy profile. I look forward to seeing you then. Until next time, happy analyzing. In the previous tutorial, we talked about the accuracy paradox. Hopefully now you see why we need more robust methods to assess our models. And today we're talking about the cumulative accuracy profile, which is in fact one of those methods. Let's look at a scenario. Let's say you're a data scientist at a store which sells clothes, and your store has a total of 100,000 customers. I'm placing that number on the horizontal axis. And you know that from experience, whenever you send an offer, like an email to all your customers or to any random sample of your customers, approximately 10% of them respond and purchase the product. So I'm going to place 10,000, which is 10% of the total, on the vertical axis. And so what we're going to do is we've got an offer that we want to send, and we want to see how many customers are going to purchase our product if we send it off. So if we send it to 0 customers, obviously we'll get 0 responses, right? What do you think will happen if we send it to 20,000 customers? How many do you think will respond? Well, because this is a random sample and we know that about 10% respond, so we would say about 2,000 would respond. Fair enough, right? If 40,000, if we send to the offer to 40,000 of our customers, then about 4,000 will respond. 60,000, 6,000, 80,000, 8,000, 100,000, then 10,000 of our customers should respond. And this is a random selection process. So here we can draw a line which will actually represent this random selection. The slope of the line equals to that 10% that we know that respond on average to our offers if we just send them out like that. Now the question is, can we somehow improve this experience? Can we get more customers to respond to our offers when we send out our letter? So basically, can we somehow target our customers more appropriately so to get a better response rate? And how about, instead of sending out these offers randomly to, say, a random sample of 20,000 customers, how about we pick and choose the customers we send these offers to? And how do we pick and choose? Well, to start off with, let's build a model just like we did in the previous section. Basically a customer segmentation model, geodemographic segmentation model, but which won't predict whether or not they will leave the company. It will actually predict whether or not they will purchase a product. It's a very similar process. Actually, in fact, it's the same thing, because purchased is also a binary variable, yes or no. And we can also run the same experiment. We can take a group of customers before we send out the offer and then look back and see who purchased, were they male or female, which country were they in, what age predominantly were they browsing on mobile or were they browsing via computer. And all of these factors, we can take them into account, measure them, put them into a logistic regression, and get a model which will help us assess the likelihood of certain types of customers purchasing based on their characteristics, so their geodemographic status and other characteristics. And once we've built this model, how about we apply it to select the customers we will send the offer to? So what the model will tell us, just like in the example in the previous section where female customers of a bank whose favorite color is red, they're most likely to leave the bank. Here we'll have a similar result. It'll say perhaps male customers in this certain age group who browse on mobile are most likely to purchase a product. It will tell us something, or it'll actually rank our customers. It'll give them a probability of purchasing our product. And then we can use that probability to actually contact our customers. So, of course, if we contact 0 customers, we'll get a 0 response rate. But if we contact 20,000, we'll probably get a much higher response rate than just 2,000, because we're picking out the customers that are at the highest risk of accepting this offer. We know from their previous behavior or from the previous behavior of customers similar to them that they have a 90% chance or an 80% chance of purchasing this product. And we will go for them first. We will put them at the top of our list of people who we contact. Then when we contact, let's say we contact not 20,000, but 40,000, our response rate will be higher than 4,000, which we get in the random scenario. If our model is really good, then by the time we're at around 60,000, so just over half of our total customer base, we're already getting to that 10,000 mark. So we know that 10,000 people will respond in total. There's no way we can get above that, because that's just the response rate. If we contact everybody, it'll be 10,000. But we're getting very close already. So even at 60,000, we're already at 9,500 respondents or purchases. We could actually stop here. We've already pretty much contacted everybody. But if we want to contact more, if we send it out to 80,000, we're getting even closer to 10,000 responses. And if we contact 100,000, we will still be back at our 10,000 responses. So now let's draw a line through these crosses. So what you see, this line here is called the cumulative accuracy profile of your model. And as you can imagine, the better your model, the larger will be the area under this line. So the area between the red and the blue lines, it will increase as your model gets better. And if your model is worse, then this red line will be closer to the blue line. So it'll be closer to random. The next step we want to do is convert these axes from absolute values to percentages. So they range from 0 to 100%. And this is how the cap curve is normally represented. Now let's say we ran another regression model, and this time we used less variables, less independent variables, or just because we had less access to independent variables, or we didn't see that there's a multicollinearity effect in a model, or something else that went wrong. And that model, because it'll be worse, this is what its cap curve will look like. And therefore, by plotting the cap curves, you'll be able to compare models to each other and understand how much gain, this is also sometimes called the gain chart, how much gain you get in each of these models compared to the random scenario, or how much gain you get, additional gain you get from switching from one model to the next, or from the green one to the red one, for instance. You're improving your hit ratio, and therefore you're improving your return on investment. So therefore, the red model is better. And this is how we are going to be assessing models. So let's label them. The blue line is a random selection process. Like a monkey could do that. You just pick out random sample and you send the letter, or you just send it to everybody. You get your 100% of respondents. The green line is a poor model. So it's a model, it's better than random, but it's still not as good as the red one. The red one is a good model. As you can see here, at around the 50% mark, we're getting just over 80% responses. That's considered a good model. And there's one more line that you can think of here, and it's this line. This line is the ideal line. And this is what would happen if you had a crystal ball. If you could predict exactly who is going to purchase and contact those people, this is what it would look like. Why? Well, because if you look at that, the place where that spline occurs, you will see that it's exactly 10%. And 10%, as you remember, we know that only 10% of our customers ever purchase. So basically, you're saying that on the horizontal axis, I'm going to take 10%, and each and every single one of those customers I pick in that 10%, they are going to be those that purchase. That means I will go right straight to 100% with this last scenario. This actually took me a while to get my head around when I first heard about it, because I never understood why is there this spline at the top? Why does it break like that? But that's exactly the reason, because you can imagine that you have a crystal ball and you contact in the first 10%, or however many in your specific business scenario customers ever purchase. You contact them right away, and then it's just flat from there, because it doesn't matter how many more you contact, they're not going to purchase. That's just the reality of things. And that is the curves that you can have on a cap curve. If you ever see a model that goes under the blue line, I didn't even draw one here, but if that happens, that's a very bad model. It's basically doing you a disservice if you see the curve under the blue line. And we'll talk about model deterioration further in the course when we're talking about maintaining your models. So that's it for the cap curve. For the introduction to cap curve, we'll be using the cap curve very actively in this section to assess our model. And in fact, we'll actually build two of them, and one for our model and one for our test data. So that'll be very interesting to compare. One last thing I wanted to mention is a note that we have the cap, which is a cumulative accuracy profile, and we have a ROC, which is a receiver operating characteristic. A lot of people get these things confused, and myself included, I used to get it confused. I even tried proving one time a colleague of mine who knew this stuff really well at the time, when I was just learning it, that he was wrong, but that was a funny experience. But they're not the same thing. So cumulative accuracy profile is the one we talked about. Receiver operating characteristic, we won't be covering in this course. It'll be in my advanced course on statistics. It's very similar. It looks similar, and that's why a lot of people get it confused. And actually, I think the other reason is that the ROC curve is in Wikipedia. There's an article for the ROC curve, but there isn't one in English for the cumulative accuracy profile. So it's quite hard to find information on the cap curve just by searching in Google. So maybe you'll be the first person to write a Wikipedia article on the cap curve. Who knows? Maybe. Anyway, I look forward to seeing you in the next tutorial, and where we will be working with the cap curve. And until then, happy analyzing. Hello and welcome back. In the previous tutorial, we talked in theory about the cumulative accuracy profile. Today, we're actually going to practice it. We're going to build our first cap curve for our model. It's going to be an exciting tutorial, and you will learn a very important technique that you'll be able to take away and apply in your future work as a data scientist. The cap curve is important because it allows you to assess models. It allows you to compare models side by side and choose the best one. And it also allows you to assess how models deteriorate over time. All those three are very important elements of the work of a data scientist. So let's get straight into it. I've got the dataset loaded up into Gradle here, and I've already created the dummy variables, and I've created the derived log of balance variable. So actually transformation of balance. And I've actually even prepared the model according to the file that we saved. So I totally understand that this is not the best way to save models in a text file. And other tools like R, SPSS, SAS, and so on, they'll definitely allow you to save your model for future use. And I'm sure there's a way to do it in Gradle. I'm just more familiar with this approach. So what we've done here is just basically copied the regressors, the same ones that we had in our model previously. We've copied them into the new model that we're going to run just now. And I'm going to run this. And here, what you can see is the coefficients. We just have to check that they're the same. So just check some random ones. And then the R squared. So basically everything's the same. Good. We can close this file now. So the model is run. And now what we need is the prediction. We want the probabilities so we can build the cap curve. In order to get the probabilities, we're going to go to analysis, forecasts. We're not going to forecast anything. We're just running it for the same data. And there it is. So that's our exited, the actual value, and the prediction. We're going to save this value, so the prediction. By default, it selects the exited hat name, but that's not exactly correct. The correct name is here's p hat because it's the probability. And the description is forecast of exited probability to be completely correct. Okay, and now we can close that. We'll leave the model for now. So here we've got the p hat variable, and now we want to export it. So we'll go to File, Export Data. We want row number, then we want exited, and we want p hat. That's all we want. Okay, okay. Now select the folder. I'm not gonna overwrite my data. I'm just gonna call it churn modeling forecast. Save. Okay, now we can move away from Gradle and go here. So there it is, churn modeling forecast. And now I'm going to bring up Excel, and this is where the fun will start. Okay, so we're copying churn modeling into here. I'm going to zoom in. First thing that we want to do is right away save it as an XLSX file so we don't lose anything like colors and stuff like that that we're going to be adding. All right, good. Second most important thing is, like, I put the filters on, and now we want to filter by p hat, and we will sort by largest to smallest. Take the filters off. So why did we do that? Well, because remember that scenario, and I'm going to bring up this image because we'll be using it quite a lot. Remember here what we did is we said for the cap curve, and just logically, if we have a model that tells us that these people are the most likely to take up the offer, because look at the probability, 93% chance, 92% chance. If they're the most likely to take up the offer, then we should contact them first. So this is us over here. In the first batch, we're going to have the most likely people. And as we get further away, their likelihood is going to decrease. But we want to get the bang for the buck. So we want to make sure that we reach out to the people that are most interested in this offer. So this, by the way, this is not just a like business focused, very mercantile approach that we don't care about people's feelings. No, in reality, like, why would you want to reach out to people who don't care about your product or who have other better things to do? You want to get to the people who want your product. So you're also taking care of the customer. It's a win-win for everybody. So here, that's why we've ordered it by probability. We want to get to these people first. They are the most likely to take up our offer, and they are the most interested in that offer. So once again, we're trying to create this right now. This is random. This we know how to do. Anybody can do that. Okay, So let's add some rows. Then here I'm just going to put stats because we're going to type in some stats. First thing we want is total exited. So I want to count how many people exited in total. It's going to be the sum, right, of this column over here, or basically of all the ones in this column. So if I just do sum, then I get 2,037 people left the bank. Then total records, let's call it records. This one, let's make some space. This one's going to be count, and you can count exited or you can count the number of rows. So let's count the number of rows. And then we're going to have an exit ratio. So that is we'll go back to the cap curve just now. So total exited divided by total number of records. And I'm going back to the cap curve. Where is it? There it is. So total exit ratio over here, 20%, is, remember that 10% that we were talking about in the cap curve, that the total number of people that will ever take your offer, or in this case, the total number of people that will ever leave the bank, is 20%, or that time it was 10%. So here we're going to change this to a percentage, so it looks better. Okay, good. That's that part done. Now what we want is a few extra columns, right? Maybe let's take out one row. We'll start with a column for just total select. Total select. So if I select people one by one, this column will tell me how much I'm selecting. So 1, 2, 3, and so on. So if I continue this down, as you can see, just telling me how many have I selected so far. If I'm selecting from the top to the bottom, I've selected 10, I've selected 11, I've selected 12, and so on. So here we want a percentage, total select percent. I want this divided by the total records. Don't forget to press F4 to lock it in. Okay, let's save it there. So as you can see, it goes up to 100%, right? That should make total sense. Total select percent. And next we want to, well, let's color these two columns in a nice soft gray. Okay, there we go. The next one is, what if we select at random? So right now what we want to do is we want to build this blue line. How can we build this? Well, let's start selecting at random. Random select, right? By the way, you can copy what I'm doing. It's a good exercise, but I will also give you this template in the next tutorial, I think. Yeah, so you'll get this template. So don't worry if you're not following what I'm doing on your computer. Random select. What do we want to do? We want to select at random. So we're saying this is the number of people that we've selected. So if, say, we select a random 10 people, a random 5 people, how many of them are going to exit? What's, like, statistically, is going to be 5 times, right, the exit ratio. And we'll lock the exit ratio in. So we can copy this column there, right? And go to the bottom, go to the top, copy. And so you can see that 10 people, so 2 will exit. If we select 50 people, 10 will exit. If we select 100 people, 20 will exit. Should make sense, right? At the bottom here we have 2,037 because we've gotten to 100%. We've selected all of them, and so 20.37% have exited. A random select, and let's do random. Random select percent. Right, so this one is going to be just how many we selected divided by the total number of exited. Once again, we need to lock it in by pressing F4. So as you can see, I'm just going to copy it like that. We get to 100%. So let's just go over this one more time. Random select is out of the people we've selected. So if we select this number of people, how many are statistically going to exit? If we select 100 people, how many is statistically going to exit? And then random select percent is the percentage of the total. So I'm going to color this in a light blue. And why am I coloring in a blue? Because the color of this line is blue. And that's basically what we constructed. We're saying as we select more people, right? So this gray over here, let's move somewhere lower where there's, you know, whole numbers, or a bit higher. There we go, somewhere here, I guess. So this number over here is the bottom line over here, or in percentage terms, that's the percentage. So 33%, that's how many we've selected. And the blue is how many of them actually, in this case, purchased, in our case, exited. So if we select 33.74%, then obviously 33.74 of the people that will actually eventually exit will be selected as well, because it's a random selection. So this number will always be equal to that number. Random select. And finally, we want model select. So if we're ordering by probability, how many are we actually getting? How many of the exiters or churners are we hitting? Well, we need to look at this column, exited. And here we need to add this value. So I'm just going to copy. And as you can see, let's go through this a bit. So if we select 10 people, we're going to hit 7 churners, right? If we select 20 people, we're going to hit 14 churners. And the way you can see it from here is that, so this person didn't actually leave. And according to model, we did need to select them. So our model made a mistake there. It's not the best person to select. But then this one did leave and we selected him. Good. Didn't leave, so it stays at 1. Did leave, did leave, did leave, did leave. And then didn't leave, so that's a 0. But what we're comparing is we're creating the red line here. So this line is being compared to the random select over here. So as you can see, by the time you get to 10 people, the random select has only selected 2 people. We have already identified 7 people correctly, right? If we get to, let's say we get to 60 people, random select only gets 12 people. We're already on 39. So let's bring up the curve again. So as you can see, we are taking off. We're moving away from the random. The random is going slowly. It's going in line with the total percent contacted. So it's just a straight line. Whereas we are overtaking, we're going faster. We're finding these people better. Our model is performing. So let's do another one, 100. So here, 100 people were selected. If we take a random 100 people, then of them, 20.37 will be leavers. But if we select these 100 people according to our model, then of them 70 will have left, or we will select correctly 70 churners. So that is like more than 3 times the performance of a random select. And that is exactly what we're after. So that's model select, and this is going to be model select percent. All right, now we want a percentage of the total that left. Don't forget to lock it in. By the way, this thing I'm doing, I'll do it again. If you're not aware of what I'm doing is I'm just copying it. I'm going to this column so that I can go to the bottom with Control down. And then from here, I'm going to Control Shift. And then, so from here, I can go Shift and select many. But if I go Control Shift, it goes to the top. And then I just press Enter. So that is the model select percent. Let's color it in a nice salmon kind of red that I found here. Okay, good. And now let's take this, and this. We'll format, and we'll format it as a percentage. Okay. So this is the red line, this is the blue line, this is the horizontal axis. And you can see that the red line is by far overtaking the blue line, right? 7, so you see how fast this is increasing, how slow this is increasing? I can even press page down, it'll be even faster. See, by the time we've selected 12% with random, with the model we've selected 33. And without further ado, let's introduce the cap curve. All you have to do from here, and you can do the same thing in your template. So the template will take you up to this stage. You just select this, this, and this. And then you go to Insert, up at the top here. You select Line, and you select this first one. And there you go. One thing I will change though is I will change the name of this just to total. Whoops, not that one, that one. All right. Then get rid of this, we don't need it. And there is your cap curve. So that's how you create it in Excel. And in the next tutorial, we will analyze this cap curve. Cap analysis. We've talked about cap a lot, and in fact, we've talked about cap that much that I'm no longer even saying cumulative accuracy profile, because I assuming that you're entirely comfortable with this abbreviation and the whole term and what it means. So let's see how to analyze the cap. As we've discussed, there are three lines that are important on the cap curve. The blue line, which is the random line when you select your samples at random. The red line, which is our model line, and different models will have different red lines, but basically it looks something like that. And the gray line, which is the perfect model, or when you have a crystal ball, when you can select all of the future churners or purchasers or whatever action takers, and you can select them right away on the dot without even selecting one single person that you don't want to select. And so these are the three main lines. And how do we analyze this cap curve? We already know how to build it, but what can we derive? What insights can we derive from here? Well, it's kind of intuitive that the closer your red line is to the gray line, the better your model. The closer it is to the blue line, the worse. So how can we quantify this effect? Well, there is a standard approach to calculate the accuracy ratio. And to calculate the accuracy ratio, you need to take the area under the perfect model or the perfect line, which is colored in gray here and is called the AP. And then you need to take the area under the red line, which is colored in red here, which is AR. And then you need to divide one by the other. So you need to divide AR by AP. And then this ratio that you get is obviously between 0 and 1. And the closer this ratio is to 1, the better. The further it is away from 1 and closer to 0, the worse. However, it can be quite complicated to calculate this area under the curve. Statistical tools can do it for you, but how can you assess the cap curve by just looking at it, so visually? It's not that easy to get this quantifiable metric just by looking at the curve. So there's a second approach, and that's what we're going to discuss now. Let's get rid of the areas, and instead of looking at the area, what you can do is look at the 50% line on the horizontal axis and look where it crosses your model, and then look at where that line, the horizontal line from there, crosses the vertical axis. So basically, how many churners will you pick up, or action takers, or how many positive outcomes are you going to identify if you take 50% of your population? And in this case, we can see it's around 90% or something like that. And just by looking at that, there's a rule of thumb how you can assess your model based on that X number. And here it is. Are you ready? Here we go. So if X is less than 60%, the model is rubbish. Basically, it's not useful at all. You can create a better one. Probably you can create a better one, and you need to try again. If your model, your X is between 60% and 70%, then the model is considered to be poor or average. And by the way, this is my rule of thumb. Other people might have a different rule of thumb, but this is what I go by. If it's between 60% and 70%, it's a poor model, to be honest. Like you can do better than that. If X is between 70% and 80%, that's a good model. That's already where you should be aiming for. Anything above 70%, that can deliver good quality insights to the business and actually deliver value. Anything between 80% and 90%, like we see here, is very good. It's extremely good. If you can get a model over 80%, that is an amazing result. And anything above 90% up to 100, that is just too good. It is too good to believe, and there's one option that you should be very careful here with, is overfitting. If your model is showing you results like 90%, or say if a model is showing you 100%, then the obvious answer there is that one of your independent variables is actually a post factum variable, meaning that it shouldn't be in the data because it's looking into the future. The person who supplied you that variable forgot to take it out, or forgot to explain to you that their credit score actually is turned into 0 after they leave the bank, and therefore everybody with a 0 credit score obviously has left the bank, and therefore your model is picking them up like it's super easy. So if you have 100%, that's definitely something wrong with your variables. Even if you have 90 to 100%, you have to check that there could be some forward-looking variables. The other thing is overfitting. You could be overfitting a model, and what that means is that your model has been so well fit to that specific data set that you supplied it, that when you that it's just heavily relying on the anomalies in that data set. And when you feed it a new data set, like in a month time, or something like not training data, not the data that you trained your model on, and we'll talk about this a lot more actually in the coming tutorials. But so if you feed this model some data that you want to actually predict on, then it will crash. Well, it won't crash. It won't perform as well. It will perform, at the 60% mark or something. So that means your model is overfitted, and be very careful about that. We'll talk about overfitting more. In fact, in the coming tutorials, we will learn how to avoid that problem. And finally, if you can get an X or this parameter to be between 90% and 100%, and you're not using forward-looking parameters, or you're not overfitting, then give me a call, because I might have a job for you. People like that are rare, and I have a lot of headhunters looking for people who can do modeling like that. So definitely keep that in mind. And now, to finish off today's tutorial, we're going to jump into Excel and have a look at our model and see how it compares, how it actually performs on that scale. So we're going to take a line, very simple visual analysis. So there's the 50% line. We're going to drag a vertical line over here. As you can see, it crosses the model at about 80%, so 80.5%. Very good model. So all we have to do now is make sure we're not overfitting it, and then we can start using it. So in the next tutorial, what is going to happen, I will give you the CAP template that I promised, and then after that, we will learn how to check for overfitting in models and learn how to use test data and the differences between training and test data. And I look forward to seeing you then. Until next time, happy analyzing. Hope you enjoyed the previous tutorial on assessing your CAP curve. And today, as promised, we're going to go through the CAP curve template, which I have prepared for you. And I've already downloaded the template. You can get it in the course materials. I've got it on my desktop here. And in fact, I'm actually going to copy it into my project folder. There it is. Copy. There we go. And so now I'm going to get Excel and open up the CAP curve template, and I'll walk you through it. So I've already zoomed in. Normally it's like this, this size. So this is zoomed in, and over here you can see a confusion matrix, which will be populated as soon as you copy in the data, which is always nice to have, like a nice bonus for you over there. But mainly the CAP curve is over here. This is the main working area for the CAP curve. And going from the top, you can see right away total number of exited. That's the total number of successes that you're going to have in this column and column B. So from here downwards. Then total successes, I mean, of course, like ones in your binary outcome for the dependent variable. Then total records, that's the total number of rows you're going to have in your data. Percent exited is the rate at which they exit, so one divided by the other. Row number is basically just required so that you have a row number in here. Then exited is your binary outcome, so your actual, what was actually observed. And p hat is what your model predicted, so the probability that the model predicts for that specific row number to exit, and that's why the row number is in there. And then you've got the gray, blue, and pink, as we discussed previously. So what you need to do, and we'll do this in a second, what you will need to do is you need to copy your data here, and it has to be ordered. So you see this instruction here, and that means that you have to order your data by p hat first in descending order. So the most probable people to exit should be at the top, which makes sense, right? So if you're going to contact them, you're going to contact the most likely ones to perform the action first. And then after you've copied your data in order, in its ordered form, then you will need to populate this bit. So you'll have to delete this row and then just drag this cell downwards. Just this one row, these 6 cells, you just drag them downwards to match the number of rows you have here. So let's go ahead and do all of that. Where's our project folder? And now we are going to look for churn modeling forecast. So that data set that we prepared previously, I'm going to bring up another Excel. and I'm going to drag a churn modeling forecast. By the way, here's a quick tip for you. If you want to bring up another Excel like I did here, quite a few people have asked me this, so actually. Very easy. On your start menu, which I don't have brought up because it's on my other screen, all you have to do is, you know how you click Excel there? You left click to bring up a program in the toolbar. It's the taskbar, in the taskbar. Well, just instead of left clicking it, click it with your middle mouse button. So click it with your wheel, and like I can bring another one, and there's another one. I'm just clicking it with the middle mouse button. And so if you, instead of going through file, open a new Excel and so on like this, you can just bring up as many of them as you want. And, you know, maybe that'll help you out. Maybe that will be a handy trick you'll use someday. Otherwise, you know, all of your tabs, all of your worksheets are in one Excel, and you can't freely move them around like this. I find this is sometimes handy. Anyway, back to our research or analysis. I'm going to zoom in here, and I'm going to select all of this, and I'll do it. I'll put in a filter like this time. So we'll order largest to smallest. There we go. So remember, you don't need to copy the top row. You just need to copy. You don't need to copy the header. You just copy all the data. There we go. Copy, and let's paste it in here. Voila, there it is. Data is in there. Now, one thing you should keep in mind. I'm gonna expand this. By the way, here's our. Here is our confusion matrix. It's working totally fine, so that's good. That's exciting. You can see that the total in here is 10,000 a record. So we see here 10,000. You can always just do that check. And the other thing I wanted to mention was, look in these formulas. You can see that I've put them up to 1 million. So they go, this formula goes from here all the way down to 1 million. This formula goes from there all the way down to 1 million. So just make sure if you have more than 1 million records in your data set, well, first of all, probably Excel won't fit them. But anyway, just make sure that you're not exceeding this limit. If you are, you might have to adjust this formula. Otherwise, everything looks good. We've copied our data, and now we're going to do this part. So I'm going to just delete this text, and you can just go ahead and drag them like that. Or the fastest way is just double click this little square, and they get dragged all the way down to, like, I'm just going to press Control down, and here you can see that exactly how much we need. Okay, everything looks good. All you have to do now is the last bit. Just select through Control, hold down Control, select E, G, and I, insert line, this line, bam, get rid of the legend. All done. That's how you use the cap curve template. As you can see, it's the same result as we had previously. If you want to insert a shape, just go ahead, hold down Shift, and that'll be a vertical line. And there you go. So that's 80.5%. That's how you use the cap curve template. It's all yours to take away and use in your own work. That's it. Have fun, enjoy, and I will see you in the next tutorial. Until next time, happy analyzing. In this tutorial, we're talking about the difference between training and testing your model and how to avoid overfitting. Here we've got the data set that we want to build a model for. And what we've learned so far is that we have to simply select the right parameters and throw them into a logistic regression, and that will spit out scores or probabilities that we will be able to use in our geodemographic segmentation. And that is all good. However, you might want to take a part of your data set, a sample, so a random sample, about 10 to 20%, and split them, separate them from the people that, or the records that you're actually going to be inputting into your model. And why is that? Well, the reason for that is that then you can move these people aside, or these records. You can train your model just on the remaining 80 or 90% of your population, or of the sample that you're training your model on. And then later you can test how your model works on the sample that you've separated. And that way you will be sure that that test, the second test, is not biased. So as a result of testing this model, or training it and then testing it, you'll have two accuracy ratios. So one accuracy ratio will be for the trained data, and that is the larger data set that we'll be building our model for. And then you will have an accuracy ratio for your test data set, the smaller one. So the first ratio, the train ratio, even though it does tell us a lot about the model, at the same time, it might be a bit biased because we did use the same data set to build the model, and now we're checking how the model predicts that same data set. Whereas the test dataset is completely separate from the model. Those records were not used in the construction of the model, and therefore the second accuracy ratio that you will get will be a validation for the first. So if you see a significant difference, then that means that perhaps your model might be overfitted for the data that was used to generate this model. Remember we talked about overfitting, that if your model relies on some anomalies or some specifics of that data set that you put into the model, then it might become overfitted, and then when you apply it to real data, the results might be different. Well, here you're kind of creating a safety net for yourself, that if it was overfitted, or if the model isn't the best performing model, so it's just working good on the training data set, then you won't find this out on real data when you actually make predictions. You'll find it out early on. You will see it on the test data set, and that way you'll be able to rebuild the model. So if something goes wrong, you just go back and you use the old training data set to build a different model, then you do the same procedure. So separating a test data set is very common. It is actually a standard technique used in modeling, and you should definitely do that when you are creating your own models. In our example, when we're building our geodemographic segmentation, the test dataset has already been provided for us, and as you will see in this section, we'll be using that to verify the model that we've already created. However, further down in this course, I will show you some tips and tricks on how to properly separate a test dataset, because even such a trivial procedure has some underwater stones that come with it. So we'll definitely talk about separating your training and testing datasets further down in the course. Now that we've talked about training and testing your model, today we'll actually start doing this in practice. Today we will run our model on the test dataset that we have been supplied with, and in the next tutorial we'll actually compare the performance of the model on the trained data and the test data. So let's go ahead and do all this work now. So geodemographic segmentation, and here are the two datasets that we started with, churn modeling and churn modeling test data. In order to run this model on the test data, I'm going to do the following thing. So I'm going to bring up Excel. I'm going to copy the test or the normal churn modeling dataset in here, and then I'm going to copy the test dataset into a separate Excel file. So now I've got two of them here, and all I'm going to do is I'm going to take all of the rows from the test dataset, except all of the columns except for the last column, which actually tells us the result, because we don't want the model to know the result for these people. And I'm just going to copy all of them. So I'll go to the bottom. There's 1,000 records here. I'm going to copy them, and I'm going to add them to this data set at the bottom. So I'm just going to copy them in here. So here you can see that they've been added at the bottom, but they don't have the result, right? So now when we put the model or the data into Gradle and we build the model, we're going to be using these records because they do have the result, and Gradle can build the model based on the outcome, so it can find the right coefficients for the model. And then we will use these to actually evaluate our model. So we will ask Gradle to come up with probabilities for these records, and then we'll assess the model on these records separately. So I'm going to save this as a separate file so I don't overwrite my existing file. Churn modeling. Let's call it with test data appended. Okay, we'll save that. So there's our data set, and now we're going to run Gradle. File, open data, desktop, and there it is. And that's all good. So basically we're just doing the same thing as usual right now. What do we normally do? We add dummies for gender, and we add dummies for geography. So I'm going to change this France. Okay, so I've created the dummy variables, I've renamed them, and I've added the log balance variable. Now what we need to do is we need to rerun the model. Here we've got our parameters, and I'm going to put them into our model. Alright, so I have inputted all of the regressors into the model. I've put in the dependent variable, show p-values, put the tick here. Looks good, so now we can run the model. And what you should see is you should see exactly the same coefficients as we had previously. Same r-squared, everything. Because even though we did add records, Gradle's not using them. Gradle's only building the models using observations 1 to 10,000. Because the last 1,000 records don't actually have a value for the outcome. And therefore, Gradle cannot simply just cannot use them in the modeling process. But what we can do now is we can go to analysis forecasts. And we want to forecast for this range. You see Gradle Smart is already picking up the range from 10,001 to 11,000 for those records. We don't want any pre-forecast observations, so we'll put a 0 here. And we don't want fitted values. It doesn't really matter because we're not going to have any of those anyway. So now we'll just click OK. And there you go. So these are our new records that we added from the test data. As you can see, they don't have an exited value, but they have a prediction. And this is the fun bit. This is the important bit, that Gradle, without even knowing, without knowing what is going to happen to these records, it built a model on the other records, as we discussed in the previous tutorial, and now it has applied the model to the new records. And as you can see, there are probabilities here. Now, what is the interesting bit is how right has Gradle gotten them, or how right has this model gotten them? How correct is our geodemographic segmentation? Because we actually know the result. We just didn't include it in the file. It's in a separate file. And that's exactly what we're going to do now. So we're going to save these records. This is not going to be exit hat. This is going to be p hat, as we discussed. P hat, and maybe we can call it test data. And here we're going to say for probability. Okay. So we've saved that. Don't need that. So there's our new data set, new column, and now we're going to export it. File. We're going to export data. So all we need is row number. We don't need customer ID. We only need row number and p hat test data. CSV, comma, okay, I'm going to save it here. And at the end, I'm going to add, as last time, forecast. Save. Don't need that anymore. All right, so there is our data set. Let's open up Excel and have a look. There it is. So NA means that these records didn't have a prediction because we didn't ask for them to be predicted. And that's right. That's the first 10,000 records. And then as you can see, the predictions begin here. So what we're going to do is we're going to remove these records that don't have predictions. All right. So this is our test data predictions. Now what we're going to do is we're going to open up our previous test data file, so the original one. And now what we want to do is, let's get rid of this one. We want to copy the actual exited value from here into here. So normally what you would do is a VLOOKUP, right? But I'm not going to waste your time with that because I know that I can already see that they are lined up correctly. So I can just take this column, exit it, and copy it into here. And I can close this. And now what you'll see is that we don't just only have the probability, but we also have the exited value. So this value didn't participate in the modeling, but we have appended it now, and we can verify how well our model went. The last thing we want to do is copy it and just put it before this column. So Should have done that. Anyway, so now we can see that row number exited and then p hat test data, because that's the order in which we need to copy them into our template. And that is we're going to use our cap curve template in the next tutorial to build the cap curve and then compare the results on the train and test data. So don't forget to save the file. And once you're done, I will see you in the next tutorial. In the previous tutorial, we ran our model on our test data. And here's the result. So we have the row number, we have the predicted probability of the person leaving, and we have the exited, the actual value. Did the person leave or not? And I just want to clarify one more time that when we ran the model, we did not use this test data. We created the model using the main data, which is in our churn modeling file. Then we input this data, or it was appended to our churn modeling file, but these test records, they didn't have the exited column appended. We added that later. So this prediction is in no way associated with this exited actual value. And so what that means is the model is predicting whether they will or not they will exit, and all we need to do now is actually check how well it is predicting, because this is like the real deal. It's a simulation of a real application of the model in a real environment. So what we want to do now is run this data through our cap curve template. Now let's go ahead and do that. So I'm going to bring up the cap curve template. There it is. Maybe expand this whole thing. Okay. So where is our data set? It's in this file. And the first thing we need to do, remember, we need to order our data set by this last column. So, by the way, I'm going to maybe this time just do it like this. So data, filter, and now I will sort it by largest to smallest. So that's the most probable person to leave, and the least probable person to leave is at the bottom. That's the probability. And now all we have to do is copy this data, copy, and go to our cap curve template. All right, and we need to put in here, remember it says ordered, so we did do that, we ordered it. So I'm gonna paste it in here. Okay, I'll just, oh, that's right, I click delete. There we go, let's do it again, paste. So that's good. You can see there's a total of 1,000 records, total exit is 260, 26% exited. Now we will delete this, and all we need to do is take this last row, not two, just the last one, and either drag it like that, or you can just double click on the corner and it will automatically go to the end. So as you can see, it's all populated. Just go down to the bottom and check that there's no issues along the way. Yep, so everything adds up at the end. There's 1,000 records, 260 exited, 260 exited, 100% everywhere. Everything's good. Okay, and actually even the confusion matrix is already populated for us as well. So you can see how many type 1, type 2 errors the model has made. And now all we have to do is, as we did previously, select this column, press Ctrl, hold Ctrl, and select these 3 columns, insert, line, bam, done. So get rid of that. There is our cap curve. So that's what it looks like. And it looks very similar to the one we had for the real, for when we were building the model, but it's a bit different. So if I do the 50% line, which is somewhere over here, you can see that the model is performing less than 80% at the 50% line. So once again, we're not going to calculate the area and then the area of the ideal line and calculate the actual accuracy ratio. We'll leave that to stats programs to do. But just by looking at this picture, we can see that the model is performing well, really well, but a bit worse than it was on the trained data. So let's go ahead and bring up the trained data result over here so we can compare side by side. There it is. We saved it in our Excel file over here. So this is what we had before, and this is what we have now. All right, so here they are side by side, and you can see 2 things right away. First of all, the model is performing a bit worse on the test data. And you can see that because at the 50% mark, the model is only capturing about 78, I would say, maybe 75% of the churners in this scenario, in the test scenario. At the same time, in the training environment, the model was able to capture 81%. So about a 3% drop over there, 3 to 6% drop, just moving from trained data to test data. And don't forget that the test data is pretty much just part of the test data is part of the trained data, just we separated it before we built the model. So these people actually came from the same time snapshot that when we created this whole data set. And the second thing that you can see is that this model is a bit more rugged. So like you can actually see the bumps in this model. They're more obvious than they are here. This one looks a bit smoother. So the second observation, it can be explained by the fact that there's less records. So there's only 1,000 records here, and therefore the concentration of records here is 10 times less than here, and therefore any kind of deviation or anomalies or randomness in the records, you can sense it more because there's just generally less records, and therefore that's why the line looks less smooth. Here you can still see some ruggedness, but it kind of smoothens out because there's 10 times more records, and even if 1 or 2 are deviating from the norm, then they're smoothed out by the other 8, and as opposed to here where there's 10 times less. So that's the first thing, and you will notice that the less data you input into the model, the more of these jagged lines you will have. And the first observation, the main one, that the deterioration of performance, well, there is a couple of reasons why that could be. First of all, perhaps maybe our model is overfitted, and you will find that to a certain extent models will, it's natural for a model to be better fitted to the data that it's trained on. It's like in anything. Say, even if you're doing martial arts, right? You're better at the gym that you are training at than at a gym where you go to, or let's say soccer or American football, right? If you're the home team, you will always play a little bit better on your own ground than when you're playing away on somebody else's field. So that's okay, as long as it's not too much of a drop. The other reason why this could happen, the drop over here, is once again because there's less records. Because we only have 1,000 records for this test, which is okay, which is fine. But maybe there is some, maybe all of those records, somehow it happened that they are a bit skewed one way, or they have a certain characteristic that these other records don't have, and that can affect this what you're seeing. And that has also to do a lot with how the sample or the test sample is selected from the overall the whole data set that you have for your training and testing. It is very important to select it correctly, and we will talk about this further down in the course, how to correctly select your test samples to minimize any potential for this effect when just because you select your test sample incorrectly, the results are not matching up. So, but otherwise, this is good. It validates that our model is performing. So basically, in this case, even without knowing anything about this data, our model was able to predict quite well. So imagine this, like you can, by contacting just 50% of your sample of these 1,000 people, by contacting 500 of them, you will get nearly 80% of those who are actually at risk at leaving, at a high risk that will actually leave. So that is a great result, and that's why we consider models between 70 to 80% good models. And so our model has passed the validation. This is how you use test data to validate. One other thing I wanted to mention is that this is a very powerful technique that we use just here. We plotted the cap curve, the cumulative accuracy profile for both models, and we compared it. So just visually comparing. Of course, we can calculate the area and so on, be more mathematical about it. But just visually comparing, we can tell right away which scenario is better. So the model is performing better here. But you can also use the same exact technique to comparing models to each other, different models. So if you had 2 options of a model, so you created one model and then you created the second model, and you didn't know which one was better, Then you could put them side by side like this. Use this same template, the cap curve template, create the cap curves, and for two separate models, but run them on the same data set. So here we're using different data. We're using train data and test data. But if you run them both on the test data set, for instance, this model on the test data set and then a different model on the test data set, and you compare, you can just say in the same way compare visually the graphs, and that way you can assess which model is better. And it's not just going to be like a random metric or an unreliable metric like the accuracy rate from the confusion matrix. Here you can actually, it's a more reliable metric because as you can see, it's taking into account all the records. It's you can visually see how it's going. So if there's any problems with the model, you will find that you will see it right away. And the third scenario when you can use this technique as well is when you're comparing a model to itself over time. So this is how your model is performing now. This is how it's performing on test data. And then, 6 months later or 12 months later, you run this same test, but for a new data set in the future, like for the people that are going to be banking with you in 6 months and for their behavior and for that geopolitical environment, you run the same model on those people and you see how it changed. You look at the curve, and this is a very important technique. We'll talk about this more as well when we're talking about iteration over time. I just wanted to run ahead a bit so that you're prepared and you're kind of thinking about this already now before we get to that tutorial. You will see that over time maybe your model will be getting worse, and like this curve, this red curve, will be getting to the blue one every time you check your model every 6 months. And that will speak of model iteration. But more on that later. This is all for today. I hope you found today's information useful, and definitely use this technique in your career. It can help you create much better models. Already, end of the section. We were just getting started into the fun stuff. But don't worry, in the next section, we will talk about some very powerful insights you can drive from models. And for this section, this is what we learned. Number one, we talked about the accuracy paradox, and that helped us understand why we cannot just use the accuracy rate, which comes from the confusion matrix, as the driving factor for defining whether our models are good or not. Next, we talked about the cumulative accuracy profile, and we got so used to it that now we just call it the CAP or the CAP curve. And basically what it is a measure for how well your model is performing. There's a mathematical way to assess the CAP curve, which is calculate the area under the ideal scenario, calculate the area under your model scenario, and then divide one by the other, get the accuracy ratio. However, we also talked about a rule of thumb, which is very visual, which is very quick. Just look at the 50% line, see where your model is sitting there, and then you have some certain thresholds, which I told you about, the ones that I personally use. And then what we talked about is how to build a CAP curve in Excel, plus you got the template. So hopefully you now know how to build one, but also hopefully the template will save you lots of time and you can just use it again and again and again. It took me a while to come up with that template. Usually for me, it was always very messy when I was building these CAP curves, but now I know how to structure it in a great way so that it's very efficient and I don't get cluttered with all of these extra columns that I don't need. Number 4 is how to assess your model using the CAP curve. So that's we talked about that already. That's the 50% line, and just visually see how it is, how the curve is structured, how close it is to that ideal curve that you can never achieve, but you always want to get as close to it as possible. We also talked about overfitting models and how you can avoid it. So using a train data and test data, so separating a test group from your data set early on, so that further down the track when your model is ready, you can actually apply the model to your test data and then see how well you went on in that scenario. So then compare the accuracy ratio in your train scenario and your test scenario and make sure that there was no overfitting in your train data. We also practiced how to verify models via test data. So we didn't just talk about the theory, we actually did it in practice. And this time we had our test data prepared for us or separated for us in a separate file. Further down the course, we will talk about the correct way of separating your test data from your training data yourselves. But this time we already had it, and we did actually practice and visually compare the two. And I really think that's a good exercise, because you'll be doing quite a lot of that if you want to build robust models. And number 7, there was a preview as to what's coming next. So we talked a bit about how models can deteriorate over time, and how you can compare models side by side, even if they're different models, using the cap curve. So all of that's coming further down the track in this course. Hope you're enjoying the material so far, and I look forward to seeing you in the next section of the course.
Welcome to the section on deriving insights. Now that we've built the model and we've assessed its performance and we're comfortable and confident with it, we can finally derive some insights. I will show you how to use the cumulative accuracy profile in order to understand how your business can become more efficient and save costs at the same time. We will also talk about the coefficients of the logistic regression to understand how your business can take advantage of certain patterns in the behaviors of your customers. So this is going to be a very interesting and insightful section, and I look forward to seeing you in the first tutorial.
Today we'll talk about drawing insights from your cap curve. The cap curve is actually a very, very, very powerful feature in modeling, and you can derive lots of valuable insights for your business just from this one tool. So let's see what we can get from here. We're going to look at 3 things. The first one is the obvious benefit of the likelihood score. So the score that we get by running our model tells us which customers are most likely to leave the company. In this case, it's leave the company. It could be take up an offer, or for which observations the event is most likely to occur. So where is it most likely that the dependent variable will be a yes, a 1, and not a 0. So this score allows us to already derive insights, and we can rank our customers, we can create deciles or quartiles and address different groups of customers differently. So if they have a high score, then they'll have one treatment. If they have a low score, they'll have a different treatment. Maybe it will be a different offer, maybe it'll be a different type of message and things like that. So that's the first thing, and that's kind of before the cap score. That's already an obvious benefit for the business, just having this ranking available. So a new parameter of your customers gives you a lot of insights which you can work with. Now the cap curve itself gives you 2 main things. The first one is to do with budget constraints. Let's forget about this situation for a second, that we're dealing with customers that are churning, and let's imagine that the model that we've constructed is for customers that take up an offer. So basically, we send an email offer, and we built a model to see what is the likelihood of customers actually clicking on our link and buying the product. So the end result that we're measuring, the dependent variable, is did the customer buy the product or not. And in that case, here we've got total number of customers that we in our test was 10,000. Total number that bought the product was 2,000. The percent that bought was 20%. And here we also have the same score, but this time it means that the likelihood of the customer to buy. So the predicted probability that the customer, this specific customer in this row number, will actually go ahead and purchase the product. And what does the cap curve tell us in that case? Well, it allows us to, once again, we're using the ranking to create the cap curve. So at the start, we'll have the most likely customers to buy. At the end, we'll have the least likely customers to buy. Now, when we're talking about budget constraints, this is a very, very common feature. And this is something that you might come across in a marketing department in a company. And let's say they can only send this email to a certain number of customers. Of course, an email isn't that expensive to send. It costs maybe like, I don't know. I don't have the exact figures, but I would assume maybe about 1 cent or 1/10 of a cent to send an email or something like that. But it still costs some money. So if a company has 10 million customers, and even if it costs 1/10 of a cent to send an email, right? So that's already going to, what's that going to make? Like $10,000 just to send all of those emails. And obviously the marketing department has other activities to do, so they might allocate a certain amount of money just for this specific activity and might not be sufficient to cover all of the customers of the company. And in that case, you have to pick and choose who you send to. If you don't have a model, then you will have to send to a random sample of, let's say you have 10 million customers and you can only send it to 5 million. In that case, you would have to select a random sample of 5 million and just send it to them. But if you have a model, then it's very obvious who you're going to send it to. You're going to send it to these first 50% that are ranked here in the top 50% because they have the highest likelihood of responding. And in fact, you can tell right away from the cap curve, you can go back to the marketing manager and say, look, I have a model, I've built a model for you, and you can, even if you send to 50% of the overall base of our customers, you send this offer, you will already hit 80% of the churners. So yes, ideally, or 80% of the people who are most likely to take up the offer. Let's fix up this axis over here so it's not confusing us. So maximum will be 1, right? Let's close that. So that makes it a bit better to visualize, right? So what you're saying is it would be ideal if the marketing manager could send it to everybody, and then he would obviously hit 100% of the people that are likely to actually take up the offer. But you understand that you and the marketing manager, that you both understand that this is budget constrained, and he can only send it to 50% of the customers. If he sends it randomly, right? If he sends it to a random 50% of the customers of the company, he'll obviously looking at this blue line, he'll obviously only get 50% of the people that churn, which makes sense, right? If you take 50% of a sample, you'll get 50% of, I keep saying churn, you'll get 50% of the people that are actually going to take up the offer. But if he uses your model, then if he sends it to 50% of the people in the company, according to your model, according to your ranking, then he will actually benefit because he knows that he'll contact about 80% of the people who will take up the offer. So he's getting more for the value, more for the money that he's investing. He's expecting to only get 50% of the people that will take up the offer. He'll actually get 80%. And that is how these models and the cap curve can help you in situations with a budget constraint. So even if he can only contact 25, right, over here, you might see that the effect is even stronger. So here you're going from 50, instead of 50, you're going to 80%. Yeah, so that's a 30% increase. So a relative increase of just more than half, right? Over here, this part is just more than half of this part. Well, whereas if you only have 25, right? If you can only contact 25% of the people, then you're going from 25% of the people that will take up the offer, you're going all the way to 55% of people will take up. You're more than doubling his expectation over here. So, and that's like a normal thing to observe. Whenever you're to the left of the halfway line, you're more likely to increase the benefit substantially. When you go to the right, the benefit is increased less because the curve is much steeper over here. So you can already tell that whatever budget constraint you have, you can add a lot of value to the business. So like even here, instead of if he contacts 8.3% of the customers, you can help him reach 22% of the people that are likely to take up the offer. What a value add to the business. The marketing manager will love you for this. This is incredible stuff. So that's the first main benefit of the cap curve. And the second benefit of the cap curve is efficiency. So sometimes you might not have a budget constraint like this, but at the same time, what's the point of sending the email to 100 people when you can send it to 100% when you can send it to less and still get approximately the same result? So let's go back to our example of churners, right? Here, for instance, let's say you can contact all of your customers in your company and then you'll definitely hit the 100% mark. But at the same time, you already know that these people on the back of this curve, they're very unlikely to leave the company. The likelihood of churning is very low compared to these people, right? So that's number one. Number two is, even if you contact, so this is somewhere about 80%. No, that's not 80%. That's 80%. So this is even less. This is about 70%. So even if you contact about 70% of your customers in your bank, you will already cover approximately 91% of the people that are likely to leave your company, that are likely to leave your bank. So That is very close to 100%. That's number one. And number two is that the remaining 9%, they're actually very, very unlikely to leave your bank. The likelihood is minimal. So therefore, you're saving these 30%, the money that you would spend on contacting these people. And not only the money, it's also messaging people without, you can't send too many emails to the same person in a month or even in a quarter, because they'll consider it as spam, and they'll, it's not a good customer experience. So you're saving the money, and you're saving the people the trouble of having to read this email, which isn't that relevant to them. And you're still getting a lot of the potential churners. You're getting 90% of the people that are actually going to churn. So you're getting 90% of the people that will churn. Even if you contact just 70% of the customers, you're getting 91%. So I think that's a good trade-off. You save money, you save people the trouble of reading your email, and you get the most likely ones that are going to churn the company just by contacting about 70% of your customers. So this talks about efficiency, how you can add efficiency to existing business processes through looking at the cap curve and creating models like this. And those are the two main benefits that you can derive. So budget constraints and efficiency. Let's recap quickly on what we learned in this tutorial, because I feel this is quite important stuff. Insights from your cap. The first one was actually before the cap curve. This is the likelihood score, and this is the score that you get for your customers. It adds another dimension to your understanding of your customers and allows you to work with it and create offers based off of it, or segment your customers according to that new dimension. It's a very insightful feature that can be used across the business for lots of various things that you might be required to do with your customers. Number two is budget constraints. So you can use a cap curve directly to understand who to contact to get the best bang for your buck. If you have a budget constraint in your marketing department or whatever department you're creating this model for, this can really, really help get the best outcome for the investment into this activity. And three, efficiency. Sometimes you won't even have budget constraints, but creating a model and building a cap curve will help you increase efficiency in terms of understanding where to stop, when to draw the line of who you want to contact, who you don't want to contact. And this doesn't only have to do with contacting people and in customer related companies. This can be in any type of organization where you're creating this model. It will help you understand where to draw that line. And actually, last thing I wanted to mention before we go, sometimes your cap curve won't have a flat profile like this. Sometimes there might be kinks in here. Even in our cap curve, we see a little bit of a kink over here, a little bit of a kink over here, then a bit of a kink, a few kinks over here, but they're not that pronounced. If you have more pronounced kinks, which of course you have to make sure that they're not crazy. If your cap curve is like going all over the place, then something's wrong with your model. But if your kinks are a bit more pronounced than they are here, then that can give you some hints where to set the cutoff points. So let's say, for instance, you want to set a cutoff point in terms of efficiency somewhere between 20%, so between this line over here, and let's say 40%, so between this line over here. And you don't know where to set it. You can pretty much set it anywhere. You can set it at the maximum, at the minimum. But then you see a kink over here, and you see that the cap curve is growing really fast before the kink, and then let's say during the kink it flattens out, and then it grows slowly. Well, that's giving you a hint that any additional investment that you make after the kink into this specific project or into this specific activity is going to yield a much lower return on investment than what you had before the kink. And that might be a good place for you to set the cutoff point. So you set it right before the kink, if the curve flattens out afterwards, and that way, whatever you're losing between the place where you set off the cutoff point and your maximum threshold for the cutoff point is not going to be as great. So basically, you're finding a great place to set your cutoff point just by looking at the profile of your cap curve. Once again, that's not all the time. Sometimes the model will give you hints and ideas like that. And going back to our presentation, 1, 2, and 3, likelihood score, budget constraints, and efficiency. Those are the 3 things that you can derive from your model. The last 2 are directly from your cap curve. And I hope that these techniques will help you to help other people in your company and also work around budget constraints and add efficiency to existing business processes. And I look forward to seeing you next time. Until then, happy analyzing. Plan of attack. All right, Kirill, what is this all about? What are we talking here? What kind of attack is going on? What we're going to be talking about in the next couple of tutorials is an advanced topic, and that's why the tutorials are marked as advanced. And we will be looking at a very specific thing. Let me explain. Remember, we previously talked about the do's and don'ts of a logistic regression. And we specifically said that you cannot interpret magnitudes of the coefficients to quantify associations between the dependent variables and independent variables directly. And this is very different to a multiple linear regression. So this is our logistic regression here, and we can't look at the magnitudes of these coefficients to compare the different variables between each other. We could totally do that in a multiple linear regression. It was very handy to tell us which independent variables are having a more significant impact on the dependent variable and which are having less. So basically comparing independent variables between each other and also actually physically quantifying the effect of the change in the independent variable and how that will affect the dependent variable. But here for logistic regression, we can't do that, and that just hurts. That hurts so much. We have to be able to do it, and that is why we have this special part of the course, this special couple of lectures or tutorials, which are advanced because they will involve quite a bit of mathematics and some advanced understanding of probabilities and odds ratios and things like that. But if you can power through them with me, I have broken them down into manageable sections or manageable topics, which we will cover off in the next tutorials. And today is about setting that plan of attack, and it's pretty straightforward. So first, we'll talk about the odds ratio. It's an important topic. You will see what odds are in sports betting, so that's kind of like a side effect of this section of the course. You will learn a bit more about odds in sports. But the main focus of this tutorial will be to link odds and probabilities. Then we will talk about coefficients. So this will be the math-heavy tutorial where we will actually understand how to plug odds into our logistic regression and then see for ourselves how a one-unit change in a independent variable translates through the coefficient into a change in the odds. So there's your hint, wink, wink, into a change in the odds, not in the probability. So that's going to be interesting. And then finally, in the third tutorial, after this plan of attack, we will see the practical application. I will show you how to get the odds ratios in Gradle. I will show you how to export everything into Excel, how to prepare your report in Excel, and then actually how to put it into PowerPoint and the way I would go about presenting your logistic regression or your geodemographic segmentation to your manager. So we'll have a heat map and it'll be very, very evident what the main insights are from our geomographic segmentation and what the bank, in this case, what the bank should do in order to address the issue of increased churn. So it's going to be an exciting couple of tutorials. Bear in mind they are going to be advanced, so prepare yourself for some advanced mathematics. Well, I wouldn't say too advanced, but some mathematics are going to be in there, but we'll definitely power through them together. And I look forward to seeing you next time. Until then, happy analyzing. Odds ratio. We hear about odds quite a lot when it comes to sports, whether it's betting on horses or on soccer matches or even gambling. And I bet you've heard phrases like the odds are 10 to 1 or the odds are 7 to 5 or the odds are 3 to 2 in favor of this and that and etc, etc, etc. And today we will talk about odds. We will try to understand what exactly odds is. But more importantly, we need to understand how is probability linked to odds, because we will be working with these terms quite a lot in the coming tutorials in this section. Here are the odds for the Melbourne Cup. The Melbourne Cup is a horse race which runs in Australia in November every year. And what we're looking at here are the dollar odds. And I'd just like to say here right away that I'm not advocating gambling or anything. This is just a great example for us to do our calculations of, and nothing more than that. Here we've got dollar odds, and as you can see, they're increasing for these 10 horses as you go down the list. So what do they mean? Well, basically, it's telling you how much money you will get if that specific horse wins. So as you can see, the horse at the top will bring you the least money because it is deemed to be the most favorable horse, the most likely to win the race. The horse at the bottom will give you the most money because it is deemed to be the least favorable horse out of these 10. Now, we want to move on to a different type of odds. We want to talk about losing to winning odds rather than dollar odds. So how do we convert dollar odds into losing to winning odds? Well, first of all, you have to split the dollar odds into two parts. Here, what the dollar odds are telling you is that if you put $1 on this horse, which is called Fame Game, the first one in the list, then if that horse comes first, you will get back $11. However, those $11 already include your $1. So basically, you're going to win only $10. So let's just quickly recap on that. If the horse doesn't come first, you won't get your $1 back. You will lose your $1. Or a random person who is betting on this horse will lose their $1. Now, if the horse does come first, you will win $10 and you'll get your $1 back plus $10. So in total, 11. So therefore, if you divide one by the other, in the case if this is a losing horse, then there's a $1 loss. If it's a winning horse, it's a $10 win. So $1 to $10 is your losing amount divided by your winning amount. However, the losing to winning odds are different. They're inverse. So basically, you have to take the two amounts and flip them. So the losing to winning odds are 10 to 1. Now, why is that? It might be a bit confusing, but why is that? Well, because you're getting, if you win, you're getting $10. So obviously that must be a much less likely event than the event of losing, right? Otherwise, that company that is running these odds is going to go bankrupt. So what this means is that you will get $10 if the horse wins. However, it is expected or assumed that this horse will only win 1 out of 11 times. So if there's 11 races, then 1 time out of these 11 races, the horse might win. Well, will win. That's what this company that did this calculation is assuming. And on the other hand, you're losing $1. You're losing a tiny amount. But why is that? Well, because the horse will probably lose 10 out of 11 races. And that's how the losing to winning odds work. So in this case, an $11 odds actually means a losing to winning odds 10 to 1. So you might hear the phrase that Fame Game has 10 to 1 odds, meaning that it will only win 1 out of 11 times. And therefore, the amounts, the remuneration is calculated through that as well. So now we want to get to probabilities. How do we calculate the probability of winning? Well, it's pretty simple. You just need to add the two numbers. 10 plus 1 is 11. As we said, like out of 11 races, the horse will probably win 1 time. So you take 1 divided by 11, gives you 0.09. So there's a 9% chance of this horse winning. Now, be careful in terms of terminology. At the top, you've got losing to winning odds. And at the bottom, you've got the probability of winning. If you want the probability of losing, then it's obviously 1 minus the probability of winning, which gives you 91%. Now, let's concrete all of this in by putting it into a formula. So some math. What did we do just there? If we assume that losing to winning odds is given by this ratio L to W, then what we did just there was probability of winning equals W divided by W plus L. So if we take 1 minus probability of winning, it will give us L divided by W plus L. Now if we divide one by the other, we'll get probability of winning divided by 1 minus probability of winning equals W divided by L. And if we rewrite that, then our winning to losing odds, so not the losing to winning odds, but the winning to losing odds, W divided by L equals probability of winning divided by 1 minus probability of winning. Now, if we put that all into a formula, this is the formula we get. Win to lose odds equals P divided by 1 minus P. Now, this is all we need from this tutorial. From here, you can move on to the next one. We are going to be working with odds. However, if you want to stick around, I wanted to show you something extra. A graph of this chart. Why I wanted to show it to you is just so that you kind of can grasp what's going on here and have like a kind of visual understanding of odds in your head. So feel free to stick around. I'm going to bring up the chart now. So here's a website. It's a German website, one of the first ones I found on Google to plot a chart online. And what we're going to do is we're actually going to just input this formula into here and see what it plots for us. This is x squared as default. That's not what we're after. So let's go ahead and plot that. So I'm going to take x. In this case, x is going to be instead of p, right? So x divided by 1 minus x. I'm going to plot it in blue, and let's draw that. So what you see here is the function, which looks like that. But we also know that probability, in this case, x, is always between 0 and 1. So it can only be between here. So let's cut it off at 0 and 1. And let's draw that. So here is your function, right? Let's maybe change the x-axis range. So we'll start x-axis from 0 and the y-axis from 0 as well. So let's draw that again. And so that is how your function looks. As your probability is changing, maybe we can also change this bit also. So x-axis goes to 1. Let's try that. So there you go. So here you can see that as x, or probability, changes from 0 to 1, like from here to here, what happens to your odds is it changes from 0 to infinity. It goes all the way to infinity. And why is this helpful? Well, this shows you that as probability increases, your odds, the good odds, the odds of winning. So remember, there's two types of odds: losing to winning odds and winning to losing odds. The ones we're talking about here are winning to losing odds. Those are the ones we're going to be talking throughout the rest of the tutorials in this section. The winning to losing odds are increasing, and that's important because we'll be relying on this information further down, that as probability grows, the winning to losing odds, or the odds ratio, is growing as well. If probability is decreasing, the ratio is decreasing as well. You can already tell that from the formula right away, but at the same time, having this chart visually present in your mind will allow you kind of to remember this and always be, confident in what you're doing and what we're talking about with the odds ratio. So that's how the odds ratio works, and we will definitely talk about it more in the next tutorial. We'll take it where we take it to the next level, and I look forward to seeing you then. Until next time, happy analyzing. In the previous tutorial, we talked about odds and how they link to probability, and today we're finally going to get to the bottom of this challenge with the coefficients of a logistic regression. I gotta warn you right now, it's gonna be a math-heavy tutorial, so you have been warned. Let's proceed with care. Last time we ended on this probability: win to lose odds equals probability divided by 1 minus probability, and basically this is the formula that links your odds ratio to your probability. So when you hear people say the odds of this team winning are 10 to 1, now you know how to convert that to probability. Basically use this formula. Well, this one actually converts probability into win to lose odds ratio, but we also looked at the other equation that works in the opposite direction. So we'll be using this equation, and let's quickly transform it into this one. So from now on, when we say odds, we mean win to lose odds. All right, now you remember this from way back when we were talking about the logistic regression, how probability is linked to an independent variable x in this case. Well, do you remember the equation that actually described this curve? There it is. So I'll remind you there. That's the equation. It's a logarithm of a p divided by 1 minus p equals b0 plus b1x. So this is in the case of a simple logistic regression. And now let's put the two equations side by side. So this is the one the green one's the one we talked about a long time ago when we were just introducing logistic regression, and the one on the right is the new equation that we now know for the odds ratio. Do you notice any similarities here? Like on the left, on the right, the ratio is actually the same one. So what we can do is take the p divided by 1 minus p and plug it into the first equation as odds, and in that way we'll get this equation. So this is logarithm of odds equals to b0 plus b1x. It actually has a special name, log odds. So that part on the left is called log odds, and that's just for a reference. We won't be talking about log odds at all. We will be focusing on odds because that's what we want to get to the bottom of. Now, this equation is exactly the same for a multiple logistic regression or just logistic regression in general. So that's what our geodemographic segmentation would look like in terms of odds. Now what we can do with this equation is do a mathematical operation which is called taking the exponent of it. So we'll take the exponent of both sides of the equation, which will give us this. So e to the power of natural logarithm of odds equals e to the power of that whole right part. Now the left part of the equation is very simple. E to the power of the natural logarithm of anything equals that anything which is in the brackets, so basically odds. The right side can be broken down by replacing addition in the power of the exponent with multiplications of the exponent itself. And this brings us to this equation. So this is a very nice and fluffy equation to work with. What we're going to explore is one individual independent variable. So let's just take any random one over here. Let it be b1, x1, and let's look at it separately. Now, what will happen, and this is what we're actually interested in, this is what we want to find out. What will happen if if we hold everything else constant, but we increase x1 by 1 unit of that variable? What will happen to the odds? What will happen to this whole equation? Well, as you can see on the right, if we take e to the power of b1 times x1 plus 1, that is actually equal to e to the power of b1 x1 times e to the power of b1. Now here you can notice that e to the power of b1 x1 is that part of the equation as it was before we increased x1 by 1 unit. So the new part is this part over here, e to the power of b1. That is what happens to the odds. They get multiplied by a factor of e to the power of b1. And this is the part where you shout, Eureka, we've got it. This is what we were after. Now let's put this in writing so that we definitely remember what we just found out. You know how I don't like putting too much text on my slides, but this time is an exception, important conclusion, and we're going to write it out. Increasing an independent variable xi, so any independent variable x, by 1 unit will increase the odds by a multiplicative factor of e to the power of bi. So that's exactly what we talked about here, that if you increase x1 by 1 unit, then your odds will actually get multiplied by e to the power of the coefficient of x1, which is b1. Very, very important conclusion, very, very insightful. And don't forget, we're not talking about probability, we're talking about odds here. So the odds that we discussed in the previous tutorial. So now let's look at an example. This is our model from previously, the model we built for our geodemographic segmentation. And here we've got a variable called age. Let's look at what happens when we increase age by 1. So as per our conclusion, the odds will increase by e to the power of bh. Bh is the coefficient of age here. So that means e to the power of 0.0726550, and that equals to 10754. So this means that whenever you increase age by 1 year, so if you take 2 people and hold everything else constant, all of the other variables, credit score, number of products, is active member, the gender, the country, the tenure, and the logarithm of their balance, if you hold those other variables constant, but one of those people is older by 1 year than the other, then the older person, their odds of leaving the bank increase by 1.075. So they get multiplied by this factor of 1.075. So what does that give us? That gives us 2 things. First of all, we now know, as actually we did previously, that if you increase age, the odds will increase, meaning that the probability will increase, because we remember that if odds increase, probability increases. If odds decrease, probability will decrease. But the second, the more important thing is that now we have a quantifiable metric to tell by how much exactly the odds will increase, how many times, what's the multiplicative factor. And that is very powerful because it will allow us to compare the different independent variables and their contribution to this model. And we'll do that. We'll start doing that in the next tutorial. And I look forward to seeing you next time. Until then, happy analyzing. Alright, done with the math. Hope you survived that. Hope you powered through and got some valuable insights and knowledge from the previous couple of tutorials. And today we're off to the fun part. We're going to work with Gretel. We're going to recreate our model, and I'll show you how to get the odds ratios for your coefficients in your logistic regression. And then I'll show you how to take them and export them into Excel. And then actually I will show you how to put them into PowerPoint, and I will show you the way I would go about presenting them to a manager or to an executive and so on. So the knowledge that you'll gain in this tutorial will be applicable regardless of what tool you're using. Just like everything that we're learning, regardless of what tool you're going to be using for modeling, you're going to be able to apply this knowledge in your work. All right, so let's get straight into it. So I've already got Gradle open up somewhere over here. There it is. And before you do anything, don't pause this video. Before you do anything, before you recreate the model just like I did, you have to do one other thing. Otherwise, you'll have to do the work twice. And so just go to File, and we're going to install a package. I'll explain what I'm doing now, and then you'll recreate the model. So don't create the model for now. Just watch this explanation. So if I go to Model and I run the model, so I've already done the coefficients here and everything is ready to run. If I run this model now, you'll notice that it doesn't have any information on the odds ratio. So this is like we're used to seeing, what we're used to seeing, but other packages, other software packages for modeling, they will add another column over here which tells you about the odds ratio. So it already knows that you want to take the exponent of the coefficients, so it'll do that for you and add another column. Gradle doesn't do that, but there's a workaround. We can install a package that will help us get that information. So just close that. Well, I'll close that. Before you create the model, what you need to do in Gradle is you go to File, actually go to Tools, go to Function Packages, go to On Server, and here, scroll down and find a package which starts with the letter O and it's called Odds Ratios. So once you found that, it's by Ricardo Jack. So once you've found that, click Install, right click and click Install. It's installed. My one doesn't ask me to restart Gradle because I already had it installed, but yours will ask you to restart Gradle. So that's why I warned you from creating a model, because you would have to restart Gradle and you would lose all of that. So once you've installed it, restart Gradle, and then we'll create the model. All right, now assuming that you've installed the package, go ahead and import your dataset, which is churnmodeling.csv. And as we did previously, create the dummy variables for geography, for gender, and create this new variable log balance, which is log 10 balance plus 1. And now we're going to go run the model. So model limited logit binary. And as you can see here, I already have the variables. And I use that file that we saved a while back to remind me which variables we decided to keep. And I've put on show p-values. So just copy them from either that file or from my screen. And once you've done that, click OK. And here we have the model. And as we had it previously, right? But now we know one extra thing. We know something special about the coefficients, that we can now interpret them. And isn't that a bit exciting? So what we can do with these coefficients, we can take an exponent of the coefficients, and that will tell us how the odds ratio is impacted when you have a 1 unit change in the underlying variable. Now, we don't have that column as discussed, but after you've installed the package, if you go to Analysis, there'll be a new menu here, which is Logit Odds Ratios. And if you click that, you will get the odds ratios. So basically the multiplicative factors that will be applied to your odds ratio if your variable, the underlying variable, is increased by 1 unit. So this is the really cool part. Now we get to take all of this and put it into one Excel spreadsheet, preparing it for our report. So there's Excel. What I'm going to do now is I'll move it here somewhere. I'm going to take all of this, and I'm going to go File, Edit, actually, Copy. And I want to copy it as this comma separated. Okay. Copied there. Perfect. Now I'm going to take this and I'm going to, there has to be a button there, copy. Just plain text is fine. And I'm going to paste it somewhere here. Right? So now I'm going to select this column. So I'm going to zoom in a bit for you to see better. All right. So pretty much we've taken all the information about our model from Gradle and we've put it into Excel. Great. Now let's make it look pretty. I'm going to select this column just for this odds ratio stuff, because as you can see, the information here is in each cell, just long line of information. Select the column. I'm going to go to data, text to columns, our favorite. We'll go delimited, and we'll just select space. Forget about tab, select space, make sure that is checked. Treat consecutive delimiters as 1. Next, and just click finish. There you go. So now it's all separated. Great. Now we have these variables, right? Don't forget there's no constant, just starting from the variables. Take the odds ratios, copy them, and put them here. Not the constant, the second line. And don't forget the name, put it over there. All right, great. So now we can get rid of all of this. Delete that. Now we can get rid of all of that. Delete that. Get rid of all of that. Delete that. Okay, so this is us preparing a report. This is the fun part. We're preparing a report for the manager or for the executive, or whoever you're presenting to, an audience of 10 people. You want to explain to them how their bank is performing, why are people leaving, what has this test done, what has it told us, and what are the steps going forward, what should the bank focus on. So obviously they're not going to be interested in standard error or the Z value, so we can get rid of them. The less information, the better. People digest smaller chunks of information better. You might want to keep the p-value just as evidence of your approach of, that these are statistically significant variables, and then maybe you'll have a chat about the tenure that it is greater than 0.05, but you decide to keep it in, and there is a red flag there that this is, that it's doing the opposite. So basically, we'll just keep them in, but we'll gray them out. We'll gray them out so people understand that this is not actually the most important part of the report. What is important is the coefficient and the odds ratio. And as you now know, the odds ratio is directly linked to the coefficient. It's the exponent of your coefficient. You can actually, we could have done this without the package. We could have just gone in Excel equals exponent of that, right? And just copied it down. And so you can see it's exactly the same value, So why I did it through the package is because other software modeling packages, they actually give you this column. So I wanted to, you be comfortable with having this column in here already. So we have this column. What can we do with it? Well, let's do the most important part. We're going to go to home, and here we're going to do conditional formatting, color scales, and let's just select this one. Right away, we can visually see a heat map, and we can see what is going on. We can see right away Germany, bam, it is the highest impact for people leaving. So green in this case is we actually need the reverse heat map. So that's good that we noticed that. So let's do the reverse heat map, so the second one. So people in Germany are the most likely to leave. So this is, well, the way this works, probably the best way to say it is, this is the most important factor, the most important independent variable that influences people leaving, right? So if you change from not Germany to Germany, then the odds ratio increases by 2.1. Basically, the odds ratio doubles. Then next one is gender. So when you go from a male customer to a female customer, all else held constant, female customer is the odds ratio of a female customer leaving are 1.7 times greater than for a male customer. So basically the odds ratio increases by 70%. That's huge. And then is active member is the opposite. So here you can see it's less than 1, which means that when you go from a member who is not active to a member who is active, the odds ratio gets multiplied by 0.34. So it basically drops by 66%, which is also a great result. It's a great result in terms of retention, keeping the customer. Then these are yellow, and anything below 0.8. So this is actually a good rule of thumb for you here. Anything below 0.8, you don't include it. So it's not that important. It doesn't have that much of an impact. Anything above anything above 0.8 and below 1.2 doesn't have much of an impact. So you can kind of ignore those variables. So the odds ratio here changes, gets multiplied by 0.98, or here it gets multiplied by 1.07. So not that much of a change. If you want to, you can explore these further, but what this heat map is telling you that these are your alarming red flags. You gotta focus on these. This is important, so you try to make your members more active. and you have to cater to the German market, to female customers in the German market. Something's going on there. So that's the important part. And that is what you're going to be presenting to your executives. These are your key findings. Remember, data science is about finding insights from the data. These are your insights. Another thing I wanted to show you here is that because we're taking an exponent, you know that e to the power of 0 equals 1. So if you have a 0 here, it'll be exactly 1 here. Anything below 0 here will be a value less than 1. So a negative means less than 1. A negative, less than 1. Negative, less than 1. Negative, less than 1. Anything above 0 will be a positive value here. So positive and greater than 1. So anything above 0 will be a value above 1 here. Positive above 1. These are positive above 1, positive above 1. So just showing you that there is an alignment between the sign here and whether the value is greater than 1 or less than 1 here, which is as we expected, right? So now we're going to take this, and I've actually got a report prepared here. So this is going to go to your manager, or to our manager. And now I'm going to just increase the size a bit, make some space, zoom out. Let's copy that, and let's paste that in. So there's a report, maybe where's view, grid lines? No, so there you go. So that is the report that you'll be sending off to your manager, and maybe you can add some footnotes saying, okay, these are the insights. Active members, least likely to leave, and very, very impactful metric. So we want to try and make our members as active as possible, get them working with our bank, right? And then there's something going on in this geography with female customers. Perhaps they're not happy with the products that we're providing, or there's a competitor that is targeting them, so we have to do something about it. And then these ones, you would only look at them next. So probably this one is the next important one, number of products. So if people have more products, they're less likely to leave, as you would expect. So there you go. That's how you analyze the coefficients of a logistic regression, and more importantly, a geodemographic customer segmentation. I hope this tutorial was useful, very insightful. When I learned this for the first time, it was like mind-blowing. It took me a while to get my head around it and actually understand how to use it. I kept forgetting how this odds ratio was derived, because there is there's quite a lot to remember, I understand, but you can always come back and refresh this knowledge if you forget. But do also know that you can use this in your modeling now, and I hope that this information will help you in your work. And I look forward to seeing you next time. Until then, happy analyzing. Section recap. So what did we learn in this rather intense section? In this section we learned, number one, ranking dimensions. So we saw how our model has provided a new dimension which we can use to look at our customers. That dimension is their ranking in the model, their probability to leave the bank or perform a certain action, and that allows us to drive additional insights or segment our customers, create deciles, quartiles, and so on, to better service our customers. Number two, how to draw insights from the cumulative accuracy profile. And specifically, we looked at two types of insights. Number one, if you have a budget constraint, what do you do? How do you find out the people you contact, and how do you talk to the manager of the department that's contacting these people? How can you say exactly what the return on investment will be for that budget? And two is efficiency. So sometimes you don't actually need to contact everybody to get a good and efficient outcome. So basically, you can save a lot of money, or maybe focus on other things and deliver a better customer experience, because you're not bothering people with too much emails or contacts. And by the way, just to clarify, we are talking in terms of customers and a customer geodemographic segmentation. But as I mentioned a couple times throughout this part of the course, all of these principles are also applicable in other industries, whether it's a factory that's producing toothbrushes, or it's a fraud investigation, engagement, anything. So just basically replace your dependent variables with the correct observations that you are interested in, or correct effects that you're looking for, and you'll get the basically the same result. They're numbers after all, right? So it doesn't matter what form they take. It matters how we deal with them and what insights we're able to produce. So just keep that in mind, that it doesn't have to be a customer geodemographic segmentation model. And number 3, odds ratio. So this was one of the advanced topics. This is where they started. We talked about the odds ratio and how it links to probability. Then we talked about how you can actually interpret the coefficients of logistic regression. It's not as direct and straightforward as in a multiple linear regression. That's why these topics were advanced, because we had to go into a bit of math. But we did find out how a 1 unit increase in an independent variable of a logistic regression actually translates into a change of the odds ratio for the probability of the event occurring. And number 5, we looked at the practical application. So I gave you an example of how I would go about presenting my findings in a logistic regression to a manager or to an executive of the company, and how to really visually portray your findings using a heat map. So that's all for this section. Hope you enjoyed it. Hope you had fun and learned some valuable knowledge here. And I look forward to seeing you in the next section of the course. Until then, happy analyzing.
Welcome to the section on model maintenance. I've put this information as a separate section because I believe that model maintenance is often either overlooked or underestimated. And organizations that just start into modeling, or data scientists that are new to modeling, often don't have a strict step-by-step procedure that they follow once in a while in order to make sure that their models are robust and still performing at their best. And in this section, we'll talk about why models deteriorate over time and what you can do in order to make sure that they are at their peak performance even 6 months down the track, 12 months down the track, or 2 years down the track. So let's get straight into it.
Model deterioration. This is going to be an exciting topic, maybe even unique on the whole internet. I'm not going to claim that, but maybe, because I haven't seen it anywhere else. We're going to find out how models deteriorate. What does it look like when a model deteriorates? All right, so we have our cap curve. Our cap curve is a very powerful tool that allows us to see our model, to have a graphical representation of our model, which includes as well how well the model is performing. And remember, we had this rule of thumb that you look at the 50% and you see where it crosses your model line, where your cap line is crossed by this vertical 50% line. And that allows you to determine how well your model is performing, how good this model is. And we had this rule of thumb where anything below 60% is a rubbish model, anything between 60 and 70 is a poor model, 70 to 80 is good, 80 to 90 very good, 90 to 100 too good, practically very unlikely that can be achieved. So let's observe a model over time and see how it will deteriorate. It's going to be fun. All right, so we start off with our model, and at the top, in the top left corner, we're going to say how old it is. This is a brand new model. You've just delivered it. You're very excited about it, very proud, and it's performing at 81% at the 50% mark. So it's a very good model. And let's see what happens to it next. 6 months down the track. How well is it performing? A bit worse, 75%. So it is just a good model. It's not a very good model anymore. It's just a good model. But still pretty solid. It's giving good results, good predictions. You can derive value from it. Then 12 months down the track. What do we see here? 69%. It just crossed into the poor path or the poor threshold. So as you remember, 60 to 70 is kind of like a poor model, but it's still around the 70% mark, still maybe driving insights, not as good as when it was brand new, 81%, but it's kind of still doing all right, fairly all right, but venturing into the poor territory. Another 6 months down the track, after 18 months after deployment, how well is our model doing? Only 63%. That is definitely a poor model. Can't really derive a lot of value from that. But, we are not maintaining it, so let's see what happens 6 months later. 24 months down the track, 55%. And that is already a red flag, a warning. 55% is not much better than a random coin toss. Just a 5% increase on top of a coin toss. And like, what's the point of having that model? What's the point of wasting processing power and actually using it in business processes? This is kind of already useless. That's why we call them rubbish models. Total rubbish model. And believe it or not, 6 months later, even this can happen. And I've actually seen one of these models where it's driving negative value for the business. 42%, when if you use a random coin toss, you'll actually get a better result. Definitely, this model is not just rubbish, it's actually doing worse for the business. So that's how a model can deteriorate over time. The timeframes used over here are completely out of the blue, so it might not be a 6-month period between each one of these. Might be 12-month period, might be even 3-year period. Depends on the industry. It could be faster, it could be a month, it could be 2 months. Depends on the dynamics in the industry, in the company, in the population, in the country, in the economic environment, and so on. So depends on what you're modeling as well. So if you're not modeling populace, like people and your customer base and so on, if you're modeling defects at in a factory, then your model might last longer. But then if something changes, for instance, the plastic or the materials change, then your model might start deteriorating. So it all depends on the circumstances, but models do deteriorate over time, and we'll actually find out why in the next tutorial. Hope you enjoyed this one. I definitely found it quite visual, and hopefully it illustrates the concept of model deterioration quite well. Why do models deteriorate? Now, this is going to be an interesting tutorial because I can't just simply give you a blueprint or framework here, because there can be literally a myriad of reasons why models deteriorate. Nevertheless, we're going to throw around some ideas so that you can see which way to think when you see deterioration in your model, so maybe you will find the reason. All right, so we saw that a new model in 18 months can easily go from 81% in our rule of thumb assessment to 63%. What could be the reasons? Well, let's have a look at some possible reasons. Additional factors. For instance, your model includes only some variables, and then there is actually another variable that appears that your model doesn't include. A good example would be, say, in a factory, you've got a model that predicts defects, but then you add a new component to your element that you're producing. So whether it's a toothbrush or something else, whatever you're producing, a car. So you've added a new variable, a new component, but that variable is obviously not included in your model because your model was built before that variable was added. Another one could be changes in behavior. So if we're modeling the behavior of human beings, like in the example of the bank, people might change their behavior. Why they change their behavior, that's a different question. It could be a result of something else. So that's like another effect that caused the change of the behavior. For example, when smartphones came out, they became so popular very quickly that maybe people started banking with their smartphones and they don't like the color of your bank's app, or your bank doesn't have an app, something like that. Changes in process. So going back to the factory example, maybe now your toothbrushes are being produced in a different way. So maybe you've changed the conveyor belt somewhere, or maybe you have excluded an additional step from the actual process of manufacturing, and that wasn't taken into account in your model previously, and now it's not performing as well. Changes in existing factors. Going back to the example, we're jumping around with examples here. Going back to the example of customers in a bank, maybe the distribution of ages of your customers changed. So with time, this is a good one. With time, customers get older, and maybe, obviously not as quickly as 18 months, but maybe over a couple of years, your customer base has gotten older and you haven't done anything to maintain that distribution curve as you had when you created the model, and which can be fine. Maybe you're not aiming to get younger customers. Maybe you started as a young bank, a new bank, and then your customers naturally aged over the period of 5 or 10 years, and now obviously their behaviors are different, the distribution of their age is different, and therefore your model hasn't been adapted to the new customer base. So that could be a reason. That's actually a good example, because people get older with time, models will also get older, and people's behavior changes, and also the actual distribution of the variable age has changed, whereas the model is expecting a different type of distribution. So there you go. That could be a reason. Competitor, maybe a competitor entered the market, or multiple competitors have been entering the market, and they have been changing things, or they've been taking a share of your customers, and more customers have been leaving disproportionately more to what the model is expecting. Changes in the industry, that also could be to do with competitors, or maybe something, say a new product has been introduced in the industry, or maybe there's been a lot of consolidation in the industry, and now there are major players that are that customers are gravitating towards, or the opposite. Maybe companies have broken down into little ones, or maybe there's been acquisitions or mergers or something like that. That's something in the industry. You would know this if you have the intrinsic knowledge and you on top of things, and something changes drastically, or even slowly over time, but still drastically. You would hear about it, and you would think that maybe that is causing the changing model. You will know what I'm talking about when you come across it. When you see a change in the industry and you see it affect your model, or you see a change in your model, you will link the two. It's sometimes very obvious when this happens. Changes in regulation. That's a good one, because it can actually really impact a model very quickly. Let's say something changed in the regulations overnight, and now a process has changed. The way you do things has become different. For instance, previously, in order to get people to perform an action, which you're measuring with this model, you had to send them direct mail. So you had to send them physical mail to get them to do something. Let's say it was to get their phone number. You don't have their phone number, and you want their phone number, and this model is predicting the likelihood of people giving you their phone number. So previously, according to regulation, in order to get their phone number, you had to send them direct mail physically. But now the regulation has changed, and you can send them electronic direct communications, right? EDMs, and they can reply by email and give you their phone number that way. Of course, it's going to be easier to get their phone numbers, and therefore your model is not going to be performing as well, because it's not used to this drastic change. It's built for direct mails, or direct communications. Now you're sending electronic direct communications, completely different situation. You have to rebuild the model. Changes in product. That's another one. Maybe you're predicting how likely people are of uptaking a certain product, and then you release another product which is cannibalizing the demand for the first product. So you're kind of competing with yourself, and the model doesn't take that into account. So the model was built in the circumstances. What we're trying to understand here is that, or the message I'm trying to convey is that a model is built in a certain environment. It is nurtured, grown, and deployed in a certain environment. If the environment changes, then the model might break. It might stop working. These things are very fragile. They can only work. They're very powerful and strong when they work in the environment where they were created. As soon as something about the environment changes, the models can deteriorate and even break. Depletion. That's an interesting one. If a model over time has used up the customers or the elements that it's modeling, so it's kind of a vicious cycle here. So it doesn't apply always, doesn't apply to almost, only some situations. So when, say, you want some action which is a one-off action, you can't get that person like a repeat purchase, or you can't get him, you don't even need to get him to do that action. It's like the example of providing a mobile number. Once you have the mobile number, that's it. That person's out of the equation, and perhaps your customer base is not growing that quickly, and say you created a model on a small sample, like 10,000 people. You created this model, and then you want to apply it to your whole population. Well, after you've applied it once and you've sent out the communications to get those phone numbers, and you've gotten them from the most probable people to give them to you, that's it. If you apply the model again, your population has changed, right? You're not going to apply it to those people that already gave you mobile numbers. You're going to apply it to those that didn't, and therefore your model is not going to perform the same way, because you've already depleted that potential for people to give you mobile numbers, which is actually a good thing. So you've actually gotten the phone numbers. Just the thing is that you can't reapply the model in that case. So situations like that can occur. Be careful of those. And number 10, what I think of here, spontaneous changes. Okay, this is an interesting one. Something in the industry, company, behavior, regulations, product, any of these happened like very, very quickly and unexpectedly. And why I brought this one up? Because I wanted to show you, as a bonus, 2 additional examples of model deterioration. These are going to be a bit weird, and they're going to be funny, and they're going to be a bit challenging to understand. So let's go ahead. So example number 1 is this one. What do you think happened here? What does this look like to you? It looks weird, right? It's you wouldn't think that the red line can be both above and below the blue line. But let me explain what happened here. And I'm going to use my mouse for this because this is important. So when you see something like this, obviously something happened, something went wrong. It's not just like gradual deterioration like this over time. This was like a spontaneous kind of thing. So what actually, in fact, happened here is the way kind of to determine this is look at the area under the chart. Remember long time ago, a couple sections ago now, we were talking about the correct mathematical accuracy ratio is defined as the area under this model over here divided by the area under the perfect model, which we can't see over here. And what we're using is just a rule of thumb because it's faster and it's very visual. So look at the area under the curve here. What do you see? You see that the area under the curve has decreased, right? So there's a less area under the curve. What this is telling us is that the model is not predicting as many churners. And in this particular case, what exactly happened is the number of churners drastically increased. And this might be a bit weird to look at it this way, but look what's happening. So the model's predicting, still predicting, even though it's going under the blue curve, doesn't matter. It's still predicting that people are leaving. So as this is growing, you're growing here. So as long as you're going up here, that means you're getting more churners or more people that actually left. And so as it gets over here, then you have this drastic move, bam, very quickly. So basically here, every single time you take a person from the horizontal axis, you're picking up a lever, an actual churner. Then you pick up another person, he's also a churner. So here, it's every single time, it's spot on, you're hitting a person that's leaving. And then it starts predicting again with some sort of rate. So what this is telling us is that before, it looked like this. Before, there was just a normal curve here. So as you were picking up like a certain number of people, some of them were churners, some of them were like people who left the company, some of them weren't. But here they all became leavers of from the company. So what this is telling us is there's something drastic change in the industry that all these people that used to be here now all of a sudden have left, or all of these people all this classification, the people that were placed here according to the model's classification have now left. A good example of that is a categorical variable, like let's say country. Let's say we have 3 countries, right, in our data set, and let's say all of these people are from Germany, then these people are from France, and these people from Spain. Of course, the model doesn't do that, but if there is a very distinct difference between the regions, they might end up grouped together. So if everybody from Germany is much more likely to leave than people from France, and they're much more likely to leave than people from Spain, then that's how the model is going to structure it. So the logistic regression will put people from Germany at the start, then people from France, and people from Spain. And then what happens here? Everybody from France decides to leave the bank. That's it. Maybe that's a good example of change in regulation. Maybe they're not allowed to bank with your bank anymore. That's it. Your bank has been prohibited of working in France. Everybody in France is going to leave your bank. And that's what we're seeing here. That's why as soon as the model gets to the people that it previously placed in this part, which were all from France, and were kind of like at moderate risk of leaving, now they're all leaving spontaneously. And as you can see, that is blowing up the model. So what would you do in this case? Well, first of all, if you know the exact reason and you can see that there's this categorical variable, of course you would exclude it from your modeling because you would treat them separately. You would treat the population of your bank or the people that bank with you in France, you would treat them separately because there's no point in modeling them. They're all going to leave anyway. You already know that. What's the point in putting them in a model? If it's not such a drastic change, you just rebuild the model and you would try see how that can be accommodated by the model. The other one we're going to look at is also a bit weird. What do you think happened here? And this is a great example actually of the fact that you can't always use the rule of thumb. You can use the rule of thumb when models are like normal, like that. When this happens, look at this model. So here you can see that at 50%, this is, by the way, this is the same model. This model is the same as this model. And what you can see here is that at 50%, this model is actually predicting a lot more. So like nearly 89% of churn. So this rule of thumb assessment has gone up really well. So this looks like a much better model if you assess it that way. But what is happening in reality is if you get over here, you see the model's predicting. And then once you get over here to these people that were placed somewhere between 60% and 80%, so you get to these people, you're not picking up any leavers. None of them are actually leaving the company, or none of them are performing that action that you're measuring. So similar to this situation, but the opposite. Here they all decided to leave. Here everybody in France decided to stay. Once again, it could be a regulation, could be a new product, could be maybe there were only 2 banks in France, and one of them just closed down, and that's it. You're the only one, so everybody had to stay with you. It could be anything like that. But once again, in this case, something major happened, and you can see that your model broke. So in this situation, I wouldn't measure it with this rule of thumb. In fact, I would do something about this categorical variable because it is definitely doing something wrong to the model. And also you have to rebuild or retrain the model. Speaking of rebuilding and retraining, that's our next topic. Now that we know what it looks like when models deteriorate and why they can deteriorate, it's about time that we talked about maintaining our models and making sure that they're nice and fresh all the time. And we will talk about that in the next tutorial. Model maintenance. We've been leading up to this tutorial in the previous 2 where we talked about how models deteriorate and why they deteriorate. And today it's time to understand what we can do to prevent them from deteriorating, or at least find out that they're deteriorating on time to replace them. And I'm going to cut straight to the chase here. This is the process that I'm going to be talking about. It's called the RR process. That is my own abbreviation, ARR, and we're going to go through every single one of these letters one by one. And the way this process works is it's a hierarchical process. So first you do the first letter, A. If that works, then you're good. If that fails, then you move on to the next letter, R. If that works, then you're all sweet. If that fails, then you move on to the last step, the last R. So let's find out what they are. A. A stands for assess. This is by far the most important part of the model maintenance cycle. You have to look at your models. Periodically, you have to assess them and see how they're going. You can't just leave them alone and hope for the best or wait until they tell you that they're not working, because that's not going to happen. You have to take your models and once in a while run a fresh sample through them. And for one that you already know the outcome, say take another 1,000 people randomly selected from your bank, or 1,000 toothbrushes sampled, or a couple thousand, and see what happened there. Like, you already know the outcome. You already know whether or not those people left, whether or not those toothbrushes were faulty, and but run the data through your model and see what it would have predicted. Create the cap curve, check the rule of thumb, see how much worse it is than the original model that you created, and determine for yourself, are you happy with that or not. If you're happy with that, great. Your model's doing fine. Let it keep running. If you're not, you got to move on to the next letter. Next letter is R for retrain. So this is the point where you're not happy with how your model is performing. It's the cap curve is flattening out, and you got to do something about it. So retrain implies keeping the variables that you've already selected. So in retrain, you don't have to do that whole process that we went through. You don't have to throw everything, take all the variables that you have in your company, throw them at the models, obviously select them logically, but then still throw them at your model, and then do the backward elimination process and then find out the coefficients. You don't have to do all of that. In retrain, you keep the variables that you've already found out. Like for instance, we decided we'll keep the dummy variable called Germany. We'll keep the dummy variable for gender. We'll even keep tenure, but we'll exclude other things from our model. And all you have to do, since you're keeping the variables, you just have to give your model a fresh sample to train it on. So what will change is the coefficients. The coefficients of your logistic regression will change because you've given your model a fresh sample. Of course, you'll have to have training data and test data just like we did. And once you've used the training data, then you check your model on the test data. And if the cap curve improves, then from there you deploy the new model or the refreshed, retrained model. That's what it's called, retrained model. You deploy the retrained model, and maybe you monitor for it for a bit, a bit more frequently. So instead of if you are monitoring your models once every 6 months, this one you might check up on it in 2 months, and then in 2 months again, and then in 2 months again, because it is kind of on probation. It's a new thing. You've retrained the model, and but that might fix the situation. That might be sufficient, and that might happen when your variables are still explaining what's going on. It's just that the coefficients are not sufficient. For instance, let's say age is a important factor, and also tenure is an important factor, right? But in our model, age was way more important than tenure. But let's say that over time things change, and they're still both important, just that tenure has become a bit more important or much more important. And now the coefficient for tenure has to be greater, but your model hasn't had a chance to understand that. You have to give it some fresh data and train it on that, and maybe that it'll pick that up, and maybe it'll start working well from there. So if that gives you a cap curve that you're satisfied with, then perfect. Keep that model and continue going down that path. But if that fails, then you have to move on to the last R, which is rebuild. You have to rebuild your model from scratch. And we're talking about everything. Completely scrap the model that you have. Or if it's not doing that bad, if this is like a preliminary phase, and we'll talk about this in a second, then don't scrap it completely. But basically what you have to do is go all the way back, find the variables, do this whole process again, and get a new model. Now, speaking of this whole scrapping business, sometimes if your model is performing really poorly or it's rubbish, then of course you have to scrap it and build a new one. But if you're doing this model maintenance process right, then you'll pick up the fact that it's deteriorating on time. You'll pick it up early. And the model's not working poorly yet. It's still doing a good job, but you just want to see if you can do a better job with a new model. So in that case, once you build the second model, you run them side by side. And this is called a champion challenger setup, where your existing model is the champion and your new model is the challenger. And you're running them side by side, and you want to see which one performs better over time and basically in real life situations, and then you'll keep the one that's performing better. And you can do this in different ways. You could run the champion challenger and only use the output of the champion, or only use the output of the challenger, but just monitor them at the same time. Or you could actually split your population in half and run half through the champion, half through the challenger. It's up to you how you set this up, but that is a good, valid approach to make sure that if you are going to replace your model, that you're not replacing it with something that's actually worse. And that's basically how you do model maintenance. Remember to do it on time. sounds like a car maintenance, right? Don't forget to do your car maintenance. But it is a fair point. You should do your model maintenance on time. You should schedule it. Frequency depends on the industry, depends on what exactly it is you're modeling. It can vary. It can be 3 months, 6 months, 12 months, 2 years. But I would actually, that is the frequency of when you need to update the models. I would actually assess them at least every 6 months. So at least once 6 months, you go ahead and just quickly assess your model. It doesn't take that long. And then maybe if things are changing quickly, or you're in a very fast-paced environment, a business environment, then Then maybe assess your models once every 3 months or so. Too frequent is also, there's no point in that. So assessing a model every day is definitely doesn't have a point. But you will gauge over time what is the right frequency for your environment and for your specific models. Just don't forget to do it because it's really sad when somebody deploys a model and it deteriorates over time and nobody picks it up on time to fix that or replace the model. So there you go. That's how you do model maintenance. Nothing complicated, just a 3-step process, ARR. And that brings us to the end of this tutorial. I hope you picked up something useful and hopefully this will help you in your day-to-day role. Section recap. So what did we learn in this section about model maintenance? First of all, we saw what model iteration is and what model iteration actually looks like. And I think that was very important for you to see how that will look in real life so that you can easily detect the situation when it occurs. And I think we really drove the point home with those interesting visuals that we had in that tutorial. Number 2, why models deteriorate. So we looked at why they deteriorate over time, then spontaneous deterioration. So although there is no blueprint here, there can be myriads of reasons why models deteriorate. We still threw around some ideas that will help you understand why a model is deteriorating if you do come across this situation. Then we talked about the 3 levels of model maintenance, or the ARR process. Assess, retrain, rebuild. It's not a complicated process. All you have to do is make sure that you assess your models quite frequently, at least once every 6 months, maybe a bit more frequently in some industries and for some types of models. And then we talked about the champion challenger setup. So if you do decide to build a new model and your old model is not performing too poorly, then you might want to run them side by side to see if the new model is actually performing better than the old model in real life situations. And that brings us to the end of this section. I hope you enjoyed it. Hope you picked up a lot of useful information. And I look forward to seeing you in the next one. Until then, happy analyzing.
Welcome to part 3 of the Data Science A to Z course. As you have guessed from the name, this part is about data preparation. Well, Kirill, why are we spending so much time on data preparation, you'll ask? Well, the reason is that from experience, the work of a data scientist is at least 70% data preparation on any given project. And that's if you know what you're doing. If you don't, then it's probably much more than that. And to be honest, a lot of courses out there, they don't teach you data preparation. You come in, you learn to program, you learn to build a model, the data is nice and fluffy and everything goes smoothly. And then you're out in the real world, your first project, and bam, you get a code page error or a text qualifier error or a truncation error or something like that, and you don't know what to do, and well, it's like a slap in the face. Like, what was all that training for? Well, this course fills that major gap. I have been there, I have seen the good, the bad, and the ugly, and I have an ethical duty to make sure that when you graduate this course, you know how to deal with real world data. And that is exactly what we're going to be focusing on in this part of the course. These sections are going to be extremely hard. Metaphorically speaking, they're going to beat you to the ground. And the data sets are going to be so cruel that you'll just want to rip the hair out of your head. And that's not all. In these sections, you're actually also going to have homework. Homework where you can't just follow along the tutorial. You have to do it all on your own and apply the skills that you've learned. But the good news is that if you can succeed through these sections, then you can succeed in the real world. Finally, I wanted to mention that in this part of the course, we will be using Microsoft tools. We'll be using SSIS and SQL. And by default, most large companies also use Microsoft tools. However, if you find that your company doesn't use Microsoft tools and uses other software, then I recommend that you still go through these tutorials and then later you can adapt what you've learned to your tools. Because the main focus of these sections is not learning the tools, it's rather learning the concept, learning the framework, and learning the blueprint that we'll be using for our data preparation process. And I can't wait to see you on the first tutorial of this part of the course. Let's jump straight into it. I strongly believe that when it comes to learning, foundation is key. In order to be successful, you've got to know what you're doing and why you're doing it. And that's why in this section we will cover off some key concepts like what is data warehousing, what is the data journey, and what is extract transform load. Also in this section we will install all of the required software for the rest of this part of the course.
What is working with data? In order to get from raw data to insights, your data has to undergo a journey. And broadly speaking, this journey consists of 4 major steps. These are ETL, database, analyze, and visualize. Now, analyze and visualize are pretty straightforward. These constitute the creative part of the work of a data scientist. Whereas working with data comprises of the ETL and database steps. And this is what we will be talking about in this part of this course. This is the preparation phase. And I will share a secret with you now. From my experience, you'll spend approximately 70% of your time as a data scientist on any given project in this preparation phase. And that is if you know what you're doing. And only 30% of your time is spent in the exciting part, which is analyze and visualize. And so this is why this part of the course is so voluminous and also so important. I will be giving you the exact step-by-step blueprints and tools so that you can sail smoothly through the ETL and database work and move on to the fun stuff faster.